Welcome to 600, Part 1. We're delighted you're going to join us for the next several weeks as we explore interesting issues around computational thinking and programming. Now, what are we going to do in this course? What do we want you to take away? At the end of this course, what is it we'd like you to have in your armamentarium of great problem-solving tools? We're certainly going to teach you about programming. We'll teach it in a particular language called Python. But more importantly, we want you to start learning how to think computationally, to think algorithmically, to think like a computer scientist. And what does that mean? It means we'd like you to think about, when given a new challenge, how can I get the computer to solve this for me? How can I describe the stages I want to use to get this done in such a manner that I don't have to do it, I can get the computer to do it? That's the notion of computational thinking, of algorithmic thinking, and that's what we're going to try and teach you about in this course. Now, that means you really want the computer to do the work for you. It's going to be your servant, and that means you need to think about how do you get it to do the things you want it to do. To do that, we're going to cover a range of topics, and we'll see all of these over the next several weeks. We want the computer to compute something for us, infer some new knowledge for us. That means we have to think about how do we represent that knowledge. And we'll do that with particular things inside the machine called data structures. We want it to infer new information or to find information, and we're going to see there are standard tools for making that happen, things called iteration and recursion, and we'll come back to those over the next several lectures. A big part of what we want to do inside the computer is to have it be able to deal with things in a manner that we can see and understand. And that says we're going to use the notion of abstraction to capture elements and then treat them as if they were primitives and reuse them. And that leads naturally to the idea of modularization, creating modules, tokens, elements that we can stitch together to come up with solutions to problems in interesting ways. Once we started learning how to build algorithms, to think algorithmically, we're going to see that there are standard classes of algorithms. And we're going to use those for common problems like searching and sorting. And we're going to see as well that different algorithms have different costs. And we want to see how to use that to reason about the expense of doing something and better ways of finding a solution to different problems. So here's our roadmap. These are the things we're going to deal with over the next several weeks as we talk about and get you engaged in computational thinking. If we're going to get the computer to do this for us, though, we could start by asking, so what does it really do? Boy, that sounds like a dumb question, right? Of course, computers do all sorts of amazing and awesome things. They can play Go. They can find things on the World Wide Web. They can do all sorts of wonderful, marvelous things. But fundamentally, a computer really only does two things. It performs calculations. Well, duh. But in this case, the calculations are actually very simple things. Turns out they can do them amazingly fast. But all they really do, they perform calculations and they remember things. Early computers didn't have much of this power. Modern computers have a lot, but those are really the basis of them. Perform a lot of calculations really quickly and remember results. Now you could ask, how fast is it really in terms of performing calculations? The machine you're using can probably do about 1 billion calculations a second. And just to put that in context, if I had a lamp sitting on my desk here, about a foot above, and I hit the switch, by the time light went from the bulb to the table, your computer's performed 2 operations. That's amazing. It's really fast, and it sounds like that's going to let a computer do almost anything. How about remembering things? Depends on the size of your computer. You probably have a few gigabytes of memory in there. A big computer or something on the cloud might actually have hundreds of gigabytes of storage. What does that say in terms of what it can hold? Well, if you took the standard novel and you put it inside a machine, a typical machine could hold about 1.5 million books of a standard size. So if you're going to start reading those great classics now, it's going to take you a while before you get through all the things that are stored on your machine. So it sounds like computers are amazingly good, even though they only do simple calculations and they remember results. Hold that thought because we're going to come back to it. Because we can also ask, well, what kinds of calculations does the computer actually do? Every computer comes with a set of built-in operations. These are typically primitive arithmetic operations, multiplication, addition, division, and simple logic operations, comparing true and false values in order to make decisions with that. If that's all we had, that's going to be a real pain. And so what we want to do through this course is figure out how to define new calculations, new operations, things we create and give to the computer so that it can abstract them, encapsulate them, and treat them as if they're primitives. But to start with, the computer simply performs a lot of those calculations, those simple primitive calculations, very quickly. Is that enough? Might be. If that's the case, we really don't have to do a lot in terms of computation. And I want to give you a couple of examples to show you why, even with the speed of modern computers, you need to be able to think carefully, cleverly, algorithmically. Here are two obvious examples of things you might like to do. You want to find a piece of information on the web, something you do every day with a search engine. You might want to play chess or have your computer play chess for you. Suppose you want to search the web. How much could you do if you just were using simple calculations? Well, here's a little computation I did before I came in to capture this lecture. There are about 45 billion pages right now on the World Wide Web. On average, there are about 100 words on a page. And for sake of argument, let's assume if we want to find a word on a page, it's going to take us about 10 operations to try and find that, whether that word is on that page or not. We'll see later on how we could get it down to about 10 operations. That says, if I'm going to just brute force try and search everything on the web to see if I can find the thing I'm looking for, it's only going to take me about 5.2 days to find something. You probably don't want to wait that long. So even with a very fast machine, using these simple calculations, it's not going to be enough. How about playing chess? An expert will tell you there are about, on average, 35 moves for every setting on the chessboard until you get to the end game. Suppose you want to look ahead 6 moves in order to try and decide what you want to do in order to beat your opponent. That says you got about 1.8 billion boards that you need to check. And if it's going to take you, for example, 100 operations for every choice, it's going to take you about 30 minutes to decide each move. Probably too slow. And this is simply a way of saying that even with fast computers, we need cleverness, we need algorithmic thinking to take those simple computations and turn them into something more powerful. And that says good algorithm design is going to be crucial, and it's one of the skills you're going to learn throughout this course. What about storage? Got lots of storage in a machine. Why don't I just compute everything once, store it away, and then just look it up? So let's go back to chess. Imagine I just want to look at all the possible chess games and store them away so that when I'm in any move, I'll just know what I'm going to do in order to get to a winning position. Well, experts would suggest that there are something on the order of 10 to the 123 different possible chess games. That's a really big number. And in fact, there are only about 10 to the 80th atoms in the observable universe. So there's no way that we can store all of that information away. And again, it comes back to saying we can't just use brute force or pre-compute. We need to be clever about how we come up with solutions. Even with that, we're going to ask, are there going to be limits to computation, even if we can build clever algorithms? And in fact, one can suggest that there are still some limitations to what a computer can do. Some problems are still, at least at the moment, too complex, even with clever algorithms, to come up with solutions fast enough. I'd love to know what the weather's going to be right in my neighborhood every morning before I get in my car to come to work. I just don't have enough data and enough compute power to be able to model at that level of scale. Maybe eventually, but not yet. In some cases, the fact that some things are too hard to compute actually works in our favor. And encryption schemes are an example of that. Things that you want to store on a computer encoded so nobody can break them rely on encoding or encryption schemes that in turn rely on the fact that some problems are simply too complex to be solved by a computer. And in some cases, even if the computers get faster, it's still not going to be possible to solve them. Some problems are just fundamentally impossible to compute. And a classic one from computer science is called the Turing halting problem. And it simply says, if I want to write a piece of code, a program, that could take as input any other program and tell me whether it will always work, whether it will always stop with an answer, it turns out you simply can't compute that in all cases. So there are going to be limits to computation. But not to worry, there's going to be a lot of things we can do, and that's what we're going to do throughout this course. With these new data types in mind, strings, with some of the other pieces we've added in, let's go back and just remind ourselves about branching programs so that we can build on that to start creating iterative programs. So just to remind you, what's a branching program? It's something where I have a conditional that I test. If that test returns the Boolean value true, then I have a block of code I'm going to run. If it returns the Boolean value false, I got something different I'm going to run. And I'm going to simply take either this branch or that branch and pick up the remainder of the code. We've already seen a simple version of that with an if. To do the testing, we had comparisons, things like comparisons on ints and floats. These are simple numerical things. I will simply remind you again, the double equal checks equality, equal sign does not. And we had logical operations to put things together. With that in mind, we could start then building the simplest of the branching code, which were either if statements, which says if this condition is true, execute a set of code, an if else, which said if this condition is true, do this, otherwise do that, or the more general if else, which says if this condition is true, do this. If it's false, check to see if this condition is true, in which case do this, and keep doing that until I get through all of the else clauses, and if all of the conditions are false, pick up the else clause and do the rest of that. It's just repeating what we've done before, things that you've already seen. With that, though, I'm still stuck with things that can only flow through code once. I can take different branches to get there, but I can't go back and do something again. And let's think about where that might actually not help the way I'd like. As I said, simple branching programs just make choices. Sometimes, though, I might want to do something over and over and over again. How would I do that? Well, imagine you're writing a simple little video game. And part of that game has a character that gets lost in some woods. And I agree the graphics here aren't great, but you get the idea. I'm stuck in a set of woods. What I'd like to do is to say to the character, if you go right, you're going to get back to the same place. You're going to be stuck in the same piece of the woods. How would I write that as code? Well, you could say, gee, I could have an if statement that says, if I'm told to go right, here's a set of things I want to do. Otherwise, if I go left, I'll get out of there. Okay? But I want this to be something that if I keep going right, I keep getting stuck in the same spot. All right, you say, gee, that's easy. I could have another if statement that says, if the command is still exit right, do something. On the other hand, if I exit left, I'll get out of the woods. But I want to do that again. If I'm going right, I want to keep doing it. You can see the problem. I want to be in literally an infinite loop in this little video game that says, if I'm going right, I'm always coming back to the same spot. How would I write code to do that? Well, I could say, I'm going to assume that a character doesn't push go right more than 100 times. And I could write literally a big loop here, not a loop, sorry, a big sequence of ifs that was 100 deep. But maybe somebody's really persistent and they want to do it 1,000 times. You can see my problem. I don't want to write code when I have an indeterminate number of things that I want to do. I need a different way of controlling this, and I have that. It's called a while loop. We're going to look at it in detail, but the idea is that I'm going to say, here's a check, a condition. If it's true, I'm going to do this, and I'm going to go back around and do it again. And I'll keep looping around and around on this while until this condition is false, in which case I'll jump out and do the next kind of thing. And that says no matter how many times I go right, I'll always be in that loop until I finally go left and break out of it. So I can control the flow. Now for the first time, not just in a linear way, with something that lets me check conditions. And so the format of a while loop is very simple. There's the while expression. There's a test that's going to return a Boolean value, either true or false. And then with indentation, a set of expressions I'm going to evaluate. And the performance of this is exactly what I just described. If the condition is true, I'm going to do all the steps inside that code block. I'm going to go back up and check the condition. And I'll keep going through that loop until the condition finally comes out as false. All right, how might I use that to do something a little more interesting than trying to get out of the woods? Well, first of all, let's fix the woods. Here's a nice little piece of code that will do that for me. The first one says, input based on this prompt, an instruction, left or right. So n's going to be either the word left or word right. Notice what the while loop says. It says if n is equal to the string right, then I'm going to execute this block of code, which simply again says, you're in the lost forest, go left or right. And notice what that while loop will now do. As long as n is equal to right, it will keep prompting me, asking for an input until I finally type in left, at which case this will be false, and I'll jump down and pick up the print statement. I can have an indeterminate number of times here. It's still always going to do the same thing. A little brain damage, but it's still going to do the right thing, and that's kind of nice. Now, let's see how we might use this then in other kinds of things. So here's a while loop, and notice what I need to do inside a while loop. I need to set up a variable outside so that I can test it and then do some pieces, and I need inside to have something that actually changes that variable. Otherwise, I'm never going to get out of the loop. And we can see what this does. If I type this in to my Python shell, I can set n equal to 0, which is done, and then I can say while n is less than 5, colon, I'm going to print out n, and I'm going to set n to n plus 1. Cool. It just did what I'd expected. Starts out with n equal to 0. Is 0 less than 5? You bet. So it prints out n, changes n by 1, goes back around and checks again. Is 1 less than 5? You bet. And you get the idea. That pattern is something that we would use pretty regularly. That pattern is also slightly annoying, because what if I forget to set n equal to 0 before I start? I'm either going to get an error, because n isn't bound to anything, or I'm going to get a performance I don't expect because n has got some value I didn't expect. Similarly, what if I forget to increment? I set n equal to 0 and I say, well, n is less than 5, print n. Well, I'm going to print out 0 a billion times until I finally stop the machine because I haven't incremented. So it turns out there's another form that we're going to use that is much more convenient, and that's called a for loop. And the for loop has a particular syntax. It has a variable. It has the keyword in this case. And then it has something we're going to come back to in a second, but an expression. And what for does in this case is it is going to work through all of the values returned by that expression one at a time, executing the body of the code. Now, range is something that returns basically a sequence of integers starting at 0 and ending before 5. 0, 1, 2, 3, 4. It actually does something a little different we're going to talk about later in the course, but think of it for now as giving us the collection of integers 0 up through 4. And so if I go over here and type it, I say for n in range of 0 to 5, print out n, I get the same behavior. But this code's easier to see. It says for n in this sequence, do something. As we said, range gives us back, in essence, the integers 0 up through 4. We'll see some other variations on range shortly in terms of other ways in which we control it. But the for loop gives us a nice way to capture easily an iteration, a repeating of code some number of times, based on, in this case, a specific number, although I could also base it on a test. There's, just to recapture this then, the overall general format for a for. The special character in this case using range to give me out a set of numbers, and a body of code that I'm going to execute. And just to remind you again, it says each time through the loop, variable is going to take a value. The first time it starts at the smallest value in range. The next time it gets the next value, in this case for range added by 1, and so on. Now I can actually be a little more clever about range, because maybe I don't want to do every value in that range. Maybe I want to skip some of them. So in fact, I have something that says I can start at a different point than 0 if I give it 2 arguments. In this case, it'll give me the range of numbers from 7 up to but not including 10. Or I can give it 3 arguments. Start at 5, end when I get up to or past 11, but do it by 2. And in each case, I'm going to get a different range out. So let's look at what those do. If I go over here and say my sum is 0, and then I'm going to say for I in the range 7 to 10, I'm going to increment my sum by I. And then if I print out my sum, I get 7, 8, and 9 added together, which gives me out the thing I would expect to see. If I do the second one, my sum, again, starts out as 0, and for I in the range 5 to 11 by 2, this should give me 5, 7, 9, but not 11. And again, I'm going to say my sum, I'm going to increment by I. Remember, plus equal says add to my sum the value of I. And I print out my sum. I get 21 in this case. 5 plus 7 plus 9. Sounds right. So I can use range to actually give me a set of values. But the nice part about all of this is the for loop always will just run through all of those values, executing the body of the loop each time through. Now, as I'm doing these loops, it might be the case that I want to get out of one of them. I might want to stop if something is actually, for example, a condition is true. And for that, I have another special thing called a break, and does exactly what you'd expect. If I'm running through some code and I execute, or see rather, that special keyword break, it stops the execution of that loop at that point, or that code block at that point, and breaks out of it. So in this case, if I'm inside this while loop and I hit break, it will never execute that expression. It will pop out of all of this and pick up at that point. That lets me control how I want to deal with loops. For example, I might see a particular condition is true, and based on that say, I don't want to do the rest of this, and jump out of it. I could write it as an if, but the break gives me a natural way to control where I am inside of that loop. And so there's an example. I could set my sum equal to 0. I could run over that range, but I'd say, in this case, if it's actually equal to 5, I can just break out. While I'm typing that in, think about what this might do. So I'm going to set my sum to 0. For I in range 5 to 11 by 2, I'm going to increment my sum by I. And then I'm going to say if my sum is equal to 5, break out. And what do you think? If I look at the value of my sum, it's just 5, which is exactly what I'd expect, because the first time around I is going to have the value 5. I'm going to increment my sum by 1, but then this test is true, and this break pulls me out of that entire loop and stops the computation. Silly example, I agree, but it lets you see how break controls the actual processing. I'm breaking myself out of a loop when I decide I'm ready to do that. And there's the body of code it's going to break out of, which is why it stops after only the first stage. To put all of these together, here's a little summary of for and while loops. In a for loop, we know the number of times it's going to run through an iteration, although I can end it early with a break, because I've defined the range of things over which I'm going to do the work. It uses a counter that's captured inside the for loop itself. I can always rewrite a for loop as a while loop by taking that variable that I'm using, that counter I'm using, pulling it outside, initializing it, and explicitly doing the increment to the counter inside of the loop. A while loop can have an unbounded or unknown number of iterations. Again, I can always end it early with a break statement, but I here have to just set up the counter ahead of time outside of the loop, and I have to make sure I increment it inside the loop. And unfortunately, I can't always rewrite a while loop using a for loop. You'll see in most code, we tend to use for loops when we know what we're going to do as a computation. We'll use the while loop when there's going to be a condition that we can't predict that's going to allow us to break out of that loop. But both of them give us the first version of iterative algorithms. This notion of an iterative algorithm is really valuable. It broadens dramatically the class of things that we can compute. Again, if I just have branching things, I can only go through the code once. Now I can start generalizing. And so we've got things that do much more than just the simple arithmetic we were doing earlier. We can repeat a sequence of steps multiple times based on a decision. One of the things that comes out naturally once we have this idea of repeating things is a set of methods that are sometimes called guess and check methods. They're very useful, even though they're not always the most efficient technique. And I want to extend that notion of iterative algorithms to capture examples of guess and check methods. Go back to what we talked about in an earlier lecture. Remember, we had that declarative definition of square root. Square root of x was that y such that y squared was equal to x. And I said, If we were lucky somebody gave us a guess, we could at least use it to check whether we were right. Now, we went and looked a different direction. We looked at an algorithm to actually compute it, but we can go back to that idea. Because if we had a good way to generate guesses, we could use that declarative definition to check. That's the basis of guess and check. I'm going to have to come up with a way of systematically making guesses for the possible answer, check them, and keep doing that in an iterative algorithm until I find a good solution. Let's see how we might do that. I'm going to use cube root rather than square root just to change it up a little bit, but the same idea would work. One way to use this idea would be to try and find, for example, starting at 0, try 0 cubed, then 1 cubed, then 2 cubed, and so on until I get to a point where I find a k such that k cubed is greater than x. If I found the cube root before then, I stop, but once I've got something greater than x, I know I can stop. Now clearly this is only going to work for integers. I can't do it for all possible numbers, but in this case there's only a finite number of things that I need to try. So let's see what that would do. Here's some code that would actually make it happen. I'm going to start by inputting an integer. Notice my use of input. I'll remind you that says it's going to print out that message, then read in whatever I type in into the environment inside Python. Remember that input returns something as a string, so I'm going to convert it into an integer. It's going to assume I typed in an integer. If I give it something else, it's not going to work. And then I'm just going to have a little loop. I'm going to set up answer to be 0. And then, as long as I have something that's less than the thing I'm trying to find the cube of, I'm just going to increment, add 1 to it. And I'm going to keep doing that until I get something that is something where the cube is either equal to x or greater than x. And once I get there, I'll simply check to see, did I actually get the cube by doing a test. Let's try this out. Again, I've got a same piece of code over here. I'm going to load it into my system. It says enter an integer. Let's give it something reasonable like 27. So in my environment, I give it 27. Oh, good. Cube root is, in fact, 3. Let's try something else. Again, I'm going to load this into my system. And I don't know, let's pick 38. And it says, doesn't work. It's not a perfect cube. All right, my code runs. What was this doing? It's simply using a loop right here to generate guesses. And it's going to keep doing that until it gets either to something that is the right thing or has gone too far, and in which case I'm simply going to do a check to see which case I'm in. Here I'm using that declarative knowledge because there's the test. The test is right there to see, do I have something that is in fact the cube root? That's nice. That's what I'd like. What could I say about this piece of code? Well, first of all, it's only going to work for positive integers. Okay, I could easily fix that by just keeping track of the sign and then looking for the solution to the positive case. And I do this because one of the things we want to do with code is think about how well does it run? Does it run on all the things I expected? And how might I modify it? And here the modification is actually pretty straightforward. I'm going to do the same kind of thing. I'm going to run the code, but I'm going to use abs, which is a built-in function, to take the absolute value of x. I'm going to check the cube root against the absolute value of x. And then when I'm done, I can just decide down here whether in fact I want the negative or positive version of that. I could make that change and run it. I'm not going to do it. It'll work for me, but it simply shows you that I can easily extend my code to build new versions of things to handle cases that I didn't think about when I wrote the first version of the code. There's the first version of a guess and check method. A little slow, but it does the right kind of thing. Now, one of the things that we've talked about is that we know when we do a loop that we need some characteristics. In particular, we need a loop variable that's initialized outside the loop, that changes within the loop, and that's used to test when I'm done. That notion we can also capture in a little bit more general form, because it's useful to think about what's happening inside the loop. How do I know the loop's actually going to stop? And for that, we often want to think about something we call a decrementing function. The idea is that we're going to map all of the program variables into an integer, and when the loop is entered, that value is going to be something that's non-negative. When I go through the loop, it's going to keep decreasing, and when that value gets less than or equal to 0, I know I want to terminate. So this is a capturing of this idea of the loop variable in terms of looking at what's being done inside the loop. And in my case here, I was simply using the absolute value of x minus answer cubed as my decrementing function. If you think about it, every time through the loop, that is decreasing. And once it gets to a stage where it's either less than or equal to 0, I'm ready to stop, and I'm going to be able to go on to see whether I've actually computed a perfect cube or not. What could go wrong? Well, these are the standard problems with a loop. Suppose I don't initialize the variable. Most likely thing is I get something called a name error, which is I'm going to try and refer inside the loop to something that I haven't defined outside the loop. There is no value. I can't look it up. That's at least okay. I'm going to stop. What's worse is if I've used that loop variable somewhere else in my code before this, I'm actually going to get something that starts up the computation in a place I don't expect. And that's a harder problem to find. So this is one of the things we always want to remember with loops. Make sure we initialize the variable before we start it. What if I forget to change the variable inside the loop? I'm in trouble, because I'm going to go through that loop until I get really tired of the machine running. It's going to simply go through what we call an infinite loop, doing exactly the same code over and over and over again, because it will never reach a terminating condition. And those are two standard problems with using a loop. A while loop in particular is I've got to make sure I set up the variable ahead of time, I've got to make sure I'm changing it inside the loop, and I need to make sure that the termination test is actually using that variable appropriately. But as long as I get into the discipline of that, set the variable, write the loop, decrement the variable inside the loop, and check for it, I should be okay. So that gives us actually a broad class of algorithms. Not the most efficient, not going to work in every case, but a good guess and check algorithm is something where you guess a value, you check to see if it's right, you change the conditions inside the loop, and you keep guessing until you find a solution or you've used up all the possible values. This is an example of a set of algorithms called exhaustive enumeration. And you can see why exhaustive. Two reasons. One, you're going to exhaust all possible options to use. And two is it's going to take a while to run, so you get tired waiting for it to finish. But as computers get faster, surprisingly many of these algorithms can actually work quite well. On the other hand, I might not want to always think about making sure I initialize a loop variable, do a while loop, and then change it inside. So I could clean this code up by using the other kind of iteration structure, a for loop. So here's a nice variation of that. I could set up a value for cube. I could have read it in, but I could set up a value for the thing I'm trying to find the cube root of, and then just run a for loop, because I know that the cube root has to be less than cube itself, at least for positive integers, things greater than 1. So I can simply use range to generate all possible things I want to use as a guess, and then run a for loop, where I'll run this and simply say, again, check to see is guess cubed equal to cube. If it is, I'm done. Let's see what happens if we try that one out. So I've got a little simple version of that over here. I'm going to start off with cube equal to 8, and if I run it, it does the right thing. It says cube root of 8 is 2. Let's try 27. And if I run that, wow, it's great. Cube root of 27 is 3. This is working really well, okay? But suppose I now give it something different, like 28, and I run it. What happened? Well, it completed. I can check that over here if I go back to my process. I've got things here, but it didn't print anything out. Because I made a slip when I wrote the code. That code is going to run through all possible options for guess, but it's only going to print something out if, in fact, I find something that is the cube root, if there is a perfect cube. With 28, that's not going to happen. It didn't give me anything informative. So I ought to clean that up, and I can, by simply saying, do the same thing. I've actually cleaned it up to add in abs here so that I'm going to deal with the negative cases, but do the check here. And if I get to a place where I've gone too far, simply break out of it, okay? Otherwise, run through the loop, but now, when I do the check, do the print. Otherwise, do the check with the second piece. And actually, I've done that in an inverse way. Here, I'm checking to see it's not a perfect cube, and I'm going to print that out. If it is a perfect cube, I'm going to basically determine whether I want the positive or negative version of it. So I'm cleaning up two things here. I'm allowing for negative integers, but I'm also allowing for it to print out something that's going to do the right thing. And let me show you what would happen if I run that version. So now when I run this, cube root of minus 27 is minus 3. And if I give it a minus 28, it says it's not a perfect cube, and I'm all set. What was my point? When I run the code, I shouldn't just run it on things I'm expecting, like perfect cubes. I should run it on other things to see if it does the right thing. When it didn't, I wanted to add in a different check. And I added in a second thing here, which I had done earlier, which is to make sure I can deal with negative integers and not just positive integers. But that now gives us a nice tool. I've got exhaustive enumeration, guess and check methods that can work on problems where there's a finite number of choices. I can come up with a way of exhaustively testing all of those, and it's a good way to generate guesses in an organized manner using those iterative loops as a technique to tell when I'm done and to return a great answer. And we're going to build on that idea as we move on. So far, we've just been typing things into our Python shell. And for simple expressions, that's okay. But it's even there a little bit painful. And when we want to do things that we might like to run multiple times, or when we want to do things with multiple commands, we'd really like a better way to deal with that. And for that, we'd like to have a text editor. Just like an editor you'd use for writing Word documents, we'd like an editor into which we can type Python expressions. And in most cases, that comes as part of something called an IDE, an integrated development environment. I happen to be using one from Anaconda. IDLE's another version of it. And that IDE comes both with a text editor, into which I can enter things, I can edit them, and I can save them away. A shell, which is that place where I'm going to be able to interact and where I can load that information in before I do that interaction. And as we'll see later on, an integrated debugger. And I want to show you just an example of how I would use that text editor as part of the IDE. Your own computer may have a slightly different version, but you should be able to figure it out. Let me simply show you an interaction on mine. So on my computer, I have both a text file opened up as well as the shell. And here I'm going to type in a couple of expressions. I'm going to set x to the value 5. And then I'm going to create a little conditional. I'm going to say if x is not equal to 5, and remember, I'm going to close that conditional with a colon to tell me I'm at the end of it. When I hit a carriage return, the editor automatically indents, which is really nice. I know that the next set of things should be indented. So in this case, I'm going to say print out, I am here. I have no idea why, but it seems like a reasonable thing to print out. I hit a carriage return. I'm still at the same place, but then I'm going to put in an else clause. And notice it nicely indents back because the else should be at the same level as the if. And then I'm going to say print, no, I am not. Now I want to run this, meaning I'd like to load this information into my shell. There are a number of ways to do it, but the easiest one is if I go up to my menu item at the top, there's something called run. And if I click on that, it gives me a set of options, including something called run. And I hit run, and it's going to ask me where to store that file. I'm going to give it a name temporarily. And it said I didn't like that. So I'm going to try it again, giving it a place that I know I can store it to. Let me do that. I'm going to pick a particular place, save it away. Oh, nice. If you now look at my shell, it's actually evaluated that code. It turns out that I have other options here. Under that menu, I could run the entire file, or I could pick something out and run just a portion of it. I could select a thing using the mouse or run a line. One of the other things I'd like to do is to run that file multiple times. So for example, I could say I'm going to change x from 5 to 6. And now, turns out on my machine, there's a shortcut, which is just function F5. It may be different on your machine. It automatically saves the file away, executes it, and again, on my shell, I've now seen a printout. This is going to be really nice. It's going to let me have easier ways to edit files, edit code before I run them. And so what you have then is that ability to have both a place into which you can type things, save them away, and a place in which you can then evaluate them in order to do the kinds of computations we've been discussing. As we've already seen in our programs, we need to be able to both read input in and print stuff out, or return values. I want to now spend a little bit more time on that. We show a very quick example of it earlier on, but I want to come back to that to be able to give you a sense of how you can control that. So let's start with output. I want to be able to print something to the monitor as I'm doing computation, not just at the end of a computation, but perhaps partway through that. And here we have a keyword called print that's going to do that for us. And I've got a simple little example here, which I'm going to run on my machine. I'm going to define x to have the value 1. I could just print x. So the keyword print followed by an open paren, followed by, in this case, a name x, followed by a closed paren, simply prints out that value on the screen. Kind of trivial in this case. But I want to show you some examples of how I could control the print a little bit differently. So I'm going to define x string to be the string x. And notice what I'm doing here. X is an int. str is going to actually cast it into or convert it into a string. That is the symbol x. And I'm going to give it a name. In this case, I've called it x underscore str. If I do that on my machine, I've now got a binding for x string. Now I can do printing. And printing here can take multiple arguments. You can see it on my slide. I'm going to print out a combination of this expression, that expression, a sequence of expressions, all separated by commas. Let's see what happens if I do that. So I'm going to do print of my favorite number is a comma to say I've got something, and then I'm going to give it x, and then I'm going to give it a period enclosed in double quotes, and then I'm going to give it something that says what's the actual value of x and x. Sequence of things. And if I print it, I get something pretty funky. It says my fav number is 1. Oh, but then there's a space before the period. And then it says x is equal to 1. What happened there? Well, what happened is that print is literally printing each element followed by a space. And in particular, x has a value that's going to show up separately from the period. On the other hand, if I give x as a string, it's simply going to put the two pieces together. And so I can do a second kind of print, which is I can say print my favorite number is, and then I'm going to add to that or concatenate x string, and then I'm going to add to that period, add to that the last part of the string x equals, and add to that x string. And if I print that out, I get something a little bit better. In fact, I blew it. I wanted to have a space between the period so that it would actually print it out as saying my favorite number is 1. So let's do that one more time. Print my favorite number is, and a space, concatenate x string with period and a space, concatenate that with x equals, with a space at the end, and concatenate all of that with x string. And I finally get what I wanted. What am I showing you here? In the case of print with multiple arguments, it will print each one of them spaced apart. In this case, I am concatenating the entire thing into one long string and then printing it out, and I can control the spacing around it. So this is going to give me a way to give out input, or rather to give out output to the machine, telling me what I've done as I control it. What about the other direction? I want to bring in input. And here I have another keyword called input, not surprisingly. And it takes a single argument, which is a string. And its behavior is it's going to print out whatever's inside of those quotes, that string. It's going to wait for me to type something in. When I hit enter, it's going to evaluate whatever I typed in and return that as the result of the input statement. Typically, I'm going to want to bind that to something, so I can bind it to a variable name, like text. And if I try this, I can say text equals input, and I'm going to simply say type something. Notice what it did. It just printed out, typed something. It's waiting for me to do something. And I can say foo. What did I do? I bound that to the name text. If I look at text, there it is. So if I wanted to really be annoying about it, I could then say print 5 times text. And there it is. Now maybe you're looking at it and saying, wait a minute, why are the double quotes there? Because I typed them in. Input simply expects everything to be a string. So I could do the same thing. I could say text equals input type something. Again, it's waiting for it. In this case, I'm simply going to write in the string bar. And what's text? It's just bar. And in fact, if I say what's the type of text, it says it's a string. So if I'm going to type something in, it's automatically going to read it in as if it's a string. But that says if I wanted to get a number in, I need to cast it. And that's what this last example does down here. Input, even if I type in a number, is going to interpret it as a string of the characters of the number. And so I need to turn it into an int before I actually use it. The notion of a for loop or a while loop extends the ability to write programs considerably for us. That generalization of a concept of iteration goes much beyond what we could do with simple branching programs. Remember, with a branching program, based on a test, we could either execute one piece of code or a second piece of code, but we would then proceed below that and would not be able to repeat that code in any insignificant way. With an iteration, we can now do more. We can use the same code multiple times. As with a branch, we start with a test. If that test is true, then we're going to execute the loop body once, go back and check the test again. And we'll keep doing that until the test evaluates to false, at which point we go to the code following the iteration statement and execute that. So this says we can go through this loop multiple times before we come out. Whereas in the branching program, we only went through the code once before we executed. That's a powerful tool, and we're going to capture that a lot as we move forward. Here's an example that will give you a sense of this. And the example here is to do squaring by repetitive addition. So another way of saying it is, if I wanted to compute n squared, that's n plus n all n times. I could write a little piece of code to do it. I've got it here. I'm going to run it in a second. I'm going to start off with something that I want to square. In this case, x is equal 3. I'm going to start off with an initial value for answer. That's going to be where my answer goes. And I'm going to keep track of how many times I need to go through the process. Remember, I said that before about loops, like while loops. I need to set a variable outside. Then I'm going to see, do I have anything left to do? And if I do, if I'm not down to 0, I'm going to increase ants by x. I'm going to decrease the number of steps by 1. And I'm going to go back around the loop. And I'll do that until I'm done. So if I look at a version of that over here, now in my IDE, I've got a little file I've written that is going to do that. It's exactly that same code. And I'm going to load it into my environment. And wow, there it is. It printed out, as you can see on my little computer screen, 3 times 3 is 9. It ran through that loop. Just to check it again, let's make something a little bit bigger. I'll change x to 5. Again, I'm going to load it and run it. And it computes the computation as we'd expect and returns 5 times 5 equals 25. Okay, big deal. I can square things. But what I want you to see here is that idea that I've now got a loop that lets me use the same code arbitrary numbers of times. When x was equal to 3, I ran through this portion of the code 3 times. When x was equal to 5, I went through it 5 times. That's a notion of iteration. That's really useful. Let's make sure it really did what I thought it would by actually stepping through this. Again, I've got a copy of the code there. And on the side, I've got a little table that gives me the values I'm going to use. I'm going to start off with x equal 3. That comes from that statement. I'm going to start off with answer equals 0. That comes from that statement. And I'm going to start off with the number of iterations left equal to 3, the value of x. Here's what the code does. First thing it does is it checks to see is iters left equal to 0. So it does that test. Answer is no. So what does it do? It takes answer and x, adds them together, gives us a new value to store an answer. It takes iters and reduces it by 1, restores a new value. Now I've got another version of the computation. The while loop says go back around. I check. Is iters left equal to 0? It's not. So same process. The current value of answer, or ans, which is 3, is added to x to give me sex. Iters left is reduced by 1. Go back around the while loop. Is 1 equal to 0? No. One more time. Change answer by incrementing it by 3, the value of x. Change iters left by 1 to get it down to 0. Now check. Is answer left equal to 0? It is, and I return 9. And aren't you glad I didn't pick 27 to do this on, but it's something simple like 3. My point is you can see how the while loop executes appropriately. It keeps reducing one variable, the thing that's counting how many steps I want to go through here, while accumulating an answer in ants as it goes through. And you see the properties we need for this kind of a loop. I need to set the variable outside the loop. I need to test it to determine when it's done. And I need to change the variable inside the loop in addition to whatever other work I want to do as I go through this. And in fact, what we see then is that we've now got a greater capability. Branching structures, things like ifs, only let us go through a different piece of code based on a test once. They run in constant time. They're only going to go through the code once. Looping structures like whiles let us repeat code until a particular condition is satisfied, but now the amount of time that it takes is going to depend on the values of the variables as well as the length of the program. And later on in the course, we're going to come back to look at that in more detail. We've described a recipe. We said it's a sequence of mechanical steps. It's going to capture the sequence of things I want to do in order to compute something. But now I want to get it inside the computer. I don't want to just give it to my friend and have him do all the work for me. So the next question is, how do I capture a recipe inside a mechanical process? Go back to my square root example. I'd like to get a machine that's going to compute square roots for me. Historically, there were two choices here. The first one was to use what was called a fixed program computer. And this would be a computer designed specifically to calculate a particular computation. You've actually seen them. Actually, you may be too young to have seen them, but people my age have seen them. Handheld calculators were a fixed program computer. They did addition, subtraction, multiplication, a simple set of arithmetic operations. That's all they could do. If you wanted it to search the web, good luck. Wasn't going to happen. Very famous historical example was Alan Turing's bomb. This was a machine designed during World War II to break German codes for the Enigma machine, and it was designed specifically for that process. It was also built out of devices you don't see anymore, like vacuum tubes and relays. And you can imagine the challenge of building such a machine, but it was designed to be a fixed program computer. That'd be boring if that's all we could do. I don't want to have to carry around a computer for square root and a computer for cube root and a computer for quadratic root. You get the idea. The alternative is what's called a stored program computer, and that's what you're used to seeing. Difference with the stored program computer is that you can load into it that description, that sequence of instructions, that recipe. And then inside that computer, there's going to be a set of parts that are going to do those instructions when I ask them to. And in particular, there's going to be a special program inside the computer, typically called an interpreter, which when you start it up is going to walk through each of those sequence of instructions in turn, doing the computation I want. And the advantage of a stored program computer is I can load in a different program and have it do the same thing. In essence, that stored program computer is emulating or imitating a fixed program computer for each program that I load in. It gives me an infinite range of things that I'm going to be able to do. So what I want to now think about is how do I take a description of a process in those mechanical steps and write it in such a way that I can load it into the computer and the computer can do the work for me. Before I do that, I need to think about what's inside the machine. So we're going to take just a second to open up the hood and look inside a typical computer. Basic machine architecture of a computer has some simple pieces. It's obviously got some memory, places in which I'm going to store things. Now up here in this memory, it could be data, but it also could be a sequence of instructions that are my program, that mechanical set of steps. I haven't said exactly what they look like, but you got a sense of them from what I did in that square root example. I'm also going to have a way to load things into the machine and print things out of the machine, input and output. We'll come back to those later on. Inside the heart of the machine, there are two elements. The first is often called an ALU. an arithmetic logic unit. And what this unit does is it takes information from memory, reads it in, often two pieces of information if I'm going to do an operation that takes two inputs, is going to do a primitive operation, could be addition, could be subtraction, could be testing to see if something is true or false, and then typically it's going to store stuff back up into memory. To make that happen, we need one more piece, and that's the control unit. And that's going to keep track of what specific operation I want to do in that ALU at each point in time. And inside the control unit, there's an important thing called a program counter. So very simply, when I load a program into the machine, in a second we'll get into how to do that, but I load a program into the machine. It's a sequence of instructions up here, and the program counter points to the location of the first instruction. And when I ask the machine to execute, that program counter reads that first instruction. It's going to cause an operation to take place, and it's then going to add one to the program counter, which is going to take it to the next instruction in the sequence, just as we saw in the square root example. That's going to do another operation, typically doing some arithmetic operation, moving things back into memory, and it's going to increase the program counter. Eventually, we're going to get to a test, and that test is going to say whether something is true or false. And based on that, we're going to change the program counter to go back up, for example, to the beginning of the code. But that's in essence what happens inside a modern machine. Control unit tells me where I am in a sequence of instructions. I've read into the machine, that stored program. That causes a simple loop inside the machine of operations. When I get to a test, it's going to potentially change the program counter. And when I get to something that says stop, it will, and it'll print something out on the machine. That's the heart of a machine. That's all there is inside a computer. All right, there's a lot of stuff inside there, but that's basically what the machine's going to do. And our goal is now to figure out how do we write that sequence of instructions so that the computer can do the things I want it to. To summarize, a stored program computer then is going to be that sequence of instructions. It's going to be built out of simple arithmetic and logic instructions. It's going to be built out of simple tests, and it's going to allow us to move data around. And associated with that is going to be this special program called the interpreter that's going to execute each of those sequences of instructions in order, changing things with the flow of control when a test says, I want to go somewhere else. And then finally, when I'm done, print out the answer. That sounds great. So what are the basic primitives? Most machines will come, as I said, with simple arithmetic and logic operations. But in fact, you can go even simpler than that. And if you go back to that gentleman I mentioned earlier, Alan Turing, one of the greatest computer scientists in the history of the world, Turing showed that you can compute anything with just 6 primitives. In fact, there's something called a Turing machine, an example of which is shown in that little image on the slide. A Turing machine is an infinite tape with a set of squares on it. In that, each square there's a symbol, could just be a 0 or a 1. And what Turing showed is if you have 6 operations, and those are move left, move right, scan, read, write, do nothing, with just those 6 primitives, you can compute anything that's computable. You're now panicking and looking to find a different class, because if what you had to do was program a computer by saying move left, move right, read, write, scan, stop, you don't want to program. Fortunately, modern programming languages come with a more convenient set of primitives. But the fundamental idea is that with a simple set of primitives, you should be able to compute anything. Equally importantly, you don't want to just write everything in terms of addition, subtraction, logical tests. What you want to do is write descriptions, like that square root program that we talked about earlier, and then abstract them. And I'm going to highlight that word because abstract is going to be really important. You want to treat that square root as if the manufacturer had built a little primitive and installed it in your machine. You want to be able to use it as if it was something that came with the machine. And that's what the power of computational thinking is going to give us. One last thing about computation. Let's go back to that Turing machine idea. I said you could compute anything if you just had those 6 moves. There are some nuances to this. A more sophisticated computer scientist could debate some of those details. But there's a fundamental property which says anything that's computable in one programming language is in fact computable in any other programming language. Wow. That's amazing. It says, while you may get heated debates between people about whether Python or C or Fortran or Lisp is the best computer programming language, they're all the same. Okay, slight misstatement. Some are going to be easier. Let me rephrase that. In some languages, it's going to be easier to do some kinds of things than others. In MATLAB, it's easier to manipulate matrices. In C, it's easier to deal with web programming. But nonetheless, anything you can compute in one language, you can compute in any other language. And this is a property called Turing complete. That's one of the fundamentals of computer science. So we've now seen the beginning of programming. Simple expressions, ways of putting them together into more complex things with means of combination, and the very first version of abstraction, giving names to things. But so far, all we've been able to do with these pieces is just behave like we're a simple calculator. We can do arithmetic. Let's add one more piece in, which is the ability to make decisions based on tests. And for that, we have to compare things. We have to decide, am I close enough to square root that I'm done? Am I close enough to something else that I'm done? So we have to be able to compare things. And since so far we've just talked about numbers, what are the comparison operators for integers and for floats? They're the things that you might expect from arithmetic. If I and j are any names of variables, they have values as numbers, then we have ways of testing if something is greater than something else, if something is greater than or equal to something else, less than, or equal. So is 2 less than 3? And if I do a simple example over here, 2 less than 3 returns true. That's good. 2.0 greater than 3.0 returns false. Also good. Is 2 less than or equal to 2 returns true. On the other hand, is 2 less than 2 returns false. Simple comparisons. I also want to be able to tell when something's equal. And you might think, oh, that's easy. Is 2 equal to 2? Wait. We already used equal as an assignment statement. So that won't work. And as a consequence, equality is done with double equal. Is 2 equal to 2? So for example, 2 equal to, oops, try that again, returns true. And then finally, if we want to know is something not equal, we use the exclamation point followed by the equal sign, often referred to or pronounced as bang equal or not equal. That will return true if I is not equal to j. Simple comparisons. They're going to let us build the very first kinds of programs that are going to let us make decisions, because based on whether something is true or false, I'm going to be able to decide which operation I want to do next. You're going to get a chance to explore all of these, but these make sense because they're simple arithmetic things other than that double equal sign, which, as I said, is there because equal is already reserved. Once we have logical expressions, we also need to be able to combine them. I might want to say, is something less than this and greater than something else? And so if I have two expressions that are Booleans, I can also combine them using either and, which is true if both are true, or, which is true if either of them are true, and of course not, which will be the opposite. Not A is true if A is false if A is true. Once I've got those pieces, I can put together more complicated expressions to decide tests. How might we use these? Well, here's a simple little example. This is actually a map of MIT. MIT students are always looking for free food. So imagine there's some food stored away somewhere at MIT, and I want to give instructions to a student to find them. All right, this is a complicated map, but we could use a simpler version of it. I've got my student. He's over here with his backpack ready to find that free food, which is way over here, and I want to think about how would I instruct him to get there? What would the tests be that I might want to use? Well, I might say, if you can go to the right, keep going to the right. On the other hand, if you get to the right and it's blocked, change and go forward. Unless both the right and the front are blocked, in which case go to the left. Unless all of them are blocked, in which case backtrack. Won't be perfect, I could still get stuck, but this will work pretty well to get my way through a maze. What I've just described are 4 simple tests to let me think about how I would instruct somebody to solve a problem, in this case trying to find the free food. Oh yeah, I'd need one more thing, which is to test when I found the food to know when to stop. Simple tests. With those ideas, I can put together the first kind of actually more reasonable or interesting program called a branching program. And it would say in that case of the maze, move forward unless a test is true. That test might be moving to the right is blocked. If it's not blocked to the right, I'm going to do one thing, keep moving forward. If it is blocked to the right, I'm going to move ahead. And a branching program then simply consists of a test, something that's going to return a Boolean true or false. If the test is true, it's going to have some code that tells me what to do in that case. On the other hand, if the test is false, it's going to have some code to tell me what to do in that case. And in either case, once I'm done with those pieces of code, I can pick up the rest of the computation. You can see why it's called a branching program. It takes one of two branches based on that test. In Python, we don't necessarily have to have the false block. We have to have the true block. If this is true, there should be something I would do. But if it's not always the case that I want to do something even when it's not true, I can skip that. With that in mind, I can start now building a little bit more interesting programs. And so here's a simple example. There's some pieces here we're going to come back to. Don't worry about them. Pieces like input, which is going to give me a way to read something in. But what I want you to see here are the tests. And the first case of a branching program is an if statement. That's a special symbol. It is treated differently, and when the Python evaluator sees this, it says, given that's an if, I'm going to evaluate this expression, which should return a Boolean. It says if the remainder of x divided by 2 is equal to 0. Notice the double equal sign there. If it's equal to 0, if that is true, then I want to execute this set of code. It's going to print out a blank line and then print out the word even. If it's not true, I need to tell it what to do, and I use the special symbol else for that. These are often called if-else expressions. If this is true, do this. Otherwise, do that. And here, again, I've got a block of code. In this case, it's going to print out a blank line and then the word odd. In either case, when I'm done with all of that, I'm going to go down to the rest of the code, which is just going to print out a simple thing that says I'm done with this conditional. You could type this in and run it. I invite you to do that. But what I want you to see here is a couple of things. This if-else structure. And I said in a branch there should be three pieces, and you can see them. There's the test. There's the first block. That's the true block. And there's the false block. Now, how did I know, or rather, how did Python know those are the blocks? Because of this indentation right here. The fact that those lines of code are inset are important because it tells us that's an entire block of code. And when I get done here, I'm going to pick back up the rest of the else. And more importantly, when I get done there, it tells me where the rest of the code picks up. Simple example of a branching program. I've already said this, but I want to recap it. I've got a test. It evaluates to true, when in fact in this case x divided by 2 has a remainder of 0. As I've already said, notice the double equal sign rather than a single equal sign to do the comparison. As I've also said, the indentation is really important. It tells us what pieces are associated together. And notice how that indentation gives us a nice visual structure for seeing where the code is, to see the semantic structure of the code. What's the true block? What's the false block? Now, it turns out that you can have nested conditionals. Inside of a block, I could also have a conditional. And that's perfectly fine. It says if this is true, then I'm going to go in and look at this portion. And if this is also true, I'm going to do that. On the other hand, if this is true, but this is false, I'm going to jump down here and run that piece. Again, I invite you to type this in and try it. But it's going to do something that, based on what the value of x is, prints out whether it's divisible by 2 and 3, by 2 and not 3, or by 3 and not 2, as it runs through that sequence of branches appropriately. And finally, we can have compound Booleans. As I said, I have things that can be combined. This is a Boolean, that's a Boolean, and the combination with the and also gives me a Boolean. So in this case, if x is less than y and x is also less than z, then the combination is true, and I'm going to print out a particular thing. Again, don't worry about what this actually does. What I want you to see is the structure, including one last piece, which is elif, also shorthand for else if. This says if this test is true, do that. But if this test is false, then see if this is true. If that's true, do that. But if it's false, then skip down. In this case, there's an else, and I'll always do this. I could have multiple elif statements. It's a way of giving me a sequence of tests in order. If this is true, do something. If it's false, but this is true, do something. If that's also false, but this is true, do something, and so on. This just then pulls them together. I've got a basic conditional. If this condition is true, do a sequence of expressions. I can also have an if and an else, or I can have an if, a sequence of elifs, and an else. And again, notice how the indentation tells us which things to do associated with which block of code. That indentation is how we are going to capture other pieces as well, and it doesn't have to just be conditionals. I could have something that has other statements inside of it, such as a print statement here. Again, don't worry what this code does. It's a simple piece of code to execute some simple comparisons on numbers. What I want you to see is how we walk through the branches. And with that, we now have the first kind of code. There's one set of blocks, inside of which I've got another set of blocks. And again, if this is true and that's true, I'll get to that point. But if this is true and this is false, so true here but false here, what happens? Oh, there is no code here, so nothing happens. It simply skips out to the end and jumps past. Again, I invite you to try this to see if it works the way I've described it. What I want you to see is the form of it. One other piece I want to remind you of is the fact that when we do comparisons, we need to use the double equal. Equal sign binds a value to a variable. Here I want to compare two things, and this is a standard place. I make it all the time where you'll get a bug. Don't worry when you do it. Python's going to complain at you saying you're trying to do a binding in a place that you can't. But remember, this is a place where when I'm doing a comparison, I want to use the double equal sign in order to make the comparison of two values and return a Boolean. Okay, what have we added? First simple kind of program. Branching programs allow us to make choices and do different things. But it's still the case that at most each statement gets executed once. I might skip a set of statements if I skip over that branch because I don't get there. But as a consequence of this, these are what we would call linear programs. They run in constant time because I execute each instruction at most once. And the maximum time to run the program is going to depend only on the number of instructions that I have there. Still valuable to make some decisions, but it's not going to give us the power that we want to really build interesting algorithms, and that we're going to get to next time. So far, we've just been playing with numbers. Names for numbers, but basically just with numbers. Now we want to add in one more type of object. We've seen ints, we've seen floats, we've seen bools, which are ways of getting values back out of tests. The last thing, or the next thing rather, we're going to add in is a string. We'll see a few others as we go along, but strings are going to be valuable to us. And what's a string? A string is simply a sequence of characters. Letters, special characters, could be spaces, could actually be sequences of characters put together into words, put together into sentences. And those are all contained within either double quotation marks or single quotes. Let me show you some examples. I've got some on my slide, but let me show you some examples with my screen. I can give the name hi to the string HELLO space THERE double quote. Those quotes on either end say, treat this entire sequence as literally a sequence of characters. And if I ask for the value of hi, it prints it back out, in this case with a single quote around it. As we said, we can either use double quotes or single quotes. Why? Partly historical. One would really work, but a place where double quotes are handy is if I actually want to use an apostrophe somewhere in a string. Because from Python's perspective, the apostrophe looks like an end of a quote. And so, for example, if I want to say, foo is, this isn't right. Notice that the single quote does not get interpreted as the end of a quote, and I can put out the value of foo. Once I've got strings, I can put them together. So for example, I could say, I'm going to give name the value Eric. I could certainly print out name. What's its value? There it is. But I could also put things together. And the next expression looks a little unusual. Greet is hi plus name. And when I print out greet, sorry, if I type properly, it would help. Print out greet. It puts the two things together. Hi there and Eric. Two things going on here. The first one is, whoa, a little funky to think about adding strings together. But just as we can add numbers together, strings have a natural way of getting combined. In this case, it's to concatenate them together. To literally take the first string, glue the second string onto the end, that creates a new string, and I can print it out. But if you look at my computer monitor, it didn't quite do what I wanted. It said, hello, Theric. I have no idea who Theric is. I'd really like to have it say, hello there, Eric. And so I can get that by adding in a little blank space. And so if I type in greeting as hi plus a space plus name, then the value of greeting is what I wanted. Hello there, Eric. Really nice. Notice concatenation, just as with numbers, could have multiple things in a row. So I can concatenate multiple things together as I did here. What we say when we talk about using addition this way, by the way, is we say we have overloaded it. We have had addition apply not only to numbers, but now to strings. Oh yeah, we talked about that earlier on. Remember when I said in the first lecture that the type of an argument, the type of an object, would tell an operation some important information. Here it does that because it's telling addition. If the two things are strings, concatenate them. It's also telling addition if I give you two numbers, just add them together using straightforward arithmetic. So I can use addition in multiple places to let the type of the object define what's going to happen. Once I have strings, I need operations on them. We've already seen the first one. We can do concatenation. But we can do some other things with strings. In particular, we can do successive concatenation. So if I type 3 times the string Eric, I get an echo. 3 versions of Eric are stitched together. So I can successively concatenate things together. It's kind of nice. And again, notice I'm overloading multiplication here. I'm saying multiplication of a number times a string is simply saying give me 3 versions or n versions, however many versions of that string put together. I can ask for the length of a string. And that makes sense. It tells me how many characters there are in that string. And that will include, by the way, counting spaces. So the length of hi there includes the space, not just the characters. It tells me how many literal elements there are inside of it. Strings have things inside of them. They're the first version of a non-scalar object in that I can get out pieces. And one of the ways I can do it is say I can index into it. So if I take the string Eric and I want to get out the first element in square brackets, I can say give me the first element and it gives me R. Wait a minute. That's not the first element. The first element's E. In Python, we have chosen to decide to start counting starting at 0. So if I want to get the 0th element of Eric, I would say, give me the 0th element. And there it is. I've already bound name to be Eric. So notice, by the way, I could ask for the 0th element of name. and it gives me the 0th element of the value associated with name, which pulls back out the E, exactly what I wanted. If I try and index beyond the length -1 of a string, I'm going to get an error. And that's because I start at 0. So even though this is of length 4, if I take the string Eric and I ask what's the 4th element, it gives me an error, something called an index error that says you tried to go too far outside of it. One last thing about strings. I can certainly get a single element out. I might want to get a chunk out of it. And so I can slice a string apart by giving it a somewhat funky looking expression. I take Eric, and again, in those square braces, I give it a starting point, which is 1, and a colon, and then an ending point, in this case 3, and it gives me the first and second elements of the string, R and I. I can choose to say everything starting at the beginning. I could use that as a 0, but I can also do that by saying give Eric with nothing before the colon and just 3. And it gives me all the elements up to, but not including the element number 3. And similarly, I could do it by saying, take Eric, give it 1, but nothing after the colon, and it gives me all the elements starting at element number 1. And if I just want to make a copy of the whole thing, I can say open square brace, colon, close square brace, and it gives me literally a copy, not the original, but a copy of this entire string. Now that we have the idea that we want to put together expressions by putting together primitives in legal ways, we can take up that idea of how to use that to start capturing recipes, start capturing algorithms. So let's talk about a Python program. Python being the language we're going to use in this class to do programming. And a program, just as we saw with the recipe, is going to be a sequence of definitions and commands. Definitions, as we'll see a little bit later on, are ways of either assigning names to values or, more importantly, creating procedures that we're going to treat as if they're primitives. Those we refer to as being evaluated. Commands are simpler expressions that we can execute directly within Python. And we do that in something called a shell. And in a moment, I'm going to use a shell. A shell is simply a window into which I can type expressions. They get passed into the Python interpreter. It follows the set of instructions to figure out what's the semantics, what's the meaning associated with that expression, and then it prints out the result. Commands are statements that instruct the interpreter to do something. So the commands could be simply do this arithmetic operation, or commands could be apply a primitive that I created to do some work for us. The last piece, and we're going to see both of these as we go through the course, is that we can either type things directly into the shell. That's a window that the interpreter is listening to. That's something where we type something in and the machine does something with us. Or we can store it in a file that gets read into the shell when we're ready to use it, but otherwise can be saved away. To start with, we're just going to type directly into the shell, but we'll see examples of files in a little bit. Okay, we're almost ready to start programming. We know the pieces we need. Let's start with what are the fundamental primitives that represent data. Those we call objects. And programs manipulate data objects in order to get out parts of those objects or to do something with those objects. Every object has a type associated with it that tells us what kind of thing it is. And more importantly, that type is really important. That type tells programs whether they can act on it or not. If a program is expecting a number and I give it a string, it's not going to try and do something with it. So the type of the object is really valuable. Finally, objects come either as scalars, which says they can't be subdivided, or if they're scalars, obviously non-scalars, which are things that have internal structure into which we can pull out parts. Let's start with the simplest version of these. Scalar objects in Python. There are very few of them. We have ints. These are integers, standard numbers that you recognize, 5, 17, 27, -6. We have floats. These are real numbers, things with numbers after the decimal point, 3.27, 3.14159, my favorite. You have something called a bool, short for Boolean, and that represents true or false. Those are going to be important when we get to tests, because we want to know if a test is true, do something. If it's not, do something else. There's one weird one. It's called none type. It's a very special one. It has only one value, which is none. We're going to see why that's important later on, but just to be careful, none type is a scalar object. Those are 4 fundamental scalars. There are only a couple of more which we'll get to a little later on. Once I have knowledge of those different types, I can also find out the type of an object by using a built-in procedure called type. And I want to show you some examples. So I'm going to go over to my little machine over here, and I'm going to skip down. I'm now talking to a shell. And you'll notice it's got a little prompt that says in, saying what's the input you want to give. The fact it's got 30 on the machine is because I was doing some other work earlier. So this is going to be the 30th expression typed in. And I'm simply going to type in a number. And the output is the number itself. Well, duh, you say. But it's actually important because what the machine did was it read in that sequence of characters, understood that it was a number, and the value associated with the number is simply the number. And in fact, I can check it because I can say, what's the type of 3.5? Notice the open and closed parentheses around it, and it says it's a float. And I can have integers, and if I say, what's the type of that? It's going to give me back an int. Simple things. Okay. Again, just to recap, what this says is here's what I'm going to type in to this Python shell, and here's what shows up after I hit enter, as you just saw. And in and out are simply going to identify what I typed in the output that you've recovered. Sometimes I want to change types, especially with numbers. This is called casting, and I can cast types of different forms. And you can see the example. If I say I want to take an int, such as 5, and turn it into a float, I can ask it to do so by giving it the special command float, the thing contained within parentheses, and it converts it. The other direction also works. If I want to take a float, such as 3.9, and convert it into an int, here you say, boy, there might be some choices. Python simply gives the whole number part of it. It doesn't round it to the nearest integer, as you might expect. If you want to build your own programming language, knock yourself out, you could do that. But it simply will truncate it down to that int. So I can convert back and forth. Now, once I've got these things, I can start putting things together. And in particular, here's a legal expression, 3 plus 2. That has a value associated with it. And in fact, that expression is to take the 3 and the 2 and apply the arithmetic operation of addition to them. And when I evaluate it, it simply returns out 5. Makes sense. Sometimes I might want to use something that's going to print, and I can type, for example, print, which controls output to the console by saying print 3 plus 2. Little bit of a difference. And in fact, there's no out here because no value is returned. Print returns that none type and doesn't print anything out. It just printed something. At this stage, you may be saying, well, why do this? Why the difference? What we're going to see is when we're in the middle of a computation and we want to print something out to the shell, we can use a print command to do that. If we just return the value, that goes back into the computation to be used for the next step. And so in the simple first case, the whole value of the computation was 3 plus 2 equals 5. It was printing out 5. In the second case, the side effect is to print something. The value returned is nothing. There is no value. We'll come back to that as we go along. I've already hinted at this, but now we can start putting things together. To combine objects and operators into expressions, we use a standard form. And the syntax is simply an object, an operator, and another object. Any expression like this that is syntactically valid has a value, which is itself a type. So we talk about the types of scalar objects. We talk about the types of more complicated expressions. What would those expressions look like? Well, here's the first set of them. There's a lot on this slide, but you're going to get used to them, and most of them make sense. If I want to add together either 2 ints or 2 floats, my expression is to have 2 numbers as I just did, 3 plus 2. The value associated with that is the combination of adding the 2 things together. I can subtract, I can multiply. And for these examples, if both I and j are ints, the result is an int. If either of them or both of them are floats, the result is a float. And let's look at an example. If I do 3 plus 2, I get 5. If I do 3.0 plus 2, I get the float 5. So Python is always using, if you like, the higher level representation when it does those kinds of operations. Division's a little trickier because I have both standard division, which will be a float, and I have integer division, which will be the quotient without the remainder. And let's look at two examples. If I do 5 divided by 2, I get 2.5. If I do 5 with 2 slashes divided by 2, I get the integer part, which is 2. The 0.5 is thrown away. And if I wanted to get the 0.5, I could do 5 remainder 2, which is the percent sign, and that gives me the piece left over when I divide those two pieces together. Finally, I can raise something to a power, and that is done right here with I, 2 stars, j. So 1 star is multiplication, 2 stars gives me power. Once I've got that, I'm ready to start putting together pieces. In particular, I've got different operations, so I have to think about how do I put together pieces in ways that control what I want it to do. And here we're going to use parentheses to tell Python in what order to do the operations. There's a precedence to those operations, and those are shown right down here, going in this order. Exponentiation, powers, are always done first. Then multiplications, then divisions, and then finally additions or subtractions. And overall, it's done in a left to right order as it appears inside the expression. And that means that as I change where the parentheses are, I'm changing the order in which I'm doing things. So to do an example, if I take 3 times 5 plus 1, that's going to give me 16. And that's because the multiplication is done first. 3 times 5 gives me 15, and then the addition is done to give me 16. On the other hand, if I say 3 times, and then in parentheses, 5 plus 1, the parentheses say reduce this expression first. Add 5 and 1, that gives me 6. And then do the multiplication, which gives me the 18. As a consequence, I can create very complicated expressions, and I will simply use parens, open and close, to define what operations to do first, always simplifying inside out before then using the operator precedence order in order to decide what the expression actually means. So we've now seen primitives. We've also seen means of combination, simple arithmetic things, expressions that we can use to compute values. I said earlier there was one last piece, abstraction. Ways of giving names to things, so I can refer to a value just by its name and reuse it. We're going to see other kinds of abstractions as we go along, but that's probably the most important first one. And so we can now introduce that into our programming language. In Python, we do an assignment using an equal sign. And you see an example of it right here. There is an assignment of a name to a value. And in particular, the value will just be computed the normal way. In this case, it's simply that float. That's what we call a variable. It's a name. And the equal sign gives us an expression called an assignment that says bind to or associate with the name pi the value 3.14159. Once we have that, we can use pi wherever we would like. So in fact, if I go over to my machine and I do the same thing, I say pi is equal to 3.14159. If I now ask for the value of pi, it prints it back out. I've bound pi to a number. I could do other things. I could give an approximation to pi, and I want to put this one up because I want to remind you that if I were to use double slash, I would get just the expression 3, but here it's going to give me something a little different. And if I do pi approx, I say 22 divided by 7, and I ask for that value, I get a little bit better, or maybe not better, representation of pi. That value is stored away in computer memory. It's in something we call a name table, where the variable pi has associated with it a value. And as we said, we can just retrieve it by asking what's the value associated with that name. Once we have that, we can start putting together more complicated expressions. So why will we give names to values of expressions? A couple of reasons. One is I want to just reuse the name and not redo the computation to get the value. If I actually had some very complicated arithmetic expression that reduced to a simple value, I don't want to redo it every time. I just want to give it the name. The second one is it can give me code that's much easier to understand. The name ought to be informative. It lets me think about what it's telling me about what this represents. And finally, it's going to be easier to change the code later if I've just got a name and I want to change the binding of the name and reuse it. So here's a simple example. I can bind pi to a value. I can give a radius, say 2.2, and then I can compute the area, pi r squared, and that'll give me a simple little computation. Those expressions also tell me something about what I'm trying to capture, and so those names turn out to be really valuable. One of the things to keep in mind is that this is simply following the sequence of steps we talked about. It's not like doing math. In programming, you do not solve for x. So for example, in this little example, I define pi to be 3.14159. I set up a radius. This is just a comment. We're going to come back to that. That hash sign says it's just something that's going to be there for me to read. The computer doesn't do anything with it. I can now compute the area. And then I can decide I want a different radius. And in fact, look at this expression here, because what it says is get the value of this expression, which is what's the value of radius? 2.2. It's the value of 1. Add them together, that gives me 3.2. And change the binding so that radius is now 3.2. This does not change area. It's not like a set of mathematical expressions. It's simply following the sequence of instructions we gave it. And that means that if we want to do something different, we would need to recompute area. Again, I just want to repeat what we said because it's important. An assignment statement says, find the value on the right-hand side of the expression, take the name on the left, and assign that name that value. One last thing, we're going to see a lot of shorthand here. That expression, adding 1 to something, it's something we're going to do a lot. It's called incrementing. And so there's a shorthand, which is you could write this instead as just plus equals. And that is simply short for saying radius plus equals 1 is radius equals radius incremented by 1. The last piece here is you saw we could change the bindings. I can rebind a variable name in a new assignment statement. The previous value may still be around in memory, but it's lost. There's no handle, no way to get to it. And as we just saw, the value for area doesn't change until you tell the computer to do the calculation again. Another way of thinking about it is, if this cloud is my memory, when I do a binding for pi, it associates the name pi with a value off in memory. When I do radius, I get the same thing. When I compute area, it looks up radius, squares it, multiplies it by pi, and then associates the name area with that value in memory. And now, if I change radius, it loses that first association and creates a new one. But area hasn't changed. If I wanted to recompute the area for this circle, I would need to do another call to area to make it happen. We've been using exhaustive algorithms, guess and check algorithms. When we got integers, we saw that's nice because there's only going to be a finite number of solutions, but we won't be able to find, say, square roots or cube roots of numbers where that isn't a perfect square or perfect cube. We've generalized that to look at something that does a different kind of guess and check, where we take incremental steps, still enumerating all the possibilities within the resolution of that step, trying to find the solution. And we saw that that either means we take very small steps and we take a long time, or if we take larger steps, we might miss the solution. And I suggested we want to find a more effective way of doing that. So here's an example of that, and a wonderful tool that we're going to see a lot as we go through the course. It's called bisection search. Let's think about square root. One of the things we know about the square root of a number is that it lies between 1 and that number, if that number is bigger than or equal to 1. We'll do fractions in a second. So square root of 25 lies somewhere we know between 1 and 25. Here's the basic idea. Rather than trying everything starting at 1 and taking small steps, suppose we pick a number in the middle between 1 and say 25, 12 and a half. If we're lucky, that's going to be close enough. Well, it's probably not close enough in this case. We know where it is, but it's a nice start. But we can take that idea and generalize it. If it's not close enough, then we can ask, well, was the guess too big or too small? And in particular, if that guess g squared is bigger than x, we know it's too big. So what can we say? Well, we know that the answer has to lie below g. And that's really cool because it says all of this stuff here, throw it away. I don't have to look there. I know that the answer has to be somewhere between 1 and g. Do the same thing. Pick something halfway between. That's my new guess. Try it again. If it's close enough, I'm done. If it's not, ask the same question. And for example, in this case, if g squared is less than x, then we know it's too small. So we can throw that stuff away and only focus on this portion. And again, pick something in the middle and keep trying. You can already see why this is going to be really nice, because on each step, I'm throwing away half of the things that I don't have to look at anymore. And that's going to let me hopefully very quickly zero in on finding the right solution. That's a wonderful idea. It's called bisection search, and we're going to use it. So what did we say? At each stage, I'm losing half the values. Really cool. Let's see what happens if we wanted to actually make code for it. So this is a little bit of a busy slide, but we'll walk through it. This is an example of computing square root using that example of bisection search. I'm going to start off just giving it the thing I'm going to look for. X will be 25. That's the thing I'm going to use as the root. Again, I'm going to pick something that I'm going to use to tell how close I am. And I'm also going to keep track of how often do I actually run through the loop, just to compare it to what we saw earlier. I need to set a low value and a high value, the range in which I'm going to look. Initially, that is 1 to the number itself. And then I'm going to make an initial guess, which is halfway in between. Just high plus low divided by 2. And then I run through one of those nice little loops. What do? I say, if the difference between the answer squared and x is bigger than or equal to epsilon, I'm not close enough. And in that case, I'm going to print out some information, increase the number of guesses by 1, and then do what I just did, which is if answer is too small, that is, its answer squared is less than x, then I can change the low part of the range to move up to answer. And if answer is too big, I can change the high part of the range down to answer. As I did before, I start out here. If answer was too big, I change the high range to bring it down into there. If answer is too small, I bring the low range down into there. And I keep sorting it down until I get into something that's reasonable. This algorithm just captured that idea I just described. So let's try it out. We'll do it with 25. Here's a bisection search on square root. And if I run this code, wow, it actually got there very quickly. It did it in 13 guesses. I'll remind you, in the previous case, we took 30,000 guesses to get there. I don't want to print all that out on my screen. And notice how quickly it zeroes in. It starts off with low 0 and high 25. And then it says low 0 and high 12.5. And then low 0 and high 6.5. You can see if you look at the printout how quickly it narrows in on the range. That's really cool. Okay? Do the same thing with cube root. I can do exactly the same idea. This is almost exactly the same code. The only difference is I'm using guess cubed rather than guess squared. And I'm going to keep track of otherwise exactly the same information. And let's compare that. If I go over and pull up my cube root example, we'll start with 27. Again, I'll remind you that in this case I was doing 30,000 checks to deal with this. Now I run it, and in 14 guesses, it gives me a really good answer. And if I pick something that's not a perfect cube, like 54, and I do the same thing, in this case, it took 15 guesses to get me a really good answer. This is a powerful tool. That idea of bisection search, throwing away half the possible values at every stage, lets me very quickly zero in. As before, I can ask, well, can I do everything? This is only going to work for numbers bigger than 1. What about fractions? Well, I know with fractions between 0 and 1, now the difference is that the root doesn't lie between the number and x itself, or it lies between 0 and that number. But that's an easy ways to change, and we could actually think about making that change. But just to remind you of how powerful this is, notice what happens. If I start off with the number n, on the first guess, I reduce the set of things in half. On the second guess, I reduce it by another half, so it's now n over 4. After g guesses, I've got a range that's only n over 2 to the g. And what this says is that in an amount of time that is going to grow as the log of n, I'm going to get to an answer. That's really nice because it says I don't take linear time, I actually take less than linear time to get there. We'll come back to that idea later on in the course, but this is a great example of a logarithmic time algorithm finding an answer very quickly. I jumped ahead a little bit because I already started talking about what happens if I want to look for cubes only greater than 1. I could modify it to look at negative cubes, and I could modify it to look at things where the answer is less than 1. And so, for example, if x is less than 1, I just changed the search space. So now, rather than going from 1 up to x, it goes from 0 to x. Rather than going from 0 to x, I want to go from x up to 1. I'm not going to do it. I'm going to leave it for something you to try out, but it's really easy to make that change. And again, notice what I've done. Start with the basic set of code, check to see what it runs on, and then decide if I wanted to use the same code, how could small changes have it run on other kinds of solutions. What can I take away from this? Bisection search really radically reduces computation time. I went from 30,000 times through a loop to 10 or 15 times through a loop. That's really nice. And this should work on any problem with what we would call an ordering property. That is, the value of the function being solved varies monotonically. That is, it increases as the input value increases. G squared has that property. As I change g, it grows. G squared grows as g grows. G cubed, same kind of idea. So bisection search will work on any problem that has that kind of property. We're going to see more examples of that as we go through the course. We've been using exhaustive algorithms, guess and check algorithms. When we got integers, we saw that's nice because there's only going to be a finite number of solutions, but we won't be able to find, say, square roots or cube roots of numbers where that isn't a perfect square or perfect cube. We've generalized that to look at something that does a different kind of guess and check, where we take incremental steps, still enumerating all the possibilities within the resolution of that step, trying to find the solution. And we saw that that either means we take very small steps and we take a long time, or if we take larger steps, we might miss the solution. And I suggested we want to find a more effective way of doing that. So here's an example of that, and a wonderful tool that we're going to see a lot as we go through the course. It's called bisection search. Let's think about square root. One of the things we know about the square root of a number is that it lies between 1 and that number, if that number is bigger than or equal to 1. We'll do fractions in a second. So square root of 25 lies somewhere we know between 1 and 25. Here's the basic idea. Rather than trying everything starting at 1 and taking small steps, suppose we pick a number in the middle between 1 and say 25, 12 and a half. If we're lucky, that's going to be close enough. Well, it's probably not close enough in this case. We know where it is, but it's a nice start. But we can take that idea and generalize it. If it's not close enough, then we can ask, well, was the guess too big or too small? And in particular, if that guess g squared is bigger than x, we know it's too big. So what can we say? Well, we know that the answer has to lie below g. And that's really cool because it says all of this stuff here, throw it away. I don't have to look there. I know that the answer has to be somewhere between 1 and g. Do the same thing. Pick something halfway between. That's my new guess. Try it again. If it's close enough, I'm done. If it's not, ask the same question. And for example, in this case, if g squared is less than x, then we know it's too small. So we can throw that stuff away and only focus on this portion. And again, pick something in the middle and keep trying. You can already see why this is going to be really nice, because on each step, I'm throwing away half of the things that I don't have to look at anymore. And that's going to let me hopefully very quickly zero in on finding the right solution. That's a wonderful idea. It's called bisection search, and we're going to use it. So what did we say? At each stage, I'm losing half the values. Really cool. Let's see what happens if we wanted to actually make code for it. So this is a little bit of a busy slide, but we'll walk through it. This is an example of computing square root using that example of bisection search. I'm going to start off just giving it the thing I'm going to look for. X will be 25. That's the thing I'm going to use as the root. Again, I'm going to pick something that I'm going to use to tell how close I am. And I'm also going to keep track of how often do I actually run through the loop, just to compare it to what we saw earlier. I need to set a low value and a high value, the range in which I'm going to look. Initially, that is 1 to the number itself. And then I'm going to make an initial guess, which is halfway in between. Just high plus low divided by 2. And then I run through one of those nice little loops. What do? I say, if the difference between the answer squared and x is bigger than or equal to epsilon, I'm not close enough. And in that case, I'm going to print out some information, increase the number of guesses by 1, and then do what I just did, which is if answer is too small, that is, its answer squared is less than x, then I can change the low part of the range to move up to answer. And if answer is too big, I can change the high part of the range down to answer. As I did before, I start out here. If answer was too big, I change the high range to bring it down into there. If answer is too small, I bring the low range down into there. And I keep sorting it down until I get into something that's reasonable. This algorithm just captured that idea I just described. So let's try it out. We'll do it with 25. Here's a bisection search on square root. And if I run this code, wow, it actually got there very quickly. It did it in 13 guesses. I'll remind you, in the previous case, we took 30,000 guesses to get there. I don't want to print all that out on my screen. And notice how quickly it zeroes in. It starts off with low 0 and high 25. And then it says low 0 and high 12.5. And then low 0 and high 6.5. You can see if you look at the printout how quickly it narrows in on the range. That's really cool. Okay? Do the same thing with cube root. I can do exactly the same idea. This is almost exactly the same code. The only difference is I'm using guess cubed rather than guess squared. And I'm going to keep track of otherwise exactly the same information. And let's compare that. If I go over and pull up my cube root example, we'll start with 27. Again, I'll remind you that in this case I was doing 30,000 checks to deal with this. Now I run it, and in 14 guesses, it gives me a really good answer. And if I pick something that's not a perfect cube, like 54, and I do the same thing, in this case, it took 15 guesses to get me a really good answer. This is a powerful tool. That idea of bisection search, throwing away half the possible values at every stage, lets me very quickly zero in. As before, I can ask, well, can I do everything? This is only going to work for numbers bigger than 1. What about fractions? Well, I know with fractions between 0 and 1, now the difference is that the root doesn't lie between the number and x itself, it lies between 0 and that number. But that's an easy ways to change, and we could actually think about making that change. But just to remind you of how powerful this is, notice what happens. If I start off with the number n, on the first guess, I reduce the set of things in half. On the second guess, I reduce it by another half, so it's now n over 4. After g guesses, I've got a range that's only n over 2 to the g. And what this says is that in an amount of time that is going to grow as the log of n, I'm going to get to an answer. That's really nice because it says I don't take linear time, I actually take less than linear time to get there. We'll come back to that idea later on in the course, but this is a great example of a logarithmic time algorithm finding an answer very quickly. I jumped ahead a little bit because I already started talking about what happens if I want to look for cubes only greater than 1. I could modify it to look at negative cubes, and I could modify it to look at things where the answer is less than 1. And so, for example, if x is less than 1, I just changed the search space. So now, rather than going from 1 up to x, it goes from 0 to x. Rather than going from 0 to x, I want to go from x up to 1. I'm not going to do it. I'm going to leave it for something you to try out, but it's really easy to make that change. And again, notice what I've done. Start with the basic set of code, check to see what it runs on, and then decide if I wanted to use the same code, how could small changes have it run on other kinds of solutions. What can I take away from this? Bisection search really radically reduces computation time. I went from 30,000 times through a loop to 10 or 15 times through a loop. That's really nice. And this should work on any problem with what we would call an ordering property. That is, the value of the function being solved varies monotonically. That is, it increases as the input value increases. G squared has that property. As I change G, it grows. G squared grows as G grows. G cubed, same kind of idea. So bisection search will work on any problem that has that kind of property. We're going to see more examples of that as we go through the course. We've been using exhaustive algorithms, guess and check algorithms. When we got integers, we saw that's nice because there's only going to be a finite number of solutions, but we won't be able to find, say, square roots or cube roots of numbers where that isn't a perfect square or perfect cube. We've generalized that to look at something that does a different kind of guess and check, where we take incremental steps, still enumerating all the possibilities within the resolution of that step, trying to find the solution. And we saw that that either means we take very small steps and we take a long time, or if we take larger steps, we might miss the solution. And I suggested we want to find a more effective way of doing that. So here's an example of that, and a wonderful tool that we're going to see a lot as we go through the course. It's called bisection search. Let's think about square root. One of the things we know about the square root of a number is that it lies between 1 and that number, if that number is bigger than or equal to 1. We'll do fractions in a second. So square root of 25 lies somewhere we know between 1 and 25. Here's the basic idea. Rather than trying everything starting at 1 and taking small steps, suppose we pick a number in the middle between 1 and say 25, 12 and a half. If we're lucky, that's going to be close enough. Well, it's probably not close enough in this case. We know where it is, but it's a nice start. But we can take that idea and generalize it. If it's not close enough, then we can ask, well, was the guess too big or too small? And in particular, if that guess G squared is bigger than X, we know it's too big. So what can we say? Well, we know that the answer has to lie below G. And that's really cool because it says all of this stuff here, throw it away. I don't have to look there. I know that the answer has to be somewhere between 1 and G. Do the same thing. Pick something halfway between. That's my new guess. Try it again. If it's close enough, I'm done. If it's not, ask the same question. And for example, in this case, if G squared is less than X, then we know it's too small. So we can throw that stuff away and only focus on this portion. And again, pick something in the middle and keep trying. You can already see why this is going to be really nice, because on each step, I'm throwing away half of the things that I don't have to look at anymore. And that's going to let me hopefully very quickly zero in on finding the right solution. That's a wonderful idea. It's called bisection search, and we're going to use it. So what did we say? At each stage, I'm losing half the values. Really cool. Let's see what happens if we wanted to actually make code for it. So this is a little bit of a busy slide, but we'll walk through it. This is an example of computing square root using that example of bisection search. I'm going to start off just giving it the thing I'm going to look for. X will be 25. That's the thing I'm going to use as the root. Again, I'm going to pick something that I'm going to use to tell how close I am. And I'm also going to keep track of how often do I actually run through the loop, just to compare it to what we saw earlier. I need to set a low value and a high value, the range in which I'm going to look. Initially, that is 1 to the number itself. And then I'm going to make an initial guess, which is halfway in between. Just high plus low divided by 2. And then I run through one of those nice little loops. What do? I say, if the difference between the answer squared and X is bigger than or equal to epsilon, I'm not close enough. And in that case, I'm going to print out some information, increase the number of guesses by 1, and then do what I just did, which is if answer is too small, that is, its answer squared is less than X, then I can change the low part of the range to move up to answer. And if answer is too big, I can change the high part of the range down to answer. As I did before, I start out here. If answer was too big, I change the high range to bring it down into there. If answer is too small, I bring the low range down into there. And I keep sorting it down until I get into something that's reasonable. This algorithm just captured that idea I just described. So let's try it out. We'll do it with 25. Here's a bisection search on square root. And if I run this code, wow, it actually got there very quickly. It did it in 13 guesses. I'll remind you, in the previous case, we took 30,000 guesses to get there. I don't want to print all that out on my screen. And notice how quickly it zeroes in. It starts off with low 0 and high 25. And then it says low 0 and high 12.5. And then low 0 and high 6.5. You can see if you look at the printout how quickly it narrows in on the range. That's really cool. Okay? Do the same thing with cube root. I can do exactly the same idea. This is almost exactly the same code. The only difference is I'm using guess cubed rather than guess squared. And I'm going to keep track of otherwise exactly the same information. And let's compare that. If I go over and pull up my cube root example, we'll start with 27. Again, I'll remind you that in this case I was doing 30,000 checks to deal with this. Now I run it, and in 14 guesses, it gives me a really good answer. And if I pick something that's not a perfect cube, like 54, and I do the same thing, in this case, it took 15 guesses to get me a really good answer. This is a powerful tool. That idea of bisection search, throwing away half the possible values at every stage, lets me very quickly zero in. As before, I can ask, well, can I do everything? This is only going to work for numbers bigger than 1. What about fractions? Well, I know with fractions between 0 and 1, now the difference is that the root doesn't lie between the number and x itself, it lies between 0 and that number. But that's an easy ways to change, and we could actually think about making that change. But just to remind you of how powerful this is, notice what happens. If I start off with the number n, on the first guess, I reduce the set of things in half. On the second guess, I reduce it by another half, so it's now n over 4. After g guesses, I've got a range that's only n over 2 to the g. And what this says is that in an amount of time that is going to grow as the log of n, I'm going to get to an answer. That's really nice because it says I don't take linear time, I actually take less than linear time to get there. We'll come back to that idea later on in the course, but this is a great example of a logarithmic time algorithm finding an answer very quickly. I jumped ahead a little bit because I already started talking about what happens if I want to look for cubes only greater than 1. I could modify it to look at negative cubes, and I could modify it to look at things where the answer is less than 1. And so, for example, if x is less than 1, I just changed the search space. So now, rather than going from 1 up to x, it goes from 0 to x. Rather than going from 0 to x, I want to go from x up to 1. I'm not going to do it. I'm going to leave it for something you to try out, but it's really easy to make that change. And again, notice what I've done. Start with the basic set of code, check to see what it runs on, and then decide if I wanted to use the same code, how could small changes have it run on other kinds of solutions. What can I take away from this? Bisection search really radically reduces computation time. I went from 30,000 times through a loop to 10 or 15 times through a loop. That's really nice. And this should work on any problem with what we would call an ordering property. That is, the value of the function being solved varies monotonically. That is, it increases as the input value increases. G squared has that property. As I change g, it grows. G squared grows as g grows. G cubed, same kind of idea. So bisection search will work on any problem that has that kind of property. We're going to see more examples of that as we go through the course. We just saw an example where we could have multiple recursive calls inside the body of a function. Perfectly fine. I want to show you a different example now in which we could have multiple base cases inside of a problem. And for this, I'm going to use another classic old problem called Fibonacci numbers. And here's the story behind Fibonacci. Leonardo of Pisa, also known as Fibonacci, posed the following challenge. He said, imagine I put a newborn pair of rabbits, one female, one male, in a pen or an enclosure. And I'm going to assume that rabbits mate at age 1 month, and that rabbits have a 1 month gestation period. That is, they produce a new pair. The female produces a new pair at the end of a month. He's also going to assume that rabbits never die, and that the female always produces one new pair, one male and one female, every month from its second month on. And Fibonacci wanted to know how many female rabbits are there at the end of 1 year. So let's do a little sort of simulation of this, and then we'll figure out how to actually solve it. So we start off with a pair of immature rabbits, a male and a female, the first month. At the end of 1 month, they've matured. They can therefore mate, and at the end of the next month, they're still around, but they've produced offspring, another male and a female. At the end of the next month, the original pair have produced another pair of offspring, and the first pair of offspring have matured. And that means at the end of the next month, both sets of mature rabbits now produce offspring, and another one is matured. And that keeps happening as we start generating more rabbits and more rabbits and more rabbits until we're overrun with rabbits. Question is, could I model this to deduce how many female rabbits are there at the end of a year, 2 years, 5 years, and when will Australia completely get overwhelmed with rabbits, just to take an example of a place with too many rabbits. So, what does this say? I've got a little sequence here. In fact, they're known as the Fibonacci numbers, in which I have the following property. At the end of 1 month, I've got 1 female. At the end of the 2nd month, I've also got 1 female, who's now pregnant. At the end of the 3rd month, I got 2 females, 1 pregnant, 1 not. And in general, at n months, I've got however many females there were at the previous time, and I've also got however many females there were 2 months ago. Why? Because every female alive at month n-2 will have produced 1 new female at time in month n, and those can be added to the number that were alive in month n-1 to get the total that were alive in month n. So there's basically the definition of Fibonacci numbers. And how do I capture that in code? Well, here I've got 2 base cases. I've got how many females at time 0, how many females at time 1. And my recursive case, notice, involves 2 invocations of that function, 1 for n-1 and 1 for n-2. And if I want to turn that into code, there it is. I've got 2 base cases. I'm doing it in 1 test, but I'm saying if x is either equal to 0 or x is equal to 1, return 1. Otherwise, return fib of x-1 plus fib of x-2. And if I were to run that, I can see that I can actually compute Fibonacci. Given fib, I can check that my base cases work. Fib of 0 gives me 1. Fib of 1 gives me 1. And just to do a couple of trials, fib of 2 should give me the sum of those, and fib of 3 should give me the sum of those, and fib of 4 should give me the sum of those. And you can see, in fact, it is doing what I expected it would do. Here's a case where I've got 2 base cases. And in fact, I kind of know I need it because my return here in the general case needs 2 different invocations of that function. And I need 2 base cases to make sure that I can settle that out. Now that we have the ability to create functions, to define our own functions, we're going to be able to start solving some really neat problems, including some of the ones we've just looked at. But one of the things that's going to happen is that we're going to be able to create lots of functions, and that means that we need to think about how to handle them. So far, we've assumed that all of our code is stored in 1 file. And that's cumbersome when I've got large collections of code, or especially when I've got a collection of code that's going to be used by different places or different people in different places, and I'd like to be able to access it directly. And so for that, we're going to introduce something you're going to use a lot. It's called a module. And basically a module is a Python file that has something with the .py extension to it that's a collection of Python definitions of statements. Once I've got that module, I can use it, and I need to talk briefly about how do you use it. So for example, imagine I've created a little file called circle.py. It's a Python file called circle, and it's got in it a couple of simple functions for dealing with properties of circles. Compute the area, compute the circumference. I've also put a definition of pi inside of there. I've saved that file away, and now I want to use it. How might I use it? Well, I can import it. I can either import it into the shell itself, or I could import it, in fact, into some other file because I want to use it there. And so the usage here is if I invoke the command import circle, it goes and finds that file and reads all of the statements, including the definitions and assignments inside that file, into, in this case, the shell. Now, inside of the shell, I could redefine pi to be 3. That's okay because I'm walking inside the shell. I could print that out, and in that case, it's going to print out 3. But then I could print out the value of pi that was defined in the module circle. And to do that, I use this notation here of circle with a dot followed by pi. It's telling me in the module circle, look up the value of pi. And that will print out what I defined there, 3.14159. And similarly, I could call the function defined in circle, again, the dot that says inside of the circle module, get the function called area, and call it on an argument 3, and it prints out something. And the same thing with circumference. So I can import things into my environment, whether again it's the shell or, as we'll see later on, inside of another environment, or inside of another file itself, because I want to use it there. If I don't want to refer to the functions and variables by their module, if I don't want to use that slightly clunky circle.py or circle.area, and I know that the names in that module don't collide with things I'm using directly either inside the shell or inside of a new function, I can in fact do a slightly different version in which I say from a module, in this case circle, import everything. And the everything is done by simply giving it a star. That will bring all of the definitions, all of the assignments into that environment. But now I simply refer to them by their name. I don't have to put that extra circle dot in front of them. This has the effect of creating bindings within the current scope for all of the objects defined within circle. And the statements, as a consequence, within a module are executed only the first time a module is imported. If I want to redo something, I have to recall that actual invocation. But that gives me a nice way to start building modularity at a higher scale, by files as well as by functions. And that leads to the last piece we're going to deal with today, which is we need a way to save our work for later use. And we certainly have that if we do something inside of the text editor, but we also want to be able to do that inside of computations we're doing. Every operating system on a computer has its own way of handling files, and so Python handles this by providing an operating system independent way of accessing files called a file handle. And the way that is done is by using the special command open and giving it the name of a file and giving it a command. So in this particular case, open is going to open up a file handle, that is an access into a file with the name kids, and the W here says that it's opened for writing. I'm going to be able to write into it. And I've bound that to a name so I can refer to it. Name handle is the handle that gets into that file. That allows me then to use it. So for example, I could write a little loop that says to the user, type in a name, and I'll write it into that file by, again, using name handle and the dot and then the write command. And this little extra character here is a string that just says do a carriage return or start a new line after the end of this write. I could do it as many times as I want. In this case, it was just going to be 2 times. But what I'm doing is I'm writing directly into a file, in this case called kids, things that I'm inputting on the terminal. You could imagine I'm also doing computations and writing them away. When I'm done, I close the file handle by invoking the method close. Again, with name handle, because that's the one I set up here, dot close, and the open close paren to say that it's actually an invoking of a function that closes up the file. And finally, I can do the same thing where I want to read from a file by giving it the special string R. And in this case, I could read from that file and just print out a set of things, and when I'm done, again, close them off. So this gives you a little bit more power now, and it's part of that idea of modularity. I have functions giving me modularity. I can have collections of functions inside of files. I can create files as I'm interacting with them, and I can use all of those ideas to really control the complexity of the systems that I'm building. Now that we've introduced the idea of a definition, a function in particular, as a way of doing encapsulation of information, we can start exploring some of the variations to them. And I want to show you one place in Python that's actually can be very handy. And that is that I can have a function definition that I can change in terms of how I want to think about invoking it. So let's start with a simple function here. This is a very simple function that says if the last argument is true, then I'm going to print the last name, comma, first name. Otherwise, I'm going to print the first name, comma, followed by the last name. And I'm going to expect those to be strings. And I've got a simple little implementation of over here. I'm going to import it into my Python shell so I can use it. But at this stage, you can hopefully look at this function and realize, given some value for reverse, I'm going to test that. If it's true, I'm going to do this, which is just a print. It's not going to return anything. If it's false, I'm going to do that. Okay? Now, here's one of the nice variations on it. First of all, that first call does sort of what I'd expect. And in fact, if I go to my Python and type it in, I can say if I do print name, and I'll do myself of Eric Grimson, and I give false as the value for reverse, it prints it out in the order I expected. I could do, by the way, the same thing. I could say print name just to show you it does the right thing of Eric and Grimson. Notice the commas, by the way, to separate the parameters, and I give it true. It would help if I can type, so I'll do it one more time with Eric Grimson and true. Now it prints it out in the other order. But here are some of the variations. I could say explicitly, give the binding to the parameter name reverse the value false. So doing it in the same place, but I can actually specify it. I could similarly, for any of the parameters, in the invocation, literally say the parameter followed by an equal sign and the value that I want. And all three of these are going to print out exactly the same thing. And in fact, so will the last one. But notice here, I've reversed the order. So if I'm not going to use this kind of formalism, I have to give the parameter in the place it expects. But in this case, I reversed it. Even though the function expects first name, then last name, I've said I'm going to have last name have the binding Grimson, first name have the binding Eric, and reverse equal to false. That's nice if I forget the order, or if I just decide I want to call them in a different way. I can do some other things here, though. I can change the definition of my function to give a default value to one of the parameters. In this case, the syntax is there's the parameter name, and I'm saying let it have initially the binding of false. And that means that if I call the function, as I do right here, without an explicit parameter passed in or value passed in for that parameter, the default holds true. In this case, I'm going to assume that reverse is false, and therefore I'm going to do this particular print statement. On the other hand, if I want to change the value of that, I need to give it an explicit value to overwrite the default value. And this is handy if I've got a parameter that normally I expect just to have a particular value, but on rare occasions I might want to change it. My invocations don't have to always pass in those values. So a nice little variation on how we pass values in to parameters of definitions of functions. Now that we've got an understanding of floating point numbers, now that we've got the idea of generalizing guess and check methods to do things that can do approximations to find solutions to things, we can really start building some pretty powerful programs. We've already seen something that searches for cube roots of numbers, even if they're not a perfect cube, square roots of numbers, even if they're not a perfect square. And we've seen how we can get to quick solutions very nicely using things like bisection search, have great accuracy and still find good answers. I want to show you one last example just to give you a sense of the power of computation we can now do. I'm going to stick with the idea of finding roots of things, but show you how you can actually capture things very dramatically. And that's to use a technique called Newton-Raphson. It was discovered by Sir Isaac Newton 3 or 4 centuries ago, also discovered by Raphson at about the same time. And here's the basic idea behind Newton-Raphson. It's a general approximation algorithm that's going to let us find roots of any polynomial in one variable. So that could be, for example, the polynomial like this. I've got p of x is some coefficient times x to the n plus some other coefficient times x to the n plus minus 1 and so on. And what I want to do is find the value r such that p of r is equal to 0. It's called a root. It basically is the root of this equation. Newton-Raphson will apply to any polynomial. I'm going to show you an example of using it to find square roots. And you can say, well, I already did that with bisection search. You're right. But it's a nice way of looking at how we can generalize the computation. So in particular, if I want to find the square root of 24, I'm going to use the polynomial x squared equals 24. Because if I can find the value of x for which this is 0, then x is, in fact, the square root of 24. What Newton showed was that if g is a good guess to that root, then you can get an even better guess by taking g and subtracting from it the polynomial evaluated at g divided by the derivative of the polynomial evaluated at g. And if you haven't done calculus and you don't know what a derivative is, don't worry. We're going to show you what it is in this simple case of a square root. But I want to see I want to let you see the power of doing Newton-Raphson. So Newton showed If I got a good guess, I can make it better by taking P of G divided by the derivative of P at G and subtracting that off of G. So in the simple case, if I've got an equation that is some constant times x squared plus another constant, then the first derivative of c times x squared is just 2cx. So in my case of looking for square roots, x squared is plus k is the thing I'm trying to find a solution of, the derivative is just 2x. And so Newton-Raphson says, given a guess for the root, take the polynomial at that point, which is g squared minus k, take the derivative of that point, which is just 2g, take that ratio and subtract it off from g. Cool. We ought to be able to build that, and we can. It's a nice, tight, little iterative loop. So here's a nice way of generating the guesses. Again, I'm going to have some epsilon that's going to let me decide how close I am to an answer. I got the thing I'm going to look for, and my initial guess I'm just going to pick as that value divided by 2. And then here's the loop. As long as guess squared minus y, the absolute value of that is too big, I'm going to keep going. And as before, I'm going to count the number of guesses to see how long it takes. Each time around, I'm going to use that little equation from Newton-Raphson. I'm going to take g squared minus y, divide it by 2 times g, or guess, subtract that off of guess, and go back around. That's just the thing I did before. And I'm going to run through that loop until I get something close enough, and then I'm going to jump out. So let's see what happens if we do it. I've got the code over here. I'm going to load it in and run it. And in 4 guesses, it got a good solution. 4. Okay, it's a whole lot better than 30,000, which is where we started. With the bisection search, it was about 15 or 20. Now I've got it down to 4. Let's pick another example. Let's take my favorite example here of 54. Same thing, and I run it. And in 5 guesses, it gives me a good solution out. This is really cool. I know you don't believe it, but it really is cool because it lets me not only find cube roots and square roots, it lets me find the solution to any equation very quickly. So what we've now seen is that this idea of a guess and check method builds on reusing the same code over and over again. It takes the idea of a looping mechanism and adds to it, building into it different ways to generate the guesses and then checking to see whether I'm close enough or I want to keep going. And we've already seen now simple exhaustive enumeration, bisection search, which cuts down the amount of expense dramatically, and now, at least for root finding, Newton-Raphson, which improves it even more formally. So you've already seen 3 different classes of algorithms, and you've got a lot of tools for doing numerical computation. We're going to come back to that as we move on through the course. In the last lecture, we added looping variants. We had for loops, we had while loops, we had the notion of iteration. We used that to start generating some examples of guess and check algorithms. In this lecture, we're going to go back to that idea, but extend it, and we're going to add in another kind of data type, a string. We talked about it a little bit earlier on, but we're going to use it to actually look at ways to generate algorithms that can start to do some more interesting kinds of things. Just to review, I want to remind you what we did inside of loops. Here's an example of some code that's going to compute a square root of something. And it does it by running through a loop. As we've done before, it's going to set up an initial value, which it gets here by inputting something that enters an integer. And then it's going to run through a little while loop where it does guess and check. It keeps trying different versions of answers, starting at 0, then 1, then 2, going on until it sees whether that answer squared is bigger than or equal to x. Once it gets to that point, it checks to see if it's actually the square is equal to x, in which case it prints out that it's found the cube root. And if not, it tells me that it's not a perfect cube. And just depending on whether it was a positive or negative thing, it gives me a little bit of additional information. You can look through the code. I'm not going to run it. What I want you to see is that idea of guess and check. I generate values for answer until I get to a point where either I'm done and I have the answer or I've gone too far. And again, as before, I've got something where I'm setting up the variable outside and I'm changing the variable inside with a test that depends on it. We're going to use that idea as we generalize, but I want to remind you of what loops do. And as before, I don't need to do that actual version of answer equal answer plus 1. I could use plus equal as a variation of it. We also talked about strings earlier, and I just want to remind you of those because we're going to use them in this lecture as well. Think of strings as a sequence of characters. In fact, case-sensitive characters. For letters, could be lowercase or uppercase. As with numbers, I can compare them. I can say if two strings are equal by using the double equal sign. I can use greater than or less than, using lexicographic order to decide if two strings are greater than or less than each other. Length can give me the number of things in the string. And as we saw before, we can use square brackets to do indexing into a string. We can get the 0th element. Remember, it starts at 0. The first element, the second element. And if I have a string 3 long and I try and get something 3 or bigger, it's going to complain, telling me that I've tried to access beyond the end of the string. We also saw slicing in strings. This lets us go into a string and pull out pieces of the string. And here we saw we can specify a start point, a stop point, and how many steps to take as we do the accessing. And that lets us pull out different elements out of a string. One unusual thing we haven't seen before is if the step is -1, we actually access the string in reverse order. There it is right there. Otherwise, if we say, for example, start with the element 3, it says 0, 0, 1, 2, 3. So I start here, and I stop just before the 6th one. So 3, 4, 5. I'm going to pull that out, which gives me the piece that I wanted there. One last thing about strings is that they are what we call an immutable type. You can't change them. They can't be modified. And to see that, let me do a little example. I've shown it on the slide, but let me actually type it in over here. I'm going to define the string s to be, I'm going to define the name s to be the string hello. If I print out s, it gives me back. If I say what's the type of s, it tells me that it's a string, which is great. I can certainly index it by saying, give me the 0th element of s. But if I wanted to change the 0th element of s, for example, saying, I want to have the 0th element of s be the character y, it's going to complain. I can't go in and change a piece of s. We're going to see other structures where we can do that are called mutable. Strings are not. I can't say, I want the 0th element of s to be y. I can change it, but I have to redefine s. So I could say, let s be the character y plus the rest of s starting at 1. And I could, in fact, say until I get to the length of s, or I can just say 1 all the way on to the end. And now, if I look at s, it's yellow. Misspelled for yellow. Point is, I've now changed the definition for s. So I can't change it individually. I have to redefine s. And that's why I say strings are immutable. One of the things I would suggest to you is if you're not sure what a command does, look it up or try it out yourself. That'll give you a sense of the different things you can do with strings as you move along. And here, just to remind you, s was initially bound to hello. When I do the last call, I'm changing that binding and redefining it to be a changed new version of a string. The original string is still stuck in memory. It's just floating around. I can't access it anymore. Finally, remember for loops, the quick recap, we have that idea of having a loop variable that iterates over a set of values. And we can either do that with simple things like the range shown here, which is going to go from 0 up to 4, but I could also do it starting at 4, going up to 8. Expressions inside the loop are going to be executed for each value of the variable that I use. And so range is a nice way to iterate over numbers, but a for loop variable can iterate over any set of values, not just numbers. And so, for example, I could loop over strings. That sounds kind of neat. So here's a simple little piece of code. I've defined s to be a string, the first set of letters in the alphabet. And I can now write a for loop that says, loop for the index over the range of the length of s. Boy, that's a lot of words. Let's say it a little bit better. It says, I'm going to see how long is s, and then I'm going to use range to generate the integers from 0 up to s, the length of s minus 1. I'm going to call that index, and then I could run through a loop that says, if the element of s at that point is either an I or a U, I'm going to print out a little piece of information. No big deal. That just looks like a normal loop over integers. But I could also write it this way. I could say loop for character in s. And that's kind of cool. S is something we call an iterable. It says I can actually write a loop that lets characters start with the first element of S, and then the second element of S, and then the third element of S, doing the same kind of test as I move along. And it will do this until it runs out of characters in S, in which case it will execute, or exit from the loop rather, and move on to other kinds of things. That second piece of code is much cleaner. It's easier to see what I'm doing. I'm looping for all the characters in a string, as opposed to saying I'm looping for an index over all the indices into the string. And that's one of the nice things about both strings and especially about loops. I can iterate over anything where I can successively enumerate each of the elements of that piece. So now I've got strings as something which I can use as parts of loops, and that's really nice. Let me give you one last example, sort of a fun example. I'm going to set up a little loop that is going to run over basically a set of words. And what is it going to do inside of here? I got a little while loop here that says as long as, rephrase it, I'm going to input a word based on some input I give there. And what it's going to do is it's going to loop over all of the things inside of the word, basically saying if the character in the word is in a special set of characters, I'm going to print out something based on that. If it's not, I'm going to print out something different based on that. And then I'm going to increment I, and I'm going to keep going. So again, it's a while loop, but I'm using the character inside there to loop over particular elements of a string. Let's see what this does. So here's the code, and if I load it into my environment, it says I'm going to cheer for you. Give me a word. So we'll give it the best word I know, which is, let me just get it over here, which is MIT. And it says, how enthusiastic are you about MIT? Well, I like MIT a lot, so I'm going to give it a 10 out of 10. And it says, I'm not going to repeat it all, but give me an M. M, give me an I, give me a T. T, what is it spelled? And it prints it all out. All right, it's a lame example, but you know what? I'm from MIT, I like it. What I want you to see is how I'm looping over, especially here, in this place right in here, I'm using the loop over a set of strings in order to be able to decide what I'm going to do. And why am I doing that? Because if it's something that is a vowel, I don't want to say give me a, I want to say give me an A. If it's something like an M that we pronounce that way, I want to say give me an M. Whereas in the other cases, I want to say just give me a C, give me a D. Okay, cute example, key point. I've now got two different loops going on here. The outer one is walking through each of the elements of the word. That's this one right here. And that's just doing the standard thing where I've set an iteration variable outside, right there. I'm changing it inside the loop. But in the loop, I've got another one, which is right here where I'm looping over all of the elements of a string. I can do it either way, and that works out really well. On that cheery note, we're going to move on to another topic. We've now begun to look at functions. We're going to do more of those in a second, but it's important to take a little break here to talk about one other piece of a function, and that was the idea of a specification. This is something we're going to use to be able to decide how we want to use a function, and think of a specification, therefore, as a contract. We don't enforce it necessarily, but it's a contract between the implementer of the function and the people who are going to use it. That specification ideally will say, here are the assumptions. Here's what the implementer of this function assumed was going to be true, especially about the values of parameters. If you like, it's the conditions that a client needs to guarantee are true before they use it. And then if those assumptions are in fact met, the second part of the specification are the guarantees. It says, here's what the function will do, provided it's been called in a manner consistent with the assumptions. The way we do it in Python is to use this idea of a docstring. And there's my earlier definition of is-even. It has a condition on the input. It says, if you give me an integer, which I'm calling I, in particular a positive integer, then here's what I guarantee, that it will return true if I is even, otherwise it's going to return false. Now, you're not required to put in a docstring or a spec, but good programmers always do, in part because somebody else might use this and you want to tell them how you expect it to be used. Or because a year from now, 2 years from now, you may come back to this function and you'd like to know, what was I thinking when I built it? So I encourage you to build your own docstrings, even though it takes a little more time, because it helps you understand what's expected of a piece of code and where can I use it. We've seen some simple examples of recursion. Factorial, doing multiplication by doing recursive addition. These are nice places to start. But recursion is actually really a powerful tool, and I want to show you a very different way of thinking about recursion on a problem that's otherwise hard to solve if you don't think about it recursively. And this is to take a classic problem called the Towers of Hanoi. The story is that somewhere in a temple in Hanoi, there are 3 tall spikes on which there are initially 64 discs of different sizes all stacked together in decreasing order, with the largest at the bottom going all the way up to having the smallest at the top. And the goal of the priests in this temple is to move the entire stack from one spike to another one, moving one disc at a time, but with the property that they can never have a larger disc covering up a smaller disc. And there's a little animation you may be watching at the bottom here that's showing an example of that with a stack of size 3. We want to figure out, how would I write a program to tell the priests exactly how to move those discs so that they can move all 64 from one spike to the other. And I'm going to do a little demo to show that to you. So I want to demonstrate for you how to solve Towers of Hanoi, and especially how to use recursive thinking to do that. But to begin with, I'm simply going to show you solutions to Towers of Hanoi and see if you could figure out how to write code to describe the set of moves that would solve it. Let's start with the easiest case. I have a stack of size 1. Moving it is easy. I just move the disk. If I have a stack of size 2, I know I've got to move the smaller disk to the spare place while I move the bottom one, and then move it over. Pretty straightforward. If I want to move a stack of size 3, it takes a little more work because I got to move the top disk. I got to be careful not to cover up a smaller disk with a larger one. But once I've cleared the bottom disk, I can move it. And again, move the top disk to the spare one so that I move the entire thing without covering up a smaller disk with a larger disk. Also pretty easy. But what about a stack of size 4? It takes a little more thinking because I have to really be careful here that I'm not accidentally covering things up. And it takes a lot more work to, in fact, expose that bottom disk, which I'm now ready to move. And now I got to get all of those back over again without covering a smaller disk with a larger one. And so that allows me basically to make that set of moves to get to that point. Great. Easy to write code to do this, right? Probably not. But if I think about it recursively, it's really easy. So what does that mean? I want to move a stack of n disks. And recursively, I would say, if I already knew how to move a smaller stack, what's my solution? Oh, that's easy. Move a slightly smaller stack to the spare disk. Now I can move the bottom disk and move that stack to the target. And what does it mean to move that stack to the target? Move a slightly smaller stack to the spare disk, move the bottom one, and move that stack. And I'll just keep unwinding that until I'm just moving single disks. Recursively, this is easy to see, and that leads to a very natural implementation. Okay, what you saw in that demo is that it's going to be hard, even if you watch things like moving a stack of 3 or a stack of 4, how would you write the code to do it? And then what you saw is if I think about it recursively, it's actually really easy. Because recursively, what do? I solve a smaller problem. Move a stack of size n-1 onto the spare disk. Then I've got just one disk left on the bottom of it. I move that one, it's a simpler problem. And then I move that stack that I temporarily moved to the other side back onto the place I'm going to. Recursively, this is really easy to see. And so even though this looked like a very hard problem, it's very easy to write code to do it. And so there is, in fact, a little set of code that says, I got a function that simply says, print an individual move from the from stack to the to stack. And then here, notice what I've got. I've got a test for a base case. If I've got just a stack of size 1, I'm just going to print the move to take it from to 2. Otherwise, I actually now have to solve 2 recursive problems. So it's a little bit different. I'm going to move a smaller stack from the from to the spare spot. Having done that, I'm going to move the simple case to the place I'm trying to go to. And then I got to move that smaller size stack from the spare over to the to spot. But the code itself is really straightforward. And if in fact I go and run this, on a stack of size 4, it gives me very nicely all of the moves I want to do to move that stack over. What I want you to see here are two things. One, I can have multiple recursive calls inside of a function body. It's perfectly fine. And two, this is a problem that I suggest is really hard to solve iteratively, but elegantly easy to solve recursively. And I want you to think about that notion of break it down into a smaller version of the same problem, assume that can be solved, build your solution with that and other simple operations, and let the recursion then unwind it to get to the solution that you want. Just as strings come with standard operations in Python, so do lists and tuples. And I want to show you examples of standard operations in lists that are really valuable to have. The first one is I could add something to the end of the list, and that's going to be nice as I want to accumulate results. So let me show you a little example here. I'm going to type in a definition for L as the list, so a squared brace of 2, 1, and 3. And just to make sure it's right, I'm going to print out what L is, and there it is. If I want to add something to the end of the list, I can do that with append. And there's a dot there that I'm going to come back to in a second, but I could append 5 to the end of the list. Doesn't print anything, but it's done something for me. And what's it done? It's actually added 5 to the end of L. So there's now the structure of it. And the key issue here is it has mutated it. It has actually changed L itself. So anything that was depending on L being 3 elements long is now in trouble because it's now 4 elements long. Now, what about that funky little dot? We've seen an example of this earlier. We're going to see more of it later on. This dot is taking advantage of something inside of Python. Everything in Python, or almost everything in Python, is an object. And lists are an example of a Python object, a collection of things put together. Objects have data inside of them, but they also have methods and functions. And we get to that by using that dot. So given an object name, for example, here it was L, the dot says get out some method, or if you want to think of it, some function associated with that kind of object, and then call it with open paren, followed by close paren. And that's literally what's happening here is this dot is saying, look at L, what is it? It's a list, so get the append method or function associated with lists and apply it. We'll come back to that later on, but that's what's happening when we use the append there. Key point here is append can add something to a list. Good thing to have. We can also concatenate, as we did with tuples or strings. So if I've got one list L1 and I've got another list L2, then I can add the two together. So let me, in fact, do the same thing here. I've got L1, let's call it again the list 2, 1, 3. I'm going to create L2. It's also going to be a list 4, 5, 6. And I can concatenate them. I could say, let L3 be L1 plus L2. And when I do that, I can look at L3, and it's now the list of 6 things together. Notice, by the way, that in this case, L1 has not changed, nor has L2. L3 is a new list that has been formed by concatenating together copies of L1 and L2. If I wanted to extend a list, I can do that with an explicit call. An extend basically does what you say. It says take a list and add to the end of it. And so I can do L1 and extend it, for example, with 0 and 6. And now if I look at L1, it's changed. It mutated, and that's the point. So concatenation does not mutate. Extension does, and it makes sense. Extension says you should take something and add to it, as opposed to you should take something and do something interesting with it, which is what concatenation does. I can also remove things from lists. I can delete an element at a specific point, and I use that with just the general command del for delete. And I basically can do it by saying remove something from a particular place. And I do it, in fact, by giving it a specific element. All right, and so let me take an example here. Here is L1. And if I do del of L1, and let's pick, I don't know, the third element here. Now I look at L1. Oh, good. That element has disappeared. I can also remove the element from the end of a list, something that's very handy when I'm trying to walk down a list, and I do that with the pop method. It comes from an old expression of popping something off of a stack. And it returns that actual element as well as changing the list itself. I can remove a specific element by using remove. And what it will do is look for that actual element in the list and remove it. If that element occurs multiple times, it's only going to remove the first occurrence. And if you try and remove something not in the list, it's going to give an error. So for example, if I set up L to be this list, 2136370, if I call L with remove of 2, it will mutate the list, change the list, taking that element out, as you can see. If I say remove 3, it will take the first instance of 3 out, but it leaves a second one around, as you can see right there. If I delete a specific spot in the list, I already did that, it takes out the next one in that list at the first index, which is right there. And if I pop, it removes the last one and returns it, again mutating the list. So operations that I have on lists. These are going to become handy as we start thinking about doing things with lists. I can go back and forth between lists and strings. If I've got a string and I want to convert it into a list, I can literally call the procedure or function list on that string. And it returns a list with every character in the string now separated out as a separate element of the list. So let me show you a simple example. I'm going to set list to be the string ABC. Not very interesting, but it'll work. And if I now say, give me the list of S, it nicely gives me back a list with each character as a separate string inside of that list. I might want to do some processing on these strings or on these lists as well. And so one of the things I can do is I can use the split method to split a string on a particular character. If I call it just with a standard call on split, it will do it on a particular character. I can also split it on spaces if I give it no parameter. And so I've got an example down here. I've set up a string S. I can turn it into a list. There it is. I could also split the string and turn it into a list. And that I've done by saying I want to split it at this character. And notice what it's done. It has literally broken it up into two parts. There's the first part, there's the second part, right there. I can also do conversions of lists back into strings. So if I create a list such as this one here, I can join them together using this call. There's the join operation, there's the dot, and I'm giving it an empty string, and it's basically saying, given that this is a string, use the join operation on that string to merge everything together, and it will return out just the string with the pieces stuck together. If I want to, I can do a join, but have the join insert a character between each of the things. And in this case, I give it an underbar, I use the dot, I ask it to join, and it returns the string with it A underbar B underbar C. So I can go back and forth between lists and strings. Again, something that's going to be really handy in a little while. There are a couple of other list operations of value. I've already said, while I talk about a list as being an ordered sequence, it doesn't mean the elements inside of it are ordered, but I can do that. I could actually sort a list. And I have two ways of doing the sorting. I can sort the list and return a new version of it, or I could actually mutate the list and sort it itself. And so I want to give you an example here. If I set up L to be the list of 9, 6, 0, and 3, it's certainly not sorted. And if I look at L, there it is. If I call the special function sorted on L, it returns a sorted version of L. But L itself has not changed. That's handy if I want to keep L around, but I want a sorted version of it. On the other hand, if I really don't care about what I do with L afterwards, but I want the sorted version, I can call L dot sort. Again, it's a method with coming off after that dot to tell me to do this. I do an open close to say invoke the function. And now if I look at L, it is in fact sorted. Similarly, I could reverse a list by calling reverse as a method, using the dot to say use the reverse associated with lists. and it will change L itself and create something in reverse order. Handy things to have. Things are going to let us start manipulating larger data structures as we move forward with thinking about how to do computation on bigger collections of pieces. We can now bring all of these pieces together because we've got loops, functions, range, and lists. And how do I want to bring them together? We've already talked about range. We said it was a special procedure. And we said it returns something that behaves essentially like a tuple, or if you want to think about it like a list, but really more like a tuple. It doesn't generate all of the elements at once, however. Rather, it generates the first element and provides a method that says, when you want the next one, I'll give it to you. That's nice if I don't want to have to generate a huge range before I start doing some computation. But I can think of ranges now as acting like a tuple. So range of 5 really behaves like the tuples 0 through 4. Or if you want to think of it that way, like the list 0 through 4. Range of 2, 6 is going to behave as if it was that collection of those integers, as a tuple or as a list. And as a consequence, when we use range in a for loop, what that loop variable is doing is just iterating over that range as if it were a list. We could write it directly, but it's going to be a nice, convenient shortcut to have, because we're going to be able to do things much more efficiently without generating the entire range before we start working on it. Just as strings come with standard operations in Python, so do lists and tuples. And I want to show you examples of standard operations in lists that are really valuable to have. The first one is I could add something to the end of the list, and that's going to be nice as I want to accumulate results. So let me show you a little example here. I'm going to type in a definition for L as the list, so a squared brace of 2, 1, and 3. And just to make sure it's right, I'm going to print out what L is, and there it is. If I want to add something to the end of the list, I can do that with append. And there's a dot there that I'm going to come back to in a second, but I could append 5 to the end of the list. Doesn't print anything, but it's done something for me. And what's it done? It's actually added 5 to the end of L. So there's now the structure of it. And the key issue here is it has mutated it. It has actually changed L itself. So anything that was depending on L being 3 elements long is now in trouble because it's now 4 elements long. Now, what about that funky little dot? We've seen an example of this earlier. We're going to see more of it later on. This dot is taking advantage of something inside of Python. Everything in Python, or almost everything in Python, is an object. And lists are an example of a Python object, a collection of things put together. Objects have data inside of them, but they also have methods and functions. And we get to that by using that dot. So given an object name, for example, here it was L, the dot says get out some method, or if you want to think of it, some function associated with that kind of object, and then call it with open paren, followed by close paren. And that's literally what's happening here. Is this dot is saying, look at L, what is it? It's a list, so get the append method or function associated with lists and apply it. We'll come back to that later on, but that's what's happening when we use the append there. Key point here is append can add something to a list. Good thing to have. We can also concatenate, as we did with tuples or strings. So if I've got one list L1 and I've got another list L2, then I can add the two together. So let me, in fact, do the same thing here. I've got L1, let's call it again the list 2, 1, 3. I'm going to create L2. It's also going to be a list 4, 5, 6. And I can concatenate them. I could say, let L3 be L1 plus L2. And when I do that, I can look at L3, and it's now the list of 6 things together. Notice, by the way, that in this case, L1 has not changed, nor has L2. L3 is a new list that has been formed by concatenating together copies of L1 and L2. If I wanted to extend a list, I can do that with an explicit call. An extend basically does what you say. It says take a list and add to the end of it. And so I can do L1 and extend it, for example, with 0 and 6. And now if I look at L1, it's changed. It mutated, and that's the point. So concatenation does not mutate. Extension does, and it makes sense. Extension says you should take something and add to it, as opposed to you should take something and do something interesting with it, which is what concatenation does. I can also remove things from lists. I can delete an element at a specific point, and I use that with just the general command del for delete. And I basically can do it by saying remove something from a particular place. And I do it, in fact, by giving it a specific element. All right, and so let me take an example here. Here is L1. And if I do del of L1, and let's pick, I don't know, the third element here. Now I look at L1. Oh, good. That element has disappeared. I can also remove the element from the end of a list. Something that's very handy when I'm trying to walk down a list, and I do that with the pop method. It comes from an old expression of popping something off of a stack. And it returns that actual element as well as changing the list itself. I can remove a specific element by using remove. And what it will do is look for that actual element in the list and remove it. If that element occurs multiple times, it's only going to remove the first occurrence. And if you try and remove something not in the list, it's going to give an error. So for example, if I set up L to be this list, 2136370, if I call L with remove of 2, it will mutate the list, change the list, taking that element out, as you can see. If I say remove 3, it will take the first instance of 3 out, but it leaves a second one around, as you can see right there. If I delete a specific spot in the list, I already did that, it takes out the next one in that list at the first index, which is right there. And if I pop, it removes the last one and returns it, again mutating the list. So operations that I have on lists. These are going to become handy as we start thinking about doing things with lists. I can go back and forth between lists and strings. If I've got a string and I want to convert it into a list, I can literally call the procedure or function list on that string. And it returns a list with every character in the string now separated out as a separate element of the list. So let me show you a simple example. I'm going to set list to be the string ABC. Not very interesting, but it'll work. And if I now say, give me the list of S, it nicely gives me back a list with each character as a separate string inside of that list. I might want to do some processing on these strings or on these lists as well. And so one of the things I can do is I can use the split method to split a string on a particular character. If I call it just with a standard call on split, it will do it on a particular character. I can also split it on spaces if I give it no parameter. And so I've got an example down here. I've set up a string S. I can turn it into a list. There it is. I could also split the string and turn it into a list. And that I've done by saying I want to split it at this character. And notice what it's done. It has literally broken it up into two parts. There's the first part. There's the second part right there. I can also do conversions of lists back into strings. So if I create a list such as this one here, I can join them together using this call. There's the join operation. There's the dot. And I'm giving it an empty string. And it's basically saying, given that this is a string, use the join operation on that string to merge everything together, and it will return out just the string with the pieces stuck together. If I want to, I can do a join, but have the join insert a character between each of the things. And in this case, I give it an underbar. I use the dot. I ask it to join, and it returns the string with it A, underbar, B, underbar, C. So I can go back and forth between lists and strings. Again, something that's going to be really handy in a little while. There are a couple of other list operations of value. I've already said, while I talk about a list as being an ordered sequence, it doesn't mean the elements inside of it are ordered, but I can do that. I could actually sort a list. And I have two ways of doing the sorting. I can sort the list and return a new version of it, or I could actually mutate the list and sort it itself. And so I want to give you an example here. If I set up L to be the list of 9, 6, 0, and 3, it's certainly not sorted. And if I look at L, there it is. If I call the special function sorted on L, it returns a sorted version of L. But L itself has not changed. That's handy if I want to keep L around, but I want a sorted version of it. On the other hand, if I really don't care about what I do with L afterwards, but I want the sorted version, I can call L dot sort. Again, it's a method with coming off after that dot to tell me to do this. I do an open close to say invoke the function. And now if I look at L, it is in fact sorted. Similarly, I could reverse a list by calling reverse as a method, using the dot to say use the reverse associated with lists, and it will change L itself and create something in reverse order. Handy things to have. Things are going to let us start manipulating larger data structures as we move forward with thinking about how to do computation on bigger collections of pieces. We can now bring all of these pieces together because we've got loops, functions, range, and lists. And how do I want to bring them together? We've already talked about range. We said it was a special procedure. And we said it returns something that behaves essentially like a tuple. Or if you want to think about it like a list, but really more like a tuple. It doesn't generate all of the elements at once, however. Rather, it generates the first element and provides a method that says, when you want the next one, I'll give it to you. That's nice if I don't want to have to generate a huge range before I start doing some computation. But I can think of ranges now as acting like a tuple. So range of 5 really behaves like the tuple 0 through 4. Or if you want to think of it that way, like the list 0 through 4. Range of 2, 6 is going to behave as if it was that collection of those integers, as a tuple or as a list. And as a consequence, when we use range in a for loop, what that loop variable is doing is just iterating over that range as if it were a list. We could write it directly, but it's going to be a nice, convenient shortcut to have because we're going to be able to do things much more efficiently without generating the entire range before we start working on it. The second compound data construct we're going to introduce is called a list. And a list looks a lot like a tuple, but it has one key difference. Again, it's an ordered sequence of information accessible by an index. And I'll remind you, ordered means not that they are in ascending order, but rather they're ordered so that I can say, give me the 0th, the 7th, the 9th element. They're denoted a little differently. They're denoted with square brackets to tell us that this is a list, not a tuple. They can also contain elements. Usually they're homogeneous. All integers, all strings, all tuples of integers or strings. But we can, in fact, have mixed types in them. But the big difference is that lists can be changed. So a list is mutable. And that means that I can go in and change the element of a list to be something different. Very different from a tuple or a string. We said those were immutable. I could not change portions inside of them. I can with lists. And we're going to see that that's both really useful and can provide some real problems or cause some challenges because it opens up opportunities for making mistakes that we don't expect. With lists, again, I've got the same kind of idea that I have an element at a particular index or position. I start at 0 as I've done before. So I can create a variable name. I can bind it to an empty list, much as we would do before. And I can index elements of a list starting at 0. So the examples I show here are things you would expect for any kind of construct like this. I can ask for the length of a list. We've used len before. I can get out the 0th element. I can get out an element and do something to it, like adding 1 to it. And if I try and go beyond the end of the list, I'm going to get an index error. So this has got things at 0, 1, and 2 indices, nothing at 3, and so this will give me an error saying I'm trying to go too far beyond the end of the list. An index can also be an expression or a variable. It doesn't have to just be an integer. It could be a value. So for example, if I bind I to 2, and then I ask for the element at I minus 1, since I is 2, I minus 1 is 1, and L of I minus 1 gives me out that element right there out of the list. And we're going to see that's handy as we want to think about how to use expressions to tell us where to look inside a list to pull out a value. As I said, lists are mutable. And so one of the things we want to look at here is how do we do it, and then what's going to be the implication of that. In particular, if I have a list like the one shown here, 2, 1, 3, I can now evaluate this expression. It says take the first element, or the element at index 1, and change it to be 5. And that will literally change L itself. It does not produce a new list, it changes the same object. So this is different from strings and tuples, an important distinction. And one way to think about it is, when I first bound L, it pointed to that structure, that list in memory somewhere. When I evaluate the second expression, it literally changes that middle element. But L is still pointing to the same expression. A lot of advantages to this, but some real challenges. And that's what we're going to look at next. Before we do it, one last piece. Just as I can iterate over tuples, I can iterate over lists. They are also iterable. And so a common pattern would be to, for example, walk down a list and add up all the elements if there are a bunch of integers. I could certainly do that the traditional way. Here I'm running through a for loop that's going over the range of possible indices. So length, or ln, of L gives me the number of elements in a list. Range will give me something that gives me everything from 0 up to but 1 less than the overall length of the list. And I could simply add things up. Standard way of doing it. Much cleaner is to recognize that I can simply iterate over the elements of the list themselves. So that loop says, let I take the first element of the list, then the second element of the list, and so on, and simply add those together. And this creates cleaner code that makes it easier to see what I'm actually doing here. So lists are iterable, the same way that strings and tuples are iterable. A great property to have. Now that we've introduced functions into our language, we have a lot of power for doing computation. But so far, all we can do is do computation on strings and on numbers. Still a lot of things we can do, but we'd like to not only have the ability to do strings and numbers, we'd like to be able to look at bigger collections of data. And the same way that functions let us group things together, common computations, ways of grouping data together into things we can treat as primitives, as simple things, is going to be equally powerful. And that's what we're going to talk about today. We're going to introduce two new kinds of data structures, things called tuples and things called lists. And so let's start with a tuple. A tuple is an ordered sequence of elements, which can include any different kind of element within them. Now, when I say an ordered sequence, I don't mean that the elements in the sequence are ordered, meaning smallest to largest. I mean that the sequence itself has an order so that I can get to different parts of the sequence by simply indexing, much like we did with strings. One of the issues about tuples is that they're immutable, meaning I cannot change values inside of them. And in fact, that's just like strings. Remember, we could take out parts of a string, but we couldn't change the inner pieces of Remember, we couldn't change the inner pieces of a string. How do we build tuples? Well, I've got examples here in this slide. I'm going to just show you some of these inside of a Python environment. I can create an empty tuple by simply giving it an open and closed paren. The parens designate that this is a tuple. We'll see why that's important in a second. So TE is an empty tuple. I could make another tuple by giving it a sequence of elements, the integer 2, the string 1, the integer 3, for example. I could print it out. It's going to give me back the same thing. And like with strings, I can index into them. So I can say, starting again at 0, what is the 0th element of the tuple? And because I'm indexing, I'm using square brackets or braces to get to it. And that gives me out the first element. As with strings, I can concatenate using basically the same kind of structure. So I could take T and add to it another tuple, say 5 and 6. And that gives me back the longer tuple, all concatenated together. And just like with strings, I can slice to get out portions of a tuple. However, I can't, as with strings, try and change them because they're immutable. So if I try and change the first element of T, say I want it to be 4, it's going to complain. It gives me a type error saying that this is not something that supports that kind of an operation. They're tuples. Really good. Okay, with those, I can now start adding up other kinds of pieces. Before I do it, though, let me point out one last thing, which is the funny thing about the example I just highlighted here. If I go to T, there it is, and I say, give me basically the first element, so T from 1 but up to 2. So give me the tuple, I should say, rather than the first element. Give me the tuple that basically goes from 1 but not including the second element. It gives me back a slightly funky looking thing. It gives me back an open paren saying this is a tuple. It gives me the element, but then it gives me a comma before the closed paren. That extra comma is telling me that this is, in fact, a tuple. And to see that, let's look at the difference. I could create a tuple by saying 1 and a comma, and it gives me back a tuple. What would happen if I did open paren and the string 1 close paren? Oh, it just treats the parens in this case as if they're scoping things, and it just gives me back the element. So for tuples, we have to give that extra comma to tell us that, in fact, this is a tuple and not just an expression that's going to reduce to a single element. So there are tuples. One of the nice things about tuples, they're really convenient for things like, say, swapping variables. So again, imagine I've got x and y and I want to flip the values. We saw this before. The first version won't work because I'm going to take x and give it the value of y, and then when I want to bind y, the value of x is lost. I could do it by creating a temporary variable. I've done that before. Hold the value of x so that I can move y's value into x and then take that temporary value and put it back into y. But tuples do it directly. So this is a perfectly legal command in Python that says, create the tuple with bindings for x and y by simply taking the opposite versions in that tuple. And that gives me a nice way, for example, not only to swap variables, it also allows me to nicely return more than one value from a function. So if I wanted to give back, for example, the quotient and remainder of dividing x by y, I could compute the quotient, I could compute the remainder. Return's only going to return one thing, but if I return the tuple of q and r, then I can bind it using an expression that has on the left-hand side a tuple of names. And that will give quote the value that q holds, it'll give rem the value that r holds. So tuples have some really nice properties. And in particular, it's letting us think about a tuple as a single construct, out of which I can pull out the pieces. Great. Another nice thing about tuples, they're iterable. Just like with strings where I can walk down them, I could do the same thing with a tuple. So here's a little procedure. I'm going to walk you through it. It's kind of a funky procedure. The idea is that I'm going to give getData a tuple. And that tuple is going to itself consist of tuples. Weird. But it says each element inside that tuple is itself a collection of things. And in particular, it's going to be a collection of ints and strings. And what I want getData to do is to create two outputs. So let's look at it. First, I'm going to set up nums to be an empty tuple. And that's how I do it, open close paren. Words is also going to be an empty tuple. And I'm going to take all of the numbers and gather them together into a new tuple. And I'm going to take that in the following way. Here's my little loop. And notice I'm iterating over the tuple. I'm saying for t in the tuple. That says the first time through, t is going to be pointing to that. Second time through, that. Third time through, that. And what do I want to do? I want to get the number out. So I'm going to index in the first, or in this case I should say it better, the 0th element of t gives me that thing right there. And then the paren would just treat it as if it was a single expression. So the comma, as we've already seen, is important because it's going to give me that singleton tuple. And I'm going to add it into nums. And add here says concatenate. So nums is now a little longer tuple. And then I'm going to, for words, say if the word part, this part, if it's not inside things I've already gathered together, I'm going to do the same thing. So I'm basically gathering up the unique words as well as all of the integers. And so they'll get put into there. And when I'm done, I'm going to return the smallest number, the largest number, and the number of unique words that I found. And that's what the bottom part does. And if I were to run it, I've got a little example over here. I simply load that into my environment. And it didn't print anything out, but that's okay because my binding is I've now bound small to be the first part of what was returned. And that is the number 1, which was the smallest number. Large is the largest number, 7. And words should be the unique words, or the number of unique words, and there were 3 of them. So I simply ran that on a set of data. And what I want you to see here is how I can iterate over the tuples, treating them as if they're just a single construct, just the same I would with a range or I would with a string. Okay, we want to start thinking about how do we get a computer to do things for us. So we can start by saying, well, what do we want a computer to do? We want it to compute something. Sounds like a deep philosophical question. And in fact, it is. And that leads to an even deeper philosophical question, which is if we want a computer to compute something, we can ask, well, what's the knowledge that it's going to use to do that computation? And that actually leads to an interesting distinction, because we can divide knowledge into two types, what we're going to call declarative knowledge and what we're going to call imperative knowledge. Declarative knowledge, those are statements of fact, statements of truth. For example, if I were lecturing here at MIT, I might have gone in ahead of time and strapped some or taped some candy under one of the chairs inside the lecture hall. An imperative piece of information simply says, there's candy taped to the underside of a chair. It doesn't tell you anything about how to find it. It doesn't tell you where to look for it. You'd either have to do it in parallel by having every student reach under the chair or search the entire lecture hall. It's simply a statement of fact. Imperative knowledge is a recipe. It's how-to knowledge or how-to information. And this gives us a sequence of steps to find a solution. Again, if I stuck candy under a chair inside the lecture hall, I might say to the lecturer, do the following. Face the students at the front of the room. Count up 1, 2, 3 rows. Start in the middle section, left side, go in one chair. Look underneath it, candy is there. It's a recipe. It's a sequence of how-to steps, very mechanical, to get things done. Those two kinds of knowledge are important, but only the second one's going to really be of value to us, because that's what's going to help us get the computer to do something for us. To see it, let's look at a simple example. Suppose I want to compute the square root of some number. To make it easy, I'm going to start with just an integer number. Here's a statement of fact. The square root of the number x is that y such that y squared is equal to x. And I'm just going to highlight it right here. There it is. There's a statement of fact. Does it tell me how to find a square root? No. If somebody gives me a good guess, I can use this to check. So if I'm trying to find the square root of, say, 16, and somebody gives me a guess of 4, I'm lucky, because I can say 4 times 4 is 16, and I'm done. But it doesn't help me find something. Here's a version of imperative knowledge. And this is actually a very old algorithm. It's attributed to Alexandria of Haran, dating back into the 2nd century BC, although other people suggested it existed earlier than that. But here's a recipe for finding square root. I'm going to start with a guess, and I'm going to call it g. If g times g, if g squared, I'm going to go back. If g squared is close enough to x, then I'm going to stop and say g is the answer. Otherwise, I'm going to create a new guess by taking g and x divided by g and averaging them together. Take the average. Okay? Once I've done that, I'm going to repeat. I'm going to go back up and do the same thing again. And that's going to give me a little algorithm, because it's going to let me now say, start with a guess, check to see if the guess is close enough, and if not, keep going. And you can see that at a little graph at the bottom. I start with not a very good guess. G is equal to 3. I square it. That's 9. 9 is not, as you can see here, very close to 16. So I'm going to take x divided by g, which is right there, and I'm going to take g, and I'm going to average them together to get a better guess, right there. With that better guess, I'm now going to do the same thing. I'm going to go back through that loop, go back up to step number 1, and say try it again. And you can see the steps here. I square 4.1667, I get 17 and change. It's really not close enough. I take x divided by g, I take the average of x and x divided by g, and I get a much better guess. And you can see after the next round, I get a guess that's close enough, I'm probably ready to stop. So, this is a nice example of a little algorithm. It's a little recipe. And let's capture those pieces together. What's a recipe? 3 pieces. It's a sequence of simple steps. It's a flow of control, a process that's going to tell us what order in which to execute the steps, and it's going to give us a way of deciding when to stop. So those 3 pieces, simple steps, a sequence of things I want to do, a checklist. A flow of control, a thing that tells me when to go to the next step, when to jump to some other place in that sequence of steps, and a way of deciding when to stop. Those three pieces constitute an algorithm. And you just saw it in the little square root example. In general, the flow of control was going successively through the steps until I got to a test, and that test had me jump back to another place inside the algorithm. That's what an algorithm is. That's what a recipe is, and that's what we want to capture. So now we've got the idea of creating a recipe as a generic idea. We know a little bit about what's inside the machine. What we need to do is put those two things together. We want to now go from a description of a process to a specific set of statements that we can store in the machine so that that interpreter, that evaluator, can then run those operations to use the primitives inside the machine to do the work for us. As we've said, programming language is going to provide us with a set of primitive operations. And the next step is to start talking about how do we put them together. To do that, we use something that we call an expression. And the expressions in a language are simply more complex but legal combinations of primitives that the programming language will recognize. And we're going to start building those up. So you're finally getting to the stage, after all of this high-level discussion, of getting to the place where we're going to begin to get the computer to do something. One of the things we're going to talk about, though, is that any legal expression in a programming language, any computation, has associated with it a value. That value is the meaning of the expression, and that's going to be important. In part because if we know we want to get to a particular computation, we want to understand how do we get to that value and how do we back out of that the sequence of steps, the expressions that are going to compute it for us. So let's look at how we put this together. Every programming language can be thought of as consisting of a set of primitives, a means of combination, a way of putting those primitives together to create new expressions, and a means of abstraction, a way of taking some complex expression and treating it as it's a primitive. To talk about this in a programming language, I'm going to give you an analogy to a natural language like English. In English, what are the primitive constructs? They're words, lots of them, some of them more common than others. In a programming language, we also have primitive constructs. These are the atoms on which we're going to build things. And in a programming language, those are typically numbers, strings, or just sequences of characters, and simple operations, the things that were provided to us by the manufacturer: addition, subtraction, comparison. Given those primitives, we want to put them together. When we put them together, we have to think about two different parts. This is taking you back to an English class, because we have both the syntax and the semantics. The syntax is that parsing of a sentence to know, is this a legal sentence or not? And some combinations of expressions are legal, some are not. For example, in English, cat, dog, boy is not syntactically valid. It does not make sense. There's no verb in there. On the other hand, cat hugs boy is syntactically valid. It is a noun, a verb, a noun. That's something that makes sense. The same thing's going to happen in programming languages. Some combinations of primitives are not legal. They're not syntactically valid. For example, this expression right here, the first part, we're going to come to this in a second, is a string. It's a sequence of characters enclosed in double quotes, followed by a number. It's not a legal expression. On the other hand, as we'll see in a second, this is a syntactically valid expression. It consists of a number, an operator, and a number. So we're going to talk about how do we put together legal expressions. What is the syntax of those, both in terms of simple combinations like this and how we do it when we get to more complex aspects of the language. Associated with every expression that is syntactically valid is potentially a meaning, the semantics. What does this expression evaluate to? And here we're going to separate out both static semantics and full semantics. Static semantics tells us which syntactically valid strings actually have a meaning. In English, in bad English, the sentence, "I are hungry," is not actually meaningful. It's syntactically valid, meaning it's put together properly. It's, in this case, a pronoun, a verb, and then an adjective. Perfectly legal combination, but semantically it doesn't make sense. Same thing happens in a programming language. The first expression, 3.2 times 5, is syntactically valid. The second one, 3 plus the string high, is syntactically valid. It is a primitive, an operator, and a primitive. But semantically, it doesn't make sense. I can't add a number and a string together. So we have to distinguish things that are not statically semantically valid, because they're not going to be expressions we want to try and assign a meaning to. Once we have both syntactically correct and static semantically correct expressions, we want to then know what's the meaning associated with them, and we're going to start building this up. Semantics then is the meaning associated with that syntactically correct string of symbols with no semantic errors. Even here there can be some wonderful nuances. In English, we can have a sentence that's both statically semantically correct and syntactically correct, but can have multiple meanings. Flying planes can be dangerous. Does that mean if I'm flying it, it's dangerous? Does it mean if they come out of the air and crash on you, they're dangerous? There are multiple interpretations to it. Or from an old joke, this reading lamp hasn't uttered a word since I bought it. Obviously playing on the word reading lamp in a different way. Different meanings associated with it. In a programming language, there's both good news and bad news. The good news is any syntactically correct and static semantically correct expression in a programming language will only have one meaning. But the challenge is it might not be the meaning you intended. And that's where bugs are going to show up. And we're going to come to that as we go through the term. But these pieces now are how we're going to talk about the language. What's the syntax of putting things together, and what's the semantics, the meanings associated with them. With those three things in mind, you can ask what could go wrong. And these are also things we're going to see in the course. First of all, I could have a syntactic error. I've not written down a legal expression. These are common and easily caught. And in fact, most good programming languages or the environments that interpret them will catch those directly. As you'll see as we go along, and I'm sure I'm going to make some mistakes as I do some work here, Python will catch those right away, so you won't try and do anything with them. Once you got something that's syntactically correct, what about static semantic errors? Things where things are in the right order, but they don't make sense. Some languages are very strict about catching these. They'll actually check before you ever run a sequence of operations to make sure there are no static semantic errors. Other languages, and Python is one of them, will do it on the fly. As you're going through a sequence of instructions, when it comes to one that is not statically semantically correct, it will stop. That's good news, but it can lead to some unpredictable behavior, and we're going to see that as we go along. The bigger problem is one where there are no semantic errors, but you get a different meaning than what you actually intended. These are the bugs that are challenging and are going to be difficult to find, but you need to find. And what are some of the consequences? The program could crash, simply stop running. Even worse, the program could run forever or until you get really tired and stop the machine because it's not coming back with an answer. And even worse yet, the program gives you an answer, but it's different than what you had expected, and you're going to use that to now do incorrect conclusions based on that error in computation. So what we're going to do now is start talking about Python, and our goal is to learn the syntax and the semantics of this particular programming language, and then to use that to learn how we can translate our recipes for solving a problem into a form that can go into the computer so it can run through that very mechanical sequence of steps to compute the things that we want to do. And finally, as we do all of this, we're going to start seeing patterns of computation. We're going to build up computational modes of thought, different styles of solving problems, because those styles are going to be common and can be easily reused when we see a new problem that fits into the same category. We've been using exhaustive algorithms, guess and check algorithms, to solve some simple numerical problems. But if you think about it, they've all been doing things with integers, where there is a finite number of choices that we have to check. And that makes sense. I can certainly run through all of them until I get to either the right answer or determine there isn't a possible answer. But now suppose we want to find, say, the square root or the cube root of any non-negative number. It could be an integer, it could be a float, it could be any number. I can't generate all possible guesses. They're infinite. So I can't, in this case, guarantee an exact answer, but I could come close. Now what I just want to do is try and find a guess that's close enough to the cube root or the square root of the thing I'm looking for. I can still use that notion of exhaustive enumeration, but I'm going to now have to pick examples where I take small steps in order to generate the guess and check to see if I'm close enough. Let's see what that might look like. Here the idea is I have to define what's a good enough solution. So I'm going to start with a guess, say 1. I'm going to check to see if that's close enough. If it isn't, I'm going to change it by a tiny amount, say 1.001. Check that one, and then 1.002 and keep doing that. So I need to increment by some small value as I go along. But I also have to define what does it mean to get close enough. It won't be exactly the same because I'm not going to be able to guarantee that. So here I'm going to use, in the case of cube root, something that tells me whether I'm close enough. By looking at the guess cubed, take the absolute value in case it's negative, and look at the difference between that and cube to see if it's less than or equal to a small number. And if it is, I'm going to say I'm close enough, and I'm going to stop. One of the tricks here is that when I have these small values, I'm going to have to be careful. If I make them really small, I'll make sure I find a really good guess, but it's going to slow the program down. If I make them really large, I might actually miss the answer. And similarly, when I decide how close I want to get with epsilon, if I make epsilon big, I'm going to make it easier to find an answer, but I might get a less accurate answer. And so I have to think carefully about how I do both of those. But let's look at that idea to see how I can still use the idea of guess and check, but now with things that could compute the cube root of anything. So here's an example. I'm going to start off with some value for the thing I'm trying to find the cube of. 27 is going to be an easy one. I'm going to set up some initial values. Epsilon is going to be something that tells me how close I want to get to the answer. Guess is where I'm going to start. And increments, the size in which I'm going to increase my guess as I move along. And just to keep track of it, I'm going to set up another variable called number of guesses. I'm going to use that to keep track of how many times do I go through the loop as I do this. And then what does this code do? It says while the difference between the cube or the guess cubed and the thing I'm trying to find the cube root of, while that difference is still bigger than epsilon, I'm going to keep going by incrementing guess by increment. There's that plus equal that I've used before. And changing number of guesses by 1, saying I've done another guess and keep going. I'm going to keep doing that until I get to something where the difference between guess cubed and cube is small enough. And at that point, I'm going to stop, and I'm going to return both how many guesses did I run and some information about did I find the right answer. Let's see what happens if I run that. So there's a piece of code. Let me start with 27, which is the thing I had before. And if I load that and run it, it gives me, not quite the answer I expected. It says 2.9970000001906 is close to the cube root of 27. And that's true. We're going to see in a little bit why it doesn't just give me 3. It gives me this funny answer in there. But you can also see that it took almost 30,000 times through the loop before it got to that. Why? Because I started with a very simple answer, 0. That wasn't close enough. Then I went to 0.0001, then to 0.0002. And you can see I'm going to have to do a lot of things until I get to something that's going to give me a good guess. Now, I could pick another example. Let's make it 29, which I know is not a cube root. Let's see what happens if I do that. It's not a perfect cube, but in this case, it found it. That's actually nice. In the previous case, I could only find things that were cube roots of integers. Now I've got something where the cube root isn't an integer, but I can still find it. This took almost 31,000 times through the loop. So I could say, you know what? I want to use something where I'm going to step a little more broadly. Let's step every thousandth of a step rather than every 10,000th of a step. And now if I run it, okay, I get a little bit different guess, but it only took 3,000 trials through it. And if I change it to say the increment should be in hundredths, I can run that. And if I do that, oops, sorry, it decided it didn't like that. Let me think about why it didn't like that. What's happened here? It's often an infinite loop. And the reason it's often an infinite loop is because I'm checking only to see if I get to a place where it's close enough. I've actually gone right past the cube root and it's still running. So I need to stop this and I'm going to interrupt it to hold it back. That's something I need to fix. So if I go back to a little bit better increment here and rerun it, I get back to the thing I wanted to have. Okay, how would I fix that? I need to make sure that the guess isn't too big. If you think, and I'm going to go back to where I was. With this test, it simply says when guess cube minus cube, as long as it's bigger than epsilon, I'm going to keep going through the loop. If my step is too big, I could try something just below cubed, but not have it work, and then go past cube and keep going further and further on. That means says I need to make a change here, so I want to make sure that my guess is still small enough. And if I make that small change, which I'm going to do over here, and guess less than or equal to cube, I should be in a little bit better shape. I can still run the same one, but now if I change increment to tenths and run that, it gave me a solution. Not a very good one. It basically says I didn't find a solution, but at least I didn't keep running forever. What was the point of doing this? It's not to try and trick you. It's to remind you that as you make changes to the code, you need to think about the consequences. And this was one where my test wasn't capturing all of the cases. So what can I say about this particular algorithm? The step could be any small number. If it's too small, it's going to take a long time. But as we just saw, if it's too large and I'm not careful, it could skip over the answer without getting close enough. At least in this case, I stop rather than running forever. In general, it's going to take x divided by step number of times through the code to find a solution. And so clearly as I make steps smaller and smaller, it's going to increase the number of steps, and I'd like to find a more efficient way to solving this problem. Let's think about what we've been doing so far. We started introducing elements to our language. We started off with simple things, basic objects, ways to do arithmetic operations on them, ways to compare them. We introduced conditionals as a consequence of that. And we started looking at the first version of ways to actually put things together into pieces of code. So we've covered language mechanisms. We've also covered the first notion of for and while loops and therefore of iteration. And we've also seen that we could write different kinds of computations, each one in a different file that I save away on my machine so I can use when I want to do something with it. Each file contains a piece of code, and each piece of code is some sequence of operations. It could be a simple branching program. It could be an iteration like a for loop or a while loop. It could be something else. This is fine when our code consists of a few lines. This is fine when our problems are very small. But it doesn't really scale very nicely. As I start thinking about pieces of code that might be hundreds or thousands of lines long, simply doing it this way is a real challenge. It's hard to keep track of the details. It's hard to make sure that I've got the right information in the right place in that code. Does this go at line 95 or at line 296? I need a way to really capture this better. I need a way of structuring my code, structuring my computation so that I can think about it much more efficiently. And that's what we're going to introduce now. One of the things to keep in mind is, in fact, good programming is more than just adding more code. In fact, I would argue that a good programmer is measured not by the number of lines of code she's written, but by the amount of functionality that she's provided, the ability to do computations easily. And so to make that happen, we're going to take a really nice pivot, introduce a major new thing, and that's the idea of a function. We're going to describe it in a second, but the idea of a function is it's going to give me a way to encapsulate pieces of computation. And in fact, a function is intended to give me two really important aspects of computational thinking: decomposition, sometimes also called modularity, and abstraction. So what do those mean? Let me give you an analogy, something a little bit different. I'm sure you've all seen a projector. I think of a projector as a black box. Now, the one I'm showing here happens to have a black box around it, but by black box, I literally mean a construct whose details I don't understand. In fact, most of us don't know what's inside it, how it actually works. If you open it up, you see a bunch of electronics, and unless you're a really good electrical engineer, you probably don't understand how it works. It doesn't matter. because you know the interface. You know the input-output behavior. And in fact, that black box comes with a standard interface that says if I plug an appropriate piece of electronics into it, that box can communicate with it, and it's going to produce an output. It's going to show slides on the wall. That's the notion of abstraction. It's the idea that once I've built something, in this case a projector, might be a piece of code, once I've built something, I don't need to know what's inside it as long as I know how it works. So abstraction in some sense comes with a contract that says, if you give me appropriate inputs, I'm going to behave in an appropriate way. That's a really nice idea. That's something that we're going to want to use, and we're going to use it with code. There's a second piece to it, and we'll stick with the projector idea. If you happen to see the opening ceremonies for the Vancouver Olympics, there was a wonderful display in which there was a huge multi-story high structure in the middle of the rink onto which images were projected. Now, it wasn't one projector, it was way too big. It was a sequence of projectors. Each of them took an input, each of them produced an output, and they all worked together in synchrony to produce that wonderful larger image. That's the second big idea, decomposition. That I can, in this case, take different devices, have them synchronize so that they work together to achieve an end goal. I want to use the same thing with code. So we're going to apply those ideas to programming. Decomposition, I'm going to break a problem up into different self-contained pieces. And once I've built them, or even better, once somebody else has built one of them for me, all I need to know is what does it expect as input and what will the behavior be when it gives me an output. And the second big idea, abstraction, that I want to be able to suppress the details inside that method in order to be able to compute something using that computation. And in fact, I just said them in the wrong way. What I first described was really abstraction. Decomposition is that idea of breaking it up into smaller pieces. With those two things together, we're going to now look at how do we make programs have those two properties. Okay, inside of code, with decomposition, we're going to do the same thing we did when we talked about having multiple projectors working together. When I'm going to structure a big piece of code, I'm going to divide it up into modules. And those have the property that they're self-contained. That means they have everything they need inside of them. I'm going to use it to break the code up into pieces that I can separate apart. And they're intended to be reusable. I can use them multiple places. If you think about it, so far, even if I have a little file, I can only use it once. Or if I want to reuse it, I've got to go back and recall the file. Here I'm going to structure code so that I can use it in multiple places. And we're going to see that this idea of dividing code into modules is both going to keep the code organized and coherent. It's going to be easier to structure. Today we're going to do decomposition with functions. And in a few weeks' time, we're going to see how to do decomposition with classes. An equally powerful idea. We're going to suppress details with abstraction. Again, I said with the projector, I don't need to know what's inside, I just need to know what it does. In programming, we're also going to think of a piece of code as a black box. I don't need to see the details inside once I've written it, or especially if somebody else has written it for me. I, in fact, don't want to see the details inside. What I simply want to know is that it's going to work the way it was advertised. And we're going to achieve abstraction with something called a function specification or a docstring. And in a second, we're going to see examples of both of those. But there's the idea. Abstraction, decomposition. Two powerful ideas that we want to capture inside of computation. One of the things that comes out of this is not only do they work well together, but they can then be used many times. And in fact, not only can they be used many times, I only have to debug it once. It's one piece of code. If I want to make a change to it, I change that piece of code. Anything else that depends on that code will inherit that behavior because they simply depend on that code. We've just seen an example of an algorithm that computes floating point numbers as an answer. And we've been playing with floats earlier on. I now want to take a little sidetrack to talk about floats and how they're represented inside the computer. And in particular to deal with something that you may have experienced earlier on in the course, where you'll get answers that'll give you some funny number where you're expecting 3.0 and it gives you 3.0000125 or something else. To deal with this, we need to go inside the machine for a second and talk about how floats represent real numbers. They certainly approximate them, but it's useful to get a sense of how the machine actually stores it, because it can't store an infinite number of decimal points or digits after the decimal point inside the machine. Here's the basic idea. Let's start with the decimal number, the numbers you're used to dealing with. The number 302 is really 3 times 10 squared plus 0 times 10 to the first power plus 2 times 10 to the 0th power, or 1. It's 300 plus 0 tens plus 2 ones. Binary numbers, which is how the computer stores things, are actually represented the same way, but now in terms of powers of 2. So the number 10011 in binary is 1 times 2 to the 4th plus 0 times 2 cubed plus 0 times 2 squared plus 1 times 2 to the 1 plus 1 times 2 to the 0, okay, which is actually 16 plus 2 plus 1, or 19, in decimal notation. Internally, the computer represents every number in binary, whether it's an integer or it's a float. How would we use that idea to think about how do we represent floating point numbers? Well, let's think about how we could convert a decimal integer into a binary representation, and then we'll do the fraction portion of it. So given a decimal integer, how would we convert it to binary? Well, let's take an example. My example would be the one I just had before. 19 in decimal is 10011 in binary. If I had 19 or anything that represents that number, how could I get it out? Well, what I can do is the following little trick. I can take the remainder of that number relative to 2. And that remainder actually gives me the last binary bit. It'll give me this bit right here, because that's the remainder that's left when I divide by 2. If I then take x and divide it by 2, integer-wise, using that double slash idea, all of the bits get shifted right. That is, x double divide by 2 is now 1 times 2 to the 3rd rather than 2 to the 4th, plus 0 times 2 squared rather than 2 to the 3rd, plus 0 times 2 to the 1 rather than 2 squared, plus 1 times 2 to the 0 rather than 2 to the 1. Or another way of saying it, notice I've taken these digits and just shifted them to the right. If I keep doing successive divisions like this, I can keep track of each of the bits that comes out, because the remainder gives me the next bit, and when I'm done with all of that, I've converted to binary form. So basic idea, given an integer, take the remainder with respect to 2, that's the low order bit, divide integer-wise by 2, shifts right, do the same thing until I've exhausted the entire integer representation. So here's a little piece of code that would do exactly that. All right? If the number's less than 0, I'm going to put on a flag that says it's negative, and I'm going to use the positive version of it by taking the absolute value of that number. Otherwise, I'm going to put in a flag that says it's not. And then I'm going to simply accumulate those results. If the number is equal to 0, it's just 0. That's pretty obvious. Otherwise, as long as the number is greater than 0, I'm going to do remainder, add that in because that's the next bit into result, do the division to shift it to the right, and keep going. So if I look at that, here's a simple example of doing that conversion, converting decimal to binary. I'll start with a real simple example. If I start off with number as 3 and I do that computation, it didn't print anything, but the result is sitting in result. And there I get it. The binary representation of 3 is not surprisingly 1 plus 2. Let's just check to make sure I wasn't misleading you when I said 19 was, in fact, what I claimed it was. So if I make it 19 and I run it and I look at result, it gives me back 10011, exactly as I said. All right, cool. So I can take integers and convert them into binary. But I started talking about floats. So how do I deal with the fraction part of this? Well, I can do almost the same thing. Let's take an example. 3/8 is 0.375, and in binary, that is 3 times 10 to the minus 1, plus 7 times 10 to the minus 2, plus 5 times 10 to the minus 3. It's just the digits associated with each of the placeholders. Here's the trick I'm going to play. If I can find a power of 2 big enough to convert all of that into a whole number, that is, multiply it by something so that it gets converted into a whole number, then I can convert that into binary. I just did that. I know how to do that. And then when I'm done, just divide by that same power of 2, and I've got a representation in binary of the fractional part of this number. In this case, I picked an easy example, 0.375. If I multiply it by 2 to the third, or 8, that's going to give me out 3 in decimal. I can then use what I just did as my trick to convert that to binary. That's 1, 1. And then I divide by 2 to the third, which simply says shift it right 3 points. And there is the binary representation of that decimal fraction. That's cool, right? It's a really neat idea. What am I doing? I'm using something I did for one computation, but converting another problem into the same problem. In this case, given a fraction, I'm saying find a power 2 that shifts it into an integer, use the same machinery, and then shift it back. And I'm simply taking advantage of powers of 2 because that's simply moving the placeholder, if you like, for the decimal point, or I should say the binary point, in a binary representation. All right, there's code that'll do it. I'm not going to walk through it. I'm going to let you look at it. I'm simply going to show you that this will actually convert a decimal to a binary fraction. So if I take this and I run it, in this case it says give me a decimal between 0 and 1. Let's pick out a nice example. Let's start with the one that we had, which was 0.375. Sorry, let me make sure I'm here. And it says, oh, I'm going to tell you when I've gotten through it to get it up to something that is big enough, how many times I have to shift it over, what's the remainder, and there's the printed solution. Let's be daring and try another example I haven't tried before, just to make sure that it actually works. So again, we're going to call this out. It says, give me a number between 0 and 1. And I don't know, let's take 0.333. And what do I get? Well, it goes through a whole lot more computation. It's telling me what the remainders are, but it's running through that computation, and it says the binary representation for 0.333 is this horrible looking mess you see on my computer screen down there. But the point of this is, now I can take any floating point number, convert it into something that can be represented inside of the machine in binary form, and use it. And that, by the way, is why you will occasionally see these strange things where you're expecting 3.0 back, and it has a little bit of an extra piece on it because in binary it can get close to it, but not quite to the place it would like. But with that, we now have a way of understanding how we can represent floating point numbers inside a machine where everything is stored just in terms of binary bits. What are some of the implications of this? If there is no integer p, such that a power of 2 multiplied by x gives me a whole number, then the best I'm going to get is an internal representation that's close, which is why I won't get something exactly right. And obviously, I'm only going to do this so many times before I run out of powers of p to use this. It also suggests that when you want to test equality of floats, you should be careful. You really don't want to given two floats x and y, you really don't want to use double equal sign because it's going to check to see is the binary representation exactly the same. It might not be. It might be really close. So we're always better off using the absolute value of the difference of two floating point numbers. Is it smaller than some small number rather than using the more exact, are they exactly the same? And then finally, as I've already said, we may not always get an exact representation for a float in the way we would like, but if I do print of something, why does it always return what I'd expect, even if the representation isn't different? And the answer is because wonderfully the designers of Python designed it so that it would automatically round to the closest representation in terms of that floating point number. But there are floats. Now we got ability to do integers and floats. We're in good shape. We just saw an example where we walked through carefully the execution or the invocation of a function call, a factorial, in order to see how the different scope frames were created and to help us sort of decide that in fact it will stop when it reaches a base case and return a value. But when I start trying to design code, I have to think about the same thing. How do I set it up so that I know it's actually going to stop? How do we know our recursive code is going to work? In the case of an iteration, we know that by making sure that we've got a loop invariant that changes as we go through it in order to make sure that we actually get down to a place where we hit the end test. So mult_iter terminates because b is initially positive and it decreases by 1 each time through. I've set that up by making sure I change it by 1. And so I know eventually it's got to get down to a place where it's less than 1, which is going to trigger that end clause. And I can use that to deduce that I've written code that is in fact going to terminate if I give it an appropriate set of values. What about the recursive version? Sorry, as I said, mult is called with B1, and that it has no recursive call, and it stops. But how do I know that it stops in general? Well, if I call mult where B is greater than 1, it makes a recursive call with a smaller version of B. And so again, I know that eventually it must reach a call where B is equal to 1. This tells me that when I write a recursive version of a function, I need to make sure that I'm changing the parameter, in this case, this value, so that I'm going to get down to that test case. That's nice, but there's another way in which, in fact, I could reason about my code to decide, is it going to, in fact, terminate, or is it going to get into an infinite loop because it's going to recursively call itself over and over again? And to do that, we can use, as a little sidebar, a nice little mathematical tool called mathematical induction. Here's the idea behind induction. If I want to prove a statement that is indexed on integers, that is, it's a statement that is applied to a set of integers. If I want to prove that statement is true for all values of some parameter n, I just need to prove that it's true when n has its smallest value. For example, n is equal to 0 or 1. And then I need to prove that if it is true on an arbitrary value of n, I can also then show that it must be true for n plus 1. And with that, I can then essentially deduce mathematically that it's true for all values of n. Let me show you a little mathematical example of this. The sum of the integers for 0 up to n I claim is n times n plus 1 divided by 2. If n is 1, it says 1 times 2 over 2 is 1. If it's 2, 1 plus 2 is 3, and 2 times 3 divided by 2 is 3. You get the idea. How would I prove this is actually a true statement? Well, the proof says, take the simplest case. If n is equal to 0, what do I have? Then the left-hand side is just 0, and the right-hand side is 0 times 1 divided by 2, which is just 0. So it's true. To prove it in general, I simply assume it's true for some values, let's call it k. And then I need to show that it's true for k plus 1. So I need to show that this statement is true. Oh, but that's nice, because the left-hand side, I know that it's true for that. I just assumed that. I know that in that case, that is k times k plus 1 divided by 2. So the left-hand side is simply that, by that assumption. And if I do just a little bit of algebra, I can show that that is, in fact, the same as this. And I'm done. Having proved it, assuming k, therefore it's true for k plus 1, I can now say it's true for all values of n. So this formula is always true. What does that have to do with code? Well, I can do the same thing. Here, with my case of a recursive call to mult, I need to do the following. I need to show the base case is true. Will this return the right answer when b is equal to 1? Yep. Now, what about in the recursive case? I'm going to assume that my code does the right thing for smaller versions of the problem, meaning that I'm going to assume that mult returns the right answer. And in that case, I can then say on this piece of code, if it does the right thing, then this return does the right thing, because it's simply an addition. So in that case, I know it returns the right answer for a problem of size b. And by mathematical induction, my code will always do the right thing for appropriate values of a and b. Thus, induction tells me I've got code that works. So how do we create this notion of abstraction and decomposition in Python, or actually in any programming language? And the answer is we introduce the idea of a reusable piece of code or a chunk of code called a function. Functions are not going to be run in a program until we actually ask them to do that. So as opposed to things I was typing into my shell, every time I typed in an expression, it was invoked or evaluated, I'm going to create a definition of a function, and when I read that in, it's simply going to create the ability to do that computation, but not actually call it. And we'll see an example of that in a second. What are the characteristics of a function? Several. First, it has a name. That makes sense. I've got to be able to refer to it in the same way that I had a variable as a name for a value. A function will have a name. It will also take a set of parameters. These are arguments or values that I'm going to use inside the function when I do a computation. It's going to make sense in a second when we look at an example. Every function has to have parameters, but the number of parameters could be 0. or it's a funny way of saying it's going to take in a parameter list, but in fact it may need no parameters, and I'm going to decide when I create a function how many parameters I need. We'd like every function to have a docstring. That is a documentation that tells me what the function does. We'll see an example of that in a second. And finally, a function has a body. And the body is the sequence of commands or instructions that we want to actually have happen when we use the function. Those are a lot of words. Let's look at an example to get a sense of this. Here's a definition of a function, and I'm going to walk through each of these pieces. So, the first part of it is I've got a keyword, in this case def. And it is a keyword, meaning it's a special symbol to Python that tells me I'm about to define something. In this case, I'm about to define a function. That is followed by a string that is the name of the function. In this case, it's isEven or is_even. That's the name of the function I'm going to give, the name I'm going to give to this function. That is followed in parentheses, in those parens, by 0, 1, or more parameters. In this case, I've got 1. And I'm giving it a name. Think of it like a variable name. I'm saying I'm going to use the name I as the name for a parameter inside this function. And that's then followed by a colon to tell me I'm done with the top line of the definition. I'm about to follow it with other information. So keyword def, a name, and in parens, some number of parameters. Immediately below that, in triple double quotes, which is a wonderful expression, is a docstring. It's up to you how to use this, but traditionally you would specify what's the input to this function and what's the output of this function. It's a little bit like a contract. In this case, I'm saying I'm expecting one input, I'm calling it I, and it's a positive integer. And what I'm going to return is true if I is even, otherwise I'm going to return false. As we'll see in a little bit, one of the nice things about a docstring is once I've defined this function, if I go to call it, which I'm going to get to in a second, Python will automatically bring up a little window that tells me the docstring, that reminds me what the conditions for this function are, which is great. So, keyword, name, parameters. I've got a docstring. Immediately below that is the body of the function. This is the sequence of commands or expressions I want to evaluate when I'm ready to use this. Notice the indentation. All of this is indented here. This is telling me where the body of the function is. And in fact, it will be everything until I get back to something that returns to the left-hand side of the editor or of the shell. In this case, I've got two expressions in my body. It's going to print out simply the string hi, and then it's going to return a value. We'll come back to the return in a second. There's how I write a function. Now, how do I use it? The function has a name. The same way I could use a variable as a name inside of an expression, I can use the function name. And in particular, later on in the code, I can say an expression like is_even, and then an open paren, followed by an expression whose value I'm going to use inside of that procedure, followed in this case by a closed paren because there's only one parameter. I call this invoking or calling the function. I'm using the function. We're going to look at some examples in a second, but the basic idea here is that when I call this function, I'm going to take the value 3 in this case, and everywhere I see an I in the body of the function, I'm going to use that value in place of I. And in fact, if I look at it then, inside of this particular expression, I'm going to print out simply the string hi, and then I'm going to evaluate this particular expression, and it has the keyword return followed by an actual value. Now, I just said, in this case, if I've called isEven with the parameter 3, I now holds the value 3. So I'm going to evaluate 3 remainder 2 and say, is that equal to 0? In this case, it's not because the remainder is 1. And I'm going to then return that value to whoever called this function. So that's the expression I want to evaluate and actually return. So it returns a keyword that tells me I'm ready to stop the computation, and whatever the following expression is, that is the value I'm going to give back to the person who asked for it. In this case, it was simply at my shell. But we'll see in a second, it could be somebody else that's going to use it as part of another computation. Let's go up a level just for a second. What have we built so far? Simple objects, The idea of iteration, for and while loops, is a way of doing particular kinds of computations, reusing the same piece of code over and over again. And now we've introduced the idea of functions as a way of capturing that code. That puts us in a position to introduce another really big idea in computer science, and that's the notion of recursion. I'm going to show you an example of recursion in a second, but let me give you the sense of what recursion is about. Recursion is going to be a nice way to design solutions to problems by breaking it up into pieces that I can reuse. Divide and conquer, or decrease and conquer, are words that we're going to use around here. And it's in particular a programming technique where inside of the function it calls itself. So I'm going to define a function, say f. And inside the body of the function, I'm actually going to call f. Now, this is the kind of thing that in high school geometry class you could get into trouble, right? You don't define something in terms of itself. But in recursion, as long as we don't set up an infinite loop, we don't call it infinite numbers of times, we're fine. And so we're going to see in recursion that as long as we have one or more base cases that are really easy to solve and can be solved directly, then I can solve a problem by reducing it to a solution to a simpler version of the same problem until I get down to a simple base case. That notion of recursion is going to nicely amplify iteration. It's going to give us a much more simple way of thinking about how to break problems up into simple pieces. And so we're going to spend the next portion of this lecture just looking at different ways of using recursion. If you think about iterative algorithms to set the stage for recursion, what do we have? They're basically looping constructs, and they are captured by the idea of having a set of state variables that update each time through the loop. So I've got a while loop or a for loop. In the case of a while loop, we talked about setting up the variable outside the loop, inside the loop changing it, usually decreasing it, until I got down to a state where I'm done, and then returning a value. That's what an iterative algorithm does. So here's a simple example to think about that. Suppose I wanted to do integer multiplication. And yeah, I know that already happens in Python, but I want to use it as an example. I could think about multiplying a by b as the same thing as adding a to itself b times. So it's really, if you like, a plus, I've got b of those. That's the same thing as a times b. Iteratively, I would solve this by saying, I'm going to capture the state of the computation with an iteration variable. Let's call it I. I'm going to start it off at b because I've got b additions to do. And a current state of the computation, I'm going to call it result. And I'll start that off at 0. And then my iteration is to simply, at each stage, do one more addition and reduce that variable by 1, that iteration variable by 1. And down here at the bottom is a function to do that. Multiplication iterative takes in two parameters, a and b. It sets result when I call it to 0. And then it runs the iteration I'd expect, that little loop right here, that says as long as b is bigger than 0, I'm going to change result by adding a to it. I'm going to reduce b by 1, and I'm going to keep doing that until b gets down to 0, in which case I'm going to return the result. Cool. Nice iterative way of trying to make that happen. There's the iteration. There's how I'm changing the computation. There's where I'm changing the iteration variable. And when I'm done, I'm simply going to return the result. Okay, I'm not going to run it. I encourage you to try it yourself, but you'll see that it actually does the multiplication I'd expect. With that in mind, now let's look at a recursive solution to this problem. And here's the way about thinking about this idea of doing successive additions to compute multiplication recursively. Again, a times b is adding a to itself b times. But I could think of that as saying that's the same as adding a to itself b minus 1 times. Okay, you say, that sounds like semantics. It is, but it's an important point. Because what's this? That's just a multiplied by b minus 1. Ooh, that's cool. Because now I've taken a problem and I've reduced it to a simpler version of the same problem, plus an operation I know how to do. Okay, what's a times b minus 1? Oh, I know how to do that. That is just a plus a times b minus 2. I could do exactly the same reduction. And I could keep unwinding this computation I need to stop somewhere. I could keep unwinding this computation until I get down to a base case, something that I know how to do. And what's the base case? When b is equal to 1, the answer is just a. And boy, that's nice, because there's a recursive implementation of multiplication. Inside the body it says, if b is equal to 1, that's my base case, just return a. Otherwise, return whatever I get by adding a to doing the same thing, but on a slightly smaller problem, multiplying a times b minus 1. And that will again call itself until we get unwound down to the level that we want to get to. There's the recursive step. And that's a standard form for a recursive function and is a really elegant way of thinking about how to solve this problem. I could do the same thing. Let's think about computing factorial. Factorial, written in mathematically as n followed by an exclamation point, is the product of n times n minus 1 times n minus 2 all the way down to 1, where n is a positive integer. If I wanted to solve this problem, I could say, so what values, or for what values do I actually know factorial? And that's easy. If n is 1, factorial of 1 is just 1. There's my base case and the value I want to return. How would I return it? Well, just as I did with the multiplication case, n factorial is the same as multiplying n by n minus 1 factorial. So there's the recursive step. And I've just written the body of code for something that would be a definition for factorial or fact. What you're seeing here is a pattern. And this is the idea of a recursive function. Break it down into a smaller version of the same problem, plus some operations I want to do, and figure out when can I stop breaking it down into smaller versions of the same problem because I know how to compute it directly. In the case of factorial, when I get down to a factorial of 1. With that in mind, let's deal with something that may be puzzling you, which is how in the world does the computer know when to stop unwinding this? And how does the computer know which versions of the function, of the parameters to the function to use? I'm calling fact of n. How does it know which version of n to use? We've already kind of seen it, but let's walk it through. So here's my definition of fact. Fact of n is if n is equal to 1, return 1. Otherwise, return n times fact of n minus 1. Then I'm going to call it on a value of 4, and I want to print out the result of that. I'm going to do this reasonably quickly because you've seen these pieces before, but let's look at what happens. When I define fact, in that global scope, I create a binding of fact to some code. Hasn't been run yet, and now I'm ready to run it by actually calling it on print of fact 4. Okay, here we go. I got to call fact of 4. Fact creates a new scope inside of which n is bound to 4. And relative to that, it's going to evaluate the body of the procedure. It says, is n equal to 1? No. It's equal to 4 here. So I go to the else clause, which says return n times fact of n minus 1. Aha! I got to call fact again. I know I want to return fact, or 4 times fact of 3. That's the value of n minus 1. But I got to call fact. Great. It creates a new frame, inside of which the formal parameter, n up here, is bound to 3. And relative to that, it does exactly the same thing. So I'm now going to go faster. Is 3 equal to 1? No. So I'm going to return 3 times calling fact on n minus 1, which is 2. That calls a new frame. There's the binding for n. N still not equal to 1. I'm going to again go to the return clause or the else clause that says return 2, which is the value of n times fact of n minus 1, which is 1. And that calls one more frame. And aren't you glad I didn't do fact of 64? Almost done. In that frame, I now say, is n equal to 1? Great. It is. And so in that case, I know that's the expression I want to call, and it says, return 1. Where does that go? I'm returning 1 to the person who asked for it. And that was that call to fact. That's great, because now that expression says return 2 times 1, the value returned by that call to fact. And who asked for that? Right there. That reduces to return 3 times 2, which reduces that one to return 4 times 6, which prints out 24. And I'm done. So you can see the computer with these nested scopes, these nested frames, nicely knows exactly where to get values in order to do the computation. And therefore, the computer knows to stop at the right time. I've just said that. Simply going to put the slide up so you can see it. Each recursive call creates its own scope. Bindings of variables in a scope are not changed by the recursive call, and the flow of control passes back to the previous scope because that was the person who asked for that function call as we did it. And therefore, I'm going to be able to use exactly the same variable name. I need to because that's the formal parameter of the function, but it's always done in a different scope, and therefore it's always clear which version I'm using when I'm calling the body of the procedure. This leaves us then with this nice comparison between iteration and recursion. Both of these pieces of code do exactly the same thing in terms of what they compute. How they do it is done differently. I'll let you decide your own style. Personally, I like recursion better. I think it's more intuitive. I don't have to remember to set up a parameter variable before I start things. I don't have to worry about dealing with all those pieces. I can make them a little different. In this case, I've changed it slightly to use range rather than setting up the iteration variable. But I personally find the right-hand side easier to look at because I can easily see where the recursive call is. From the programmer's point of view, recursion may be more efficient. From the computer's point of view, it may not be as efficient, and we'll see that. But basically, the idea is each of these things does the same thing. You get to decide which one you want to use. We've seen a number of examples of recursive functions, something you're going to use a lot. But all of them so far have just been numerical. So let me show you one more example that I can do recursive problem-solving, recursive functions on other things. For example, on strings. So here's the challenge. How would I tell if a string of characters is a palindrome, meaning that it reads the same forwards and backwards? Now I'm going to cheat a little bit and remove punctuation and capitalization, but I just want to know, is something a palindrome? Probably one of the most famous, attributed to Napoleon, although I don't know that he said it in English, was able was I ere I saw elbow. If you look at it frontwards or backwards, it reads out exactly the same. Second one, attributed to Anne Michaels. Are we not drawn onward, we few, drawn onward to a new era? And you can see if I read it from right to left or left to right, it's exactly the same. I'd like to write a piece of code that can solve this recursively. And you can think about doing it iteratively, but recursive is so much better a solution to use. So how would I do it? Well, I'm going to do a little bit of cleanup first. I'm going to convert the string to just the characters. I'm going to strip out any punctuation, and I'm going to convert lowercase or everything from uppercase down to lowercase. So I just have it all as a sequence of characters. And then I've got a very simple solution. If the string is empty, it's a palindrome. If it's just of length 1, it's a palindrome. Otherwise, how would I tell if some string is a palindrome? Well, check the first and last element. If they're the same, then check everything in between to see if it's a palindrome. That's cool. That's a recursive solution. I've just broken it into a simpler version of the same problem. And of course, as I keep breaking it down, eventually I'm going to get down to either a string of 0, if the whole thing started off as even, or a string of 1, if the whole thing started off with an odd length. Can I do that? You bet. I'm simply going to write a little piece of code that's going to say, if I've got a piece of code that's called is it palindrome, I'll first convert this just into the string. I strip out all the separate spaces, the punctuation. I remove uppercase to lowercase. And then, as I said, if the first and last element are the same, then I just want to check, is that a palindrome? And there's the code. Nice and compact, nice and simple. I'm not going to walk through all of it, but you can see the first part here is simply something that's going to convert that string into characters. It takes advantage of a property of strings that I can call a method called lower that will convert everything into lowercase. And then I've just got a nice little iterative loop here that basically walks through each character in the string. There's that iteration over the string itself. It's a string iteration. And it basically says if that character is, in fact, a character, add it in. And then there's that nice, elegant solution to palindromes. It says given one of those strings, if it's of length 0 or less, if it's of length 1 or less, it is a palindrome, return true. Otherwise, check the first and last. There's that call with -1 to a string, the first and last character of the string. And check by slicing out from the string everything but the first and last character and see if that's true. And finally, I'll just convert the string and call isPal on it. Let's try it out. I've got those two characterizations over here. I've got it loaded up, and if I call it, it says, is, for example, a simple thing like Eve a palindrome? You bet. EVE is a palindrome. And what about is able, was I, ere I saw Elba a palindrome? You bet. Again, notice how thinking about it recursively has let me find a really nice solution to this problem. This is a very crisp piece of code that solves what otherwise seems like a very hard problem. Could you solve it iteratively? Sure. But you'd have to keep track of where you are on both ends of the palindrome as you decrement them to walk in. That sounds like a pain. I'd much rather think of this recursively, and that's what I did. This is, as to all the previous examples, but this is a really nice example of what we call a divide and conquer algorithm. I solve a hard problem by breaking it into a set of other subproblems that have the property that they're easier to solve than the original, in this case it's shorter, and that the solution of the subproblem can be combined to solve the original problem. We saw that with factorial, we saw it with other ones. This is a great example of it. And we're going to come back to this idea of divide and conquer algorithms as we go through the course, because they're a very powerful pattern that we want to be able to use. When I introduced lists, I said they were different from tuples primarily because they're mutable. I can change elements inside of that. It's a really handy tool to have, but it causes some really interesting potential for problems. And I want to show you where those can arise and how you can guard against them. So we're now going to talk about the idea of not only mutation, but of aliasing and of cloning. Topics that are really important, a little tricky to understand, and again, go look at the Python tutor if you want some help working through this after you've listened to what we're about to discuss. But let's think about this idea. Again, I said lists are mutable. I can change them. As a consequence, not surprisingly, they're going to behave differently than immutable types. In particular, what is a list? It's an object in memory, and I have a variable somewhere typically that's going to point to that object. That's how I refer to it. That's how I say give me something at a particular index. One of the things about a list, though, is I could have multiple variables pointing to the same list. These are now clones, if you like, or copies. Actually, I'm going to say that differently. They're not yet copies. They are the same instance, but different names for them. So they're really just aliases for that. One of the things that could happen then is that if I go in and change an element of a list under one name, it also changes under the version as I reference it from the other name because it points to the same place. And that has some really potential for big side effects that can cause interesting problems for us. Let me give you an analogy. I could have a famous person, and I could associate attributes with them. That person might also be known by many different names. So they could have nicknames, and all of those nicknames point to the same person. So for some of you, here's a famous person. It's known as Justin Drew Bieber, or as Justin Bieber, or as there's a whole bunch of nicknames for this young man. And he also has some attributes associated with him. He's a singer and he's rich. But if I add a new attribute to him, something he's done recently, all of his nicknames also refer to both the old attributes and the new ones. So that the Beeb is not just a singer and rich, he's also a troublemaker. And J. Beebs is not just a singer and rich, he's also a troublemaker. All due respect to Mr. Bieber. The point is that you share information because you have aliases or nicknames for the same structure. Same problem, same issue, same opportunity arises with a list. So let's look at a couple of examples here. I'm going to create a list, and I'm going to show you both on my computer and separately, of warm colors. So I'm going to say this is a list of red and yellow and orange. And I'm going to say hot is the same as warm. All right? In my global frame, I've actually created a binding where warm is bound to the list whose first element is the string red, second element is yellow, third element is orange. Hot, where does it point? Oh, to the same place. Because notice what I did here. I said get the value of warm, which is that arrow, and bind the name hot, to the same place. So it binds to that list. And that says, as a consequence, Two things. One is if I print warm, I'm going to get that list. If I print hot, I'm going to get that list. But now, if I append something to hot, I say at the end of hot, add in a new hot color, pink. What is hot? It's that list. But what is warm? It's the same list. And that's because I literally in hot added this element in, and because warm points to the exact same structure, it now has changed. It has mutated. And that's tricky because I might not have intended to change warm, but only hot. Since they were pointing to the same thing, one was an alias for the other, I've had that indirect side effect that I wasn't expecting. One of the consequences of this is that print is not the same as equality. Strange statement. But what it says is even if two lists print out the same thing, that does not mean they are the same structure. And I can test that by mutating one and checking. So again, let me type this in. I'm going to give cool a set of colors. Blue, green, and gray. And I'm going to define chill to also be the set of cooler colors. Notice this is different than what I did in the previous case. In the previous case, I said let hot equal warm, have it be the point to the same structure. Here, they point to different versions of the same set of strings. And you see that right here. Cool is that list. Chill is that list. And while the names are the same, they are different structures. And so, in fact, if I look at cool, or I'm going to do it more formally, if I print out cool, it prints that. And if I print out chill, looks the same, but they're not. And here's how I can show it. Because I can mutate them, I'm going to change the second element of chill to be blue. And now if I print cool, I still get blue, green, gray. But if I print chill, I get blue, green, blue. And that's important because initially it might have looked like they're the same thing. They print the same. They are not. They point to different structures. We have to be careful when we think about what we're doing to test equality, and we have to be careful when we think about how we use elements of structures that can mutate. Third thing I can do is I can clone a list. I can make a copy of it. And so I can make a slight change in what I did earlier on, which is that I could define cool, again, to be this list of the cooler colors, blue, green, and gray. And rather than copying the same set of strings over again, I can simply say I want chill to be a clone of cool. And again, notice the difference. In the very first example, I said something like let hot equal warm. I could have said let chill equal cool, but then chill would have pointed to exactly the same list. With that colon in there, I make a copy of chill, and you can see that over here. I've got cool pointing to one version. I've got chill pointing to a second version. And that now says, for example, if I mutate chill, I append to it the color black, and I print out chill. Black is there, but cool has not changed, and that makes sense because cool is pointing to this structure. I mutated or changed that structure. Cloning lists is really useful when I want to do something with the list that involves mutation, but I don't want to, in fact, change the original list. I can make a copy very quickly and use it. And I'm going to show you an example of that in just a second. But we've seen aliasing and some of the effects of that in terms of side effects. We've seen cloning, and we've seen the fact that because lists are mutable, I have to be careful when I want to ask about are two things the same, even if they print the same way. We've already talked about this, but I want to give you one more example. I can sort a list, and I've suggested there are two ways to do the sort. I could use sort, or I could use sorted. Sort mutates the list, changes the actual structure, but doesn't return anything. Sorted doesn't mutate the list, essentially makes a new version of the list in sorted order and returns that, so I'm going to have to reassign that result to a variable. And I've shown you an example here. I started off with warm as a sequence of 3 colors. I called sort on it. That's the method associated with warm. And it will literally change the order of them. And in fact, you can see over here, after I've done that, warm is now in a different order than where I started. And so I have a different structure to that. And in fact, warm now points to something different than what I really originally began with. Sorted warm has no value because sort does not return anything. If on the other hand I set up cool as this list structure and I call sorted on it, which I do right there, I'm going to return that to a variable name because sorted does not mutate the list. Cool will not change in this case. But what it will return is a new sorted list, and I've now created a binding that points to that structure. I'm sure somewhere along the line you're going to use the wrong version of sort or sorted. I do regularly. It's okay. But what you should see here is that if I don't mind the mutation of the list, in fact, if I want it, I can change it in place using sort. If I don't want to mutate the list, I use sorted. 2 useful tools to have associated with lists. I can, of course, have, as I already said, arbitrary structures inside of lists. So I could have nested lists, lists of lists. They might be even lists of lists of lists. One of the things that can happen here is that I can still get side effects that can occur after mutation. So let me show you an example of this. I've defined warm to be the list of yellow and orange. I've defined hot to be the list red. So I've got warm, I've got hot. And I'm going to set up bright colors to be a list of warm. And there's the formation of it with the square braces. And in fact, if I do it over here, I'm going to set up warm to be the list of yellow and orange. I said hot would be the list of red. And bright colors is just a list of warm, which is itself a list. So there's the value of warm, there's the value of hot, and let's look at bright colors. Oh, funky. 2 square braces. The outer square braces say it's a list. There's only one element in it, and that element is itself a list that has 2 things inside of it. Okay. Now, let's add something to bright colors. I'm going to say to bright colors, append at the end, hot. And I know what hot is. It is itself a list. I created that earlier on. And if I print out bright colors, oh, very nice. The outer square braces say it's a list, and notice I've got 2 elements inside of this. The first one is a list that happens to be of 2 elements. The second one is a list that happens to be of 1 element. And you can see that here because bright colors points to a list, each element of which itself points to a list. Now, let's append to hot the color pink. And if I do that, I've already added it over here. Let's see what happens if I print out hot. Not surprisingly, it's a list of red and pink. Okay, but notice the strange effect. I didn't do anything here that directly used bright colors. I didn't say do something to bright colors, but if I print out bright colors, it's changed. And it's changed again because of that aliasing or side effect. Because bright colors points to something, one of whose elements points to a list, when I change hot, which I did, I've also indirectly changed bright colors. And you can imagine this is occasionally going to cause you some difficulties if you change something you weren't expecting. We'll see that having aliases can be valuable, but we've already seen it could cause some side effects that I wasn't expecting and could lead to computations that aren't what I wanted. Finally, if I print out the whole thing of hot plus warm, I get, in this case, the nice concatenation of them. But again, I haven't changed anything inside of this structure. And I remind you that's why we want to, in some cases, use concatenation, because we want to make a version of things that are glued together rather than changing things in place. And just to show you that, if I go back and print hot, nothing has changed. It's still red and pink. One last topic about mutation, especially as you come around to doing things around iteration. If I'm going to iterate over a list, I really want to avoid mutating that list as I iterate over it. And here's a little piece of code that's intended to remove duplicates from two lists. The idea is if I've got two lists, I'd like to loop through the first list and then go over the second list and say, if I've already got a copy of that, I'm going to remove it from the first list. And I want to show you an example of this. I'm going to just type in very quickly, remove dupe of L1 and L2. And it says for E in L1, I'm going to say if it's already in L2, I'm going to remove it from L1. So there's a definition. Let's, as we've got on the slide, give it two examples. I got 1, 2, 3, 4 for L1, and I have 1, 2, 5, 6 for L2. And I do remove dupes of L1 from L2. And I look at L1, and it's 2, 3, 4. Wait a minute. Why didn't I remove 2? 2 also appears in L2 as well as in L1. I should have removed it from L1, and I didn't. Why? And the answer is that Python, because it's going over an iterable, uses an internal counter to keep track of where it is inside the loop. What element of the list is it going to be getting to next? It's basically saying how many times have I gone through this loop. When I mutate, which remove does, when I mutate the list, it changes the list, and it actually caused Python to never see the element 2. Because I've gone through it the first time, I've removed 1, I've mutated, it's thinking I'm going to look at the next element, but I've changed the size of the list, and the next element is no longer 2, it's now 3. So if I'm going to want to do something like this, I have a tool. I can't do that, but what I can do is make a copy. And by making a copy, by cloning the list first, now when I'm mutating L1, I've still got something that I'm iterating over that hasn't changed because it's pointing to a different structure. Again, a place where you want to be careful about accidentally causing problems because of the mutation. Just like in biology, mutation is not always a good thing. Same thing in computer science or in Python. It can be useful, but we've got to be careful about the side effects that show up. We've been introducing things into our language that are adding power to our language. We started with simple objects. We introduced the notion of doing conditionals on them. That gave us branching programs. We then introduced iteration. We then generalized that to functions, which let us do things like writing both iterative and recursive functions. And then we've introduced the first of our compound kinds of data structures, tuples and lists. We're now going to build on those ideas in two different directions. First, we're going to talk about how we can use functions themselves as objects. Sounds a little strange, but it's really valuable. And then we're going to introduce an even more powerful kind of data structure called a dictionary that's going to give us the same kinds of abilities as lists, but add other things in. So let's look at that. I want to start by going up a level and talking just for a second about functions. In programming languages, we refer to functions as first-class objects, something that's nice to aspire to. What does it mean? It means that it has a type. It also means that it can be used as elements of data structures like lists. And finally, it means that it can be used inside of an expression. It could be part of an assignment statement or as an argument to a function. And I say that because in some ways, functions can be used the same places we would use numbers, or we would use strings, or we would use lists. Numbers have a type. They can be elements of a data structure, and they can appear inside of expressions. Same thing with strings. Turns out functions can as well, and that leads to some really interesting kinds of behaviors that we might like to be able to use. And it's particularly useful when we want to use functions as arguments coupled together with doing things on lists. We often refer to this as higher order programming. We're using functions, for example, inside of lists to do things on lists. And let me show you an example of that. Here's a nice little function. It's called apply to each. You can see from the doc string, it assumes two things. It assumes that L is a list, and it assumes that F is a function. And it's going to mutate L by replacing each element with that function applied to that element. The loop is sort of what you'd expect. I'm nicely iterating down the length of the list. And I'm saying basically for each index that goes into the list, get out the element of the list, apply F to it, and then put that back in that spot inside of the list. So I'm literally applying that function to each element of the list. Remember, I'm also mutating the list as I do it. So let's look at a little example. Imagine I have a list, L, that's 1, -2, and 3.4. I have my little function apply to each. And I first say apply to each, apply that to the list L with the function abs, or absolute value. What it will do is walk down the list, applying abs to each element in turn, so that when I'm done with that, L now has the structure shown on the slide. They're all positive. I could do the same thing. Apply int to each of them. 1 and 2, of course, are already ints. 3.4 gets truncated to just being 3. If I've defined factorial, which we talked about in an earlier lecture, I could apply that to each element of the list and get 1, 2, 6. And if I applied Fibonacci, which I defined in an earlier lecture, to each element again, I would again mutate the list. All right, a little funky, but what am I doing here? I'm now able to think about doing something to each element of the list, just as an operation. Apply to each is literally saying, given a data structure, give me back a version of that data structure. In fact, it's pointing to the same thing, but give me back that data structure where I've done something to each element of the list, in this case, using a function. Handy tool to have. I could do it the other direction, which is I could apply a list of functions to a number. Again, I can loop over that list, and in this case, apply functions is assuming that L is a list of functions. And it loops over it. It says for each element of that list L, apply it, assuming it's a function, to the argument x, and print out the result. And so if I do that now with, again, abs, int, fact, and fib on 4, it prints out the absolute value of 4, the integer portion of 4, factorial of 4, and the Fibonacci of 4, treating the functions as if they were themselves first-class objects, and simply giving it a list of functions in this case, a perfectly reasonable thing to do. That idea I can generalize, and in fact, Python provides a very nice generalization, something we call a higher order procedure. It's called map. And here's what map does. In its simplest form, it takes a function that has, in fact, expects only one argument. It takes a collection, in this case, a list of appropriate arguments, and it literally creates a list where it has applied that function to each element in turn. So it will return an iterable that we need to walk down. And in fact, I can do that. Having done that map, it gives me back a collection of them, and I could walk down them in turn, printing them out. And it'll print out, in fact, the values of all of those pieces. I want to say that again, because in the previous case, I was mutating a list. Here, map gives me back a structure that's going to act like a list, but it's something that I have to walk down, iterate over to get back out. That's okay. In this case, I did it. If I wanted to convert it into a list, I could walk down it, accumulating results into a list. So map's a really nice way of abstracting this idea of applying something to a collection. In fact, map has a more general form, which is I could give it a collection of functions that expect more than one argument, what we would call an n-ary function, because it expects n arguments. And if I give it, for example, 2 lists, I can map a function down those pairs of lists, and what it will do is take the first element of each list, apply that function to it, take the second element of each list, apply that function to it, and generate for us something that has the result of doing that processing. And in this case, it's giving me the minimum of the 2 lists in each place, as you can see here. There's the minimum, there's the minimum, there's the minimum. And it reduces for me something that has that particular structure. Map, a very nice generalization about thinking about using functions just as if they were objects that can be applied in appropriate places. We've now seen different uses of plots. We've been mostly comparing orders of growth, which we've seen before. I wanted you to see the idea of how plotting lets you visualize data. And now I want to turn to a variation of that. which is to think about how can we actually use that visualization of results to help guide computation, to help guide the values of parameters we might want to pass in or the kinds of things we want to explore inside of a computation. To do this, I'm going to use a simple little example. Imagine you're planning a retirement. You want to think about making sure you got enough money saved away so that you can retire at the age you want. Let's look at basically how a retirement fund grows with compounding of interest. And I'm going to do it with the following simple little example. I'm going to plan to set aside a particular amount, let's call it M, every month out of my salary. Save it away in a retirement account. I also expect that I'm going to earn a little interest on that. I'm going to invest it in some stocks or bonds or C-bills or something else. So I'm going to expect to earn a percentage R of additional income every month on the investments I set up. And I want to explore how big is my retirement fund going to be when it compounds over time with both new contributions each month and accrual of interest each month so that I can decide when I want to retire. How much do I need to have before I'm ready to actually retire? Let's look at how we might both write code to do that and especially how we can visualize results to think about how I want to do that computation. Well, let's start with just something that computes compound interest. I've written a little procedure here called retire. It takes in 3 arguments. The amount I'm going to put aside each month, the rate at which I'm going to earn interest or if you like, grow my income through investments on it, and how many months or terms I want to compute over. How many issues or how many terms do I want to look at before I'm ready to look at retirement? This function should not surprise you. It does things you've seen before. I'm going to set up a list called savings. I'm going to set up a list called the base. That's going to be my Y and X values if you like. I'm going to compute the monthly rate. That's just the annual rate, but every month, so divide it by 12. And then I have a simple little for loop here that runs over the range of the number of terms, so however many times I want to look at this. And it just adds into each of those lists the next label for the x-axis, so the next month. And then the savings computation is a little bit different. I take the value of savings the previous month, and I add to it something that adds in the extra rate. So it's multiplying by 1 plus the monthly rate, which says I've got the savings from last time, plus I got a little bit more because I've earned a little bit more interest off of it. And then to that updated value in my savings, I add in the new monthly contribution. I'm building up 2 lists, and I'm simply going to return those. A base list, which gives me the X labels, if you like, and a savings list, which gives me the Y labels. This shouldn't look surprising to you. This is just a standard little accrual of values in a list of a compound interest plus a new contribution each month. What I want to look at is how do I visualize that? So I'm going to use retire to compute those 2 lists. And notice, by the way, I'm returning both of them. That's very nice. I'm going to use that in a second. Now, I'd like to display that. And I'm going to start by looking at something that's going to display the different growths in retirement accounts as I change how much I put aside each month. I'm going to call this display retirement with monthlies. It's going to take in an argument that is a list of different amounts to set aside each month, a rate, and terms as before. And I'm going to start setting up to do the plotting. So I'm going to create a figure with a name. I'm going to clear it as I did before to make sure that in fact I'm going to be able to reuse it. So I'm going to clear that out. And then I'm going to run over a loop. And the loop is going to, in that list of different monthly values, select a new value and run retire. I'll remind you, it said it returned 2 things, so I'm going to get back out the X values and the Y values. And now I'm just going to plot them, just as I did before. Great. I'm going to plot X values and Y values. The one other thing I'm going to do is I'm going to put in a nice label on here that actually says the label is I'm retiring, and I'm going to put in there what monthly rate I was setting aside. So I know how to associate different graphs with the different amounts set aside. And when I'm done with all of that, notice this is going to be a loop. So I'm plotting different versions here. When I'm done with all of that, I'm going to put the legend up in the upper left corner. Let's try it out. I'm going to try it out with a monthly rate of 5%, nice and healthy. I'm going to take 40 years of contributions. So I've got 40 times 12 because I'm plotting these at each month. So that's the total number of terms. And I'm going to look at what happens when I decide to put different amounts aside each month, from $500 up to $1,100 each month. And if I do that plot, nice. Now, the legend's a little big here. I stuck it in a corner where I know it would show up. But the labels are valuable because they tell me how do I correspond each color to the different graph. And you see the growth, the exponential growth that you would expect here as I slowly grow up each one of these different terms. So I've got a set of graphs over here. I can see what those differences are. I might want to zero in on those a little bit to look at some things about each one of those pieces in order to decide which one is better for me. And in particular, I can see the impact of increasing the monthly contribution. I get things that range from about $750,000 to almost 1 2/3 million as the monthly savings go from $500 to $1,100. Again, my point was to look at how do the visualizations help me think about the computation. This lets me see the range of growth as I change the monthly component. What's the effect of the rate of growth on the investments? Well, I could do the same thing. I could write another function, display retirement now with rates. And here, I'm going to give in a list of different rates. I'm going to pick a particular monthly contribution. I'm going to give it a set of terms to look at. And the rest of this looks much like before. Again, I'm going to put a label on here that lets me understand what I'm capturing. So notice, it's got the string retire, it's got the monthly rate, and I'm also going to put something in here that tells me the actual rate of investment growth so that I can associate each of those pieces with the graph. I'm going to give it a particular argument. I took something about in the middle, 800. I'm going to give it 3 different ranges of growth in terms of investment rate. And again, I'm going to give it the same number of terms. And now if I do the graph, I see that there's a different variation in the exponential growth. Here, varying the rate of growth of the investment return actually tends to spread out more rapidly the actual graphs that we see here. But again, I can now start seeing the range of variation here. I can see that, in fact, if I can have something with an aggressive growth, and hoping for 7% is probably being a little bit optimistic here, I actually end up with a much better range in terms of the total amount I've got in my retirement account when I'm ready to retire. Sounds nice. So here, I can see the impact on a different dimension. Now it goes from about 600K to almost 2.1 million. Okay, I want to look at both rates together. What happens if I both think about I want to change how much I'm setting aside each month, and I'm going to be conservative or aggressive in what I want to do in terms of my investments to decide how to get growth in terms of my, my actual and overall retirement account. So I can do both at the same time. It's a little bit more messy code, but you've seen both pieces of it. Now I'm going to have a list of monthly rates. I'm going to have a list of different rates in terms of what I expect of the return on investment, saying am I conservative or aggressive in how I do all of this. I'm going to set up a figure with an appropriate label on it. I'm going to clear it out. I'm actually now going to zero in on just the high end of the range. And here I probably should have, rather than giving it explicit values, looked at the range of terms and set it up. But I happen to know what I was going to use here. So I'm just going to look at the last 10 years of investment on these pieces. So I'm going to literally separate out the X limit on that. Notice, previous examples I set the Y limit. Here I'm choosing the X limit, the X axis, and just zeroing in on one piece of it. The last piece of it is I'm now going to loop twice. I'm going to loop over how much to set aside each month. And for each of those choices, I'm going to loop over different rates of return. As before, I'm going to set up a label, and that label is going to help me out. And now I'm going to look at 4 different monthly rates, 3 different returns, and let's see what happens when we do that graph. And I should have said that. I'm just going to focus on that last stage of the fund. And if I do that, and I put on the appropriate label, I get yuck. Well, the labels help me here. They tell me what's going on. Zeroing in on just the last 10 years was probably valuable because it lets me spread these out. But it's a little hard to figure out which of these graphs is corresponding to which color. So I ought to be able to fix that so I can really see more appropriately the comparison. And I remind you that was one of the points. How do I use the visualization to help me decide how to think about the computation? Here, there's too much overlay of the graphs. How could I separate those out into pieces that would really help me think about this a little bit better? So let's do that. I can't distinguish because of the overlap of the graphs. I could just analyze them separately, but I can also be careful about how I want to visualize the different effects. And I'm going to do that in the following way. As before, I'm going to set up a graph, clear it out, focus in on the last 10 years of all of this. But I'm going to do a couple of other things. The first one is I'm going to create a set of labels. I'm going to create a set of monthly labels. R, B, G, and K for red, blue, green, and black. I'm going to set up a set of rate labels. And I'm going to now use, notice, the color to tell me what was the monthly contribution. And I'm going to use the style of display, solid line, circle, dash line, for example, to tell me how I want to actually visualize the different rates. Inside of those loops, I'm going to select out a month label by doing the following wonderful little trick. I pick out a monthly rate from that list of monthlies, and to get the month label, I'm simply going to take the remainder after dividing by the number of those pieces to tell me which label to use. So it's going to walk through the labels one at a time, and if I have more choices than I have actual labels, it'll cycle back to the beginning. But this is going to let me select out the label. I'm going to do the same thing with the rate label. I'm going to pick it using the remainder function so that I cycle through those choices. And then when I do the display, I should get something that better separates out the visualization. So let's see if that actually happens. I'm going to create that label by putting those two pieces together. Remember, to do the label, I need both a color and a style. And so by putting those two pieces together as a string, that's going to give me the piece I'd like. And there we go. This may still look messy to you, but this is actually nice because notice the color all corresponds. For example, red is all 500. Blue is all 700. So the color tells me very nicely what was the monthly rate. And the style, solid line, circle, dash line, tells me whether it was a return of 3, 5, or 7%. And while there's still a little bit of overlay between these graphs, it's now easier to see what's the impact. Which one has a bigger impact? In fact, it's being more aggressive about your investments that has the bigger impact because that shifts things up much more rapidly than basically how much I set aside each month. You can see that the slant of the line, if you like, up here with the 3 or the 4, actually, I should have done that right, the 4 dash lines is much better than the slant of the line down here with the 4 solid lines. And that was my original point. I want to be able to visualize and use the visualization to guide the computation. And this says, start saving early for retirement because you really want to do that to get that wonderful compound interest rather than relying on getting a 25% return each year because that suggests that somebody's convinced you to invest in a Ponzi scheme and it's not a good idea. Whatever you do for your own retirement, you get the idea. I can visualize the data. I can use that visualization to guide the computation. And so that nicely leads to this summary. It's now easier to see the grouping of the plots. Color encodes, in this case, monthly contribution. Format, solid circle dashed, encodes the rate of growth that I chose for the investment. And more particularly, as you saw with this example, I can interact between the plotting routine and the computation to explore the data. Can change the display range to zero in on a particular area of interest. In this case, it was the last 10 years. I can change the set of values and visualize the effect, and that then guides a new choice of values to explore. What if I wanted to look at different rates of return? What if I wanted to look at different monthly rates? And finally, I could change the display parameters to highlight how to cluster plots by parameter. If you choose to take the second half of this course, you're going to see lots of nice examples of using plotting to visualize data, to think about what it says about a computation. But we also wanted you to see an example of using a library. And notice throughout this entire lecture, all I did was use a set of functions that I could look up inside a PyLab. That lets me rely on somebody having written code I can use and using that library, a tool you're going to use a lot as you move on in your own computation. So we looked at adding labels, adding titles to our graphs. Good thing to do if we want to save them. We want to put them in a paper. We want to hang on to them and look at them later on. But we started this discussion by saying we also wanted to use the plotting or graphing as a way of thinking about different kinds of results. We started that when we began plotting different functions in different windows. But even there, what I showed you earlier could have been a bit misleading because it looked like the linear graph and the exponential graph grew at different levels, but we didn't have a clear sense of that because we didn't change the scales. The scale on the y-axis for the linear graph only went up to 30. The scale on the y-axis for the exponential graph went up to 140,000. And we'd like to be able to better visualize differences. So, if the scales are different on the graphs, how could we deal with that? One option is to explicitly set limits on the axis. Right now, we're just letting PyLab do that automatically. It figures out what's the maximum range of y values, and it sets the axis scale appropriately. We could control it. A second option is to actually plot multiple functions on the same display, but to choose which ones I want to display. We did this earlier when we put all four together, and we saw that that wasn't really effective because the smallest ones were too small. But we're going to look at how we might do a different way of doing that multiple display to get a better sense of that kind of difference in scale. So let's look at both of these. Changing limits on the axes. Here's the code, things we've been using as before. Notice again, I'm going to get into that habit of just clearing the frame before I deal with it. And now I can explicitly say, I want to have the y limit go from 0 to 1,000. I'm picking that number because I happen to know what this display is going to look like. Some experimentation might let you decide an appropriate set. But what you should see here is that when I am plotting, I have the ability to explicitly set the range on the y-axis. By the way, I could set the same thing on the x-axis. And I don't have to show all of the values of the y function or the x function. I could actually pull out just a subset of it. So in this case, I'm going to do a plot for the linear. I'm going to do a plot for the quadratic, each in their own frame. But I'm going to set the y limit to be the same in both frames, and then I label them. And let's look at what happens when we do that. This is actually quite nice. And why is it nice? Because now I can see what's the difference between a linear function and a quadratic function. We knew that the quadratic would grow more rapidly, but now we get a sense of that difference because I've set it up so that both y-axes have the same range. Notice also I picked a value that has a little bit of a gap up here. I happen to know that the y values are going to go up to about 800. I could have lowered it down, but this was a nice way of picking a range that was going to let me see that difference. From the perspective of visualizing data, this is nice because now I can really compare how quickly does quadratic grow relative to linear while still seeing the difference. What else might I do? Well, I could overlay the plots on top of one another, but do it in a way where I actually pick which ones I want to think about. We saw earlier that trying to compare linear against exponential is going to be a wash because you'll never see the linear. But now I can go back to the idea of set up a function or a frame, clear it, and then in this case, let's plot two functions inside of that frame, pick a second one, clear it, and plot another two functions inside of that frame. And if I do that, again, because I am calling both of those plots inside of the same figure, they're going to overlay. And because I'm calling the second pair of plots inside the same frame, they're going to get an overlay. But I have a better way of doing the comparison. And when I do that, I get the following display. Now I can see the difference between linear and quadratic, and I can see the difference between cubic and exponential. And interestingly, you may not have realized that cubic early on actually grows a little bit faster than exponential, but after some point, exponential takes off and really overwhelms it. Notice at the same time, I should be careful about comparing these two graphs because this one only goes up to 900, that one goes up to 140,000. Part of the message for you here, if I want to compare things, I need to think about what I'm comparing, but it gives me a way of actually doing that visualization in a very nice way. So there are some times when I want to overlay things on the same window, and other times when I want to just have them displayed side by side. I can do a couple of other things here. Now that I'm starting to do other displays on top of things, I could also add a legend that helps me tell which plot is which. If I go back to this window, you kind of know which one's quadratic, which one's linear, but it'd be handy to label them. And I can do that. And in particular, I can add in a label for a plot. Here I'm using the keyword label, and then the equal sign, and then the specific label to put on each one of them. And I'm putting obvious labels here. I'm going to label each one of these plots so that now when I display them, I'm going to get a nice display out. One more thing before I do them. I need to decide where am I going to put the legend. And I could actually give it a location by giving under the plot function legend the keyword loc for location of upper left. Or I could simply say put the legend up, but give it no argument and let Pylab decide what it thinks is the best location to use. Notice, by the way, that I need to do this because it's not just that I've put the label here. I actually have to command Pylab to put a legend in for it to appear. Okay, with that in mind, what does it look like? Yeah, kind of cool. Remember, I said use the upper left location. There's the legend. And now each graph has a legend associated with it. So I know that the blue line, this one down here, is linear, and the green line is quadratic. When I let Pylab decide where to place it, it makes a decision that it thinks is the best location to put it. You might argue that in this case, putting it in the upper right corner really isn't great because it overlaps a little bit of the graph. It might have been better to put it over there, but we leave it up to Pylab to decide where to place it. And again, now I know that this is the cubic and that is the exponential because the legend tells me that right there. So that's great. I can start adding more information to the plots that I'm using. So we've seen we can overlay plots, we can do plots side by side in different windows, we can control the scales on the axes in order to zero in on how we want to do comparisons of displays, we can add labels, we can add legends, we can add titles. We're in good shape. Let's think now about how we might actually control even more of the parameters of the different displays in order to better highlight different aspects of what we're trying to plot. So we might want to change the color ourselves of what we're drawing in, or the style of the data sets. We might want to change the width of the lines to highlight one more strongly than another. And we might actually want to do subplots inside of a plot. Let's look at all three of these things as different ways of using plots to visualize data. I'm going to start with changing the data display. And in particular, I'm going to go back to my similar examples. There's a lot of code here, but we've seen most of it. I'm going to open up a comparison of a window that's going to compare linear and quadratic. I'm going to clear it as I did before. And now when I'm going to do the plot, I'm going to add in one more piece. I'm again plotting my samples against linear or my samples against quadratic. We've seen the labels as before. The new thing I've added here are strings that specify the color and the style on which I want to do the display. They're a little terse. That's okay. I'll let you go look at the documentation to see your choices, but the first part of the string says what color to use. B, I believe, is blue, R is red, G is green, R again is red, K is black for reasons I don't know, but the designers of Pylab do. Basically, you can look up the choices of those. The second part of the string lets us decide how we're going to do the display. So a single dash is a line, a zero is a circle, a little upper arrow or caret is a triangle, and two dashes is literally a dash. The idea is that the third argument is going to let you specify a string that says here's the color and style to use. I can still add in other keywords like label to override this. With that in mind, let's see what happens if we do the display. Ah, cool. And notice, by the way, the legends nicely reflect this. They also say here's what we're displaying here. So now I've got a dotted line compared to a straight line. I've got a dashed line compared to a sequence of triangles. I'll let you do the exploration of other kinds of variations you could try here, but you've got some control in how you want to highlight how you're actually visualizing things. In a little while, we're going to come back and use this as an example to see how this is really handy to capture different aspects of data. But you can see I've got the ability to change the visualization. So I can change the style in which I display things. What else could I change? The second thing I could change would be actually the line width. If you like, how thick a pen or how thin a pen am I using to draw these? And here you can see I'm simply adding in now one more keyword, line width, not surprisingly, and I'm giving it a size from 2, 3, 4, and 5. This is referring to the size of the pixels, if you like, on the graph that I'm using to do the display. Everything else here is the same as before. Let's see what happens when I do that. Yeah, very nice. Now you can see, again, the legend picks it up. Notice over here, exponential is a very thick line compared to cubic, compared to quadratic, compared to linear. And it's simply another example of being able to change the aspects of the display to highlight things I want to highlight. I could have picked something different. This is just a nice way of showing it off. The last thing I want to show you in terms of controlling displays takes a little bit of explanation, and that is to use subplots. So some of this is as before, creating a figure, I'm clearing it, but now I'm going to give it a call to subplot. And the subplot takes as arguments 3 numbers, which will look a little bit interesting. So let me tell you what those 3 numbers are. Those arguments are the number of rows and the number of columns inside of the plot, and then which location to use. So in these top 2, I'm basically saying inside of this figure, same figure, I want you to display something with 2 rows and 1 column. So 2 graphs like this. Down here, I'm saying do something with 1 row and 2 columns. So something that's going to look like that. We'll see that in a second. And then the third argument is saying which location am I using in terms of that display. I'm going to do one other thing here. I'm going to go back to that idea of controlling the range or the limit on the y-axis, because I know that these are of different sizes. In this case, setting it to 900. Down here, setting it to 1400. And with that in mind, I'm going to actually go ahead and do the display. Now notice I've got a call to y-lim after each of the subplots in order to try and do that kind of a display. I'm setting the limit within each subplot. I don't have to always do that, but that's a handy way to just make sure I'm being careful about how I'm doing those kinds of plots. Okay, let's see what it looks like. Exactly as I described. In the first case, I've got 1 column and 2 rows. In the second case, I've got 1 row and 2 columns. And the reason I picked setting the limits is so we can see the comparison here in the growth, because it's the same y in both of these cases. And similarly over here, I've picked the same y for both of those cases. You can also see a personal choice here. I don't particularly like this style because I start getting overlaps of values on top of the actual graphs. I find this comparison a little bit better to use, but it's your choice. Main point is I've got the ability to compare things side by side or top to bottom. My choice, but another way of thinking about using aspects of plotting to visualize the data. Now, we've seen a lot of examples of actually doing different things, looking at these different 4 very simple orders of growth: linear, quadratic, cubic, and exponential. Let's now switch gears and think about using the tools we've seen here to actually think about how do I visualize data and think about computation as part of that visualization process. Before we get to that idea of doing that visualization, though, let's look at one last thing that we can do in terms of changing things here, and that's to change the scales. And changing the scales here basically says, if I've got something that actually grows really rapidly, rather than plotting them linear and linear, I could plot them where one of the axes is done on a log scale. And I use the call y-scale, giving it the argument log, to tell me that I want to use a log scale rather than a linear scale as I do this actual plotting. Everything else is as before, and now when I plot them, I can see I can compare simply linear comparison against logarithmic comparison here. The reason this is handy is something like exponential grows so quickly that it really swamps out things very rapidly. And you can actually see it here, even with this rapid rise. When I plot things on a log scale, which is each incremental step here is an increase of an order of magnitude, I get a different way of seeing things, so that now the exponential is linear on a log scale as it should be, and the cubic starts to drop off much more rapidly. So that idea of being able to change scales lets me focus in on orders of growth in a different way. Now that we have the idea of being able to do different plots in different windows, we'd like to see what other things could we add to this. And the first thing is, I should really label things here. I should really label the axes because they mean different things in different plots. So here's a set of code, all calling functions out of that PyLab library. And notice what I've done. First of all, I open up a figure that I'm going to call lin for linear. And the next two calls are putting an X and Y label on that graph. They just take string arguments. So I'm going to say on the X-axis, I want to say sample points. On the Y-axis, I'm just going to say linear function. Obvious things to put in there. I then do the plot of my samples versus my linear, as we did before. I can open up, as I did before, another figure, quadratic, and do plotting there. I could open up another figure, which is cubic, and do plotting there. I could open up another figure and do exponential plotting. And then I might decide, you know what, I want to go back to the quadratic figure and add a label. And so notice here, having first created the quad figure there, I've done a few other things. I can come back right here and say, please reopen the quad figure. Calling figure with the same name will do that. And inside of that window, I'm going to add in another label. I'm going to put a Y label that is a quadratic function on there. Let's see what happens if we do this. Oh, nice. Now I've got something that labels the X-axis and it labels the Y-axis. And oh, wait a minute. Over here, what happened? There's no label on the X-axis. There is a label on the Y-axis. Let's go back to the previous slide and see why that happened. Notice that here I put an X and Y label, but that was in the linear function, or sorry, the linear window. Down here, when I reopened up the quad picture, I only put a Y label on. And that makes sense then. I only said put a Y label on there. The label for X happened up here only inside of the linear window, not inside of the quad window. And so if I want to fix that, I better make sure I do the labels inside of the appropriate windows. But there is my display, and it comes out quite nicely. Okay, what else might I do? If I'm really careful about this, I should not only label X and Y axes, I should also put titles on these graphs. And so I can do that by simply adding in, after I've done all of these pieces, opening up the figure, doing the plots, I could put in labels. And notice here, I'm reopening up each one of the figures and then putting an appropriate label for the title of each one of these graphs. Great. Let's see what happens when we do that. So there's the display. And there's good news and bad news. The good news is there are the titles for the graphs that I drew. But notice I've still got some labels on the axes. And in that previous code, if I go back to it just for a second, they're not there, right? I'm opening up a figure, I'm plotting, I'm opening up a figure, I'm plotting, and then I'm putting titles on. So what happened here? Why are the axes still labeled? And the other thing you might notice is, why are the colors the same in the two plots? They're both of the same color, even though I'm actually plotting different things. So let's answer both of those. The first answer is, or the answer to the first question is, we're reusing a previously created window. I had done earlier calls where I'd created those windows with those names and I'd done things in them, including putting labels on the axes. So if I want to really be clean, I should clear the window before redrawing in it. And I'll show you how to do that in a second. And the second one, if you're wondering, is why are these plotting functions using the same color? We're going to fix it in a second, but basically we're calling a plot in a new version of a window. And Pylab always starts with the same choice of color, and then we'll move on as we do other kinds of plots. As we'll see, we can control it, but if we don't give any specific instructions, Pylab's always going to start with the same color. Let's deal with cleaning up the windows first. So what I need to do is to say to Pylab, when I open up a figure, in case I've had an earlier version of it open previously, I'm going to, in fact, clear it. And it's simply going to use the CLF, or clear the frame function, inside of each one. And it's a nice habit to get into. I open up a window, let me clear it to make sure I haven't been using it previously somewhere else, and I have exactly what I want set in order to have a clean slate. Of course, sometimes I may want to use it previously, and in fact, we'll see that right here on this side. When I want to put labels in, I'm reopening that window and doing the appropriate labeling inside of it. But with that clear, I'm actually going to be able to draw appropriately inside each of them. And when I do that, I get the display I want. Titles in this case on the windows, but nothing on the axes. And I should have said earlier, of course, there were actually 4 windows that were displayed here. I'm just showing 2 of them, the linear and the quadratic. I didn't bother to show to you the cubic and the exponential, but those are going to be things that would also be displayed if I wanted to look at them. So our goal is actually to explore how visualization, plotting, helps us think about data, to see variations in data. So let's start building on that. Suppose I want to display all 4 of the graphs of the different orders of growth all at the same time. Simple way to do it. I just call plot with each of those lists as the y values. The linear one, the quadratic one, the cubic one, and the exponential. And you'll know I'm keeping the same x values here because I want to have the same x coordinate. I just want to see what the different graphs look like when I call those. So if I were to execute this in my computer, I get a display like this. Not quite what I wanted. And that's part of what we want you to see. You can see here that there are at least 3 graphs overlaid. You can guess that this one out here is probably the exponential one. It's growing really fast. That is probably the cubic one. But you notice down at the bottom, what happened to the other 2 graphs? Well, in fact, it's impossible to see the linear graph here, or even, frankly, the quadratic one. If you look closely, you can see a very slight red line down there. And that's because the scales of these graphs change so rapidly. Remember, I'm graphing things with an x-axis from 0 to 29. So the linear graph only goes up to 29, and notice the scale here goes up to 140,000. That's part of what we want to look at. How do we change things so we can actually visualize data? And the first thing we can take from this is, boy, exponential grows really fast, and certainly a great deal faster than linear. Okay, how might we think about doing the display so we can see things a little bit better? As we said, it's not helpful because I can't see things because the biggest plot just grows too fast. So could I graph each one separately? And the answer is sure. I'm simply going to call another function called figure, and I'm going to give it an argument, and that argument simply gives a name to this figure. It's going to allow me to generate different windows, different displays for different graphs. And in fact, I'm going to be able to refer back to that figure if I want to do other things inside of it. Let's look at how that might help my problem here. Idea is that when I call plt.figure, if I call it with that argument for the first time, it's going to generate a new display with that name. If a display already exists with that name, it's going to reopen it and let me do additional processing inside of it. And let's look at an example. So here are my 4 calls to my plots, as I did before. In the previous case, I just called them all, and they overlaid all those plots inside of the same graph or display. But now, I've added a call in between each one of them, saying in the figure with name lin, I'm going to do the linear one. In a new figure with name quad, I'm going to do the quadratic one. And similarly for cube and expo for exponential. I'm creating 4 different displays, each one with its own plot inside. So that lets us then see things like this. Here, calling plt figure of lin opened up a window or graph with the name lin, inside of which I plotted my samples of my linear. And I get that nice graph of a straight linear line with the range only going up to 30 because that was the maximum size of something inside of that graph. When I call plt figure with expo, that has now a new window with the name expo inside of it. And when I call plot of my samples and my exponential, it gives me a different graph. The range here is automatically set to be the largest value I need to show the same thing. That's 140,000. But now I can compare those 2 graphs. I can see the effects of these 2 different displays inside of each window without having them, if you like, buried one very tiny inside of a second one inside of the same window. So I could plot on separate graphs. That's nice. What else might I do? Well, we'll look at that in the next section. Today, we're going to talk about a different topic, but one that we hope is going to be very valuable to you. And that's the topic of how to visualize data. To set the stage for it, let me remind you that a couple of lectures ago, we looked at examining orders of growth, complexity. And there the issue was worrying about if I write 2 different algorithms to solve the same problem, but they come from different classes, they're going to take different amounts of time. They're going to take different amounts of resources. And our focus was understanding those choices between a linear algorithm, a quadratic algorithm, and God help us, an exponential algorithm. We could look at that just looking at numbers. We could look at that looking at mathematical expressions. But we also chose to look at it by looking at graphs, using graphs to help us visualize what are the differences in cost between a quadratic or exponential algorithm and a linear or logarithmic algorithm. That use of graphs gave us an intuitive sense of the differences between those choices. That's valuable. We're going to come back to that. But it also let us do something else. And in particular, it was an example of leveraging an existing library, something that was provided to us, and just using those procedures rather than writing procedures from scratch. That's also a handy tool, and it's something that modern computer scientists use a lot. In the old days, you might write everything yourself. Today, other people have done a lot of work for you. And so what we want to look at in this lecture is the idea of using existing libraries to help us examine algorithms, procedures, data, and help us think about how we want to write our own procedures building on top of those libraries. It turns out that Python provides, or most Python implementations provide a set of nice libraries for you. Could be libraries for graphing, could be libraries for numerical computation, could be libraries for stochastic computation, and many other things. And we're going to look at one example of that today to explore the idea of using existing library procedures to guide processing and exploration of data. The library we're going to use is called PyLab. Now, you've already seen how to import things into a computing environment. You just say import. Here I'm going to use a slightly different version of it. I'm going to import PyLab, but I'm going to say in particular, import PyLab as PLT, short for plot. That's going to allow me to reference any of those library procedures with their name, but preceded by PLT and dot. Just lets me distinguish in my own shorthand, this is a plotting function. I could have picked anything to do that. PLT seems like a nice choice. That gives me then access to a range of graphing or plotting procedures, and we're going to look at those in a second. In this lecture, I'm just going to look at some simple examples. There's lots of wonderful additional information available in documentation associated with PyLab. I encourage you to go look at that. And indeed, if you choose to take the second part of this course, you will see many other examples and details of these ideas. Here, we want to look at the idea of using a library and using plotting to help us think about what's our algorithm actually telling us. Let's start with a very basic function to do that. The most basic function in PyLab simply plots two lists taken as being the x and y values of some function. Other data structures are much more powerful, and you'll see some nice examples of that if you take the second part of the course. In particular, using something called an array lets you do some processing very straightforwardly. Here, we're just going to focus on lists. First, let's generate some data. So I'm going to create 5 little lists called my samples, my linear, my quadratic, my cubic, my exponential. And I've got a little for loop down here that's going to generate some samples for me. Now, if you look at this, I'm running with a range of I from 0 up to, but not equal to 30. And I'm generating simply samples of I and linear samples of I. That may seem a little redundant, but I want to separate out the x values, which are my samples, from a linear function over those x values, which is my linear. And you can see I'm computing quadratic, taking I squared. I'm computing cubic, taking I cubed. And I'm computing an exponential, taking 1.5 to the ith value. So I'm generating a set of lists, and I'm going to plot them in a second. Now, since I motivated this by talking about orders of growth, really I should have used a value like 2 for my exponentials. So 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3, and so on. Unfortunately, that grows so rapidly, it's really going to make it difficult to visualize. So I've taken a slightly smaller value of 1.5, but you could use any value in here. So this little for loop generates for me 5 lists. A list of the numbers from 0 up to 29, which are my x values. A list of linear functions of that, which again would be 0 up to 29. A list of the quadratics, the cubics, and the exponentials, all associated with that set of samples. I'm ready to start plotting. So to generate a plot, I'm going to use PLT because I imported PyLab into that name. And then I've overwritten it, but then the dot, and then a call to the function plot. It's the simplest possible function for doing our procedure for doing plotting. and I need to give it two lists, a list of the x values and a list of the corresponding y values. And here I'm just going to plot my samples, which are the x values, and the simplest of the y values, which I stored up in my linear. As I've said before, for now, the arguments are lists. They could be other structures. You'll see that if you take the second part of the course. Most important point is the lists need to be of the same length. They both need to be of length 30 in this case in order for this to work. There are two ways in which I could actually call this function, or at least in my version of Python. Your version may be slightly different, but I want to show you both of them because you have a choice. I could call the function in an IPython or interactive Python console, and that will generate a plot right inside of the console. I could also call the function in a Python console, and that's actually going to generate a separate window in which the plot is displayed. So let me show both of those working. If I go to my computer, I'm going to start off with just a Python console. And in this case, I'm going to plot 4 functions. It doesn't matter. I just want you to see what happens. And if I plot those on my computer, you will see that nothing has happened, but a separate window is shown up. And in that window, I have, in fact, 4 different graphs overlaid. We'll come back to that in a second. This is nice if you want to store things in a separate window. You want to save things away. You want to be able to actually play with different aspects of the window. I'll let you explore that yourself, but in fact, in this window version of things, you can adjust scales, you can adjust other aspects of the graph. It's one way to deal with it. The second way I can deal with it is to do it inside of an IPython or interactive Python console. And here, if I call this function, you will see that it actually embeds the graph, the plot, directly inside of that console. And I could do other things inside of here. This is convenient if I just want to visualize but not manipulate. Using the full console version is nice if I actually want to do the manipulation. So, I've got 2 different ways of doing this, and from now on in this lecture, I'm just going to show you the results of doing the graphing using actually a Python console so that I'm generating a separate window. So to remind you then, to generate a plot, I'm just going to call plot, giving it a set of x values, a set of y values. As long as they're the same length list, I'm going to be able to graph them out. And let's look now what happens if I do that. The simplest plot would simply be to plot my samples against my linear. And not surprisingly, it gives me this nice straight line because each value was in fact the x value represented as a y value. Simple example, you see what happens when I call the plot. In the next section, we're going to turn to doing more interesting things with these plotting functions. We've seen some simple classes of algorithms, constant, log, linear, and we didn't do log linear, but we'll do that one in a little while. The next class are polynomial complexity, and the most common here are quadratic. The complexity grows with the square of the size of the input. Again, I want you to see what are some of the characteristics that lead to that kind of algorithm, and one of the things we're going to see here is that this commonly occurs when we have nested loops or recursive function calls inside of the algorithm. And we need to say that in a way where the recursive function call has some costs other than constant. Because as we saw with factorial, you can have recursive function calls and have it still be linear. As before, let's look at some examples and see the characteristics that lead to this kind of behavior. Here's a simple algorithm. I want to explain it, but again, I'm less concerned about what it does. I'm more interested in showing you what the pattern is that leads to this. So this is an algorithm that given 2 lists of elements, could be numbers, could be something else, but given 2 lists is going to try and decide, is the first list a subset of the second list? Meaning, every element of the first list, does it also occur in the second list, even though there may be other elements inside the second list? Let's look at the code and the characteristics of the code, and then let's analyze it. So this starts by taking an element in the first list. It's going to set up a little flag here that initially says, I don't yet have a match. And then given that element from the first list, it's going to loop over all the elements of the second list, asking, do I have an instance of that element in the second list? If I find one right here, I'm going to set that flag to true and break out of that loop. Once I've broken out of that loop, I then test. And having set match to true, the if not match doesn't hold. And so I don't return false. I go back around to the loop and get the next element of the first list. On the other hand, if I go through all of this search here and don't find a match, then the matched flag is set to false. And when I come to this test, I'm going to break out of the entire thing by returning false. If I get through the entire set of the list L1 and I found a match in all cases, in that case I'm going to return true. Now you notice here, I've got nested loops. I got an outer loop on L1, I've got an inner loop on L2. And even though I could break out of either of those lists, either here or here, we know that it's the worst case behavior that we're interested in. And that's going to happen when, in fact, L1 is, in fact, a subset of L2, because I'm going to search through all of L1 looking for that solution. Key thing I want you to do, if I step back from this, is to notice here I've got a nested loop, a loop inside of a loop. And that's characteristic of quadratic complexity, and let's see why. So if I take my code, I can now ask, what is the order of growth here? First of all, I know that the outer loop is generally going to be executed the length of L1 times. So however many elements there are in L1, let's call that, for example, n, is going to execute that loop n times, because it's going to ask for each element, does it have a match? Yes, it's possible it could stop earlier, but in the worst case, it's going to go through all of them. What else do I know? I know that for each outer iteration, for each element in L1, I'm going to go through this inner loop, this loop, up to the length of L2 times. And in fact, in the worst case, I am going to go through it up to the length of L2 times. So, what do I have then? I've got an outer loop, I do length of L1 times. For each one of those, I do length of L2 kinds of operations. And by our multiplication law, we know that that basically says this order of growth is the product of the length of L1 times the length of L2. Okay? What's the worst case? The worst case is when they're both of the same length. And in that case, again, let's just call that n. We're going to do n squared operations, n times n operations. And as I said, the fact that we might break out of the loop earlier doesn't change the order of growth of the algorithm. The worst case is basically quadratic in the length of the list. You've seen the characteristic. Nested calls, or nested loops is a nice characteristic of something that's inherently quadratic in complexity. Here's another example. I want to find the intersection of two lists, and then I want to return a list where each element appears only once. So L1 is a list of things, could be numbers, could be something else. L2 is similarly a list, and I'm going to first start by trying to find a list that has those that appear in both lists. And then because there might be some duplication, I'm going to clean it up and only return a list where the elements appear exactly once. I'm not going to step through the code in detail, but notice again a nice common pattern. There's a nested pair of loops. And what I'm doing here makes sense. I set up a temporary variable called TMP for temp. For each element of loop 1, I run through all the elements of loop 2, asking, is that element from loop 1, from list 1 rather, in list 2? And if it is, I add it into temp. I just append it to the end of that. Once I've done all of that, I'm going to clean it up by setting up a new temporary variable called res for result. And then running through the things that appear in both lists, I simply say, if I haven't already put it into the result, add it in. But I'm not going to duplicate it if it appears more than once. And then I'm going to return the result, res down here. Key characteristic, I've got a bottom loop. That's just a loop. I've got a nested pair of loops here, and we've already seen in our earlier example that's probably an indication of the quadratic performance. So let's look at it. There's my code, and here's what I know. That first nested loop, by exactly the same analysis I did with the early example, is going to take length of L1 times length of L2 steps. Because for every element of L1, I do however many elements there are in L2 number of steps. And here there's no breaking out of it earlier. So it's literally going to be, I do length of L2 steps for every element in L1, so therefore the product of those two lengths. The second loop, at the bottom, just goes through, at most, length of L1 number of steps, if every element of L1 also appeared in L2. So now I've got a case of two different orders of growth. The first one's quadratic, the second one is linear. That second term, as we make the problem size really large, simply gets overwhelmed by the first term, and so we ignore that second term,
and we simply say this is quadratic in that product of length of L1 and length of L2. And again, worst case is in essence when they're both of the same length, and we'd say this is order n squared. So a nice example of a quadratic complexity algorithm. Characteristic, nested loops. Now, that can happen in a wide range of cases. Here's simply another example where now I'm simply doing something that's going over a range. And the only difference here is that that range may get generated incrementally as I need it, but otherwise this is exactly like the two cases I saw before. What do I want to look at here? I want to look at what's the cost of the first loop, which is I want to do it n times because of that range. And then what's the cost of the second loop? I'm also going to do it n times because of that range. So it's n times n. Again, it's order n squared. You see the characteristics of quadratic complexity algorithms. We're ready to start talking about complexity of algorithms, orders of growth. And we're going to do that using something we refer to as big O notation. Comes from the Greek symbol omicron, which was the symbol that was used to measure it, which is why we will sometimes also write it as O, and we'll be using that notation. And what big O notation is going to do is measure an upper bound on the asymptotic growth of complexity. So asymptotic means as the problem input size gets really big, what is the behavior? And how do I put a bound on that, an upper bound on that lets me describe that class of behavior? And obviously I'd like as good an upper bound as I can get. Rather than just seeing every problem as exponential, I'd like to say, no, this is inherently a quadratic problem, or this is inherently a linear problem. Big O notation is going to describe the worst case, as we've already said. And that's because the worst case can occur often, and it's usually the bottleneck in when a program runs. So I'm going to talk about what's the worst case behavior when I put that upper bound on it. And I want to express the rate of growth of a program, as I said earlier, relative to the input size. Finally, rather than using timing, I'm going to do this by evaluating the algorithm, not the machine or the particular implementation inside of it. And so big O notation is going to be our way of describing the asymptotic behavior of algorithms. Let's look at an example of what big O means. And I'm going to do this with a procedure you've seen before. This is computing factorial in an iterative fashion. So how do I do it? I set up a variable answer to 1, and then I run through a loop where basically I let n start at 1, and I keep doing that until I get to, let me say it again. Let's look at an example of this, and we're going to do it with factorial iter. We've seen this before. We're going to set up answer to be the value 1, and then basically we're going to multiply answer by n, decrease it by 1, and keep doing that until we get down to the point where n is equal to 1, and then we're going to return the answer. So it computes factorial, and I could ask, so how many steps are there here? And in fact, what do I have? Well, I know that there are 2 steps right there because literally what I'm doing is setting, if you like, n temp to n minus 1 and then n to temp as I do this, or if you like, doing both an addition and a reset. But what we can see is inside of this expression, I have the following. I have 1 step there. I have a loop here that I'm going to go through n times, and inside of that loop, I have actually 5 steps. The test, 2 steps there, 2 steps there. So I've got 5 steps, and I'm going to do that n times. So I've got find n operations, and then finally I'm going to return answer, which gives me 1 more. So the expression for the number of operations independent of the machine is 1 plus 5n plus 1, or 5n plus 2. I want to know what's the worst case behavior. And so as n gets really large, the fact that I got 2 extra steps becomes irrelevant. And that says that I can ignore the additive constants, the 2 ones. The fact that it's 5n as opposed to 7n or 3n as n gets large really also doesn't matter. Practically, it'll be a little bit difference in time, but as an asymptotic behavior, it really doesn't matter. And so in fact, I will say that this is order n. I ignore the additive constants, I ignore that multiplicative constant, and I basically say this is a linear or order n algorithm. So that says when I get expressions for the number of steps inside of a particular computation, I'm going to drop the constants, and I'm going to drop the multiplicative factors, and I'm just going to focus on the dominant terms. So if I had an algorithm that had the number of steps shown in that first example, I'm going to say that's order n squared. And if you think about it, as it says, as n gets really large, n squared is going to be much, much more dominant than the 2n factor. And so really this grows as n squared. Even if it's n squared plus 100,000 n, plus a really large constant, we still say this is order n squared, because asymptotically, as n gets really big, that's the dominant term. For the third one, it's order n, because n grows more rapidly than log n. And as a consequence, this, as things get really large, is the dominant term. For the third one, we'd say it's order n log n. And for the last one, it's order 3n. May look a little weird. N to the 30th is a big number, but as n gets really big, this grows much more rapidly than this. And so we will say the dominant term here is an exponential in 3, as opposed to a polynomial of n to the 30th power. So these are going to show us how we simplify the expressions, and you can now see what we'd like to do. Given an algorithm, we're going to count the number of operations as best we can as a function of size of input, and then we're going to ask, what's the dominant term here? Where's the bottleneck? What's the worst case behavior? And that's going to let us characterize the order of growth. We've already seen these examples. These are the kinds of behaviors we're going to look for. Constant, written as order 1. Logarithmic, written as order log n. Linear, written as O(n). Log linear, written as O of n log n. Polynomial, written as order n to the c. And I don't really care that much what the c is, but I'll at least distinguish, is this quadratic versus cubic versus something else? And finally, exponential. Does it grow as c to the n as opposed to n to the c? And if you don't understand the difference between those two, write a little program and look at some difference in values between n to the c and c to the n. Pick c, for example, as a 2 or a 3 and see how differently these change. Ideally, I'd like an algorithm that is as close to this point in the hierarchy as possible, because the higher up I am in this hierarchy, the more efficient the algorithm is. So, a couple of statements about this, and then we're going to look at some examples. One of the things I want to be able to do, as I said, is analyze the programs and talk about their complexity. And I'm going to combine complexity classes. I'm going to analyze statements inside the functions and then apply some rules and focus on the dominant term. So here are two things to look at. The first one we can call the law of addition for big O notation. And we use it with sequential statements. So if I have a piece of code followed by another piece of code, I could get the order of growth of the first piece of code, the complexity of it, and then the second one. And then I can talk about the sum of those being the order of growth of the overall combination. So for example, if I have two little loops as I've shown down here, the first one is order n, the second one is order n squared. The overall order is order n plus n squared, and as a consequence, the law of addition says that the order I want is just n squared because that's the dominant term. It says I can add up the complexity in order to do the analysis. And that makes sense. This is going to take much longer than that as n gets really big. So I've got a law of addition for analyzing these pieces. I have a second one, a law of multiplication for big order, and we use that when we have nested statements or loops. So in this case, if I have something that has a particular function, and I've got another one that I'm going to do inside of it, the order of growth of that multiplication is the order of growth of those two functions multiplied together. Another way of saying it is if I have two loops, one inside the other, so I'm going to loop over this loop, and inside of there I'm going to do a second one, then I have an order of growth n for the interior part, and an order of growth n for the exterior part, and that is the same as having an order of growth of the product. That is, I'm bringing this multiplication inside the notation, and we say this is n squared. Another way of saying it is, it's because that outer loop is done n times, and the inner loop also does n times, and since we do the inner loop n times for every version of the outer loop, it's n times n, or n squared times, in terms of execution for this particular kind of example. So I can analyze loops or nested statements, looking at what does it take the inner part, and then what does it take, how many times do I do that inner part in the outer part, multiplying that complexity together. And we saw with addition, when I have sequential things, I'm going to add the orders of growth together and then do the analysis. Now, let's assume we have a sorted list. Whether it's integers or something else, it is a list where the elements can be placed in increasing order. And it's probably simplest just to think about it as a list of integers. Other things will work equally well. I could certainly do linear search on a sorted list. And here, You can see a piece of code that would do it. I'm going to walk through a loop down all of the elements of the list. And if I find that the element's there, I can just return true and break out of the search. If I ever get to a point where the thing in the list is bigger than the element I'm looking for, since I assumed it was sorted in increasing order, at that point I can also break out of the list, and in that case return false, because I know it can't be in any of the rest of the list if all of those are bigger than the thing I'm looking for. If I get all the way through the list without having found it, I'll just return false because it says it's not present. Running time wise, this is actually going to be better than the brute force kind of search. I'm taking advantage of the fact that I know that in fact the element has the list has a particular order to it. But the cost is still linear. I only need to look until I get to a point where I can stop, but breaking out of that loop, as we've seen, doesn't prevent the analysis that in the worst case, this is still going to be linear. And as before, it's going to be order of the length of the list for the loop, order 1 to test if it's there or not. We've already seen that that's constant. So the overall complexity is still order n. Timing-wise, maybe a little faster, but complexity is the same class. Okay, with that in mind, now let's look at bisection search. And when I want to look at bisection search, I'm going to use that idea of dividing the problem in half. So here's the rough idea, and then we'll implement it. I'm going to pick an index in the list that divides the list roughly in half. If it's not of even length, I'm going to be close. I'm just going to pick a thing midway through. And I'm going to ask, is that element at the midpoint the thing I'm looking for? If it is, I'm done. Fantastic. If not, I'm going to ask, is the thing I'm looking at bigger or smaller than the thing I'm looking for? And depending on that answer, I either throw away the right half or the left half of the list, because I know it can only lie in one of those two sublists. And I'm going to then do the same subdivision. This is something you've seen before. It's a divide and conquer algorithm. I'm breaking this up into smaller versions of the problem, smaller lists, and in fact, I'm reducing the size of the problem in half at each step. And of course, the nice property is the answer to the smaller version is still the answer to the original problem. Once I found it, I return true. If I can't find it, I return false. Let's look at what that says about the way we would actually do the search. So if I've got a list of some size, I'm going to start off looking at the midpoint saying, is it there or not? N elements in that first version. If it isn't, let's assume that the thing I'm looking for is smaller than that midpoint. So then I look at only half the elements. And then let's assume in this case that the thing I'm looking for is bigger than the midpoint of that sublist. I'm going to look at n over 4 elements. And I'm going to keep reducing the size of the problem down by a factor of 2. So after I steps, I've got n over 2 to the I elements. And I'm done when I only got one element left. Either it's the thing I'm looking for or not. So what do I know? I know I'm going to finish looking through the list when n over 2 to the I is just 1. And by a little bit of math, that's when I is log n. Wonderful. This is logarithmic in complexity, where n is the length of the list. The characteristic, cutting down the size of the problem by a constant factor at each stage. Wonderful thing to have if we can get it. So this is really nice. It says if I've got a sorted list, I can do bisection search in log time. How would I implement it? I'll show you two examples, and one that has a different kind of cost than the other. So here's the first version of it. Again, I've got a list L. I'm looking for a particular element. The base case is if there's nothing in the list, obviously it's not there. If I've only got one element in the list, I'd simply check to see is it the thing I'm looking for and return that Boolean value. If it is, it's true. If it's not, it's false. Otherwise, what I'm going to do is find the halfway point by taking the length of the list and doing an integer divide by 2, which is going to give me out an int. And then I'm simply going to say, is the thing at the halfway point bigger than the thing I'm looking for? And if it is, I'm going to search only one half of the list. And if it isn't, I'm going to search a different half of the list. So there's a nice recursive way of solving this problem. But let's look at the complexity. That's constant. That's constant. That's great. That's constant. Also great. But that's not constant. And neither is that. And by that, I don't just mean there's a recursive call. We know that complexity. We know that's going to be logarithmic. The reason it's not constant is right there. I'm making a copy of the list. It's only half the list, but if you think about it, I'm making a copy of half the list in either case. And in the next recursive call, I'm going to make a copy of that half of the list, but that's going to add up to a larger complexity. And in fact, a complexity that's bigger than I want because of that cost of actually copying the list. What's an alternative? A very nice alternative is to say, keep the list, but just keep track of where I'm looking at. So here I'm going to set up, right here, a little helper function that's going to have two arguments. The lower half of the list I'm searching and the higher half of the list I'm searching. And what I'm going to simply do is change where those pointers go to. So let's look at it. Again, the base case down here is if I've got nothing in the list, the answer is clearly false. Otherwise, I'm going to call this helper function with the low pointer at the beginning of the list and the high pointer at the upper end of the list. And what does this now say? It says if the two pointers are at the same place, there's only one element there, I just check to see if it's the thing I'm looking for. Otherwise, I find the midpoint by taking the average of those two things. Ah, that's right. It says that's going to be halfway between low and high. If at the midpoint I have the thing I'm looking for, I return true. Otherwise, if the thing at the midpoint is bigger than what I'm looking for, then if there's nothing left to search, I just return false. Otherwise, I call it again with the same low point, but now my high point is reduced to the midpoint. I've thrown away half the things. And in the other case, I change my low point and keep the same high point. So if I were to think about it, it's as if I got my big list here. I start off with low pointing there and high pointing here. And after one recursive call, I might have low pointing there and high still pointing here. And after another recursive call, I might have high pointing there and low pointing there. But I'm cutting down half the search, but not copying the list. I'm just changing some numbers. And so now if we look at the complexity here, that's not constant because of the recursive call, but within it, it is a constant amount of work. And the same thing there. So the only things I'm counting now are how many times do I do the recursive call. But the call itself does a constant amount of work. As a consequence, I've got now two algorithms. The first one has log n calls, but within each of them I have to make a copy of the list, and that's at cost of n. So overall, it's n log n. I could make it slightly tighter, but it's still going to be linear because of that copying effort. On the other hand, the second implementation simply uses the indices as the parameters. The list is never copied, and so the only cost here is, in fact, the recursive call. And that's really nice. Just to give you a sense of this, I've got two versions of those two implementations over here in my code. I'm going to run them into the machine, and I'm just going to show you that they, in fact, compute the same thing by calling bisection search. And I'm going to do the first version on a test list, and I'm going to ask if the number 9 is there, and it returns true. And I could call the same thing but ask if the number 15 is there, and it returns false. And I can do bisection search with the more efficient version. Again, I'm going to call it with 9, and it returns true. And if I call it with 15, it also returns false. And it's really hard to see in the machine the difference in timing because it's a very small list. But our complexity analysis tells us that the second solution is going to be much better than the first solution. So, what do we have here? I want to search a sorted list where the size of the problem I'm going to call n, the length of the list. Using linear search, order n. Using binary search, I can search for the element in order log n, which is great. But I had to assume that the list was sorted. So what does that say about the cost? Well, does it make sense to first sort the list and then search if I'm given a list in arbitrary order? So what that says is, well, I want to know when is it better to do sort and search rather than just search. And that basically says, well, when is the cost of sorting less than order n minus order log n? And that's when the cost of sorting is less than order n. And oh darn, that's never true. Did I just waste your time? Of course not. Because while if I'm only going to do it once, it's probably not worth doing the sort. and then the search. I might as well just do a linear search. I can amortize the cost. And in particular, why would I bother sorting? Well, in many cases, I might simply want to sort the list once, but then do multiple searches. I'm looking for different elements inside of this list. I just did it with my little example on my machine. And so I can amortize the cost of the sort over many searches. If I'm going to do k searches, I then want to know when is the cost of sorting plus k searches, so k times log n. When is that less than just doing k linear searches? And for large K, that sort time becomes irrelevant because it's always going to be the case that that log cost is much better than the linear cost. So it is still important to sort and then search. And that says we now need to look at, all right, how do we do the sorting? So we want to sort things. And we're going to start with some really simple ideas and then look at more interesting, more complicated, but more elegant ways of doing the sort. The little animation you're seeing here is a demonstration where I've got n integers from 0 up to n minus 1. And I'd like to have them sorted. So if you want, along the axis here is the index into the list. And this is the value of those elements. And ideally, when they're sorted, they'd all lie along this diagonal. The first sort has a number of names. It's called monkey sort. It's called BOGO sort. It's called stupid sort. You'll see why in a second. Slow sort, permutation sort, shotgun sort. And the idea is very simple. I'd randomly assign the elements into the list, and then I look at them and say, are they in order? And if they aren't, I randomly assign them again. You may have played this game with your friends as a kid with a deck of cards. We used to call it 52 card pickup because you scatter the cards and then you pick them up to see if they're in order. Clearly not a great way to do the sort. Are they sorted? No, repeat. And you keep doing that until you come up with something that does work. It is a possibility. It's not one that I recommend unless you've got a really small size problem. So what's the complexity of BOGO sort? There it is. It says, while it's not sorted, just randomly shuffle them and keep going. Well, in the best case, it's great. It's only order n because I just have to check, are they in order? What's the worst case? Who knows? If you're really unlucky, you could be here a very long time. It's unbounded because there's no guarantee I will ever come up with a random solution that comes up with this. So I probably don't want to look at it, but it's going to set a base, if you like, to compare other things to. So there's a really simple way of doing sort. So the next algorithm we're going to look at is a clever idea, not the most efficient algorithm, but it's something called bubble sort. And the idea here is that I'm given a list of elements. I'm going to start at the beginning and compare successive elements. And I'm going to swap them so that the smaller one is always first of that pair. So if I look at the first two and the second element smaller than the first one, I'm going to do the swap. And then I'm going to look at second and third, and then third and fourth. And you can see what happens here. As I walk down the list, I'm basically bubbling the largest element so that after one pass through the list, the largest element is going to be at the end of the list. If I'm lucky, some of the other ones may already be in the right place. But having gone through it once, I can bubble that largest element to the end of the list. I go back and I do the same thing, passing through, bubbling them along. And I'll do that until, in fact, the entire list is sorted. The little animation kind of nicely shows that to you here. You can see how, as we pass through here, bubbling things along, we build up basically that diagonal from this end down. Largest element there first, and then as I go along, the next largest and so on pass through. I might not have to go through the list n times here. If I'm lucky, many of the things might be in the right spot. But in the worst case, you can already get a sense of what the complexity is likely to be. I've got to go through the list, and I've got to do that probably n times. So it's probably quadratic. But let's look at how we might build it. Here's a little algorithm for bubble sort. I'm going to set up a flag that says, initially, I've got a value false, and we'll see why. It's going to let me tell when I'm done. And then I run through a loop that says, as long as I'm not at a true point, while this flag is false, I'm going to let j go from 1 up to the length of list, and I'm just going to compare successive elements. And if in fact I have a case where the element I want to do is bigger than I want, I set the flag to false, and I do a swap. And then I go back and do it again. So that inner loop's doing the comparisons. The outer while loop is going to be used for multiple passes until there's nothing left to be swapped. What I'm interested in is what's the complexity of this? And that says basically I have to say how many times do I go through this loop. It could be, in fact, to go down the loop I have to do it n times because I got to look at all of the elements and do the swap. Inside of here there's extra work, which is why it's not as efficient because I've got to do some number of operations, but that's constant for every time through the loop. So I've got an order n, or length of the list, processing here to go through the loop. And then how many times do I do it? If I'm lucky, not very many, but in general it's probably order length n. And so I can see what the order of growth here is. It's n squared because I've got to do n minus 1 comparisons, and I've got to do it n minus 1 times. I can look at a little example of this. I've got a version of a bubble sort on my machine. I'm going to load it in. And what I'm going to do is actually print out what the version of the list is at each pass through the loop so you can see what happens here. And so if I call bubble sort on a little test list, you can see what it does. The first time, when I enter the list is just in some arbitrary order. After I've gone through the list once, you'll notice number 9 is at the end. After I've gone through the list twice, 5, 6, 8, and 9 are all in the right spot. So I got lucky. Some of them happened to be just in the right piece, although what I was really doing was bubbling 8 to its position in the list. And so you see here, I don't actually do this n times, but the complexity is still order n times through the process and order n times within each loop in order to get out the solution I want. So a quadratic solution. Clean little code, not as efficient as I would like. Now that we've seen the idea of measuring big O notation, different classes of complexity, what I want to do is look at some examples. Here are the list of classes in order of increasing complexity. And my goal here is to show you examples from almost all of these classes, partly so that when you come across a new problem, you can recognize some of the characteristics of that class. There are certain patterns that are going to put an algorithm into a class like polynomial or quadratic, or into a class like linear, or into a class like logarithmic. And so the goal is to both let you see how we analyze algorithms, to say what class they belong to, and to let you see the characteristics so that when you're creating your own algorithm, you have a sense of how difficult is it going to be to solve this problem. So we'll see examples of order 1, or constant running time complexity. Order log n, logarithmic. Order n, linear. Order n log n, often referred to as log linear. Order n to the c, which is polynomial, where c is a constant. So n squared would be quadratic, n to the third would be cubic. And finally, order c to the n, where c is a constant, which is an exponential running time algorithm, and the most expensive of the classes that we are going to deal with. Let's start with the simple ones first. Constant complexity algorithms. There are very few interesting examples of this, unfortunately. They're the nicest ones because these are cases where the complexity is independent of the input. It's going to take the same order of time no matter what the input is. While there are very few interesting algorithms in this class, often pieces of other algorithms do fit here, and we're going to use that to help us reason about the complexity of other parts of algorithms. Note, by the way, that one can have loops or recursive calls and still be in the constant complexity case. It's simply that the number of iterations or calls in that instance will be independent of the size of the input. We're not going to show you examples of these because they're mostly pretty boring. Logarithmic complexity, on the other hand, is something that's going to be very nice. These are very efficient algorithms. And here, these are algorithms where the complexity grows as the log or logarithm of the size of one of its inputs. Standard examples: bisection search, a binary search of a list. Anything that divides the space of the search in half at each step is a nice characteristic of a logarithmic complexity algorithm. So let's look at a little example here. Here's a very simple example. It's a little program that's going to take in an integer and convert it to a string. And there's standard ways of doing it, but in this case, it's going to run through a little loop to do that. So what does it do? It creates an internal variable called digits, which is a string of the digits from 0 to 9. And then it does the following. Given that input, which is an integer of some size, if it's 0, we just return the string 0. Otherwise, we set up a little loop. We set result to be an empty string. And then we run through a little while loop here, where we take I, get its remainder base 10, which is basically the lowest order digit, and then index into digits at that point, which retrieves that character of the string, and we add it onto result. And then we divide I integer-wise by 10. We shift right. So we're literally going to take each digit in turn, figure out what the character as a string is representing that, and then add it into the result. I don't care what this does. There are lots of other ways to do it. What I want to do is use it as an example to understand the complexity of this algorithm. So let's look at that. There's my code. And what do we know here? We know that we really only have to look at the loop because there are no recursive function calls here. I'm not calling int to string multiple times. Everything's in the body of this code. What else do I know? I know, and I'm going to actually jump ahead slightly here, I know that these stages here are constant. I only do it once. We've already seen in our earlier analysis, they don't matter. So all I have to do is look inside of the while loop. And in that while loop, the things I'm doing are a constant number of steps. So inside of the loop is constant cost. Therefore, all I have to worry about is how many times do I go through the loop? And the answer there is basically how many times can I divide I by 10? Because each time through the loop, I reduce I by a factor of 10. And that is just logarithmic. It's log base 10 of the size of I. So this is an instance of a log complexity algorithm. Now you might say for a second, wait a minute, isn't it linear? And it is in a funny way. It is linear in the length or the size of n, but it is log in the number of digits in n. And since I want to measure this in terms of the number of digits in n, sorry, I'm going to say that better. It is linear in the number of digits in n, but log in the size of n. And since I decided to measure this in terms of the size of the input, I would say that this is an example of a log-based algorithm. And the characteristic is I'm reducing the size of the problem by a constant factor at each step. Okay, linear complexity. Still pretty good because it's pretty efficient. Examples you've already seen. I want to search a list in order or in sequence to see if an element is present. It's linear because I'm going to walk down the list in turn, looking at each element until I find whether that element is present or not. A nice example of a linear complexity search. Another nice example, I want to add up the characters of a string, which I assume to be composed of decimal digits. So I've passed in a string. It's a string representing a bunch of numbers or decimal digits. I want to add them up to get the sum of what those digits comes to. Again, a simple example, but it's going to let you see the characteristics of a linear class algorithm. So there's a simple piece of code to do that. Passing in a string s, I initialize a variable val to 0 initially, and then I'm going to run through a loop where I take each character in s, which is a string, and I'm going to convert it to an int, add it to val, and when I'm done, I'm just going to return val. Simple algorithm. What I want you to see is the order complexity here. It's pretty obvious. What do I have to count? This is a constant time evaluation. Similarly down here, this is going to take constant time. Inside the loop is also constant. I've basically got a conversion to an int, an add, and an assignment, so it's 3 steps. All I need to worry about is how many times do I go through this loop? And the answer is however many characters there are in S, the string, so it is linear in the length of the string. Nice example of a linear time algorithm. Now, let's look at some examples where we actually have calls. And I'm going to start with an iterative algorithm, one that you've seen before, computing factorial iteratively. And to remind you, factorial of n is n times n minus 1 times n minus 2 all the way down to 1. Here, I set up an internal variable to be 1, and then I run a loop where I ranges from 1 up to n of simply doing the product of what I've already had times I and storing it back into there, and then I return the product. And again, the question is, what's the complexity of this? Well, it comes down to the same thing. The return is constant, the setting up a product is constant. What I want to measure is how much cost is there inside the loop, and I know that's also constant because it's just the same number of, in this case, 2 operations each time through, plus 1 assignment up here to set up I, so 3. So the real question is, how many times do I go around the loop? N. That's the size of my problem. So the number of operations, as we've said, inside the loop's a constant. We go through that thing n times. Therefore, this is just 3n, which we've already seen is the same as saying it's big O notation order of n or linear. So something that has a loop in it with a constant number of operations or work inside the loop, characteristic of a linear complexity algorithm. Okay, we got iterative version of factorial. What about the recursive one? Well, we've seen this as well. Remind you that the recursive version says if n is 1 or less, I return 1. Otherwise, I return a recursive call to the procedure with a smaller argument, and then when I get the result out, I multiply it by n, and I return that as a value. If you were to actually time these two, you probably would notice that the factorial version that's recursive is slightly slower than the iterative one, mostly because of the cost of setting up the recursive call. But we've also said that timing isn't the only thing we want to do here. It's really what are the number of operations we have to do. And here, this is still linear, because the number of things I have to do to set up the recursive call are just 2. And more importantly, how many times do I call this function? I call it n times. And so again, it's order n, even though it's recursive rather than factorial. Again, the characteristic here is I'm doing a recursive call once per each increment in the size of the problem. And inside of that operation, I'm just doing a constant number of things. So notice, in an interesting way, both the iterative and the recursive factorial implementations are the same order of growth. It doesn't mean they'll take exactly the same amount of time on the same size problem. But since we want to measure asymptotic order of growth, as we let the size of the problem get really large, these both belong to the same class. They're linear. Now, the next level is what we call log linear. And we're going to see that many practical algorithms fall into this class. It's another nice, efficient class. And is very commonly used on things like an algorithm called merge sort. And I'm simply going to defer you. We're going to come back to that in the next lecture. But this will be a classic example of a log linear algorithm. And you'll see it in a little while. So we've seen some quadratic complexity sorting algorithms. Okay, but not great. And clearly, we'd like to get the sort as efficient as possible. And fortunately, we already know an idea that we can use to do that. And that's to use divide and conquer. If I could somehow break the problem down into half-sized chunks and do work on that, that would be really great. And that leads to a great technique called merge sort, a very common sorting algorithm. And here's the basic idea of merge sort. If I got a list of length 0 or length 1, it's already sorted. I'm done. If I have a list longer than that, let's just split the list into 2 parts of roughly equal size and sort each of them. Once I've got them sorted, I'm going to merge them together. And I'm going to do that, as we'll see in an example in a second, by taking advantage of the fact that if I have 2 sorted lists, I can just look at the first element of each, ask which one is smaller, and put it into the result, and then look at the next portion of it. That's going to be a nice linear time solution. And so when I do that, once I've got to an empty one of those 2 lists, I just copy the rest of the list, and I'm done. You can see the idea. Break it down into smaller and smaller size problems until I get to something that's trivially sorted. And then I'm going to merge those results and keep merging those results out, taking advantage of the fact I'm splitting the problem in half at each stage. Let's look at a visualization of that to get a sense of that. Again, it's a nice divide and conquer idea. So if I've got a big list that's unsorted, I'm going to split it into half. If those are still too big and they're unsorted, I'll keep splitting until I get down to something where I've just got lists of 1 element. Once I'm down at that level, merging is actually really easy. I just look at the 2 and decide which one's smaller, and that gives me lists of size 2 that are sorted. But now merging those is also pretty easy, as we'll see in a second, because I simply look at each of the elements in the 2 lists, putting the smallest one in, and I merge those, and then I merge those, and then I merge those till I get back to something that is overall sorted. Nice divide and conquer algorithm. Should have a nice complexity. We're going to look at that in a second. Before we do, let's again get Professor Guttag and a set of MIT students to give you a little visual demonstration of doing merge sort. And then we'll come back and look at what's the actual complexity of the algorithm.
So we're about to demonstrate merge sort, and we're going to sort this rather motley collection of MIT students by height. So the first thing we need to do is we're going to ask everyone to split into a group of 2. So you split a little bit, You two are together. You two are together. You two are together. You two are together, and you are all by yourself. I'm sorry. All right. So now, let's take the first group, take a step down, and what we do is we sort this group by height with the shortest on the left, and look at this, we don't have to do anything. Thank you. Feel free to go back up. We then sort the next pair, please, and it looks to me like we need to switch. All right, take a step back. Ladies. Okay. Ladies, gentlemen. Also okay. And again, okay. And I think you're in the correct order. Now what we do is we take these groups and merge the groups. So let's have these two, going to sort these groups, have them step forward. And now what we're doing is we're doing a merge of the two sorted groups. So we start by merging them. We'll take the leftmost person in this group and compare her to the first person in this group and decide she's still the shortest. Take a step back. Now, we're going to look at you and say, you're actually taller than this fellow, so you now step up there. And we're good here. Both of you take a step back. Now we'll take these two groups and follow the same procedure. We'll merge them. Let's see, we'll compare you, the first person in this group, to the first person in this group. Now it's a little tricky. So let's see the two of you compare. Let's see, back to back. We have a winner. Step back. And now we need to compare the shortest person in this group to the shortest person in this group. We have a winner. It's you. I'm sorry. And now we're okay. Please step back. Now we'll have these two groups come forward. We'll compare the shortest person in this group to the shortest person in that group. I actually need you guys to get back to back here. You are the winner. And it's pretty clear that the shortest person in this group is shorter than the shortest person in that group. So you go there and you step back. And now we repeat the same process. And you can see that we have a group of students sorted in order by height.
So again, that visualization is, as we just saw with the students, pretty straightforward. I'm going to do sub-pieces and sort them and then merge them. And as you see with this algorithm, or the visualization of this algorithm, it starts with smaller pieces, does a merge sort on those smaller pieces, and keeps doing that until it can do a merge sort on the entire element. And you can also see, even if I get to two sublists of half the size of the problem, the merge is pretty straightforward to do. And that's what's going to give us the power of having a nice complexity to this algorithm. So let's look at the merging part, and then we'll look at the subdivision part. The idea here is if I've got two lists that are sorted, I want to simply say, look at the first element in each, that comparison, and put it into the result. The smallest one goes in. Having done that, one of the lists is now smaller. And again, I'm going to look at the first element of each. In this case, the 2 is going to go into the result. And the second list has gotten smaller. And I'll simply keep doing that simple comparison of the first element of each list, putting the smaller one into my result, until I get to a stage where one of the lists is empty, at which case I simply copy the remainder of the list that's not empty to the end of the list, and I'm done. You can see I might have to take a linear number of steps in the size of the list to be able to get to that stage, but that's still not bad. And that's going to be nice because in many cases it will actually be faster if I actually don't have to look at all the remaining elements of a list. So merging is going to be pretty straightforward. So here's the code that would do it. Right. Merging simply says, given a left and right sublists that we know are sorted, what am I going to do? I'm going to set up a result into which I'm going to store the values. And I'm going to set up a couple of indices, I and j. And basically, I'm going to let them walk down the list. So again, I'm not making copies of the list. I'm simply looking at the elements. As long as I is not to the end of the length of the left sublist and j is not to the end of the length of the right sublist, I'm going to do the comparison. And if the left one's smaller, I'm going to add that element into the result. Again, I know append is constant, so that's nice. And I change I. Just as I did in my example, I now move my index in the left list up by 1. On the other hand, if the right element is smaller, I add it in and I change j. And I'll keep doing that until one of the lists is exhausted. And then these two cases simply tell me in either of those cases, just add in the remainder of that list. Great. What do I know here? I've got left and right sublists that are ordered, so I'm just moving the indices for the sublists. It's avoiding that copy of the list. And so that cost is basically going to be linear in the size of the list. When the right sublist is empty, I copy the rest of the left sublist. When the left sublist is empty, I copy the remaining elements in the right sublist. And then I just return the result. What's the complexity here? I go through two lists, but only one pass. And I'm only comparing the smallest elements in each sublist. So the complexity is basically order of the length of the left and the length of the right sublists. Overall, I've got order length of the longer list comparisons. And so this is always going to be linear in the length of the lists. So the merge stage is linear, depending on how long those lists are. Okay, now how do I put it together? Knowing I know how to do merge, I do the following for merge sort. Given a list, I say if there's only 0 or 1 elements there, I'm done. Just return a copy of the list, and I'm all set. Otherwise, there's that nice pattern. Find the midpoint. Break this in half. Find the midpoint by taking the length of the list, doing an integer divide by 2, and then simply do a merge sort on one half of the list. That's the smaller half of the list. Do a merge sort on the larger, I shouldn't say larger, on the left side of the list and the right side of the list. Once I get those back, simply merge them together, and I'm done. So what I'm doing here is treating base case, dividing the problem in half, solving 2 subproblems, and then conquering it with the merge step to bring it back down. Nice, crisp, elegant solution. What else do we want to know here? Well, let's just look at an example of how it would do this and then look at the overall complexity. So imagine I have a list of 8 elements, as you see up here. I'm initially going to break them in half, and I need to go off and do a merge sort of the left half. Again, I break it in half, I need to do a merge sort of the left half, and eventually I get down to actually 2 base cases. The first base case, the solution I can just pass back, simply a list of 1 element, same thing with the second one, and I just am doing that merge. I do the same thing with that gets passed up to the place it wanted to do it. I do the same thing with the right half. Same kind of merge, that gets passed, and now I can merge 4 and 8 and 1 and 6 with that simple little linear search to get out the solution I would like. Halfway there, same thing on the other half. Having passed that back, I can go to the other half and very quickly get it down to a base case, merge those results, get it down to another base case, merge those results. Those 2 get back up and get merged into an ordered list, and now I can simply merge those 2 sublists to get out the overall sorted list I wanted. I show you this diagram because you can see that nice pattern. This is breaking it down in a nice way into smaller pieces of things, and you already ought to have a good sense of what's the complexity here. The complexity of the overall breaking down into sub-pieces is going to be probably, and we'll see in a second, logarithmic, because I'm reducing the size of the problem in half at each point. The wrinkle here is that the merge we saw was linear in the size of the problem. So let's put those 2 pieces together. At the first level of recursion, I've got n over 2 elements in each list. And so I've got order n plus order n, which by that additive law of complexity is still order n in terms of solving that problem. Meaning, once I've got the solution, I've got to do basically linear amount of work to do the merge. At the second level, I've got n over 4 elements in each list. And there are 2 merges there. We saw that in that diagram. So while the size of the problem is smaller, I've got twice as many searches. And if you think about it, I'm still at that entire second level looking at each of the elements probably once. So it's also order n. At each recursion level, the merge step is order n. The size of the list is smaller, but I got more of them. And that basically cancels out. I've got a linear search. The good news is, how many times do I do it? I've already hinted at it. You know the answer. I'm doing a logarithmic number of steps because I'm basically saying, given a size problem of size n, at 1 recursive call, it's n over 2. At 2 recursive calls, it's n over 4. At k recursive calls, it's order n to the k. I'm done when n to the k is of size 1. That's when k is log n. And this is an example of something I promised to you earlier. It's order n log n. It's log linear. So it's not quite as nice as logarithmic. It's not quite as nice as linear, but it's a lot better than quadratic or certainly than exponential. And this is a characteristic of a wide class of problems that are really nice. N log n, log linear. Great solution. So what do I have for sorting? I can be dumb about it and use BOGO search. Good luck. I could use bubble sort. I could use selection sort. They both have a similar property that they are quadratic in size. Timing-wise, selection sort is probably a little bit faster. One of the advantages of selection sort is that I can guarantee that the first I elements are sorted. So in fact, if I want to stop the computation after I get some number of the best elements out, I could do that without having to sort the rest of the list. And that's better than doing bubble sort. But my best option is merge sort. And in fact, while we won't do it here, one can show that n log n is the fastest time in which one can actually do a sort. But having an n log n sort time is nice because if I amortize that cost over searching, I actually have something that's going to work out quite nicely. And so now you've seen search, you've seen sort, and you've seen a wonderful example of an elegant class of complexity, which are those log linear algorithms. Just to step back for a second, we're trying to let you see characteristics that associate an algorithm with a particular class. Constant, linear. We just saw quadratic, which were things like nested loops that lead to that. The next class in that hierarchy are exponential complexity algorithms. These are the most expensive algorithms. And of course, the goal is always, if I can find a solution to a problem that's lower down in the class of complexities, I want to do that. But sometimes, unfortunately, we're going to be stuck with an exponential algorithm. And indeed, many important problems are inherently exponential. There is no more efficient solution than something that's exponential. And that, by the way, is why often when we realize that, we're going to look for approximate solutions, because we may be able to get a good guess more quickly than finding the most accurate guess. A common characteristic to an exponential class algorithm is a recursive function. That is a function that calls itself, but in each call, calls it more than once. You saw an example of that, which was Towers of Hanoi. I remind you, in Towers of Hanoi, we said to move a tower of size n, we move a tower of size n minus 1 to a spare peg, do something, and then move that tower back. So at each reduction of the problem, there were 2 recursive calls. And that's characteristic of something that's exponential class complexity. Let's look at an example. And here's actually a wonderful piece of code. It's very crisp and computes something really interesting very efficiently. Or rather, does it in a very efficient set of code. The cost is going to be exponential. And the idea is if I've got a list, say, of numbers, could be the integers 1, 2, 3, and 4, I'd like to generate a list of all the subsets of that list. So what does that mean? The empty list would be a subset. The list of 1 would be a subset. In fact, every list of 1, of 2, of 3, of 4 would be a subset. Lists of 1, 2, 1, 3, 1, 4, 2, 3, 2, 4. You get the idea. So this is going to generate a list of all of the subsets of the initial list. Let's look quickly at the code and then more importantly see what the cost is to compute this. So the idea is I set up, as always, a little variable here called res for result I'm going to return. And then my base case here is if there is nothing in the list, the only subset is the empty list. And I actually return a list of the empty list. Because I remind you, I want to return a list of all possible subsets, and the only possible subset here is in fact the empty list. The clever solution, much as we saw with Towers of Hanoi, is to say if I want to generate all of the subsets of a list, what I can do is first generate all the subsets with everything but the last element included. And I do that in a very elegant way. I get the list with everything but the last element, and I recursively call this function. That will give me back a list of all of the subsets of everything but the last element. I then set into extra a list with just the last element. And now I create another list, and for everything in that smaller set, that is all of the solutions without the last element, I also create a solution that includes that last element as part of each one of those earlier elements. It's wonderfully clever. I find a solution to the smaller problem, and then I say for every case where I've got a solution, a subset that doesn't have the last element, I'll also have a version of it with the last element. And I do that by simply running through this loop and adding small, which is the solution without the last element, tagging the last element onto it, and putting it into that new list, which is new. And then finally, I just return every solution without the last element and every solution with the last element. It's a wonderful piece of recursive coding. And in, I don't know what they have here, about 7 lines, I've come up with a great solution to it. Having said all of that, now I just want to look at the complexity. Why is this exponential in size? And let's look at that. So there's my code. I'm going to make an assumption, it's actually a very reasonable assumption, that I can do the append operation in constant time. That simply says I need to know where the end of the list is without having to walk down the list, and that in fact happens in Python. So what does the analysis now say? It says that the time that I need is going to include the time to solve the smaller problem, plus the time I need to make a copy of all of the elements in the smaller problem. So it's going to be the time I need here, plus making the copy right down here of all of the elements in the smaller problem. Okay? So what does that look like? Well, it's important to think about what's the size of the smaller problem. And there I can do a nice piece of analysis. Because I know that in order to solve this for a set of size k, there are 2 to the k possible cases. How do I get that? Well, if I've got k elements, say they're integers, for each integer I can decide, is this one in or not? So for every integer I've got a choice of 2. I've got k of them, so there are 2 to the k possible cases that could be generated as I solve the smaller problem. Now what does that say? It says to solve this case, if I've got n elements in my largest set, I need to solve a problem of size 2 to the n minus 1, all the subsets with n minus 1 elements. I need to solve a problem with 2 to the n minus 2, a problem with 2 to the n minus 3, all the way down to 2 to the 0 or 1 case. And from mathematics, we know that that is, in fact, 2 to the n. And therefore, this is a problem that is exponential. The base is 2, but it grows as 2 to the n. And if you're a little confused about how bad is it to compare n squared to 2 to the n, try some examples. You'll see that the exponential one grows much more rapidly than the quadratic one. And the characteristic here is I'm breaking this down into sub-problems that I have to call multiple times, just as we saw in the Towers of Hanoi case. So there's a nice characteristic of an exponential complexity algorithm. That now has let us have a run-through of the things we've seen. And I'll simply remind you very quickly. Constant time is just doing a set of operations. There could be a recursive call in there, but it's going to be constant no matter what the size of the problem is. Logarithmic, I'm breaking the problem in half or in portions as quickly as I can. And we want to use that idea when we think about things like bisection search. Linear, we've already seen it could be just a loop that I'm going through some number of times, the number of times being a reflection of the size of the problem, or something that recursively calls itself, as in factorial, again, a number of times based on the size of the problem. Polynomial, again, we've already seen examples of that, recursive calls being very clear examples. An exponential, characterized by having a recursive calls, but where we're breaking the problem down into multiple calls each time around. And as I said with polynomial, the most common one here is where c is equal to 2, and a great characteristic of that is nested loops. So let's wrap up this lecture by looking at a few more examples, just to see again those common patterns that are characteristic of particular classes of complexity. The first one might look a little tricky. You've actually seen a version of this earlier. I've got a little function here, I'm just calling it h of n, and what's it doing? It's assuming that n is an integer greater than 0, and basically it's adding up the digits of a number together. So it's going to take it's going to take that value of n, it's going to turn it into a string, and for each character in the string, it's going to walk down, convert that character back into an add it into answer, and then return answer. It's a slightly brain damaged, or if you prefer, computationally challenged algorithm. There are lots of ways to do it. But what I want you to see is how we would do the analysis here. I've got n as my input, and I want to say what's the complexity of this. We know that this is going to be linear in the length of s. But what is it in terms of the input n? And in fact, that's, if you like, the tricky part. And it's similar to what we saw as an earlier example. I'm converting an integer to a string. I'm then iterating over the length of the string, but that's not the magnitude of the input n. Think of it like that early example of dividing n by 10 on each iteration. And so while it is linear in the order of the length of the string, it's log in the size of the input n. And the base here doesn't matter whether it's base 10 or base 2, it's simply logarithmic. My point is, it's important to think about what am I using to measure the size of the problem, and then how do I characterize the complexity of the algorithm in terms of that size. And this is characteristic of a log algorithm. I'm reducing the size of the problem by a constant factor on each stage. Let's look at another example, Fibonacci. And I'm going to show you both iterative and recursive Fibonacci. And remind you, Fibonacci, the nth Fibonacci number was the sum of the previous two Fibonacci numbers. And the first two cases are when n is equal to 0, it's 0. When n is equal to 1, it's 1. You can see the code here. What I want you to simply notice is how I would look at the complexity of this. I've got the two base cases, and then I'm going to set up two variables, and I'm iteratively going to run from I up to the range of n minus 1 of temporarily holding one value right here, and then simply creating the next Fibonacci number by adding the two previous values while holding on to the values for the next iteration through the loop. You can convince yourself this does the right thing for Fibonacci. What I want to know is what's the complexity. We know that's constant, order 1. I only do it once. We know that that's constant because I simply set it up in the else clause. What I want to look at is inside of the loop. And there I've got basically an assignment, an addition, an assignment. 4 operations. And how many times do I do that? However many times I go through the loop, which is order n, because of range. I'm going to do this actually n minus 2 times, but that's the same as doing order n times, and then I return it. So and that last return, of course, is constant, so this is nice. This is a linear time algorithm to compute Fibonacci. Cool. Actually, the best case is order 1, but the worst case is order 1 plus order n plus order 1, which we know is order n. It's linear. Okay. A more elegant way, in some sense, to compute this is what we did initially, which is to compute Fibonacci recursively. And there we see a different kind of characteristic, because while I've got some base cases, the recursive call is actually 2 calls. I compute fib on n minus 1, I compute fib on n minus 2, and then I add them together. And I'm going to give you a hint. We already looked at this earlier and saw when we had dictionaries we could make this more efficient. And the reason we want to do that is because what do we have now? Yes, we've got a case where, as a reduction to the problem, I've got 2 recursive calls to the function. And we know that should be characteristic of exponential, and it is. Because it says basically if I want to solve fib of n, I've got to do that by solving 2 versions of fib of n minus 1, which is going to have to be solved by 4 versions of fib of n minus 2, which has got to be solved by 8 versions of fib of n minus 3, and you can see the characteristic here. I've got, again, that sequence of 2 to the 0 plus 2 to the 1 plus 2 squared all the way up to 2 to the n, and that overall sums up to being an exponential or 2 to the n problem. Interestingly, as we saw earlier, if I use dictionaries to remember earlier computations so I didn't have to recall them, I can reduce this back to the efficiency of the factorial version while preserving the elegance of the recursive call. But as it is here, recursively this is exponential, iteratively it was linear. So same problem, different algorithms, different complexity. And that's part of what you want to recognize is, can I find a solution that's lower complexity and still gives me the answer I want? One last example. When the input's a list, I have to think about how do I measure that. And we've already seen examples of this. This is simply one where I'm adding up the elements in the list. The issue here is that I have to define what the size of the input means. Many other cases it was the magnitude of the number. Here the obvious one is it's simply the length of the list. And because there's just that one loop there, this is going to be linear in the size of the list. So Big O is a really valuable tool. It compares efficiency of algorithms, and we use it to describe the growth asymptotically as the algorithm takes on bigger and bigger size problems. I want as low an order growth as I can to do that estimate, and I want it to be independent of the machine or the specific implementation. So Big O lets us describe that growth asymptotically in the worst case. And you've now seen the classes of algorithms that fall into that category. One last example is to look at lists and dictionaries, because as we've seen, both of them come with a set of built-in operations. And you might want to know, so what's the complexity of those operations? And here's simply a list of them. For many of the list operations, indexing to get an element out, storing at a spot, getting the length, adding something to the end, they're all constant because the implementation in Python is such that we know exactly how to get to that spot and do something. On the other hand, other operations, are the two things equal? If I remove an element from the list, if I want to make a copy of the list and so on, you can see somewhat naturally are linear. If I want to remove an element, I have to walk down the list until I find it because I don't know where it is. If I want to copy a list, I clearly have to look at every element. So these are clearly linear in the size of the problem. Dictionaries have slightly different behavior. Notice here that index is linear. And that makes sense. If the list, it was ordered, so I knew exactly where to go to get to an element. But here with the dictionary, we said it could be stored in any order. It gives me more power, but it has a cost, which is that it is linear compared to a list which was constant. Same thing with store, same thing with length, same thing with delete, which is the equivalent of remove. They're all linear in the cost. On the average case, they may be much more efficient. Indexing actually is going to be constant on average, but remember, we're worried about the worst case. And so what you see here is I get more power with a dictionary, but it comes with a cost in terms of the complexity of the algorithm. But you now have, I hope, a really good sense of the different complexity classes of algorithms and the characteristics that are associated with each of those classes. So far in this course, we've seen a lot of interesting different algorithms, computing a wide range of things. And we've also now started talking about the complexity of an algorithm. How costly is this going to be to compute as the size of the problem grows? We're going to look at one last class of algorithms, really valuable algorithms, really important algorithms, both looking at the solutions and looking at the complexity. And those are what we're going to call search and sort algorithms. So a search algorithm, an obvious statement. This is something where I want to find an element or an item or a group of items with specific properties within a much larger collection of items. Now, that collection could be implicit. Way back at the beginning of the class, we talked about finding the square root as a search problem. We don't generate all possible solutions and then look inside there. We may do it in a more approximate way, for example, with bisection search or with Newton-Raphson, things we've seen earlier. But these are examples of finding a square root as a search problem. And we now know the complexity of those algorithms because we have the tools to look at them. The collection could also be explicit. And we saw an example of that when we built a little database to look at student grades. Is a particular student record in a stored collection of much larger numbers of those data records? So search is going to be important. How do I know if something's in a collection? How do I find that solution in that collection? We'll see why sort's going to matter in a second, but starting with search, what could we say about a search algorithm? Well, the most straightforward way is just what we would call brute force search. Given a collection, just walk through them one at a time, trying to see if I found the solution or not. And in fact, when we were looking at square roots much earlier in the course, we did that. We had a brute force, sometimes called British Museum search, where I look at every possible version of it until I find a solution. The nice thing here is if I've got a list of possible solutions or list of things I'm searching, it doesn't have to be sorted. It can just be in arbitrary order. But it's going to be linear. And if the list is really large, that's a problem. Bisection search is a much nicer solution, but it only works if the list is sorted. And the idea, if I've got a sorted list, is I don't have to look at all of the list to find it. I can divide up the work the same way we did when we did other kinds of bisectional solutions to problems. And I want to show you two different implementations of the algorithm and look at the complexity. So, first of all, linear search, straightforward. I'm simply going to loop through the list until I find them. And here I have to obviously look through all of the elements to decide if it's not there. So the complexity here is going to be obviously linear. And notice I could speed things up a little bit by just returning true here, rather than worrying about this actually setting the flag and returning it. But even breaking out of this loop, in the worst case, is still linear. So linear cost search to run through all of those pieces. Now, I'm also going to make an assumption here. But just to remind you, it's order length of the list L times order 1 to test if the element's actually the thing I'm looking for or not. But overall, it's linear. That's great, linear time search. But I have one other piece I'm doing here, which is I'm assuming here that I can retrieve the element of the list in constant time. We said that in a previous lecture, that would be the case. But let's just do a quick aside to see why that's true, and then we'll look at bisection search. So why can I say I could get to testing, so whether something's at a particular place, I can retrieve an element of a list in constant time? Let's do the simple case. If my list is all, say, of integers, that they're smaller than some overall size, I could reserve, say, 4 bytes of memory to store each integer. And that says to represent the list, I would just set aside 4 times the length of the list of consecutive elements of memory to store things in. And then if I want to get to the ith element, I know that I've allocated that 4 bytes, for example, to each one. I know that the ith element is at whatever the location of the base element or first element is, plus 4 times I elements down. So I can go exactly to that location in memory. I can go directly here to pull it out. So I can do this in constant time. What if the list is of more complicated elements? Well, we saw that solution earlier as well. We use what's called a linked list, where I set aside a consecutive number of elements in memory to hold the pieces. They point to the next one in turn, and the entries simply point out to the element I want to do. So I simply I go straight to the ith location in memory, and then just follow the pointer to retrieve the element I want. So in both cases, it is constant time access. So brute force method, linear search, linear time to find out whether the element's there or not. And worst case is I have to go through all of the elements of the list in order to deduce it's not present. The next sorting algorithm we're going to examine is called selection sort. And I'm going to describe the idea, show you an implementation, and then we'll actually look at what the complexity of it is. The idea in selection sort is pretty straightforward. On the first step, I'm going to find the smallest element, which means I'm going to have to look at everything, but I'm going to find the smallest element, and I'm going to swap it with the element at index 0. I'm going to put the smallest element at the first spot. On each subsequent step, I'm going to look at the remaining list, find its smallest element, and put it at the next spot. So in the next step, it would find the next smallest element, put it at location 1, and keep doing that. What I'm going to do is constantly keep the left portion of the list sorted. And so at the ith step, the first I elements in the list are already sorted. All other elements are bigger, and I'm not going to worry about the bubbling of trying to put them into order. I could be a little more efficient about doing some swaps if I want to, but basically the idea is to select the next element and put it in the right location. Let's think about what this might look like. And to do that, I'm going to show you a little video of Professor Guttag with a set of students actually doing selection sort. And once we've seen that video, we can come back and do the analysis of the algorithm.
All right, so now we're going to do selection sort. The idea here is at each step, we're going to select the shortest person and put them next in line of the sorted group. So we'll bring the leftmost person forward, and we will compare her to everybody else. So one at a time, step forward. You're still the winner. You go back. Please step forward. Oh, you're definitely the winner. Next. Still the winner. Next. Ah, a new winner. All right. So you can take her place. Now we'll compare. Same old winner. Same winner. No change. It's getting kind of boring. Don't fall. Same winner. Please. Oh, close, but I think you're still shorter. All right, next. No change, which means you are the first in line. Congratulations. All right, now you step forward, and we'll compare you. You are the winner. Take your place in line. Next. It's you. And once again, we have a lovely group of students sorted in height order.
So now, let's think about what a simulation of that might look like. We saw with bubble sort, we were finding the largest elements and putting them at the end, and there was a lot of percolation of elements going through here. With selection sort, we're simply finding the next element and putting it in the right spot. So you'll notice this portion of the list doesn't change very much, and I'm now building up the list in this direction, opposite of what I did before, but otherwise it's fine. Nice, elegant algorithm. Let's build it. Before I do that, I can basically say, how do I make sure it's going to do the right thing? Simulation suggests it does, but I can use an idea we introduced earlier to say, is there a loop invariant? Is there a property that will hold true at each stage of this algorithm? And can I use that to actually deduce that my algorithm is going to do the right thing? And here it's pretty straightforward. Given a prefix of the list, that is the list from 0 up to I, and a suffix of the list, everything from I plus 1 up to the remainder of the list, then the invariant I have is that the prefix is sorted, and there's no element in the prefix that's larger than the smallest element in the suffix. From the way I've described the algorithm, that's clearly going to be true. But how do I now prove it with that induction property I've used before? In the base case, the prefix is empty, and the suffix is the whole list, so it's obviously true. The prefix is sorted, and there's nothing in the prefix that's bigger than anything or the smallest thing in the suffix. On the induction step, I'm simply moving the smallest element from the suffix to the end of the prefix. Because I'm putting at the end, after that step, the prefix is still sorted. And by the way I did it, I also know that the invariant is true because not only is it sorted, but when I'm done, there's nothing in the suffix that's smaller than something in the prefix. And when I exit, the prefix is the entire list, the suffix is empty, and so I have a sorted list. So the algorithm will work. So where's the algorithm? Well, it's actually a pretty crisp set of code to write. I'm going to set up something called the suffix store, if you like, to be initially 0. And as long as I don't get to the length of the list, I'm just going to run through the loop. And what does the loop do? It says ranging from that point to the end of the list. So it's from the end of the things that are already sorted to the end of the list. I'm simply going to compare. And if the thing I'm looking at that point is less than the thing I'm looking at the end of my suffix, I'm just going to do a little swap. Now, this is a little more work than I did before. I'm actually going to do a little bit of bubbling here, but not the complete level of bubbling I did before. I could have literally just said, find the smallest element and move it. Here I'm going to reorder things to save me a little bit of time. But what I know is when I'm done with that, the smallest element in the suffix is now at the point I wanted to look at, right at that point there, and I increase my index by 1 and move on. Notice what I'm doing here. I'm taking advantage of that idea that I don't want to copy the list. I simply want to find the right pointer and then insert in the right spot. So there's selection sort. And I could try a version of that. Again, what I'm going to do is do it where I actually print out what I'm doing as I go along. And so with a variant of that, with selection sort, again on a test, you can see in this case, I see the smallest element always being placed at the beginning of the list. In some cases, I get lucky and it was already there. But in each case, I'm going to keep doing that work until I, in fact, get out a sorted list. You may notice on my computer, it doesn't print out the overall version because I am only printing as I enter it. And if I actually look at test, you'll see that, in fact, it is now fully sorted. Real question is, what's the complexity here? Well, what do I know? I'm going to have to run through that while loop, order length of L times, because I have to go through the loop to make sure that I get the next element in the right spot. Inside of there, when I do that loop, I only have to look at a portion of the list. That's basically length of L minus whatever my index is pointing to. But that still, in general, is order length of L. It gets smaller in each step, but it's still what we would call length of L. And so you therefore see this is quadratic. And it shouldn't surprise you because I've got a loop, and inside of that I have a nested loop. And that is a characteristic of that property of being quadratic, and so it is quadratic in the length of the list. But it's another way of doing this sort, perhaps timing-wise a little more efficient than the bubble sort version we saw earlier. Throughout this course to this point, you've had the opportunity to write a lot of functions, a lot of procedures, to explore different ideas, to create algorithms to solve problems. You've also seen a number of algorithms that we've introduced that tackle important problems. And one of the questions we could ask is, are all algorithms equal? Are all algorithms equal? Are they all created with the same kind of performance or efficiency? Or are some algorithms better than others? It's a bit of an odd statement, but it's an important one to ask. And let's set the stage for this. First of all, you might say, look, computers are fast. They're getting even faster. So maybe the efficiency of a program doesn't matter. If we want to understand how efficient a program is, does it really matter if the computers are just getting so fast? Well, while they are, I would argue that so are data sets getting larger. And in fact, as you may have already experienced in some of the examples you've tried, simple solutions may simply not scale well to deal with data sets that are very large in size. So it is valuable for us to be able to have a way of talking about the efficiency of an algorithm, the efficiency of a solution. And that leads to the question, how could we decide if we have a couple of options for a program, which one's most efficient? Now, that is coupled by several issues. And one is, there's a trade-off typically between time as an efficiency measure and space. For example, if I have a program that's going to compute some particular mathematical function, I might decide to pre-compute a lot of values for expected arguments and simply store them away inside of the computer so I just look them up. And in fact, we saw an example of that when we were computing things like Fibonacci, whereby using that technique we call memoization, storing in a dictionary pre-computed or earlier computed values, we could change efficiency. So there is a trade-off between time and space, but for the most part, we're going to focus on time efficiency. Can we characterize how quickly will a program come up with an answer to a set of inputs? And in particular, are there different kinds of algorithms to do that? Now, there are a couple of challenges in understanding that. The first one, as you've already seen, is even given an algorithm, I can implement it often in many different ways. I could implement it recursively, I could implement it iteratively, I might have different choices of things. So there might be a lot of implementations, and I want to separate out choice of implementation from actual efficiency of the algorithm. While there are many ways to implement something, usually there are only a handful of different actual algorithms. That is mechanical description of a set of steps that I'm going to use to solve it. And so I'd like to separate out choice of implementation from choice of actual algorithm to solve that. And we're going to see some examples in a second. Even with that, I could ask, so how might I measure efficiency? Well, one option is just to time it. Time it on a bunch of inputs and see what the time is like and compare different algorithms based on the timer. We'll look at that and realize there's some challenges with that. The second one, a little more abstractly, is I could count the number of actual operations, primitive things that an algorithm is doing or a program is doing, and use that to compare different implementations or different algorithms. The third one is I could actually abstract that a little more generally to something we call order of growth. And we're going to focus on that. We're going to argue that this is actually the most appropriate way of associating or assessing, rather, the impact of choices of an algorithm in solving a problem and in measuring the inherent difficulty of solving an associated problem. I haven't defined it yet. We're going to do that in a second. But let's start with the first two to see why they're not quite what I need. As I said, I could just time a program. Here's a simple way to do it. I import the time module into my Python environment. And then, when I want to use this, for example, if I wanted to measure the efficiency of this simple little thing that computes Celsius to Fahrenheit, I could start up the clock by just calling that particular method, actually run the algorithm on some number, and then stop the clock right there and look at the difference in time and print out how quickly did it take me to do that. I could do that for a bunch of trials and see how well I do. Problem with this is the following. The running time certainly is going to vary between algorithms, which is what I wanted to measure. But it's also going to vary depending on how I implement it. More importantly, it's going to vary depending on what computer I run it on. Different computers have different speeds, and they won't vary a lot, but it will have a difference in that. And that's really not inherently associated with the problem itself. And finally, the running time is not predictable based on small inputs. I would really have to try it on a wide range of examples to get a sense of how well is this going to scale. Can I use it to predict what the performance is going to be like on a really large data set? So this is not particularly effective because the time varies for different inputs, but we really can't express a relationship between the inputs and the time we see because all these other factors show up, like what's the implementation, what computer am I running it on, and how well will it scale. Okay, let's generalize this a little bit. I said I could also just count operations. One way to do that is to say, let's assume that these steps just take a constant amount of time. Any built-in mathematical operation, any built-in comparison, assigning values to variable names, accessing things from memory. It's actually not a bad assumption to say they all take about the same amount of time. Then what I could do is say, let's just count the number of primitive operations executed as a function of the size of the input. And that would give me a better measure of the efficiency of the algorithm. So in the case of C to F, there's just 3 operations. I've got a multiplication, I've got a division, I've got an addition. And that captures how difficult this task is. It's actually pretty simple. In the case of my little MySum thing here, which is going to basically take in a number and letting I range over the value up to that point, it's just going to add them all up. I can count. I've got 1 operation to do an assignment. I've got 1 operation to get I out, basically from range. And in here I got 2 operations, because remember this is both doing the addition and then doing the assignment. And I'm going to do those 3 operations over the entire loop, which I'm going to go over x times. So in fact, this little function, I could say, has 1 plus 3x operations. And as I vary the size of x, it tells me how this is going to scale. And that's actually a better step. It gives me a way of characterizing the difficulty, the efficiency, the inherent complexity of this little function. So maybe counting operations is enough. Well, it gets me closer. It certainly nicely now gives me something that's independent of the computer, and it certainly is going to vary depending on the algorithm, which is what I wanted. It still depends a little bit on the implementation. It's not so bad, but it doesn't really tell us which operation to count. I could figure that out, but I have to maybe think more carefully about what operations I'm going to count. So this one is a drawback, although not a terrible one. So the nice thing here is that the count based on counting operations is going to vary for different inputs, which is what I want. And I can come up with a relationship between the size of the input and the expected count. And it has the nice property that it really depends on the algorithm, but it shouldn't in fact depend, and it is independent of the computer and is getting closer to what I want. So I'm going to take that idea and build on it. What we know is that timing and counting evaluate implementations. Timing also evaluates the machine, which I don't want, What I do want to do is have a way of evaluating the algorithm, telling how well it's going to scale, and I want to evaluate it in terms of the size of the input. So I'm going to take that counting idea, but abstract it slightly. Before I do that, I need to decide if I want to predict size or efficiency based on size of the input. I have to decide what I'm going to measure as the size of the input. I want to express that efficiency in that way, so that leads me to a choice. Many cases it's going to be obvious, but in some cases the input could be an integer. It could be the length of a list. You basically get to decide, especially when you have multiple parameters, what I'm going to use. For example, if I'm searching to see if a particular element's in a list, probably I want to use the length of the list as the size of the problem, and not the size of the element, since I'm simply looking to see if it's present. We'll see some examples of how we use that in a second. But you, as somebody doing the analysis, have to decide what's the size of the input, or better way of saying it, what is the input that matters, and how am I going to measure the size of that as I talk about the efficiency of the algorithm. Different inputs, of course, will change how the computer runs. And so when I talk about the efficiency, I need to think about that as well. Here's a simple little function that searches to see if a particular element E is in a list L. And what does it do? It simply loops over the elements in the list, asking, have I found the one I want, in which case I'm going to return true. And if I go through the entire loop and I don't find it, I'm going to return false. Obvious little searching mechanism. Here's what could happen though. If I'm really lucky and E is the first element in the list, it's really fast. It's the best case. And in fact, I could say, in the best case, how many operations does this take? Probably not all that useful, because I'm usually not that lucky. If in fact the element is not in the list, I'm going to have to go through the entire list before returning false. And that gives me the worst case, the longest amount of time I'm going to have before I answer that. That's going to be a little more important. There's a third way I could measure it, which is just to say, what do I do on average? And on average, I'm going to look through about half the elements in the list before I find it. In fact, if I run a bunch of trials, I would find that out. And so I could talk about the average case as well. Three choices. I could say, what's the best case? What's the average case? What's the worst case? Which one's more important to me? Well, I want to measure this in a general way, and as a consequence, I want to do it basically for the worst case. To give you a sense of that, again, suppose you're given a list L of some length. I could measure it with length of L. The best case simply tells me the minimum running time over all possible inputs. And in this case, it will be constant. No matter how long the list is, I find it in the first element, I'll give you a very quick answer. The average case is a more practical measure. It's going to tell me on average what I have to do to look halfway through the list. But as I've suggested, the worst case, which is the maximum running time, is really the more useful one to have, because it tells me what's the worst possible situation I would see. And in this case, that is going to be linear in the size of the list. As that list grows, the amount of time is going to grow equally or at the same ratio. And so that's going to be something that's much more valuable to me. What's the worst case behavior? As a consequence, that's the thing we're going to focus on. So our goal now is to talk about what we call orders of growth or complexity of algorithms. And the goal is we want to evaluate a program's efficiency when the input is very large. How does it grow as we scale the size of the input? We want to express the growth of a program's runtime as the input size grows. So we'd like an expression that says, as I, for example, double the size of the input, here's what happens to the efficiency of this algorithm. I can't always give an absolute bound, or rephrase it. I can't always give an absolute expression for that. So what I'd like to do is put an upper bound on the growth. Say it will grow no more than this quickly as I deal with that. And I don't have to be precise. I'm just going to use an order of growth estimate, not an exact one. And we'll see what that means in a second. As a consequence, we're going to look at the largest factors in the runtime. Which part of the program is going to be the slowest? Which one's going to take the longest to run? And what's the worst case behavior for that? And how do I put a bound on that as I describe the complexity of that particular program? What we're going to see is that we can categorize algorithms into different classes. There are things that have what we call constant running time. That is, no matter how we increase the size of the input, it takes the same amount of time, in general, to solve the problem. Things that grow linearly with the size of the problem. I double the size of the problem, I generally double or roughly double the amount of time it takes. things that grow quadratically, or with the square of the time, things that grow logarithmically, that is, with the log of the size of the problem, things that we'll see later on that grow in what we call n log n time, which are not as bad as quadratic, but a little bit more than linear. And finally, things that grow exponentially. And what you can see here is I'd obviously like, if possible, to have an algorithm that is not in this class, because that's really expensive, but is more likely to be in this class or this class, because those are not bad behaviors. And then now we're going to talk about looking at examples of each one of those classes and how we capture that pattern of behavior. Having the ability to deal with exceptions, to raise our own exceptions, to basically control how we want to deal with unexpected circumstances, really improves our ability to write good code. And it's part of that theme of defensive programming. If you think about it, what I did in those examples was I thought ahead to things that could occur that might not be what I normally expect, and thought about what I wanted to do in that case. So my example of looking at grades was saying, if there are no grades, how do I want to handle that? And plan ahead so that I don't just throw an error, I actually deal with that circumstance. We can take that idea and use one more tool from Python to think about how to do defensive programming to prevent circumstances from leading to unexpected results. And that last idea is something called an assertion. We talked earlier on about saying when we write good code, we include things like a docstring that says, here's what I assume the inputs are going to look like, and here's the guarantees I'll put on the output if you give me inputs that satisfy those conditions. But we never enforced that contract, if you like. We simply said, document what you're trying to do. We might want to be sure that the assumptions on the state of the computation really are what we expected. Not just for inputs, although that's a standard place to do it, but maybe more generally. And for that, we can use an assert statement to raise an error, an exception called an assertion error, if those assumptions are not met. As I said, could be on inputs, it could be in an intermediate state of the program where I want to check that I'm in the right place. I can do an assertion that says, I assert that the following should be true, and if it's not, raise an exception. A nice example of good defensive programming. Here's an example. If I go back to my idea of just taking average of grades, I could assert, using that special keyword assert right here, when I enter average, that I expect there to be at least some grades in that list. And so I can assert that the length of grades will not be 0. And what that says is, if I give an input to average that has a list of 1 or more elements, this statement will not be true because it won't be 0, it'll be bigger than that. And in that case, I'll skip past the assert statement and do the right thing. I'm safe to go ahead and do the division. On the other hand, if I accidentally give it an empty list, then, in fact, the length of grades is 0, the not statement is false, and since that is false, assert then will stop the execution, throw an assert exception with that message printed out. So it raises an assertion error when I get something I don't want, otherwise it runs okay. And what's nice about this is it's not going to stop execution as long as I give it legal things. And this is a simple way of enforcing the expectation I have for this function. That's a nice thing to have because I stop immediately. If the assertion's not met, I don't wait till I'm partway through the processing before I stop the execution of this particular procedure. So assertions are really a nice way of doing defensive programming. They don't allow a programmer to conclude. Let's start again on this slide. So assertions are a good way of dealing with defensive programming. What are the properties of assertions? First of all, assertions don't allow a programmer to control the response to unexpected conditions. It simply is going to ensure that execution halts whenever an unexpected condition is not met. Typically, we use it to check inputs. It's the standard place to do it. And you'll see in good programming often every function or every critical function will have an assertion at the beginning saying, here's what I expect in terms of the form of the input before it comes out. If I want to be really careful, I could actually use it to check outputs before I return a value from the function to avoid propagating bad values. And if you think about that docstring, I have an expectation on inputs. I have an expectation on outputs. Having an assertion both on inputs and on outputs is a nice way of being very defensive in terms of how I program things. The other nice thing is that having those checks does make it easier to locate the source of a bug, because I'm going to stop the execution as soon as I get an input that doesn't meet the specs of a procedure, and that tells me instantly that the bug must have occurred prior to the call to that function. And it's a little bit like doing that search I did in my earlier example, but using assertions to help me spot the places to find the bugs, rather than having to go in and put explicit prints throughout the entire procedure. So where should you use assertions? Well, these are some good examples of it. Our goal is to spot bugs as soon as they're introduced and make clear where they happened. So I can use assertions as a supplement to my testing, raising them anytime a user supplies bad input data. And good places to use assertions are to check types of arguments, to check that invariants on a data structure are met. This is a list of more than one element, for example. To check constraints on values being returned, and to look for violations of constraints on a procedure. For example, I say I expect a list to have no duplicates. Well, I could enforce that by actually doing a check and raising or using an assertion rather to stop the execution if I get to that kind of point. So using exceptions to control flow of processing through a procedure, using assertions to check conditions on inputs, outputs, and potentially intermediate values, two valuable tools to have as you think about how to write code that is bug-free and does defensive programming to try and ensure that it's bug-free. Once you've discovered that your code doesn't do what you wanted it to, you now want to do three things. You want to isolate the bug, or bugs, because there's probably more than one. You want to get rid of them. And then, as I said earlier, you want to go back and retest, and keep doing that until you're sure that the code actually runs correctly. That last point is important because all too often you spot a bug, fix it, and think, I'm set, and not realize that there's another bug hidden that you didn't get to. So do all three of these stages as you do that. Now, the word bug, odd word. Where does it come from? Well, I want to tell you a little story, and I want to go back to September 9th of 1947. One of the earliest machines, one of the earliest computers built was something at Harvard called the Mark II Aiken relay computer. And I'm sure you've heard stories like this, but this was something that filled an entire room. It was built out of vacuum tubes and electronic relays and other very large-scale electronic components. It didn't do a lot. Obviously, we've come a long way, but it was one of the earliest computers. One of the key people in the design and programming of that computer was a woman named Grace Murray Hopper, a very famous computer scientist who eventually retired as an admiral in the U.S. Navy. And shown on the left here, along with her colleagues, doing some programming on one of the earliest computers. This console is actually not from the Aiken, it's from a different computer, but it gives you a sense of the kinds of things they did. As they were testing that system on that day, they started running some tests of the arithmetic functions in there. They started up an arctan test, and they were running it. They started up a cosine test, and they were running it. And they kept getting an error. They kept getting something that wasn't working. They tried a bunch of things to debug it. They didn't use that word at the time, I don't think, but they tried a bunch of things to debug it. And finally, one of the technicians went back into the computer and unscrewed one of the vacuum tubes that was in there. And inside it, he found that a moth had flown into the computer and had shorted out the connection. And as you can see in Grace Hopper's words here, this is the first actual case of a bug being found. Whether this is the first use of the word bug or not, most of us in computer science love it because it gives you a sense of why we use that word bug. So that's where the word bug comes from. Now we're going to talk about where do bugs themselves come from. And here there are a couple of things that we want to distinguish between. First of all, there are overt bugs and there are covert bugs. Overt bugs mean that there's an obvious indication that something's wrong. The code crashes. It stops before it gets to an answer. Or worse yet, the code runs forever. It goes into an infinite loop, which you'll eventually decide when you get tired of waiting for the machine to stop and you stop it yourself. Those are obvious bugs, and you know you need to fix them. Covert bugs are ones where there's no obvious manifestation. The code actually returns a value, but it may not be the correct one. And these are sometimes harder to determine. That's where the test suite's going to be really important to try and capture I've got something not behaving the way I expected. You don't want code to return values that appear to be legal values but are not in fact the expected values. Similarly, bugs can be both persistent and intermittent. Persistent ones are the easier ones. It happens every time. Every time I run my code, it crashes or it returns a particular value. I know I've got a problem, I can find it. Intermittent ones are those that occur only sometimes, even if run on the same input. And they tend to depend on other factors. Maybe dealing with something on the web, or maybe dealing with something where the time actually is an important factor. And as you might expect, finding overt and finding persistent bugs and removing them is pretty easy. Finding covert or finding intermittent ones takes more work and are often harder to spot and get rid of. So, what are ways we might deal with this? Overt and persistent, they're obvious to detect, and good programmers typically use defensive programming to try and ensure that if the error is made, the bug's going to fall into this category. In other words, steer it to this direction because it's going to be easier to find. We'll see some examples of defensive programming that can help with that. Overt and intermittent obviously are more frustrating. They're harder to debug. But if the conditions that prompt the bug can be reproduced, they can be handled. And that often is what you'll do here is, you know there's an overt error here. You just have to try and figure out what were exactly the right conditions to make sure that the bug reappears, and that'll allow you to isolate in where you want to go to try and find the bug and remove it. The latter category are the toughest ones. They're highly dangerous as you as a programmer may not realize they're there, and more importantly, the user may not realize that answers are incorrect until the code has been run for a very long period or has gotten to a very different portion of the code, and trying to backtrack to find where that error came from can be really hard. So this is where defensive programming can be important, because if you can force bugs into this category, you're just in better shape. Once you've written your code, you're ready to start testing and debugging. And one of the things you want to do is to set yourself up so that that testing and debugging is going to be easy to do. And there's a set of very general guidelines that you could think about here. First of all, design your code so that it easily supports testing and debugging. And that means doing things like breaking the program up into simple modules, self-contained modules that can be easily tested and debugged individually. Second thing you want to do is make sure you write those document constraints, those doc strings on the modules. What did you expect the input to be? What did you expect the output to be? That's going to give you information that's going to help you design both testing and debugging, because you know what you want to look at in terms of test cases that make sure the module's behaving the way you expected it to. Third, document the assumptions you made about code design. What was your thinking process when you created this code? What were the assumptions that you were making that this code be built in this particular way? Because that's also going to guide the creation of particular test cases to make sure that your assumptions are in fact valid, or that the code is being entered in a manner that supports those assumptions. These are obvious statements. These are things that you can sort of say, of course I want to do them. And in some sense, they are examples of a motherhood and apple pie approach to testing and debugging. I use that phrase because it refers to something that is so clear-cut, obvious to do that you would never question it. And I raise it because unfortunately many programmers don't do this. They think it's so obvious that they don't bother to write the document constraints. They don't bother to document the assumptions that they want to use in here. And I encourage you to get into the habit of doing that now, because it's going to make it so much easier for you to write and test and debug code as you go forward. So, once you've actually written your code, when are you ready to test? Well, the first thing you want to do is ensure that the code actually runs. Kind of an obvious statement, but that, especially in Python, will let you remove syntax errors. It will catch them before you can go. And it will typically allow you to remove most of the static semantic errors, things that simply don't form a well-formed expression. Again, Python interpreter is pretty good at finding most of those for you. Once you know your code runs, the second thing to do is to write a list of expected results. Create a set of inputs, and for each one, what do you expect the result to be, so that when you run the code, you can spot the places where it isn't doing the right kind of thing. Having put that together, there's a set of tests that you want to run, and those fall into two different categories. The first one is what we call unit testing. That is, take each module, each function in your collection, and test it. Validate it to make sure that it's doing the right thing, doing it properly. Test each function separately. Once you've done that, what you want to do as well is go back and retest. And what I mean by that is the following. If you're testing a function, you may find a bug. Having found it, you correct it. And you think, okay, I'm set. Let me move on. But in fact, in the correction, you may have introduced something else. Or even if you corrected a first bug and a second bug, the correction to the second bug may have reintroduced a problem with the thing that was causing the first bug. So do what is called regression testing, in which you go back around and catch reintroduced errors that were fixed previously by, after each fix, testing again the same unit. And then finally do what we call integration testing, which is having debugged each of the pieces, now you need to make sure that they hand off information correctly to each other. And so test the entire overall program. Many people, unfortunately, do this last point. They're in a hurry, so they just run all of the code and they get a bug. And then they go, oh my goodness, where is it? So don't rush to do the integration testing. Make sure that you've done the unit testing and especially the regression testing so that you know all of the units work well before you do the integration testing. And finally, what you're going to discover is, after you've done regression testing, you're going to want to go back and do unit testing. And after you've done integration testing, you'll discover that something wasn't working and you're going to have to go back again and redo the unit testing. But eventually you're going to get code that does what you wanted. How do you do the testing? Well, there are a couple of things that we want to suggest here. The first one is to use your intuition about natural boundaries in the problem. For example, I've got a little function here which is testing is x bigger than y. And I've simply said, I'm going to assume x and y are ints. I'm going to return true if y is less than x, otherwise false. I want to think about where are some natural places to test that. Where are places in the numbers that are going to be natural things to look at? If there is no natural partition, and I'll come back to that in a second, you might just do random testing. Just pick things at random. And the probability that the code is correct increases with the more tests you can run. Those are certainly possible ways of dealing with it. But sometimes a better way to do it is to do what we call black box testing and glass box testing. Black box testing explores all the paths through the specification of the code. And glass box testing explores actually all of the paths through the code itself. So let's look at both of those. Black box testing. I've got a doc string for a procedure here, square root. It assumes x and epsilon are floats, x is greater than or equal to 0, epsilon is greater than 0, and it's going to return the result such that the result squared is between x and x minus epsilon and x plus epsilon. In black box testing, I never look at the code. I just look at the spec. And in fact, it could be done by somebody other than the implementer, which is sometimes nice because you avoid implicit biases that you might have had in doing the creation of the code. The testing can be reused if the implementation changes it. And what I want to do is think about what are the test cases that would deal with all the different ways in which I might go through this specification. Are there natural places to it? For example, if I've got a procedure that's operating on lists, I'd like to do it on an empty list, on a list of one, on a list of many. If I'm doing something that deals with numbers, I might want to do it on small numbers and large numbers. And I'm going to ask, as I've said, and I'm going to show you an example in a second, are there natural places, natural boundaries in the inputs that I'd like to look at? So for example, with square root, here are some examples of cases I'd like to deal with. First of all, I certainly want to look at x equals 0 because that's one of the boundary conditions here. So I'll do that with x equals 0 and a small epsilon. I might also want to look at a perfect square, because as I know numbers that are perfect squares, my code might do something different on them than it will do on other kinds of things. I might want to pick a number less than 1. I know with squares, square root behaves differently when it's a fraction than it does when it's a larger number. And I might want to take something where I know that the answer is not a perfect square. There's an irrational square root in it. I've just picked 4 boundary conditions that are nice. Another set of things I might do is just look at extremes. What happens when I have a reasonable number and a really large epsilon? What happens when I have a really small number or a really large number and a really large epsilon? And same thing the other direction. With a really small, I did that wrong. These are really small epsilons. I apologize. Those are really large epsilons. These are all examples of extreme versions of cases that I could use as I'm doing black box testing. Glass box testing is looking at inside this black box. It's looking at the code itself. And it uses the code directly to guide the design of test cases. Ideally, I would want to have a different test case for each different path through the code. And when I say different path, if this is something that has branches, I want to make sure that I have something that tests each possible branch of the code. We'll say that a Glassbox test suite is path complete if every potential path through the code is tested at least once. Part of the problem here is sometimes I can't always guarantee that. If this is a recursive function that can have arbitrary arguments to it, I can't guarantee it. And so I have to be willing to set up for testing most, but maybe not all of the paths. So that's one drawback to this, and I might miss some paths. Again, guidelines here are to look for branches and make sure that I take each branch if there's an explicit branch inside of it. If I got a for loop in there, I want to have a test case where I don't actually go into the loop, or where I go through the body of the loop exactly once, or more than once. Same thing for while loops. Look for cases that catch all the different ways to execute out of the loop. And this is going to give me a way to try and figure out different ways to test as many of the paths through the code as I possibly can. So here's an example of Glassbox testing. I've got a little thing that's going to compute absolute value. And it basically is going to return minus x if x is less than minus 1, and return x otherwise. One of the problems with path complete is I could actually miss a bug, and I'll show you an example. Here are two cases, 2 and minus 2. It's path complete in that one of them is going to take this path, and one of them's going to take that path, but it's going to miss a bug because abs of minus 1 incorrectly returns minus 1 in this case. And so I should still look for boundary conditions, which I would have gotten by thinking about what is happening right there in order to make sure I test all of the possible ways through the code. I want to show you one somewhat more explicit example of doing debugging. And I want to do this to highlight this idea of treating debugging as a search problem. We've already talked about it, but basically I want to look for an explanation for the incorrect behavior. And I'm going to do that, as I said, by looking at the available data, both the correct cases and the incorrect ones, and trying to come up with a hypothesis about why I'm seeing that behavior, something consistent with the data. Then design and run a repeatable experiment that has the potential to refute the hypothesis. This is really just the scientific method. And keep track of that until I narrow down the range of hypotheses and I find where the bug, or bugs, because there may be more than one, actually exist. One of the ways to do this is to do it literally by search. And binary search is a really powerful tool for doing that. So what I'm going to do is give you a piece of buggy code. So when you see it, don't panic. I know there are bugs in there. I put them in there deliberately. And what I'm going to do is insert a set of print statements to help me narrow down by bisection search where are the bug or bugs that may be causing this kind of behavior. And that's going to give you a way of seeing both how print statements help as well as how search is going to help me find those bugs. So here's two functions. They're attempting to tell me whether something is a palindrome or not. Similar to what I did earlier. But here I'm going to actually have a little function, it's called silly, deliberately, that's going to take in a number, and I'm going to type in a set of characters, up to that number of characters. Use that to pull together a list, as you can see, because I'm going to build a list here in result. And then I'm going to run that through ISPAL, which is going to basically take the list, take a reverse version of the list, and then compare them. Because if they're the same, that's another way of testing if it's a palindrome or not. That's different than what we did before, but it's a nice way to test a palindrome. Whether this is the best way to do it or not, I don't care. What I want to do is use this as a debugging tool. So with that in mind, I've got a version of my buggy code over here. I'm going to load it into my machine. And I'm going to run silly a couple of times just to test it out. So I'm going to run silly, with 5. And I'm going to enter A, B, C, B, A. And it says it's a palindrome. That's good. It was. That's great. Let me do silly again with 10. And I'm going to enter P, A, L, I, N, N, I, L, A, P. And correctly it says it's a palindrome. Now if I'm in a hurry, I say, great, this works. But I've only tested it on things that actually are palindromes. So let's try it on something that isn't a palindrome just to make sure that I haven't missed something here. So I'm going to do a really simple case, silly of 2, and I give it A and B, and it tells me it's a palindrome. Oh crap, I got a bug. Okay, now I want to get into debugging mode. So I need to try and figure out where is this error occurring. So I've run it as I said here. It worked on this case, it worked on this case, but it says that it was in fact a palindrome, which is wrong. So I'm going to pick a spot halfway through the code and simply look at the intermediate values. And so in particular, I'm going to insert a print statement right here, right at that spot. And that print statement is going to look at the value of result before I ever actually called ispal. I want to check to see, am I handing into the thing testing for palindromes something of the right form? So I have a version of the code like that over here, and I'm going to call it, and I'm going to run silly again, and I want to see what happens when I print out intermediate results, and I give it A and B, and I have a problem. What's the problem? Well, I would have expected at this point that I should have had the list of A and B, but when I ran the code, I just got B. Now, because of binary search, I know that at least one bug must be present earlier in the code. So I want to add a second print in, this time inside the loop, to see what's going on. And when I say inside the loop, I was looking after I'd gone through this loop, and I know that the error here says that I'm not getting the right kind of list. I'm going to do something inside the loop to see if I can figure out what's happening there. So let me now put a print statement inside the loop. And let's see what happens if we run it. So now I've got a new version of the code. I'm going to print out the result each time through as I do it. And I'm going to run that. I'm going to go over and call silly again. 2, and I give it A, and it prints out the list A, and I give it B, and it prints out the list B. Ah, that's telling me something valuable. It's telling me that each time through, I'm just putting into result just a single element. So append somehow is not doing what I expected it to do. And that suggests that the result is not keeping all of the elements. And in fact, I can probably already figure out what the problem is. The problem is that I'm initializing result inside the loop, and I really want to initialize it outside the loop. If I go back to my code, right, you can see right here, every time through the loop, I'm setting result back to an empty list and then just putting the next element into it. I really want to set up result outside the list and then see if I can append. I use this as an example because you've probably made this mistake. It's an easy one to do. So let's now move result, as I said, from this position and put it at that position. And with that in mind, here's a version of that where I've moved that initialization. I've still got the print on the inside. Let's run it. And when I test silly 2, and I give it A, it says I got the list A, and I give it B. Oh, good. I'm now at least getting the list in the right form. That's good. That's encouraging. It now tells me that the list is being delivered in the right form, but I'm still getting an incorrect answer. And that tells me that I still have another bug. So the data structure is being properly set up, but there's another bug, and that's really important. It would have been really easy to say, I'm done, but I'm not. There may be more than one problem. And this suggests that the second or maybe third bug must lie somewhere below the print statement. So let's go look at ispal. As before, let's pick a point in the middle of the code, add a print statement, and see what we can do in terms of trying to find it. And I'm going to remove that earlier print statement because I don't need it. So now up inside of ispal, I'm going to add a print statement. And I'll remind you, I need to decide what do I want to test. So here, what I'm trying to do, as you know, is take X, which should be a list of these of characters. I'm creating a temporary version of that, and I'm trying to reverse it. So I'd like to check at this point, is temp different from X? It should be a reverse version of that. All right, I have a version of that on my machine. Let's just load it and run it and see what happens. And as before, I'm going to do silly with 2, and I give it A, and I give it B. Oh, that's interesting. I was trying to reverse the list. And what was I testing here? I was saying, what is the structure of temp and what is the structure of x? I would have expected them to be reversed, one from the other, and they're not. So it should have been that x was AB and temp should have been BA, but they both have AB. So I've got a problem, and it must be happening before this point in the code, because when I get here, I have the incorrect structure. So let's add another print statement a little earlier in the code. And now I'll put a label on it so I can see where I am, because I got multiple print statements. So I'm going to now have the one I had before, which is after the reverse, and I'm going to have the one that I was going to do it before the reverse to see what's going on. Okay, with that in mind, I'm going to come over and try this. I've got now a piece of code with those two print statements. And when I run it, and I run my silly example, A and B, so it wasn't reversing. Even if temp started off as the list X, I printed it out, it was in the right form. After the reverse, it's not. So temp has the same value before and after the call to reverse. And if I look at the code, I can see the bug, and it's a standard one. I forgot to actually call the procedure. I just need an open and close paren. Okay, let's try that and see if that helps what we were trying to do. So now I've got a version of that, and I call it, and I run my silly example with 2, and I give it A, and I give it B. Some progress, but not quite what I wanted. Because now temp and X were the same beforehand, now both of them are reversed. Crap, what happened? I got a reversal, but I got both of them reversed. So putting that in led to having both of them reversed. And now we've simply narrowed it down to a single line. The error must be in that line where I did the call. And I can actually figure out what it is. The problem is we've got an aliasing bug. Reversing temp has caused X to also be reversed. And that's because they're referring to the same object. And I can see that in the code. What did I do? I said, let temp equal X. Oh yeah, that's pointing back to exactly the same structure as X. So when I reverse temp, I reverse X. I've got an aliasing problem. There's an easy fix. And that easy fix is to make a copy, to clone X before I do temp. And with that last change, hopefully I'm finally done. And if I do that, and I run it, and I run silly with 2, I give it A and I give it B. Finally. Now I can see that after the reverse, temp is reversed, X is not, and it says in this case it's not a palindrome. So it took me a while. I had multiple bugs, but I found them. And the message I want you to take out of this is that using that binary search really helped me isolate where those bugs were by thinking about what should I expect at this point, what do I actually see at this point, and what does it tell me about that hidden bug that I wasn't able to spot. So at this point, I should actually go back and check that all our other test cases still work properly. I'm not going to do that, but that is actually part of the good testing patterns, is to make sure that having fixed this set of bugs, I don't still have some hidden bug still showing up somewhere, or that I haven't accidentally introduced a new bug into some of those other test cases. So the last set of just pragmatic hits. Look for the usual suspects. What are the standard places where you might make an error? Aliasing being an obvious one. I found that by looking at when I reverse something, does it reverse everything or just the thing I was trying to reverse? Secondly, ask why the code is doing what it is, not why it's not doing what you want. The latter is because you've got a bug. Asking why the code is doing it is going to be helpful in helping you isolate where the bug might be. Third, the bug is probably not where you think it is, so try and eliminate locations. That's where the binary search, the bisection search really helps. As we've already said, try and explain the problem to someone else, including a rubber ducky. Don't always believe the documentation. It may say, here's what I'm expecting, but it may not actually explain it. So if I'm still having a hard time finding the bug, ignore the documentation for a second and try and isolate in. And finally, if you've been at it for a while and you're not getting there, take a break and come back later. A fresh look can often help you suddenly spot a problem that you weren't seeing because you had hidden assumptions about what you were looking for. So once you're ready to start debugging, here's some advice that can help you out. The first one is I want to start by pointing out that this is a steep learning curve. It often takes a lot of experience to really become very skilled at debugging, which is why a very practiced programmer has a great deal of advantage over an inexperienced programmer. They know the kinds of things to look for, the kinds of tools to use. So this is my way of saying be patient as you learn the techniques to try and figure out how to debug efficiently. There are some tools that are provided to you. First of all, there's some built-in tools into the IDEs, into IDLE or into Anaconda. And I encourage you to use them. You'll see examples of this as you go through some of the problem sets. As you hit a bug, you can use the things that are printed out by the environment to help you isolate where the error actually occurred. I know an obvious instinct is you run a piece of code, it crashes in the environment, you instantly go to the code. Stop. Take a look at what was printed out on the screen. It will tell you something about where it was in the code when it hit the problem. It will tell you something about the kind of error that occurred, and that's valuable to you. Obviously, use the tutor to help you understand this. But the third one is, again, one of those very simple things, but something that really practiced programmers use all the time, and that's the print statement. Insert statements at different points in your code that will print out, here's what I'm expecting, here's what I'm seeing. That's going to help you isolate where the code may be going wrong. It's going to help you narrow into the particular place in the code that you want to search to find the bug. And finally, be systematic in your search for a bug. Treat it like a scientific experiment. Formulate a hypothesis as to where you think the bug is occurring, what an experiment would be to test that, and then run the experiment to see if it validates or invalidates your hypothesis, and then move on. The print statement, as I said, is a great way to test hypotheses. And here are some suggestions. Print when you enter a function. Print out what the values of the parameters are to make sure that they are what you expect. Print the parameters themselves. At the end, print out the result. Even if you're going to pass it on to some other function, print it out so you can see what was returned to check whether it was what you expected or not. Another way to use print statements we're going to do in a second, which is to use the bisection method. That is, put a print statement halfway through the code, saying, here's what I expect the code or the state of the computation to be at this point, and here's what it actually is. Given that, it's going to help you narrow into where the bug may occur. Because if you get halfway through the code and it's correct, the bug must happen after that. Then you can put in another print statement and keep doing that. And so that lets you very quickly isolate which procedure, which function may be causing the bug to occur. Those error messages are often really easy to use. If I get an index error, it tells me that I'm trying to access something in a structure that's outside of the length of that structure. So here's an example that could lead to that. But more importantly, an index error tells me check the bounds of what I'm using as indices to look at structures. If I get a type error, it suggests things like I'm trying to convert something to a type that I can't, or I'm trying to use a function on something that whose type does not support that kind of usage. If I get a name error, it's likely that I'm trying to reference a non-existent variable. I haven't defined or bound the variable initially. I'm trying to use its value before I've ever created it. Here's another kind of type error that I might see. I'm mixing data types together without appropriate coercion. I'm trying to divide a string by an integer rather than casting that string into an int before I deal with that. A syntax error. That's something that will often occur when I do things like forget to close a parentheses or a quotation. Here I'm missing a closed paren right there. And so this is not a well-formed expression because I'm trying to combine a print statement with doing a length call on a structure. So let the error messages actually guide what you're looking for in terms of the bug. Logic errors are harder. This is where I actually get a value out, but it's not what I was expecting. And so what I would suggest here is a couple of things. First, think before you start writing new code. An obvious statement, but a valuable thing to do. Draw some pictures. Sketch out what you were asking the code to do. And then take a break, walk away from it, come back and look at the pictures to say, does my code actually do what I was thinking it did? And then one of the best ones, explain your code. Explain what you were trying to do. Now, you could explain it to somebody else. It doesn't matter whether they actually understand it or not. Just explaining it as a process will help you out. And there's a classic version of this in computer science. Explain it to a rubber ducky. Walking through the explanation will often help you go, oh, why was I doing that? I was trying to do this different thing. But don't just read the code to see if I can find it. Walk through the explanation. So I advise you all to go out and buy your own rubber ducky and have it handy when you try to debug your code. A great way to drive yourself into doing the explanation and helping spot where those errors may be occurring. When you're ready to do the debugging steps, here are the two obvious things to do. First, do look at the code, but ask things like, how did I get the unexpected result? Don't ask what's wrong, ask how did I get there? And is it part of a family of problems that I might be able to see? And then finally, do what I suggested earlier. Use the scientific method. Study the available data. Form a hypothesis as to what might be causing that particular error to occur. Come up with an experiment that I can use to test that hypothesis, and then pick some cases that will actually deal with it and walk through that cycle. And do it until you end up with bug-free code. So, don't just write the entire program, test the whole thing, and then try and debug the whole thing. Instead, write a module, test it, debug it. Write another module, test it, debug it. Then test the entire structure. Then go back and do the same cycle here of test each of the modules before you go through the entire integration testing routine. And similarly, don't change the code, figure I'll remember where the bug was, test it, and then either forget where the bug was or what change you made and go into panic mode. Instead, back up the code, change it, write down the potential bug in a comment, test it, and compare the new version with the old version to see what was the actual change and did it catch the piece that I wanted to find. This latter one I stress because I see too many people just go in and start messing with the code, trying to debug it, and end up with something even worse than what they had and not able to recover where they were. So when you've got code that's is buggy, save away a version of it, take a clean version and start modifying it so you can see what were the changes I made that got me to the place I wanted to get to. So far, we've been talking about how to handle exceptions. We've seen some nice power to that. That when Python throws an exception, rather than bumping us up to top level, we can actually say, in this case, I know what I want to do, and I can actually write code to handle that exception. And we saw examples of using that to build little data structures. Very nice. We can actually go the other direction as well, though, which is we could decide when to raise an exception ourselves. So rather than returning special values when an error occurs and then checking to see if that error value was returned, we could instead say, you know what, I want to raise an exception when I'm unable to produce a result consistent with the specifications of the function. And for that, we have, not surprisingly, another keyword called raise. And the idea is, inside of the code, I can say I want to raise, using that keyword, an exception, and I'm going to give the name of the error that I want to raise in doing that. It could be an error that's an existing error exception. It could be one that we're going to create ourselves. But typically it's going to be an existing error exception. So in this case, a value error. And then a message that I want to print out. And typically that's just a string that I want to have that tells me what was going on. Hopefully something more valuable than just something is wrong. It may tell me the specifics that were happening when I raised this particular exception. This is now putting me in control of deciding when to raise an exception, as well as now allowing me to do what I did in the earlier part of how to handle that exception when I get there. Let's look at some examples. Imagine I want to take in a list of two numbers, and I want to get a ratio of those two lists. That is, each list I'm going to assume is equal length, and I'm going to get the ratio of the first element of the first list to the first element of the second list, and so on. And I've got a nice little piece of code here. It has a form you might expect. I'm going to set up a list in which I'm going to record the results. I'm going to then run down the length of the first list with a little index going from 0 up to 1 minus the length of the list. And I'm simply going to try and get the ratio of those two things and put it into the thing I'm trying to accumulate. So I'm running try here. What I want to do, though, is deal with a couple of different cases. One is, what do I want to have happen if I get a division by 0? And in that case, I'm just going to put something in here that's called not a number. It's a special thing inside of Python that I'm going to insert saying, I can't return a number here because it's infinite. That's just a standard exception handler. But when I get anything else, I'm going to raise a different exception that tells me I called get ratios with a bad argument. And then finally, I'm going to try and return the ratios. Let's see what happens if we actually run this. So here's an example of get ratios. I load it in, and let's give it a couple of lists. L1, I'm going to say, is the list 1, 2, 3, 4. L2 is the list 5, 6, 7, 8. And my apologies, I'll do that again. L2 is the list 5, 6, 7, 8. And if I call get ratios on L1 and L2, it does what I expect. It gives me those ratios and it ran correctly. Let's define another list. Let's make L3 be the list just 5, 6, 7. And if I call get ratios on that with, for example, L1 and L3, oh, good. It did what I wanted it to do. In particular, it threw an error because I'm trying to index beyond the length of L2. It's one short of the length of L1. And notice up here, I'm indexing over the size of L1. And it did exactly what I wanted. It raised a value error. So it did throw me up to top level because I don't have an exception handler to deal with that. But it printed out my information, not the standard thing that would have happened if I didn't have a particular handler there. The last one I want to do is to say, let's let L4 be the list 5, 6, 7, and 0. And if I do get ratios of L1 and L4, nice. In this case, the exception handler kicked in because in this case I have a zero division error, and rather than throwing an error, I said just substitute in that special symbol, not a number, in place of the spot where I would have otherwise put it in. Again, step away from the code for a second. What we're now showing you is I can certainly handle exceptions as they come up, but I can also raise my own kind of error message for different kinds of errors as they occur. In this case, when I got a value error giving me out something specific telling me where I was when this happened, I can use that to control the flow. Let's build on that idea, and let's look at a second example. So as I said, we're managing the flow of the program by raising our own error here. Let's look at an example where we extend that. Let's assume we're given a class list for a subject. And each entry is, as we did in the earlier part, it's a list of two things. A list of the name of the student and a list of grades on an assignment, multiple grades for an assignment. So I might have a little example here of test grades for Peter Parker and Bruce Wayne. And they're both doing pretty well in this class. What I'd like to do is create a new class list with a name, grades, and an average. What's the average that they're doing so far in that? And you can see the kind of output I'd like to get here, that Bruce Wayne's doing a little better than Peter Parker. It's okay. Pick your favorite superhero and what you want to have do better than somebody else. How might I do that? Again, trying to use the idea, which we're going to do in a second, of using exceptions to handle the way we flow through the program. Here's some code that would do the straightforward way of doing it. Little piece of a little function called getStats. It takes in a list, and what does it do? It's going to build a new list, and for each element in that original list, I'm going to take a list of the first element, the second element, and an average of the second element. And I'm assuming I'm inputting things that have a list of names and a list of grades, and it's going to compute that out. An average, of course, just takes that last element, it adds them up using sum, and divides it by the length of grades. And so if I were to do that with a simple little example, here I've got an implementation of that, and I'm going to initially zero out some examples of this to do a simple version, and then I'm going to do a slightly more complicated version. So the simple version is the one that we already have, and if I run this, and then I look at test grades, which is where I asked to put the result, I get what I wanted initially. Sorry, that's test grades, and now let's actually run it. I'm going to do get stats on test grades. And I get the kind of performance I wanted to get. Looks good. Okay. Now what I want to do, however, is I want to look at a case where I've got some other entries in here. So I'm going to rerun this. I'm going to reload this file. I've got test grades in. Here's what test grades looks like. It's got Captain America with some grades, and it's got Deadpool without any grades entered yet. And if I do get stats on test grades, I get a division by 0 error. And that makes sense because in that last entry, length is 0. I'm trying to divide by 0. What could I do to deal with that? Well, as we just said, if I got somebody where they don't have any grades, I get that error because I tried to do that division. Why don't I think about handling it using this idea of exceptions? And so, in particular, I want to deal with this case. And here's what I could do. The first one is I could decide to just notify the user that something went wrong by putting out a message. So I'm going to change now average to try to return this. But if I get a 0 division error, I'm going to handle it by printing out some data. And if I go and do that, I'm going to change now my definition of grades, or of average rather. I'm going to get rid of this version of average. And I'm going to load that file in. Again, I'll just make sure I've got the right thing. There is test grades, and it's my list. And if I now say get stats for test grades, great, it ran. Notice what it did though, it made a decision. So first of all, notice on the printout, it printed out no grades data. So it gave me the warning. I handled that error by saying that's what I want to do. But in this case, notice what also happened. There's the flag for the error, but it substituted in a value. And the reason it did is because average didn't return anything. My definition of average doesn't have a return in this case. And as a consequence, the call to average gives back that special thing, the none type, and it inserted none in that spot in the pool. All right, maybe I'd like to say that that's the average for Deadpool, but that doesn't make a lot of sense. How could I handle that? Well, I could decide I'm just going to give a student with no grades a 0. Seems like a reasonable thing to do. And now I can change my handler, again catching that 0 division error idea, but putting in an explicit return. That says not only do I want to print out a note that says something didn't go the way I expected it to, but let me give me back a value that I can run on it. So now let's go and see what happens when we do that. So I'm going to remove this version of average and replace it with one that has that return inside of it. And when I call this, again, let's check and see we're in the right place. Let's make sure that test grades was loaded properly, and it was. And if I now do get stats on test grades, oh good, Deadpool now has a 0. Doesn't say how bad or good Deadpool is. He just didn't turn any quizzes and he has no grades. And so now what we see here is we still flag the error, but we've changed what gets returned to insert something that makes more sense for the data structure I'm trying to build. And so we can see we can use our own ability to raise errors, but to handle errors, to deal with things in a manner that we want, rather than simply stopping execution and pumping it back up to the user to try and decide how to handle all of that. So let's use that idea of being able to handle exceptions in manners that we decide to look at some standard places and where we might use that. Some examples of how that ability lets us, for example, control the input into a procedure. Here's a simple little example. I want to have the user type in an integer. And if I'm lucky, they do the first time around, but they might not. And so rather than having to rerun the code from top level, I'd like to create a little loop in which I keep asking for that input until it's done correctly. So I've got a while loop up here. And notice that the condition is true. So it's always going to run through this while loop. unless I break out of it. And inside of the while loop, I've got one of those try expressions. So I'm going to try and execute this code. And the code basically asks for an input. It says, please enter an integer. And then it tries to make sure that it really is an integer by saying, whatever was entered here, which comes in as a string, I'm going to cast it into an integer right there. Now, if that works correctly, the next thing will be a break. And I'll remind you that break will throw us out of the try expression and out of the while loop, because the while loop is the thing that's actually running. And I'll be able to say I've got an integer and I'm going to do that correctly. But if there's an error here, if in fact I type in a string or something else and that casting creates an error, I'm going to jump down to the except clause, handling the value error case, and I'm going to say, you didn't input an integer, try again. And because I'm inside the while loop, I'll go back around and do that. So what I've done here is I'm going to exit the loop only when the correct type of input is provided. Otherwise, I'm going to cycle through this while loop forever until you finally break down and give me an integer like I asked for. But that's a nice way to control ensuring that the input comes in the right way. And the other nice thing here is that I'm only going to get a message if, in fact, the exception is raised. So if you give me the right thing, I just carry on. But if you don't, I'm going to remind you and I'm going to keep asking about it. This only handles value errors. So if I, for some reason, had a different kind of error here, it would throw an exception that would toss me out of the execution completely and back up to the top level of the Python shell. But since I'm expecting things to be typed in that I can cast in some manner, in general, this is going to work just fine. Nice example of me controlling the exception so that I don't stop computation when an incorrect input is provided, but I remind the user of what I want and keep doing that until he or she gives me something that's valid. We can add to that by thinking about how do we get things out of files. So here's a nice example of controlling the input. Here the idea is I'm going to open up a file and I'm going to read data in from it. So the initial idea is I set up a variable called data. I get a file name by asking for input from the user, saying give me the name of a file, and I'm going to try to open the file. Again, if that works well, I'm going to open up the file and I'm going to be able to execute out. And notice in that case, I've got a nice example down here of going down and in fact saying, close up the file when you're done with all of this. Okay? If, on the other hand, opening the file doesn't work and I get an I/O error, I'm going to catch that and say I couldn't open up that file. On the other hand, if I do open it up fine, then I go to the else clause and I'm going to walk through the file doing some work. I'm going to basically process that data to add new elements in from the data into this variable data so that I can control it. And the details here are basically I'm reading in a new line. As long as it isn't just a carriage return, I'm going to take the line, split it by the commas to separate out the pieces to create a list, and then remove, using this little thing of taking everything but the last element, remove the trailing carriage return and add it in to the file. Let's look at an example of that to see what it might do. So in my computer here, I've loaded in that file, and I'm going to now run it. And it says on my machine, give me the name of a data file, and I've got a set of test data points that I'm going to now do. So let me just type that in, test grades data.py. Great, it looks like it ran properly. And so I can actually look at it. I can see what does data now look like. Oh, neat. It's a set of grades for some people taking the class. This ran well in the sense that I gave it a file that it could actually open. If I run it again, and I'm going to do that, let me rerun it, and I give it the name of a file that doesn't exist. It catches it, says I've got an I/O error, and it prints out that message saying I couldn't open the file, and it does not try to, in fact, process the data. And in fact, if I look at data, it's still just the empty list. I didn't do anything around it. Again, it's a nice way of controlling input here in that if I get an error, I'm going to close out of it. And in that case where I typed in the wrong thing, this finally clause here was important because it closed up that attempt to open up the file name, so it's not hanging around. All right, so I can now load in data. Let's look at how I could use exceptions to do other things around using this data. So, as we said, I'm going to jump out if the file name or if there is no file of that name. Otherwise, I'm going to execute the rest of the pieces. And in either case, whether I get a correct file name or not, I'm going to close the file. Important things to do. So, good news here is it appears to read the data incorrectly, and it converted it into a list of lists, which is what I wanted. I've got a list of elements, each one of which is a list with the name of a student and the grade that they're getting in that course. Now, suppose I want to restructure this into a list of names and a list of grades for each entry in the overall list. I could write code to do that, but I can use the exception idea very nicely to make this happen. Same basic structure. Again, I've got my try, I've got the except, I've got the else around all of there. Now look at what I could do once I've got that information. I could actually create a new data structure, a list called grades data. And what I want to do is walk through that data and gather up information for it. So the first thing I'm going to do is say, as long as I've got some data, because I read that inappropriately, which I wanted to check, then I could loop through it. I could say for each student in that data I want to do something. But here I'm going to use try again. And in particular, I'm going to try and take the data and take out the first two elements, the student's first and last name, and the grades, and convert that into two lists. A list of the student's name and a list of the actual grades. I'm going to do that unless I get an error. And the error will be if, in fact, I get an index error right here, meaning I try to access something that isn't available, typically meaning that there are no grades for this student. I'm going to instead get out a list of the students' names and just insert an empty list because I have no grades for that student. I'm giving you a lot of code. Let me simply summarize this. First part, just like before, but now for the second part, as I process each of those data points, I'm going to try and make sure that if there aren't any grades there, I catch that error and substitute in an empty list to deal with the case of a student that didn't show up for the exam. Let's see what happens. So I've got now a version of that code. Let me run it. And again, I'm going to give it the same data, the same file name, which is test grades data. Seems to have run correctly. And let's see what we have inside of there. So first of all, let's see what data looks like. That's good. That's that same list that I loaded in. And now I will set up this new thing. Let's look at what grades data looks like. And that's nice. And why is it nice? Because Bill Gates didn't take the quiz. I guess he was too busy doing something else. And there's an empty list there showing that he has no grades. Oh, but wait a minute. Deadpool now has a last name, 25. And Baron von Richthofen has lost his grades, but he now has a grade of Richthofen. What happened? I was making an assumption. And while I handle the case of no grades fine, I'm assuming that everybody has two names. Okay. Good news here is that I didn't throw an error. The bad news is that what I produced doesn't satisfy the properties I wanted. So I need to go back and fix it. So it works okay if it's in standard form, including now the case of no grades, but it fails if the names aren't 2 parts long. How would I fix that? Well, just by adding in another way of dealing with that try case. So same structure of the code. This is the same as before. As before, I'm going to loop over the data, but now what I'm going to do is deal with catching the error in a different way. I'm going to pull out the name for the student, and I'm going to treat it as everything but the grade. So everything but the last element. I'm going to have the grades be that last element, and I'm going to try and convert it into an integer. But in the case that it can't, because I don't have something there, I'm going to catch the value error and simply insert an empty list in that case, together with all of the elements of the student. So now I'm going to handle the case of no grades, but it's going to allow me to deal with the case of having multiple names, either one name or more than 2 names. Key thing to see here is I'm just letting the exception handle the special case. And if we go try this one, what we will see as I run it, and I type in the name of the file, It ran correctly, or it ran to completion. There's data, and now grades data. Very nice. It has each entry being a list of two lists, a list of the names, a list of the grades. And notice that it's done Bill Gates correctly, having no grades. It's done Deadpool correctly, knowing that that now is only a list of one element with a grade. And it's done Baron von Richthofen correctly, a list now of 3 names and a grade. The fact I did the grades right is really irrelevant. What's more important is notice how I used the exception handling to deal with this. In this case, using the fact that when I try and do a cast, it will throw a value error if, in fact, the last element is not a number. And in that case, it changes what I'd used to pull out the name. Now knowing that everything in the student was a name, which is why I used a copy of the list here to get all of the names, and why I inserted an empty list there to represent the fact that I had no grades. So far in this course, you've learned a lot about how to program. You learned about data structures, you learned about writing procedures that accomplish things, including doing them in different ways, and you've begun to have the ability to write fairly complicated code. And you've also undoubtedly experienced that leads to bugs. And so we've talked a little bit about how to think about testing and debugging to get your code to do what you wanted it to do. And in that discussion, we talked about things like defensive programming, setting things up so that you plan ahead to try and prevent bugs rather, or at least have them arise in a way in which you can handle them well. And we've talked about the kinds of messages that the computer gives you when things don't go the way you expected. Today we're going to pick up on both of those topics to talk about the use of exceptions and the use of assertions, both to accomplish defensive programming and to let you actually control how the computer reacts when something goes in an unexpected way. So let's look at that. Exceptions really deal with that question of what happens when I'm running a procedure and something happens I didn't expect. I hit an unexpected condition. It's an exception to what we planned for, what we wanted to have happen. And what we've already seen is you will get an exception to what was expected, and that will lead typically to a message from Python. Some examples are you have a list and you try and access something beyond the length of that list. Little example right here. I have a list of length 3, I try and access the 4th point, and I get a little message saying I have an index error. It's telling me I've tried to go too far. I could have something where I try and convert an inappropriate type. I get a type error. I try and reference a variable, get the value for a variable, but I haven't defined it yet. I get a name error. I try and mix types together without actually forcing one or coercing one into being of the appropriate type, and I get a type error. These are all examples of an exception to what was expected, at least from Python's perspective. So what will we do with those things? Well, before we talk about that, let's think about some of the other kinds of common errors you've probably seen here. Syntax error. Python can't parse the program. It doesn't satisfy the rules of writing legal expressions. A name error. Either a local or global name has not been found by Python. An attribute error. When I introduce a class, which we're going to do shortly, or when I actually try and access an existing Python class, a reference fails. Type error, we've already talked about. A value error is one where I give an expression, an operand, that is done legally in terms of the type, but the value doesn't make sense, and Python will complain. And finally, an input-output error, or an I/O error. Typically, I try and get a file, and it doesn't exist. So these are common types of errors. And again, part of our question is, what should we do when these things happen? We've seen some of the options already. So, what do we do when we run into an error? One option is just to fail silently. That is, substitute in a default value or just keep carrying on. Bad idea. Really bad idea. In fact, let me circle it because it's such a bad idea. The user gets no warning in this case that something has happened inappropriately. And while it's tempting to think about, well, let's just substitute in a default value for this and keep going, that could lead to all sorts of problems when you try and use that value later on. Second option is what we've already been doing. Return an error value. There we have questions like, well, what value should I choose to return? And if I'm going to return an explicit error value rather than printing out an error message, then I have to decide how do I have code that might get that error message, deal with it. I'm going to have to check for a special value. But it's still an option. And the third option is the one that we do right now, which is when we get an unexpected condition, we stop execution. And in Python, we say it raises an exception. It literally has a piece of code built into it with a special word raise that raises an exception with a string that describes what was going on when this happened. In fact, you've been seeing that when you've run code that doesn't run as you expect it. Python is putting out an error message, raising an exception saying, I've got a type error, and here's where you were when that happened. I know many of you have just ignored that and gone back into the code, but that error description actually is valuable. It tells you something about what was going on when an unexpected circumstance arose, and that helps you do the debugging. Okay, with that in mind, we can now think about doing things a little bit differently. And in particular, we can give you as a programmer, or Python in the built-in system, the opportunity to actually handle an exception when it happens. So here's a little piece of code, and I want to walk you through this to let you see what happens here. Try is a special keyword. And what it says is, with the indentation, here's a block of code. And what I'm going to ask the system to do is to try to execute that code. So it's just like I was having that code being handled inside of a Python shell. It's going to ask for some input. It's going to ask for some more input. It's going to then print out the ratio, and it's going to print out a message. But the difference here is the following. If try runs that block of code and everything works well, great. I jump down to here and simply print out what I had. On the other hand, if an exception is raised, the most likely one is that I'm trying to divide by 0, but I might also give in a string rather than number. If an exception is raised, particularly here in this print statement, then I'm going to jump to the except case. Again, a keyword that highlights a block of code. And in that case, I'm going to execute this information and jump outside of the loop. So say it one more time. Try says, try to execute each of these instructions in turn. But if an exception is raised, stop that processing, jump to the except clause, and execute those statements. And then carry on outside of the entire loop. This allows me to define things that I would like to do in the case that an exception arises. And right now it's simply printing out a message and stopping additional processing. But in a second we'll get to using this a little bit differently. So I'm going to now do a version of this code on my computer, and I've already pre-typed it in. So I've got an example of that little try loop, and actually I realize I've said something a little different here, so I'll change it to say OK in that place. And I'm going to add one more piece to this to make it consistent with what we had there, which is I'm going to put a print statement right here that says we're outside. And with that in mind, let's run it. So it says, give me a number. I give it 1. It says, give me another number. I give it 2. And notice what it did. It printed out the ratio as a float. And it was then able to go to the next line, which says print out OK. And it skipped past the except clause, because there's no error here. And it simply printed, I'm outside the loop. Let's try it again. But this time I'm going to give it an incorrect set of inputs. I give it a number. And I give it a 0. And in this case, I got an error, because trying to take the ratio is going to give me a divide by 0 error. It doesn't say that here because I'm handling the exception. But notice what happened. It didn't print OK because that division of A by B led to an exception. It jumped straight to the except clause, and in this case, it's printed out my error message, which says there's a bug in the user input, and then it goes to the statement outside of the overall loop and prints out outside. The difference here is, if I didn't have an exception, it would have printed out a divide by 0 error. Now I'm actually going to be able to control what do I do when I see an exception. But you can also see it stops the operation, jumps to the except clause, deals with that, and then goes outside the loop. All right, with that in mind, I can now amplify this. Let's take the same kind of example, but now say, gee, there could be different kinds of errors. Maybe I want to do something different in each case. So, for example, if I type in something that was a string, it's not going to be able to do the division because it can't divide strings by numbers. that raises a value error. It's an exception. And in that case, I could print out something useful saying, all right, in that case, I didn't have a number. I want to think about that differently. If I gave it, as I did in my example, a division by zero problem, it will print out something more informative there, telling me what went on when I had that happen. And in the final case, if neither of these exceptions come up, but some other exception does, I'll still have a default case that I'll use to handle that exception. I could run the same code. I'm not going to do it here, but I could run the same code and you would see the same kind of behavior. If the code runs properly, it will never get to any of these cases. But if I hit an exception, if it's one that I know how to handle, like a value error, I'll deal with it. A division by zero error, I'll deal with it. Otherwise, I'll go and deal with the overall general idea. What else might I have when I want to deal with exceptions? Well, two other pieces. One is, there may be some code that I want to do even if it runs without any exceptions. And so I can put in the keyword else, followed by a body of code, and that will be executed when the execution of the try body works correctly. This lets me pull things outside of the try body. I could leave them in there if I wanted, but it lets me pull things outside of the try body to isolate them as being things I always want to do if it runs correctly. And finally, I can have the finally keyword. And this identifies a body of code with the following property. This is always executed after try, else, and except clauses, even if they raise another error or they execute a break, a continue, or a return. And this is handy when I want to clean up some code, no matter what happened in the earlier code. Typically, this would be something like closing a file so that I don't leave it hanging open. But it lets me specify sets of things I will do independent of what happens in the try loop, whether it runs correctly, it hits an exception and deals with an else or an except clause, or even if it breaks out of that execution and carries on. So there are the pieces of dealing with exceptions. And we're going to look at some examples of using it to actually think about how to handle code using ways to deal with exceptions in manners that we want and not just throwing an error as Python currently does. We've been showing you a lot of great tools in computation. We've introduced simple data objects, we've introduced compound data objects, we've introduced iteration, we've introduced recursion, we've talked about using functions in a variety of ways. You now have a lot of the tools you need to have in order to build interesting code. And in fact, we've been asking you to do that in the problem sets that you have been working on as you've gone through this course. But we now come to a place where we have to be a little more clever, because you've probably already experienced problems with your code. Bugs have wandered in that you weren't expecting. They have done things that you didn't want to have happen inside of the code. And so we're going to now turn to a question that every computer programmer faces, which is, how do I test my code? And when it doesn't work the way I expected it to, how do I go about debugging it? And that's what this lecture is going to be all about. Now, one of the things that happens with debugging is that ideally you write code that's going to do exactly what you want to do the first time. But that doesn't tend to happen. So here's the challenge. You write a piece of code, you wanted to just nail it the first time. And here's a little visual of how you'd like to expect it to happen. Wouldn't you like to be able to park like this young girl? You just nail it exactly right as you zero in on the right spot. You'd like your code to do it exactly right the first time. But the reality is you set up a very complex piece of code and you start it up and it doesn't quite do what you wanted. So there's expectation and there's reality. How do we get away from the thing on the right and get to the thing on the left, which is what we really want to have happen here. So we aim for high quality. How do we get it there? Well, I'm going to give you an analogy with making soup. I'm going to acknowledge it's a little bit of a queasy analogy, but bear with me here. You're making soup in the kitchen, but bugs keep falling in from the ceiling. So what do you do to make sure you have good soup? I don't want to eat soup with bugs in it. Well, you could check the soup for bugs. You could keep the lid closed, or you could clean the kitchen. All good things to do. And all of them have nice components, in fact, of testing and debugging. Checking for soup is the discipline of testing. How do I test my code to see whether it in fact does what I expect it to do? Keeping the lid closed is what we call defensive programming. We're going to talk about that. It is how do you structure your code? How do you write code in a way that plans ahead to try and make sure that you avoid the bugs or at least detect them before you actually run the code? And cleaning the kitchen, Just eliminate the source of bugs. Do the debugging to get it done. That's what we're going to talk about in this lecture. So defensive programming at a high level basically has three parts. The first one is to write specifications for the functions you're writing. Write out those doc strings that says, here's what I expect coming in, and here's what I will deliver if I get things that are of the right form. Second nice piece of defensive programming is to write modular programs. Don't write one really long, huge single function. Break it up into obvious pieces. Those pieces are going to be valuable to us when we get around to actually testing, because I can test each piece in turn. And then finally, under defensive programming, I want to check the conditions on those inputs and outputs. We're going to see an example of that in a later lecture where we use assertions to actually formally do that. But defensive programming basically comes down to defining what I expect to come in, what I'll deliver, and then ensuring that I actually do that. Testing or validation really comes down to comparing inputs and outputs. Given a set of functions I want to test, I should write a list of a set of example inputs and what I expect in each case as an output. And then when I discover it's not working, figure out how to debug it. I also want to ask a different kind of question, which is, how can I break my program? What are the right kinds of inputs to use to make sure I test all of the different cases that are going to be important, ensuring that my program is doing the right thing? And finally, with debugging, once I have a bug, what do I want to do? Mostly I want to look at the events that led up to the error. What was going on before this error occurred? And then ask two different kinds of questions. One, why is it not working? What's causing that? And then having found that, how do I go ahead and fix it so it will work properly? Those are the tools that we want to have as we think about testing and debugging our code. Now that we've seen the idea of using class attributes, data attributes to give unique names to things or unique identifiers to them, we could start building up a little representation of MIT people. More importantly, given now we've got two classes in our hierarchy, we want to extend it to look at variations on how we inherit methods. So let's add in different kind of MIT people. We have students. They're all MIT people, but they come in different flavors. We have undergraduates who have a class year. We have graduate students who don't have a class year because we can't tell how long it's going to take them to finish up their PhD. Let's add those in. So I can extend my class again. And again, I'm going to start building now on top of MIT person, which I remind you inherits from person, which inherits from the base object class. And UG stands for undergraduate. So an undergraduate has a name. It also has a class year. And as I did before, I'm going to use the inherited, in this case, MIT person method to create the instance. Remember that in turn will use the person initialization method to create the underlying instance and then assign a unique ID number to them. On top of that, once I've created that instance, I'm going to bind year as a data attribute to the class year of this student. I could, of course, then get back the class year with a getter. The other thing I'm going to do here is I'm going to give MIT undergraduates an ability to speak that's a little different. They are going to use the inherited MIT person speak method. So notice the call. I use MIT person dot speak to get that method that we just saw used from an MIT person. What I'm going to change, though, is I'm going to add a little bit to what they actually say. And we'll see an example of that in a second. I've got undergraduates. I can also have graduate students. I'm just going to make a separate class for them. And then I want to be able to tell whether I have a student, an instance of that. And here I can use both types to actually pull them out. So I can check for the superclass of is somebody a student by simply saying, is this an instance of an undergrad or is this an instance of a grad student? Good. Let's see what would happen if we were to use this to start building up a little bit of our hierarchy. So I'm going to create some undergrads. I want to give them a class year. I'm going to create a grad student as well. And if I load these in, which I'm going to do now, I can now see what happens with this instant of things. So first of all, let me print out some information, in particular of S1. And I say if I print S1, it prints out the name, Matt Damon. Great. I can also know what class is Matt in. So I do get class on S1. S1.getClass using that getter method. And since it's a method, I do open close paren. And it says class of 2017. Hopefully he'll graduate in a year's time. And then I can use the speak method. And I remind you, in my code, I had the undergraduate speak method use the underlying MIT person speak method, but adding something to it. So if I ask Matt to say, speak, where is the quiz? It prints out, Damon says, dude, where's the quiz? So, Damon says came from the MIT person speak method, and that insertion of a dude came from the way I defined adding that to the utterance. And as a consequence, I can have his friend respond with, again, as an undergraduate would here, Affleck says, dude, I have no idea. My point of this is, notice how I'm using the underlying MIT person speak method to do the work, but I'm simply adding something in when this is an example of an MIT student speaking. I can print things out. I can have them talk to each other. All right, what else might I want to know about this hierarchy? First of all, let's remind you of what I have here. Here's a diagram that shows what we've built. We have a person, that's my base class. Under that, we have a subclass of an MIT person, and that was where things like the speak method resided. And then relative to that, I can build both undergraduates and graduate students. Now, I haven't done much with graduate students yet. You could imagine they might speak a little differently. They might have other kinds of attributes. And my arrows here are showing the relationship of subclass to superclass and the fact we inherit methods up the hierarchy as we need them. Having built that, I now realize there's another kind of student. A transfer student, somebody that comes to MIT after a year of being somewhere else. So I'd like to add a new class to my hierarchy. I could certainly do it right there. But now I have a problem. I have to rethink is student. Remember, for is student, I would simply say, see if it's an instance of an undergrad or grad student. I need to change that. One way to change it would be simply to add another clause to that expression that says, is this a transfer student? But a cleaner way to change it is to realize that I have an implicit class here, and that is a class of student. And let me add that in and show you how it cleans up the hierarchy. I'm going to create another class right up here. It inherits from MIT person. It's a student. They are MIT people. And then I'm going to have each of these subclasses inherit from student. Very straightforward, but it has two nice properties. The main one is, look at what happened to is student down at the bottom. It's changed. But before I do that, notice this strange thing in the class definitions. It was in an earlier slide and I didn't say anything about it, but here the special symbol or keyword pass basically says, at least at present, there is no expression associated with that. I'm simply passing through it. And that in particular with student is going to be nice. I don't have any methods associated with student. I simply am passing through, but it's let me clean up the hierarchy. And then finally, notice with is student, now it simply is checking, is this a student? If I were to add in other kinds of students here, it's simply a matter of adding the class definition, ensuring that it inherits from student, and I don't have to change the hierarchy or the methods associated with them. So it cleaned up it in a very nice way. And in particular, we can now go back and make sure with that change that we still have the same performance as before, that it will inherit appropriately. And so if I load up a version of that, I can do the same test. I can print out S1, still prints the same way, and I could print out having S1 speak. Where is the quiz? He's still looking for the quiz. Still prints the same way. And if I print S2 speak, again, it still prints out appropriately. Inheriting from the appropriate place. Adding that extra class in there did not change anything because my definitions were still going back to MIT person to get the underlying speak method. If I now look at my hierarchy, I've got person, I got MIT person, I've now inserted a new class, student, in between, and that says it was much easier in this case to add in that transfer student class. And this relates to something sometimes called the substitution principle, that important behaviors of a superclass should be supported by all of the subclasses. And in this case, adding student in as a superclass was gathering all that information together in one place while still allowing us to inherit methods, for example, up here from MIT person. Last lecture, we introduced classes into our language. And they're an incredibly powerful tool to add to what we've been doing. By analogy, definitions gave us a way to add our own methods or procedures to our Python system. Classes give us our way to add our own data objects to the system, and that's really useful. And whether this is in Python or in any programming language, that idea of being able to bundle together pieces of data that naturally coexist and methods or procedures or functions specifically designed to manipulate that data, that idea is really valuable. As a consequence, even though we've looked at some examples, today we're going to do an extended example, looking at the different ways in which we can use classes to build a hierarchy of a system that lets us manipulate objects in a variety of ways. The example we're going to use is to build a little system that organizes information about people. And if that's what we're going to do, an obvious place to start is with a person object. Of course, I could add lots of different data attributes to a person object. For the sake of just building the system, we're going to start with some simple things. So a person is going to have a name, they're going to have a birthday. And we want to see things like, how could we get out the name? How could we get out the last name? Can we sort groups of people? How do we get the age? Things that let us access data associated with instances of this class. So let's build the class. Here's the start for it. As before, we're building a class, we're calling it person, is going to inherit from the underlying object class, exactly as we did earlier on when we start building a system, because object is that underlying basic Python class that has associated with it standard methods we want to be able to use. As before, we need to be able to create instances of this class. So there's our init method right there. And it's just going to create a person with a name. I want to be able to get out information, so I'm going to be able to get out the last name, for example, of the person. And I want to be able to have something print out appropriately, and so I'll have a string method. Again, one of those built-in methods. We're now overriding underscore str, followed by 2 underscores. And in this case, when we print out information about a person, it's just going to print out its name. The only unusual thing I'm doing here is I want to get out not only the name, but the last name of a person. And I'm going to make the assumption that the last element in a name is the person's last name. I can get at that by taking advantage of the fact that I know a name will be a string, and using the built-in method split on it, split around spaces, will return for me a list of strings, each one a different portion of the person's name. And finally, I'm just going to extract the last element of that, as I said, assuming that the last portion of that string is the person's last name. Okay, I can build instances of people. I've got a couple of methods here. Let me add in a few more methods I'd like to be able to use. I said I want to give this person a birthday. Lots of ways I could do that, but I'm going to do this by importing a library, a module that exists in Python called datetime. And in particular, I'm going to be able to then say when I give a date of birth to a person by month, day, and year, datetime will automatically convert that into an internal representation that I could use. Now, I didn't tell you what the representation is. I'm not going to, because you shouldn't care. All I want to be able to do is to use it. And in particular, if I want to get the age of a person, as you can see in the bottom line of the slide, I will simply take datetime.date.today as a method. It gives me back a representation for today's date. I subtract from that the birthday, and then I can convert that into days, and it will give me the number of days since the person was born. And clearly then I can convert that into years or other kinds of representations of age. Key point here, I'm not telling you how it represents things internally. You shouldn't care. You should be able to just use this using the appropriate interfaces, which I'll do here. One last method. I'd like to be able to sort lists of people. And here I get to make a choice. Again, I'm defining my version of a built-in method called less than, or LT. And I'm going to make the choice that in general, I'm going to sort people by their last name, which I've already stored away, unless they have the same last name, in which case I'm going to sort them by the entire name, which in essence will come down to sorting them by their first name. There's a definition of a class. You've seen some of these methods before. I'm building in something for init to create instances. I'm building something in for string to say how I'm going to print them out. I'm building something in for less than so I can compare them. And then I've got some internal data attributes, a name and a birthday, and I'm able to access those using getters like getLastName. Let's see what happens if we were to use this. So I'm going to create a little simple database of some people. Perhaps you recognize some of these names. And some of them I've given birth dates to, some of them I haven't. And I can create a list of those. So I have on my computer a version of this file ready to go. And I load it up. And I could look, for example, at people in this list. So I could say print out P1. And it says Mark Zuckerberg. And that's great because that was how I defined string to return things. Good. So what else might I do with this? Well, I said I want to be able to sort people in this list. So we can look at a simple little example of that. In particular, I could say for every person in the person list, just print them out and see what I get out. And I've shown it here. Let's check it on my computer to make sure it does the right thing. Again, I have loaded in a version of that. And so I'm going to clear it and reload it. And when I do that, sure enough, it prints it out in the order in which I created them, which is great. Now, what I'd like to do is say, let's sort them to see if the sorting mechanism works well. And notice what I do here. I use the built-in list method sort. So person list is a list. The dot says from that data type, get out the thing that's bound to the name sort, which is a procedure. And then the open close paren says call or invoke that procedure, which will sort the list in place, mutating it. And now I should be able to print it out and see what it looks like. And again, I'm going to load that up on my computer. And I'm going to run it. And in fact, now it has sorted it. And notice, in the case of two people with the same last name, it has sorted it by the full name, whereas everywhere else, it's simply sorted by last name. Simple little example that shows that I can start manipulating elements of this data structure. Let's see what we do if we build on top of it. Okay, let's get concrete about this. Let's look at the specifics of how we both define a class and then implement instances of that class. So if we want to define our own type, we're going to start by using the keyword class, not surprisingly. And that's going to tell us we're about to create the definition of a new class. So we're going to start with the class definition. We're going to give it a name. In this case, I'm creating a coordinate. That's simply an XY pairing of points in the plane. And then each class definition is going to take one argument, which is the parent class. And initially, we're going to create classes that inherit from the underlying object class of Python. So we'll always just have object here. When we start building hierarchies, we'll see that we want to extend that idea. But just to repeat it, I've got a class definition, I've got a name, in this case coordinate, and its parent, in this case, is object. It's followed, as always, by a colon to tell me I'm done with this. And then immediately below that, I'm going to define the attributes of this class. And I'm going to have them indented, as always, to tell me where the bounds of that class definition lie. Now, the word object means the coordinate is itself a kind of Python object. And that means it's going to inherit all of the attributes of the underlying Python object. We'll come back to that in a second, but that's going to be valuable. One last piece of nomenclature. We say that a coordinate is a subclass of an object, and an object is a superclass of a coordinate. We're going to have a subclass inherit from its parent or superclass object. So, simple start, define a class with a name and an object. Now I have to get into how do I actually put attributes inside of that class definition. So first of all, what are the attributes? Well, they're going to be data and procedures that belong to this class. If I take my example of a coordinate's got an x and a y value. So I'm going to have some data attributes that are the x and y values that are associated with a coordinate. What I'm going to do is think about those data attributes as other objects that make up the class. Things that get inherently glued together and can be treated as a unit. A point in the plane is a unit. Happens to have pieces in it, but I want to have that class capture those things together. So as an example, while a coordinate is made up of two numbers, a coordinate itself is something that I can use. Those are the data attributes. We also need ways to use the data. And those are what we call the procedural attributes or the methods. Think of methods as functions that work only for this class. So for example, if I want to compute the distance between two coordinates, I could do that, and I can do that in a second, define a distance method associated with coordinates. But it doesn't typically make sense to think about doing distances between strings or distances between lists. I'm going to create a method that belongs only to this class. And it's going to be seated inside of that class as one of the procedural attributes associated with the class. Okay, so how do I do that? Well, first thing I've got to do is define how I actually create instances of this object. And for that, we use a special method called init. And in fact, it's written a very special way. It has got 2 underscores, the word init, and then 2 underscores. We're always going to do it that way. It's a special method. And this special method is going to create an instance when I actually use coordinate as a call. Now, what's inside of init? Its first argument is a parameter that's going to refer to an instance of the class. And by tradition, we always call it self. In fact, you'll notice when you type it in, the Python environment always types self in a different color and in a different, in this case, italic font to distinguish that it refers to an instance of the class. We also want to give this thing that's going to create instances the initial data. If a coordinate has an x and y value, I want my creation of an instance to take in a value for x and a value in y, and we're going to glue them together. And the way we glue them together is we're going to actually create bindings for the names x and y to the values passed in. And what you can do is think of this as when we actually invoke the creation of an instance, which we're going to do in a second, this will bind the variables x and y within that instance to the supplied values. I'm going to come back in a second to why it says self.x and self.y. But think of this as saying within that instance to which self refers, I'm binding x and y to the values passed in. This is typically the first method that we have inside of a class definition because we have to say, how am I going to create instances of this class? This is also inherently defining the data attributes associated with this particular class, an x and a y value. Okay. Let's make a couple of versions of this. So I'm actually going to do that. I've got over here on my machine a definition of coordinate. And I can now create an instance. I can say I'm going to let C be a coordinate. So I simply use the name coordinate. Oh, and that's nice. Notice when I did the open paren, I'm going to do it again before it disappears. It tells me what the arguments are that are expected. And I'm going to give it 2, an x and a y value, 3 and 4. I'm going to define origin to be the origin of my coordinate system, so it is another coordinate of 0 and 0. And notice, each time I invoke coordinate, the name of a class, it's creating a new instance. What it's doing is it's calling that init method and using that to create local bindings. Now, you might notice here that there's no version of self. Wait a minute. Didn't I have in my definition, the definition of init was self, x, and y. I did, but the style or the process, if you like, in Python is that self automatically points to the particular instance that I've just created. And Python automatically provides that argument for you. So when I call init, I only call it with the arguments that I need to provide in order to create the data attributes. Once I've got that, I now have instance variables inside of that class instance, and I can get to them. So for example, I could say, print out the x value associated with C. And there it is, 3. Or I can print the x value associated with the origin. And there it is. Just printed it out. Think of this as C giving me an instance. It did because I created it. And now I'm going to try and get the x thing associated with C. So I create a new instance of an object. I pass in the arguments. I use the dot notation to access an attribute of an instance. And what I want to think about is what does it mean to do that actual accessing? As I already said, notice that the argument for self is automatically supplied by Python, so I don't need to provide it. The way to think about this is as follows. Think of C, an instance I created with coordinate. Think of it as pointing to a frame. You may remember we saw that when we did function calls, that every time we called a function, we created a new frame. In essence, a class definition is doing that as well. Coordinate is creating a new frame associated with C. Within the scope of that frame, we bound values to data attribute variables. So inside of C, there is a binding for x and a binding for y, to 3 and 4 respectively. C.x is then interpreted as saying the following. get the value of C. Oh, that's a frame. And then inside of that frame, look up the value associated with X. So C.X says, get the value of C. That's a frame. Now I'll use the next thing to say what's the binding for X inside of that frame. And thus, that's going to make it easier to understand why C.X gives me back 3 and origin.x gives me back 0. In each case, they're referring to a different frame in which the variable x is bound. And just like with functions, there was no confusion about which binding to use. Same thing with different instances of the same object type. I want to do one last example with this little hierarchy that we're building of animals and rabbits and cats and people and students. I want to do this to introduce one more idea that can be really valuable. And to set the stage for this, with instances, we've already seen the idea of an instance variable. In fact, those are the things we've been using. Those data attributes, those variables are stored inside of each instance. They're specific to that instance. And so when I create an instance, they belong to it. I can use generic variable names within the class definition to get at them, but they're all things that belong to the instance. I'm now going to introduce the idea of a class variable, similar to an instance variable. This is going to be a variable defined inside the class definition, but outside of any of the methods, so outside of init. That's important. If it was inside init, it would be something that would be created within the instance. Here it's going to be something that belongs to the class and therefore is shared among all objects or instances of that class. It means any instance of a class that I create can get access to that variable. And we'll see why with an example that shows why this is going to be valuable to use. So, this just reminds you, there's the animal class, the kinds of methods we had. And I'll just simply remind you here that these are instance variables. Age and name are things that are created whenever I call init, which means whenever I create an instance. They can only be accessed from within an instance. I want to see what happens and why I want to have the value of having a class variable. So, subclasses, we know, inherit all the data attributes and methods of a parent class. And so I'm going to change the definition of rabbit in an interesting way. I'm going to put a tag on a rabbit. It could be a little ear tag that I'm typing onto it, but I'm going to tag every rabbit. So notice what I'm going to do here. Rabbit is still going to inherit from the animal class, but I'm going to create a class variable. And notice in particular, it is outside of the init definition. It's at the same level as those things. So when I create the class of rabbit, it is going to create within that frame associated with rabbit a binding for tag, initially set to 1. And that tag is going to allow me to give a unique ID to every new rabbit that I create. So now my initialization method for rabbit is a little bit different. In particular, I'm going to ask to pass in potentially 2 other arguments besides age. 2 parents, 2 other rabbits, because rabbits breed rabbits, as we saw when we did Fibonacci. I'm still going to initialize an instance using the underlying animal init method, as I did before, but now I'm also going to set within that instance parameters or bindings for parent 1 and parent 2. And those get set by simply taking the values passed in, which default to none if I don't pass 1 in. And I'm going to do one last thing. I'm going to create a local rabbit ID tag, or an RID, for this rabbit by accessing rabbit.tag. And that's going to get me to this point. It means the first time I call this instance, that instance is going to have as a local variable RID, and it's going to be the value 1, because that's the current value of the tag. And then the last thing I'm going to do is, having called that instance, I'm going to increase it by 1 to 2. And that means that the class is keeping track of the tag, and every time I call init again, I create a new instance of this rabbit, that instance is going to get a unique ID, the latest value, and the tag is going to increment by 1. That's cool, and this is a place where I've got data attributes associated with the class, not with the instance. Okay, let's see what happens if we do that. And that's simply reminding you of those pieces. An instance variable, how I access it, and the fact that I'm going to increment it every time I call this piece. So, having done that, there's a couple of other things I can do with the rabbit. And in particular, the getter methods will include now getting out the ID and getting out the names of the parents. The one other thing I have here is that I've got also getters I know for get name and get age that are inherited from animal. I can use those as well, but these are now things specific to the rabbit. And the one last piece here is, since this is actually a particular string, because I've set it to be string, I can fill it out with zeros to pad it so that they all print out at the same size. You'll see that in a second when I use it, but it's a little technique to basically make sure that everything prints out to the same size. In this case, it'll be 0, 0, 1 rather than 1, so that the things look and print similarly. Okay, let's use it. I create Peter, a rabbit of age 2. I set his name to actually be Peter. That's kind of nice. That's his name after all. I'm going to create another rabbit. Hopsy is of age 3, and I set her name to be Hopsy. And I'm going to now create another rabbit, Cotton, that has 2 parents. Peter and Hopsy got together. Cotton's 1 year old. And if I set Cotton's name to Cottontail, that's fine. But if I want to look at things about Cotton, if I can print it out, and again, Cotton is now an animal with with the name Cottontail inside of it and the age 1. So I've inherited all of the behaviors I would have wanted before. If I ask Cotton to get the first parent, I can print that out. And notice what I'm doing here is getting a method associated with that and then invoking it. And it prints out, exactly what I wanted. Cotton's first parent was Peter, age 2. Okay, once I've got that, I can add some other pieces to my behavior for rabbits. In particular, I can define, as I said earlier with classes, there's an inherent add method here. And what I'm going to do is define a method for rabbits. What does it mean to add a rabbit? Okay, so I've got an initial method here. Initially, it's simply going to return a new rabbit. And that new rabbit has 2 parents. This particular rabbit and whoever that other rabbit is. It's another way of saying I'm going to let the rabbits mate. And I'm going to create a new rabbit with that call to rabbit right here with parent 1 and parent 2. Let's look at an example of that. Before I do it, let's simply remind you what this is doing. The add operator is between 2 rabbit instances. It defines what it means to take rabbit 1, rabbit 2, and add them together to create rabbit 4. Initially, it's a new rabbit. I'm going to have it be a new rabbit with age 0, coming from right there. It has self as one parent and other as the other parent. And ideally, inside of init, I should check that, in fact, they are of type rabbit. I haven't done that here, but it would be a nice thing to do to make sure I'm enforcing the invariant that these are rabbits that are getting together. I go back to Peter and Hopsy, and I can now say, let Mopsy be what I get when Peter and Hopsy get together. I'm using rabbit addition. I'm creating a new instance of a rabbit. I'm giving it a binding of Mopsy on the outside. I can set its name. And now I can say, what's the parent of Mopsy? It's Peter. And I can say, what's the other parent of Mopsy? And I get out Hopsy. I know it's a silly example. What I've done, though, here is take the idea of given instances. I can now define what it means to do addition on those instances. It's up to me to decide them. And I used it here to create new instances of a rabbit. The last thing I want to show you is how I can use that idea of those tags to actually define what it means to compare 2 rabbits. What does it mean to do equal? Or what does it mean to say R double equal P, for example? I'm going to define an override of the EQ method, a built-in method. And here what I'm going to do is say, I'm going to decide that 2 rabbits are equal if they have the same parents. I could do it some other way. I could do it to say 2 instances of rabbit are the same thing if they have the same ID tag. But here I'm going to say they're equal if they actually have the same parent. How do I do that? Well, I'm simply going to look at the tag associated with the instance for each parent, both for parent 1 and parent 2 of self and other. That could be they're the same parent 1 and parent 1, parent 2 and parent 2, or they could be the other direction. And I'm going to return true if one of those cases is true. So I'm setting up Booleans here. And what I'm doing is relying on the fact that I built a unique tag with each instance of a rabbit. And if I do that, I'm simply comparing those tags. I know they're unique because of the way I define them. And if I didn't do this, if I just said, are the instances the same, I'm actually going to get into a problem where I'm going to get down to an attribute error because I can't compare the instances directly. So this is a nice way of doing that comparison. And if I try that, I create Cotton, I create Mopsy, and I say, is Mopsy equal to Cotton? Notice Cotton had parents of Peter and Hopsy. I created that directly. Mopsy has parents of Peter and Hopsy. I created that using add, and when I do the print, it says, yes, in fact, these are the same. So now I've got an example of using a class variable to gather information that I can associate with instances in a way that lets me keep track of information that belongs to each instance but is defined within the class. And so to pull it all together, what are we doing? We're bundling together objects that share common attributes and common procedures to apply to those attributes, even though the values of the attributes are different across each instance. I'm using abstraction to distinguish between how I implement something and how I use it. And now we've seen an example of building layers of abstractions with inheritance associated with them. And that lets us create hierarchies of behaviors while preserving clean code and efficient code by associating methods with each instance of a class that implement that common behavior. Now that we've seen the basic idea of creating a class and creating instances of a class, and we've seen the idea of defining methods for them, including methods that are sort of the built-in or associated methods, like what does it print like, how do I create an instance, let's look at how we would use this idea of a class. And probably the best way to do that is to simply take an example. So I'm going to create a new type of object to represent a number as a fraction, and literally as a fraction, not as the floating point equivalent of that. What do I need? I need to say, what's the internal representation? What are the data attributes I want to glue together, and how am I going to represent them? And then, what's the interface? Or if you like, the methods that I'm going to use to interact with instances of those fraction objects. In my case for a fraction, I want a numerator and a denominator, a top part and a bottom part. In terms of the interaction, the interface, the methods, I certainly want a print representation so I don't get something messy coming out. But I'd like to think about simple things like how do I add fractions? How do I subtract fractions? And one other thing I might like is, if I wanted to, how do I convert a fraction into an actual floating point number that I could then use standard Python arithmetic operations on? Let's see how we would build that. And what you're going to see here is less the details of doing fractions, more the idea of how I use the methods to define behaviors that I want to associate with different objects, in this case, fractions. Okay. So initially, I need to define the class of a fraction. I use class to say it's the definition of class. I've got the name. And as before, this is going to inherit from the underlying object class. I also need, as always, to define what does it mean to create one of these objects. So I've got an init method. It takes in two arguments besides self. That is a numerator and a denominator. And I'm just going to bind those locally within the frame associated with every instance of a class. I'm also going to define what I want to have printed out when I do this. And here I'm simply going to have it print out a string representation of the numerator and the denominator separated by a slash, sort of like you'd expect to see inside of a fraction. There's my definition initially of what a fraction looks like. Let's see what happens if I use that. So I'm going to go over to my machine, load this up, and let's do the two definitions. Let's give the name 1/2 to the fraction of 1 and 2. Let's give the name 2/3 to the fraction, obviously, of 2 and 3. And let's see if it prints out appropriately. So if I print out 1/2, yep, does what I'd like. And obviously you would expect 2/3 ought to do the same thing, but let's just check it. There we go. All right, so we can create fractions. We could create a bunch of them. Little boring. What could we do with fractions? Well, as I said, I'm going to do some operations on it, but before I do that, I want to introduce one more important idea. And that goes back to something we talked about earlier, which I'm going to pull in a second. And the new idea is to create something that lets me access data attributes. These are often called getters. I'm going to get out the elements of that. And here I'm going to define a getter for numerator and a getter for denominator. I'm going to give them obvious names. I could give them anything, but I'm going to say getNumer should give me back the numerator of a fraction, and getDenom should give me back the value of the denominator of an instance of a fraction. Why am I creating those? Well, those are going to be important because it's going to separate out accessing the internal representation from the actual use of the representation. But let's check to make sure it does the right thing. You can see what I expect it to do, and if I say 1/2, and I use getNumer, that's great. It gives me back the numerator of 1/2. Notice the call. There's the dot, and I'm going to step through this carefully. 1/2 points to an instance. It's a frame somewhere. The dot says get the binding for getNumer in that frame. Oh yeah, that was the definition that I did right back here of a method inside actually the frame of frame of fraction, but I inherit it because 1/2 is an instance of fraction. But the last piece is that simply gives me back the procedure. To make it run, I have to invoke it. And while it takes no arguments other than self, which is automatically provided, I need to say open close paren to actually invoke it. Do the same thing with getDenominator. I can get out the pieces of them. As we said, this is a procedure. I've got to invoke it. And remember again, self is provided separately for me. I can now use that to define things like how do I add fractions or how do I subtract fractions. And notice, while it looks a little messy at code, it actually is going to have an important property. So here's a definition of add. It takes 2 arguments, the instance itself and some other fraction. And inside of there, I'm just going to do the work to actually define what it means to add together 2 fractions. I take the numerator of one, the denominator of the other, multiply them together. I take the denominator of one, the numerator of the other, multiply them together. Add those up. That's the new numerator. The denominator is just the product of those 2 products. And if you're looking at the slide carefully, I notice I have some typos here. Ignore them. My method is actually going to do them correctly. That's snuck in somehow into my slide. Last piece of this is, having computed that numerator and denominator, I need to return an instance. And I create one by calling fraction with new values for the numerator and the denominator. Subtraction does the same kind of thing. Let's see what happens if I actually use that. So I've got those 2 versions there. Let's call new what I get by taking 1/2 and 2/3 and adding them together. And what does new look like? Perfect. Let's do one more example. Let's call 3/4 the obvious thing, the fraction of 3 and 4. Let's just make sure it works in other kinds of versions here. So I'm going to call second new. Well, actually, let's just print out 3/4. I can print it. And there it is. And if I let second new be, let's do 2/3 minus 3/4 because I define sub as well. It needs to type it properly. My apologies. Let's do it one more time. This is 2/3 minus 3/4. I can print that out. Great. Exactly what I'd expect. I've now got the ability to create new instances of fractions by doing arithmetic operations on them. And notice how plus and minus are overriding, if you like, the built-in versions of those. And I'm using that in order to be able to do this in a manner that lets me type things that make sense, but have things come out the right way. Last thing I said I wanted to do is to be able to convert fractions into floats. And that's easy. Convert would simply take the numerator by using the getter for that, take the denominator by using the getter for that, and just do division. And so if I ask, for example, to convert second new, I did that wrong, my apologies. I'm going to do second new dot convert. It prints out the floating point representation of those pieces. Great, it's exactly what I'd like to have. There are some examples of that, just like we did. This is something that's going to give us the ability now to think about elements of this class and simply use them. I'm going to do one more example, but before I do it, I want to say another word about those getters and setters. Why do I want to create separate getters and setters? Remember we said we don't want to directly manipulate the internal representation of an object. We'd like to separate the use of the object from what's inside of it. And those getters and setters nicely do that. It says anytime I want to access something inside an object, let me use the method that gets that part of the object out. I'm going to come back to that idea when we do our second example. And the second example is, suppose we wanted to build a little collection, a set of integers. Initially the set's empty, and I want to have the property of that set be that an integer appears only once inside the set. That's what we would call a representational invariant of this particular object. And I'm going to enforce that by the way I write the code. I don't want to have to go and check, did I have more than one instance inside the object? I want it to be the case that as I add elements to this set, I'm always making sure that there's never more than one particular version of that integer inside of that set. I need two pieces. Data representation, I'm just going to use a list to store the elements of the set. And I need an interface. How do I interact with this? And for that, I'm going to have the ability to insert an element, the ability to check if an element is there, and the ability to remove an element. And the description is exactly what you expect. Insert's going to put that element into the set if it's not already there. Member will tell me true if in fact an element's inside the set. And remove will take the element out of the set and complain if I try to take something out that wasn't already inside of the set. Again, a bunch of words. Let's do an example. Here's the definition of the integer set class. And I'm going to do this a little more quickly because you should be getting used to these pieces. I have something that creates instances. In this case, there's no argument to it other than self because it starts out as empty, and it's simply creating an internal binding for the variable vals, which is going to be my internal name for the set, to the empty list. I can insert things into the set, and here's where I'm going to enforce the representational invariant. I'm going to take advantage of the property of lists. So when I want to insert a particular element into an instance of an integer set, I'm going to first say, is that element inside the list? And I'm just using that iterable operation on lists to use that. If it isn't, I'm going to append it into the list. If it is, I'm simply going to skip by because there's nothing to do. I want to check if something's inside the list. Again, I can use the property of a list. I can simply say, return E in self.vals. That simply says if E is in that set, that list, it's going to be true, otherwise false. What else did I need? I need to be able to remove an element from a set. And here I'm going to use that nice property of exceptions. I'm going to try to simply remove directly something from a list. I'm using the property of lists here because vals is a list, remove is a method associated with lists, and it's going to try and remove the first instance, should be the only instance, the first instance of that variable E from that list. If, in fact, E was not in the list, it's going to raise an error. And the exception then is going to come down to here, and I'm going to raise my own particular error to say that particular element was not found. I'm going to override the underlying value error exception method. And finally, I'm going to use string to define how I want to print out the elements of a set. This is a little funky, but what I'm simply going to do is take vals, which is a list, and I'm going to sort it by using the sort method and call it. And notice I've got 3 dots here. Actually makes sense. It says self gives me the instance. Dot says look up vals inside of that instance, which is simply a binding. And then because vals is a list, the next dot, this one, says find the method sort associated with lists and then apply it by calling it right there. Once I've sorted it, I'm going to run through a little loop where I set result to be the empty string. And then for each element in the now sorted version of vals, I'm going to simply add it in together with a comma. And then when I'm ready to return it, I'm going to return a string that has a curly bracket on each end. And I got one extra comma hanging around at the end of the last element. So I'm going to take result and return everything but that last element to get rid of that last piece. And now let's try it out. I'll show you some examples here, but I actually want to go over and type them on the machine so you can see that it does what we would expect. So I'm going to define S to be an integer set. And I can print out what S is, and it just gives me the 2 curly braces. There's nothing there. Now, let's put some pieces inside of S. I'm going to insert 3 into S. I'm going to insert 4 into that set. I'm going to insert 3 again because I have a short memory and I've forgotten I've already done that. And I want to say, oh, wait a minute, what does S look like? Oh, that's nice. It's just got one version of 3 plus 4. I go back to what I said earlier. I'm going to enforce in my implementation that representational invariant, that an element appears only once. And if you look back at the code, you realize that second insert of 3 would have checked to see is 3 already in the internal representation? It is, so don't add it. What else could I do? Well, I could check to see if something's in the list. So I could say is 3 in the set S? Yes, it is. Is 6 in the set S? No, it isn't. And that's great. Notice, by the way, on my machine, whenever I type one of those methods, it nicely brings up something that tells me what the doc string associated with it is, what it expects to do. What are the inputs it's expecting there? Things that are going to help us think about what do these different methods do. What else could I do? I can remove something. So I can go back to S and say, let's remove 3. Okay, and it did that fine. And let's let's add in 6 to that. And if I look at what S now consists of, not surprisingly, I've taken out the 3, I've added in the 6. I'm simply using those built-in methods to manipulate that set. I could do one other thing here, and I'm not going to do it on my machine, but simply point out what will happen here. If I try to remove an element that's not currently in that instance of the set, it's going to throw an error, and it's going to print out what I asked it to print out, which is different from the generic exception that I would raise, because I raised a specific version of value error that said, please print out that the specific element and the string not found, telling me what it was that went wrong when I tried to do all of this. So there are 2 examples. Notice how we define an init method for each of them. We define a string method for each of them to tell us how we're going to print things out. And then I create methods specific to this kind of class that let me manipulate instances of that class. To solve that problem I raised, I'm going to introduce one more kind of object into Python, something called a generator. And any procedure or method with a yield statement inside it is a generator. So yield is a new keyword that I'm going to create here. And the idea behind a generator is I'm going to be able to control the behavior. So if I do gen test, which is a procedure here, it returns for me, as you can see, a generator object. And once I've done that, the behavior I'm going to get is the following. Generators have associated with them a next method. It's built into the Python implementation of that. And that next method starts or resumes the execution of a procedure. So inside of a generator, yield suspends the execution and returns a value. The next time I call for the next method, I will go until I get to the next yield method, in which case it will stop or suspend execution and return a value. And it will keep doing that until we run out of yield methods, in which case it will raise a stop iteration exception. So if I actually create this, I can go over to my Python system and try it. And so if I define gen test to be a procedure with a yield of 1 and then a yield of 2, and I call it, let's say I'm going to give foo is gen test. If I say foo of next, it prints out 1. It has gone until it found the first yield statement, it's returned that value, and it stopped operation. And if I call that again, it prints out 2. And if I call it again, it says I have a stop iteration exception raised. So it's letting me control how far I go in the computation before I stop and return a value. So this just summarizes what I just did. In this case, executing the body of foo, which was something created by GenTest until it reaches the first yield. And similarly to the second one. And then similarly until I get to something that raises a stop iteration exception. So why might I want this? Well, notice how I could use this. I could use it inside of a looping structure. Now this is a simple example, but it will do the same kind of idea because the GenTest, that generator, is going to create something that will execute until I get to the first yield point and then return a value. And the looping construct, in fact, knows to ask that thing returned by GenTest, that generator, to do that execution and then stop. And so if I were to run this particular example, it would print out each of the objects in turn because inside the for loop, it's executing until it gets a value returned, yielding, and printing it out. Great. Here's how this could be really nice. Here's a fancy operation. Let's go back to Fibonacci. But rather than writing recursive code for it, I'm going to write it in a somewhat unusual way. This is going to generate, if I wanted to do it, all of the Fibonacci numbers for me. And how might I do it? I'm going to create two internal variables, one that is initially bound to 0, one that's initially bound to 1. Those are the, if you like, the 0th or n minus second and n minus first Fibonacci numbers. And then I know that the nth Fibonacci number is the sum of those. So I'm going to run through a loop that says I'm going to set next to be the sum of those two, and I'm going to yield that value, which will halt execution until I ask it to continue, returning that value. And when it returns, I'm going to move up one step. That was what was the previous Fibonacci number is now the second previous one. Next is the previous Fibonacci number, and I'm going to go back around the loop. And notice there's no way to exit out of this while loop. So it will simply, if I were to call it, generate all of the Fibonacci numbers in turn. So let's try it over in my machine. I'm going to say fib is gen fib. Let me just make sure I call it. I'm going to set that up. And so I'm going to use that generator to create something. So fib is what I get by using gen fib to create a generator. And if I print out fib, you'll say it is a gen fib operation. And then I could start calling it. I'd say, give me the next Fibonacci numbers. It's 1. I call it again, it's 2. I call it again, it's 3. And then 5, and then 8, and then 13. And you get the idea. It runs until it gets to the next stopping point, yields up a value. And it's set up in that while loop to be ready to compute the next one when I need it. Funky way of dealing with it. And in fact, if I were to create this loop, which I'm not going to, it would produce all of the Fibonacci numbers until I ask it to stop, an infinite sequence of them. I don't recommend you necessarily program this way, but you can see the power of the generator because I'm separating where I stop in the operation from the overall operation I'm trying to encode. Why is that valuable? Well, generators nicely separate out the apparent computation from the actual one. It separates the concept of computing a very long sequence of objects from the actual process of getting them explicitly. And it allows you as a consequence to generate new objects as needed as part of another computation. So rather than, for example, generating the entire list of Fibonacci numbers and then asking for the 12th one, you could simply step through it until you get to the 12th one and then return that value. This is going to be valuable when you want to think about a way of creating things as needed. And in fact, you've seen this idea. You saw it in range. Literally what range is doing is creating something like a generator. When I say for n in range, range is returning something that gives me the first value and essentially a promise to give me the rest of it when I ask for it. I can do something with the first value inside that loop, and then when I come back around the loop again, range, that generator, will give me the next value, and so on. And this is nice because it gives us better efficiency without changing the way we think about doing the computation. I can program as if that entire sequence is available to me. The computer's going to generate it as I need it. Now, if I go back to what started this, that says that, for example, in all students, I could change the behavior. Right now, I'm returning a copy of the entire list of students. If I only have 100, no big deal. But with 100,000 or 1,000,000, I don't necessarily want to generate them if I want to do something with them on the fly or in turn. Whereas in the new version, what I could do is simply create a loop here that says, for all students in that list, just yield them up. So one at a time as I ask for them, it will give me the next one without generating the entire list as I go through them. So from this, I can move to that, and that gives me a much more efficient way of dealing with things. So what you've seen here now is how to build a hierarchy of classes with inherited behaviors, modularity to isolate changes of behaviors, classes that can have classes within their instances, and the ability to think about how I control the efficiency of all of those. And that's the power of object-oriented programming. So now we started building some classes, and we said a key advantage is that we get to cluster behaviors together around instances of a class, common behaviors. Cats are a little bit different than rabbits, for example. But an even more important property of classes is that I can have hierarchies of classes. That I can have cats and rabbits, and I do, but they are also instances of animals, as are other kinds of things. So I've got, as we already started, the general idea of a class of animal, and now I'd like to create a subclass of animal that has cat behaviors. I'd like to create another subclass of animal that has rabbit behaviors. I'd like to create a third class of animal that has people behaviors. And even within people, there may be other kinds of behaviors. students often tend to behave differently than other kinds of people. And what I'm doing is building a hierarchy. Each one of these should be a separate class. It should have common behaviors associated with cats, or associated with rabbits, or associated with people. But some of them may be shared across all of those classes. And in this diagram, all of those lie within the class of an animal. So they should have underlying behaviors. Similarly, students have behaviors, some of which are common to people, some of which are unique to students. And I'd like to build classes that reflect exactly that hierarchy, sharing the properties and the methods that are common, but having distinct properties, attributes, methods when appropriate. So, this leads to this idea of a hierarchy. We've already begun to see it. And in a hierarchy, we're going to have a parent class. Here it's going to be animal, although one could actually argue that above this was the idea of an object or underlying class. But here, animal is a parent class, and it has some children subclasses. And those children subclasses all inherit the behaviors and data of the parents, unless I explicitly override them. One of the nice things then is I could add more data to the subclasses, I could add more behaviors to the subclasses, and I could decide to have one of the subclasses have a different behavior than the parent, and I can override that. And that's what we're going to do now, is we're going to build a little hierarchy and look at how we actually get those kinds of behaviors out. There's my animal class. It's just what I had before. I've got a way of creating them with an age and a name. I've got getters, I've got setters, I've got a way of printing them out. Let's see what happens if I want to build things on top of them. So, everything here is of course an object. That means it inherits all of the pieces inside of Python. And then the new object is going to define properties that it's going to inherit from that class, but have its own properties on top of it. Let's define a cat. I want the cat to speak. It's not very impressive how it speaks, but it does have a speak method. And I also want to override the print method, because while a cat's an animal, I'd like to know when I see a cat that it is a cat. So I'm going to define a new string method associated with the class cat that prints out almost the same kind of thing. It's going to print out the name and the age. But now I'm going to ask it to print out the symbol cat to tell me that I'm looking at a cat. So I've added some new functionality with speak. An instance of type cat can now be called with those methods, but an instance of type animal will throw an error if I try and use it with a method that only belongs to a cat. Let's look at an example of that, but let's quickly remind you again. I inherit all of the properties of an animal. I've added the new functionality there, but I'm going to override other behaviors where necessary, and I don't want to have those behaviors show up in places that they shouldn't. So animals are not going to be able to speak, at least in the version I've got here. Let's build a version of that. And so I'm going to go to my computer and type this in. And let's define Jelly to be a 1-year-old cat. All right? I can set its name. Now I could actually ask what the name of Jelly is. So I could say to Jelly, give me your name. I'll use getName to get that out. And it says I don't have one. You didn't give me one yet. Okay, let's change it. And we'll say we're going to call Jelly, just for fun reasons, Jelly Belly. And now if I ask for Jelly's name, good, there it is. Now, if as a consequence, if I print Jelly, it tells me, first of all, it's a cat. That comes from the string method associated with an instance of a cat. It gives me the name of this particular instance and its age. Right? So that string method is shadowing the animal string method. And that's an important point. Remember, this is a version of an animal, but it doesn't use the animal string method when I use this. And in fact, if I wanted to go back and look at that, I could do what I just showed you there. I could print out, and here I'm going to say, take the animal class, get the string method associated with animal, and apply it to Jelly. And I have to do that because Jelly will only see the method associated with cat. And if I do that, it now prints out animal, Jelly Belly, and 1. So I can still get to that underlying method if I really wanted to use it. In a little bit, we're going to see how we want to actually take advantage of that idea. Let's make another animal, Blob. This is an animal, a 1-year-old animal. And if I print it out, It tells me it's an animal. It says you got none associated with the name because I don't have one there, and its age is 1. I could change that name as well. I could say to blob, set your name. And since there's a default empty string for this, I'm simply going to give it no argument. And as we would expect from what I've shown on the slide, when I print it out now, it prints out animal, nothing, and the name. Great. I've got ways of dealing with different kinds of objects. And you can see how the methods can shadow other methods higher up in the hierarchy. I'm always going to start with the class associated with the instance and look for a method there. If there isn't one, then I'm going to go up the hierarchy to see if there's a method defined earlier on in that chain. Okay, now let's define rabbits. Again, as we had with cats, they can speak. Rabbits can also speak. In my experience, rabbits don't say a lot. So I'm going to have it say something very quiet. And similarly, I'm going to define a string method here. It looks a lot like the string method for cat, but having me tell it it's a rabbit rather than telling me it's a cat. Easy to make the change. And now, if I go back to my computer, I've already got jelly. I've defined that. I've got blob. Let's call Peter, or give Peter to be an instance of a rabbit that's 5 years old. I can now ask Jelly to speak. And it uses the method from cat and says meow. Not impressive, I know, but it did the right thing. There it is. I could also ask Peter to speak. And he simply says meep. Why am I showing you this? There are 2 speak methods, one associated with rabbits, one associated with cats. And what the system does is say, given Jelly, let me get what that is bound to. In the global or the top level environment, that is a pointer to an instance of a cat. And so because it's an instance, the dot says, look up inside that instance the speak method. Now I didn't define speak inside the instance, but because this is an instance, I know it's a kind of cat. I look up the speak method inside of cat, which is why it does the right thing. Whereas down here, this speak method comes from rabbit, because that's what Peter is an instance of. And that's why it prints out the right thing. I use the appropriate method by letting the instance tell me what kind of method I should look up. All right, let's have blob say something. I don't know what blobs say, so let's have blob speak. Oh goodness, it complained. And it complained correctly, because there is no speak method associated with animal. Blob is an instance of animal. When I use this, I ask, the dot says, get blob, it's an instance of animal. Look up an animal, the definition for a method for speak. There isn't one. And this reinforces that idea that while I can inherit methods from higher in the hierarchy, something higher in the hierarchy cannot access a method of a subclass. Even though both cats and rabbits have speak methods, animals cannot get to them because they are below them within the hierarchy. So I get an attribute error, exactly what I'd like to have happen. I'm going to just recapture what we've already said, but do it in a little more concise form. Which method should we use? We know that a subclass can have methods with the same name as a superclass, but we always start with that subclass. It shadows that higher level method. Subclasses can also have methods with the same name as other subclasses. I have speak in cat and in rabbit. I always let the type of the instance direct me to finding the right method to use that. And thus, as a consequence, for an instance of a class, I look up the method in the current class definition. If I don't find it, I go up the hierarchy looking for it until I either find one and use it, or if I don't find one, throw an error, an exception saying I don't know how to actually use that. That nicely encapsulates or packages names inside of class definitions associated with instances. A little bit of a messy slide, but let's introduce one more kind of animal, a person. And that's a reasonable animal to have. And I've got a number of pieces here I want to highlight out. First of all, notice this again is an instance or a subclass of an animal, as were rabbits, as were cats. I've got an init method, but it's a little bit different. So let's look at it carefully. This init method again has, as always, the self is the first argument, and it has two parameters I'm passing in, a name and an age. But I'm going to now use the underlying animal method to create the instance. And to get at it, I do what I just did. I'm going to say take animal, the name of a class, get the init method associated with that, and call it to create the actual instance. So I'm calling the animal constructor here. I'm also going to use the underlying set name method of animal to change the name associated with this instance of a person. In both cases, I have to get at it by giving the name of the class and then the name of the method that I want to use. And then finally, I'm going to simply define friends in this instance directly. So I can add a new data attribute. What I'm doing here is explicitly inheriting the init method of the superclass to create the instance. So a different formal than we've seen before. Great. Now that I got that, I can create a few other things. I've got something that creates a way of getting out the friends. I got a way of adding a new friend in. This is simply adding a name into a list of things. I can have a speak method for a person that's different than a speak method for a cat or a rabbit. I can also do some other things, and here's an instance where I'm going to get the age difference between two people. And I'm going to do it by using the getters for both instances to get the difference. And then I can actually compare those to decide I want to print something different out in terms of which one's younger or which one's older as I do that. And then finally down here, I've got a string method for a person as well, something that I want to have that's going to override the underlying string method. And as before, if I really want to use the animal string method, I could. Biggest difference here is where we started, that I can explicitly call initialization or instance creation methods of other classes within the hierarchy, and I want to do that with a person. So let's create a couple of people. Eric is a person with the name Eric, and he claims to be 45 years old. And John is also a person, and he claims to be 55 years old. I can ask Eric to speak, and he just says hello. Key point again is the instance type tells me which speak method to use. What else could I do? I could ask, how old, what's the difference between Eric and John in age? And so if I ask for the age difference between Eric and John, it computes it and prints out the string I asked it to. That's great. I could also, though, do it as we did before, just to remind you, directly by saying, get the person method for age difference. And in this case, let's do it between John and Eric. And I'm doing it in the different direction than I did before, and it gives me out the appropriate kind of information. Just showing, again, I can do that all within this hierarchy, as I've done before. Okay, what else might we do here? Let's create a special kind of person, a student. A student is a person. It's going to inherit a lot of those behaviors, and it does it, again, by using person. But remember now, person is also a subclass of animal. So a student both inherits from person, but it will also inherit from animal. And that's going to be important in certain places. I'm going to create a constructor for this, and it is going to, in this case, use the person creation method, the initialization method. And remember that used inherently a direct call to animal. So I can chain up here. But the one other thing I want to do here is a student has a major. They're computer scientists, they're economists. So I'm going to define a new data attribute right here in terms of doing that. In my experience, students often change majors, so I can do that by simply having them decide they want to have a new major. And I'm going to define a speak method for a student. And here I'm going to do something a little different. I'm going to inherit from a module the ability to just randomly pick a number. And in this case, I'm going to let you look it up. I import from the random module ways of doing random, and this particular call is going to give me back a number between 0 and 1. And that's going to allow me to define a different kind of behavior for speak here, which is that students change their mind about what they want to say, depending on how many times they've done something. And finally, at the bottom, I'm going to define a string method, and that overrides the person string method, which already overrode the animal's string method. All right, let's see what happens if we create people. I've got Eric, I've got Fred, and I'm simply now going to show you what happens here. If I print out Fred, because if I go back here for a second, there's the string method. It was the label student, the name, the age, and the major. Printing out Fred prints out something different because it uses the method from student. If I ask Fred to talk, well, I can do it multiple times. And in fact, the behavior changes here because each time I call it, it computes a random number between 0 and 1, and based on that value, it either says I have homework, I'm watching TV, or I'm really starving and I should go eat. Again, Fred tells me which speak method to do, and that's really nice because I don't get confused about which behavior I want to have. So the first part of creating a new class is to say, how am I going to create instances of it? And as I said, that also tends to inherently capture what are the data attributes associated with an instance of a class. But now I need methods. I need ways of manipulating those attributes, those data attributes. And so, first of all, what's a method? It's a procedural attribute. Think of it like a function, but a function or procedure that works only with this class. It's designed for that class. As an aside, as I said earlier, that's nice because it says I can use the same name many times doing similar things for different classes without worrying about the confusion of the name. Now, when I define a method, Python always passes the actual object, the instance, as the first argument. And so the convention is going to be to use self as the name of the first argument of all methods, not just init. As we've also seen, and we're going to see now an example of it, the dot operator is going to be used to access any attribute. Certainly the data attributes, the variable names, but also the method. And we're going to see an example of that in a second. But first, let's look at actually making one of these. So let's go back to my coordinate definition. I already said I might want to compute the distance between two coordinates. So I can add a new method. And here it is. I'm going to define distance. And notice with both of these, and I should have said it earlier, these are now just standard definitions of procedures. They happen to be indented inside this class definition because they belong to the class. So I'm going to define distance. As I said just previously, we need to have the first argument be self because it's going to refer to a particular instance. It says, here's the method I want to do on this instance. In this case, I've also got another parameter because I want to measure the distance between a particular coordinate and some other coordinate. So I'm going to give it a name. I'm going to call it other. Within the body of that method, I just do the standard work I would do. I'm going to compute a couple of things. I'm going to return a value which is just the sum of the squares, the square root rather of the sum of the squares. The only other nuance here is I'm using dot notation to access the data. Other than that dot notation, everything else behaves just like you would expect. What's the dot notation doing? Well, as we already saw when we wanted to get values out, I need to do that to get the values associated with instances, not only for self, but also for this other coordinate. And just as I did in the earlier example, think of other.x as saying, get the value of other. It points to a frame because it's an instance of a coordinate. And in that frame, when I created it, I defined variable bindings for x and y, retrieve those variable bindings. But there's now a nice little method for computing distance. And so I could actually use it. And in fact, let me do it. I'm going to go over to my machine and I'm going to make sure I have that definition in place, and I do. And I've got C, and I've got origin. So let's do the following. I've defined C and origin as before. I can print out what is the distance from C to the origin. And it says it's distance 5, which makes sense. 3 squared plus 4 squared is 25, square root is 5. Notice how I called it. I called it by saying, first of all, what's the object on which I want to call the method? In this case, it was the coordinate C. What's the name of the method? And then what's the parameter I want to use? But again, notice I did not provide anything for self. And this is because in this particular version, C being a frame, I look up the value of distance. It is a method within it. And because I'm using it associated with that particular instance, Python automatically provides C as the first argument to this distance function. I could do it a different way. Again, I could have C as a coordinate, origin as a coordinate, and I could do the following. I could print out the class coordinate dot distance of C and origin. And that might look a little more reasonable to you because now I'm saying what's the distance between C and origin? And if I do that, I also get out 5. What's the difference here? Now I'm giving it the name of a class. What's that? Well, it actually also points to a frame in which all the class definitions are created. So inside of the coordinate frame, I'm looking up the distance method, and that takes 2 arguments, and therefore I apply both parameters, C and origin. If I'm using an instance to get the method, Python automatically uses that instance as the first argument. If I'm using the class to get to the method, you need to provide both arguments because Python doesn't know which is the instance that you want to use. Think of it this way. Coordinate is pointing to a frame. Inside the scope of that frame, we created methods when we created that class definition. So coordinate.distance basically says get the value of coordinate, it's a frame. The dot says look up the value of distance within it. I get that, that's a procedure definition. And then I apply it to the arguments that are provided. C.distance doesn't have a distance method defined within C, it's just an instance. But because it's an instance of the class, it inherits that distance method from it. And as we said, Python automatically uses C as the first argument. I'm belaboring this point because I guarantee you that you are going to somewhere in the near future make the mistake of either not providing an argument for self or providing one when you don't need to. And so this slide hopefully gives you a way of separating out the two differences. Okay, now that we got them, we might want to look at those coordinates. So I could just print them out. And I could go back to my machine and say, print out C. And it gives me garbage. Well, I shouldn't say garbage. It gives me actually information that says within the main environment, this is an instance of a coordinate object, and here's the actual memory location at which it lies. I guess I could go in and start playing with that memory, but that doesn't make a lot of sense. This is clearly an uninformative representation, and that's because by default, this is what it prints out. I'd like it to have it print out something that's much better at representing what a coordinate looks like, and I can do that by defining another method for my class. This is another special method called the string method, and it's typed as underscore underscore str and then 2 underscores as well. Whenever I ask to print an instance of any kind of data object, Python is going to call the string method that was used or was part of the definition of the class. And you get to decide what it does. By the way, even with existing object types, there is in essence a string method associated with lists, a string method associated with tuples. So, say we want to have our string method actually produce something with an angle bracket and then the 2 coordinates separated by a comma and another angle bracket. Well, I could do that, and it's actually pretty easy. Right down here, I'm going to define that special method string. It's going to tell me how things are going to print out. And all I require is that however I want to define it, it must return a string. And so if I go back over to my machine and I'm going to uncomment that string method, now I can evaluate that. And I'm going to define again C to be the coordinate of 3 and 4. If I print C, oh nice, it prints out a much better representation of the coordinate, something that I can recognize. And that's going to make it easier to think about what's inside of that coordinate. Having done that, I can now also think about a few other things I might like to do with classes. I could say, what's the type of this particular object? So I could print, as you can see there, what's the type of C? And it actually gives me back something that makes sense. It says C is an instance of a class, and the class type is coordinate. The dot main just tells me it was defined up in that overall environment to which I interact, that Python environment in which I interact. And in fact, it makes sense because I can say both what is a coordinate, it's a class, and what's the type of a coordinate, it's a type. So I can make instances, I can measure things about them, I can print them out. One of the other things I might want to do is to know what kind of thing is this? Do I have something that's an instance of a coordinate? I could do that by looking at the type and trying to check what's the type of this thing. But you've already seen right here that the type of C is this complicated thing. I really don't want to write, is the type of this object equal to class underscore main dot coordinate? That's messy. So instead, I'm going to use another built-in method associated with any object, which is instance. And I can use that to check if an object is an instance of a coordinate. So I can say, for example, is C an instance of coordinate? And it says, you bet. I could do that with built-in objects, by the way, saying, is this thing an instance of a list? Is this thing an instance of an int? I can often do shortcuts in those cases, but that underlying method of is instance comes from basically the objects that exist within Python. We also have a few other methods that we saw with other kinds of objects that we can build into our new class definitions. There's a long list of them. I'm going to simply let you go look them up, but basically many of these come provided, but I can override them. And the standard ones are I can define what it means to add two instances together, to subtract them, to test if they're equal, to test if they're less than, to print out the length, and we've already done print here, that's the str. Each one of these methods has a built-in name that I can use to override the underlying version of that. So for example, imagine I want to subtract two coordinates. I could do that by simply defining what sub should look like, and I'm going to do that by going to my computer where I've built one of those in. And what sub should do is simply take the instance itself and another instance, subtract coordinate-wise the x values, and then return a coordinate. And if I run that, again, I'm going to create two versions of it here. I'm going to let c be the coordinate at 3, 4. I'm going to let origin be the coordinate at 0, 0. And if I want to say c minus origin, great, I get out a coordinate. Let's give it a name. And I can print foo, and it gives me back what I would expect, which is just the vector between that point and the origin. Key thing to note here is I can have my method return simple values. I can also have it return new instances of things I created, and that's a really nice thing to have. When we introduced definitions into our language, in essence what we were doing was giving you as the programmer the ability to create procedures that you could then abstract and treat as if they were provided by the manufacturer of the computer. The same way that you have addition and subtraction, you could create new variations of procedures and treat them as if they were behaving exactly the same way that those primitive procedures did. We want to do the same thing with data. We're going to talk now about creating objects, classes of objects, that you can define as a user, and that switch is going to add a tremendous amount of power, flexibility, capability to our language and to our ability to create new systems. So let's see what that means. Let's start by talking about the objects you already know about. As you know, Python supports a number of different kinds of data. We've got integers, we've got floating point numbers, we've got strings, we've got lists, we've got dictionaries, a few others like tuples, but basically we have a primitive set of data objects. Each one of those examples that I have on my screen is an instance of an object. And every object has three pieces. It has a type, int, float, dictionary. It has an internal representation. It's a way of gluing together the pieces that compose the object. For primitive things like numbers, it really doesn't make sense to talk about it as anything other than a scalar. But for a list, it would say, how do I get the different pieces, elements, if you like, of a list and glue them together? So every object has a type, it has an internal data representation, and associated with it, it has a set of procedures that allow you to interact with an instance of that object. We're going to look at some examples in a second, but those three pieces are key to defining an object. And indeed, every instance that we create is a particular type of object. 1, 2, 3, 4 is an instance of an int. If I define A to be, quote, hello, end quote, A is now an instance of a string. So we talk about objects as having types because that brings with them the ability to manipulate them. Okay, if everything in Python is an object and has a type, what does it tell us about how we might think about using them? And the first one is we want to think about each object as being a data abstraction. It captures an internal representation of the data attributes. We'll say what those are in a second. And it defines an interface for interacting with the object through methods. Think of them as procedures. And those methods define a behavior but hide the implementation. Again, in a second we'll look at an example, but every data abstraction is an internal representation and an interface for getting to that internal representation, doing something with it, and then returning an answer. Associated with every object, we have the ability to create new instances of that type of object, and we have the ability to get rid of it, to destroy objects, either explicitly using del, which we know is a universal way of removing something from our environment, or just forgetting about them and letting the system eventually garbage collect or reclaim inaccessible or destroyed objects. But that idea of an object having a type, an internal representation, an interface is going to be really important as we think about how do we want to create our own objects. We want to talk then about data objects and that idea of internal representations and ways to manipulate them. We have some built-in data objects, lists, tuples, strings, and we're going to see examples of how they have both an internal representation and associated procedures. And we're going to take that idea and generalize it to look at the ability to create our own data object types. And that wraps back to what I said when I began. Once we can do that, we want to then treat those data object types as if they were provided to us and treat them as the same way we would treat any built-in data type. Let's look at an example to make this a little more concrete. This is an object of type list. It's an instance of a list. One of the questions we could ask is, how is it represented internally? Do you know? You shouldn't, because we haven't talked about it. And you shouldn't have to worry about it. You just want to use that data object through a defined set of procedures. It's possible inside your machine that a list is represented by allocating a sequence of consecutive slots in memory. The list would point to the first slot, that would be the first index. Incrementally, the next slot in memory could be the second index. Turns out that's not a great way to represent lists because it's limited in the ability to change them, to mutate them, or to have arbitrary sized elements inside of them. So in fact, the more common way to represent a list is using something called a linked list, where the list points to a cell in memory, actually to a pair of cells in memory, the first one of which contains either the object or perhaps even a pointer to an object elsewhere, and the second which points to or links to the next location in the list. It might be the next spot in memory. It might be somewhere else in the memory. And when I want to index into a list, I'm literally walking down the list, finding the right spot, and retrieving the element from it. That's a nice way to think about building lists. Is that the way you do it? Doesn't matter, because what you use with the lists is a set of procedures, a set of methods to actually manipulate the elements of the list. And you've seen lots of these. I can get out a specific element. I can slice into it. I can do it with a specific set of jumps. I can have procedures that actually compute things off of a list or get rid of an element of a list. I have associated with lists a set of methods. And there's that dot notation that we've talked about earlier, and we're going to talk a lot more about in a few minutes. The key point here is I've got a set of ways in which I standardly interact with and manipulate lists. And from your perspective, you think about this. You don't worry about what the internal representation is because those procedures take care of that for you. As a consequence, that internal representation really should be private, meaning you don't know what's inside of it. And the correct behavior, in fact, could be compromised if you try and manipulate the internal representation directly. Ideally, you should always use the defined interfaces to get at portions of or elements of a list or any other data object that you've created. We're going to take that idea now and we're going to talk about how do you create your own objects and how do you use your own objects. And we've already seen we're going to need an internal representation and we're going to need methods to enable us to talk about how we want to manipulate that internal representation. To do this, though, we're also going to make one more distinction, and that's between creating a class and using an instance of a class. To wrap it back to earlier terms, the idea of a list is a class. But the example I had of the list 1, 2, 3, 4 is a particular instance of a class. And as you know, I could have many instances. I can use them in different ways. When we want to create our own objects, we need to do the same thing. How do we create a class? How do we make an instance of a class? Creating the class is going to involve defining the name of the class, so I can reference it. It's going to involve defining the class attributes. I'm going to come to that in a second. And an example of this is, in the list case, somebody wrote code to implement the list class, giving it the name list and defining the attributes associated with a list class. When I want to use the class, that involves creating new instances of that object, different kinds of lists, and then doing operations on those instances. So for example, if I have the simple list L is the list of 1, 2, then there's an operation on it. And that's operating on that particular instance, not on the whole class. I'm going to take those same ideas now and try and make them more concrete in terms of how do we define a class and how do we actually use instances of the class. But before I do it, let's talk about why. What I'm trying to do is now bundle together data into packages. That bundling includes linking together different pieces of data that are associated in one place, but it's also associating with it the methods that are going to manipulate that data object. And this is actually an idea we've talked about a lot, because this is simply a version of abstraction. By doing this idea of bundling things together, I can now treat that bundle as an abstract data representation. To get into it, I need to define methods that can pull out pieces and do things with them, but I can treat the whole thing simply as an element. And that's also going to be really important as we think about building our classes. Second key advantage of object-oriented programming is it gives us a divide and conquer approach to development. I can implement and test the behavior of each class separately. And once I have that done, then I can start doing the whole system as a larger entity. And that increased modularity reduces the complexity of the code I write associated with any class. As a consequence, it makes it much easier to reuse the code. In fact, many Python modules define new classes inherently, and each class therefore has a separate environment. That means I don't have any collisions over the names. If I want to use a method with a particular name in one class, I can use a method with the same name in another class because they're captured inside of a module. And as we'll see a little later on, we're going to have the notion of inheritance, in which we can define subclasses of classes that will capture or inherit behavior of its parent class and potentially modify it. But it makes it easier for us to write code because we don't have to write the same behavior for every class if, in fact, we can have it captured in a single class. We're going to take those ideas and now start to make them much more concrete. Now that I've started building a hierarchy, one of the things I'd like to show you is how that modularity, that associating methods with different data attributes around a particular class, makes it easy for me to change behaviors for one class without changing behaviors elsewhere. And to do that, I'm going to add in one more kind of object to my hierarchy, a professor. Also a kind of MIT person, but behaves differently, as you've probably already seen. And I'm going to use this, as I said, as an example to see how one can leverage methods from other classes in the hierarchy, but use that modularity to isolate changes to methods when I want to. Let's start by defining a professor. Again, it inherits as a kind of MIT person. I'm going to have an initialization method, as before. And as I did with students, I'm going to inherit or use the inherited MIT person initialization method to set it up. But I'll add in one more attribute, the department in which this person is a professor. This professor can speak. Again, I'm going to use the underlying MIT person speak method, but I'm going to add in a few other things to the utterance. And you can see the example here. I'm going to in fact say what department the person's in and how they say things. And we'll see an example in a second. Professors not only speak, they lecture. And so I'll give the professor the ability to lecture. And notice here, I'm going to use my own speak method, or the professor's speak method, to lecture by adding some other pieces in. So this method will shadow the MIT person speak method for professors, although it will use that inherited speak method. And lecture will use the base speak method associated with a professor, but add other things in as we do it. Let's see what happens if we were to do this. So I'm going to go back to the things I've already built, some of my early examples, and just look at how the different speak methods work. So I've got an MIT person, and I can do that. I can say I'm going to print out asking M1 to speak, and just say a very simple hi there. And it prints out, as we saw before, Gates says hi there, because that's the speak method for an MIT person. Now, I know that that uses that base method. Let's look at another example. I'm going to print out for a student. And if I do print S1 speak, again, just saying hi there, it prints out Damon says, dude, hi there. It's using the undergraduate speak method, because that was the kind of student we created, which uses the MIT person method, but simply adds dude to the front of the utterance. What else might I do? Well, let's have a faculty member, and I've created a faculty member here. Let's just have a faculty member speak. And if we ask that faculty member to say hi there, I should have said earlier, the faculty member I created was a professor named Dr. Arrogant in course 6, and he prints out, in course 6, we say, hi there. And this is coming from the change I made to that speak method for a faculty member. And finally, if I were to have a faculty member lecture, so I asked this faculty member that I created to lecture on the topic of hi there. He says, or rather it prints out, Arrogant says, in course 6 we say, it is obvious that, hi there. So notice what the lecture method does. It uses the professor's speak method, which incorporated that in course 6 we say, but it added into it as part of the utterance this little annoying phrase, it is obvious that. Key point, each class has a speak method. And in the hierarchy, we start with the class instance, or the class of which we have an instance, use that speak method. We may inherit from higher up in the hierarchy, but we have all of those pieces nicely contained to the instances. So speaking different kinds of objects do in a different way. With that in mind, we could make some changes. So in particular, because I've got that isolation, I could go into the MIT person speak method and change how we have this actually print out. In particular, I'm going to have it return the name rather than just the last name as part of that says method. Let's see what would happen if I did that. So I have a version of my file over here that does that. And if I now change that in the person method, I'm going to reload that file. And in particular, if I were to go through the same instances, now the print methods, notice, all add in front the full name. Why? Because all of these methods use the underlying MIT person speak method. They just added other pieces into it. In the case of a student, it added in dude. In the case of a faculty member, it added in course 6 we say. In the case of lecturing, it added in other pieces. But in all cases, ultimately it calls that underlying MIT person method. So all of these classes inherit that. But I could make a different kind of change. For example, I could decide that I'm going to change the undergraduate students' speak method to, rather than saying dude, say yo bro. And if I were to make that change and come back and try it, I load it into my machine and I were to print those things out, I would get the following behavior. It looks exactly like the previous case. The only difference is right there, that the undergraduate speak method uses yo bro. Notice it doesn't change faculty member either speaking or lecturing. It doesn't change the MIT person. And for two different reasons. For the MIT person case, undergraduate is lower in the hierarchy. So in fact, it would not have a change there. In the case of a faculty member, it's in another place in the hierarchy. And it does not use the student's method. It uses the MIT person's method. I've modularized it. I've captured a behavior locally. And that's really nice. Now, as we saw last time, a key element about having classes is that we can build hierarchies. That is, classes that inherit from other classes. It gives us a very crisp way of building code that can be reused. It lets us build modules that easily interrelate. So let's look at that idea here. I've got the idea of a person. Now I'm going to add a new kind of person, an MIT person. Contrary to popular belief, MIT people are people. They have the same properties. They're born. They have a name. We'll add a few other things, though, to an MIT person. They have an ID number. And one of the things we want to look at is how we can use the ID number to identify specific instances and use that, in fact, for things like sorting. So let's look at how we might build an MIT person. So here's my class definition. And I want to show you a couple of highlights here, things that are important. The first one is, as I did in an earlier example, I'm going to create a class attribute. So this is a definition of a data object that's built into the class. Does not belong to an instance, it belongs to the class. And it's going to let me keep track of how many ID numbers have I assigned. I'll initialize it to 0. That's a good place to start. Even though MIT person is a kind of person, I'm going to build an initializer, something that creates instances for this class as well. But the interesting thing here is I'm going to use the underlying person method to also create the instance. So when I call MIT person, it's going to create an instance, but it's going to call the person class initialization method to initialize the same kinds of things, the name, and as a consequence, it'll set up a birth date in case I want to use that. Second thing I'm going to do, though, is assign to this instance an ID number. So self here will say that I'm going to, in this instance, bind ID num to a particular value, but I'm going to use the value associated with MIT person. I do MIT person dot next ID num. It will get the value of that data variable and assign it to this instance. And then finally, I'm going to increment that global class data attribute by 1, so that the next person I create is going to have the next number in the sequence. Once I've done that, I could get out the ID number of a person. And sorting here, I'm going to do simply by comparing ID numbers. If I want to sort a list of MIT people, I'll do them by ID number, starting at 0 and moving up. The last one I'll come back to later on is I'm going to give MIT people the ability to speak. I'll give them a string that I want them to say, and they'll return something that says their last name, says, and then a string. We'll look at an example of that in a second. With that in mind, let's look at what would happen if I built some examples of this. So a way to think about this is, in my memory somewhere, I have a representation for the person class, and I have a representation for the MIT person class. When I call for an instance of MIT person, it's going to use this init procedure because it's that class, and that's the one that's visible inside this environment. But as we saw in the code, calling that init procedure then calls the person init procedure. It literally goes into the person class definition and finds that init procedure and calls it. And that will set up a binding for name and birth date rather, inside of that instance. In particular, that is returned to the MIT person class because that's the place where the call was done. But the bindings come from the init procedure that's associated with person. So I've just created that instance, and having done that, and that'll have a binding, for example, to a last name, the next thing I do is I get the value of the ID number from next ID num inside of MIT person, and I bind that to the ID number for this instance. Great, this is now person number 0. And that's because of this call right here, which says within that self, bind ID num to what we see inside the class definition. And then the next thing I do is I update next ID num by 1 inside that MIT person environment. That's great, because now I have an instance with an ID number associated with it. And if I were to call for another instance of MIT person, it will go through the same process, calling the person init method to set it up. But now, next ID num is 1. So the binding here is ID number 1, and that gets incremented to 2. You see as a consequence how that class attribute can store information I can use to associate with instances of the class. Great. Now what happens if we create it? Well, again, I'm going to take a similar set of characters. I'm now going to make them MIT people. I'm going to create a Mark Zuckerberg, a Drew Houston, and a Bill Gates. I'm going to give them birthdays. And I'm going to, you may notice here, even though I'm going to create them in this order, I'm going to change the numbering so that M3, although it's the first one I created, I'm going to have the third element in my list down here as I build it. And let's see what happens if I were to go and do that for this particular example. Let me just set up my computer. And if I call that, I now have a set of people in my system. And let me just look at an example. If I print out M1, I get Bill Gates. That's great. That's what I called him down there. If I print out M3, I get Mark Zuckerberg. And one of the things I said is I could have these people say something. So I could print M3 speak, and I'll just have him say something pretty straightforward like, hi there. And it prints out, as I expected, Gates says, hi there. Okay. One of the reasons I wanted ID numbers was so that I could do things like sort people. I'm going to use them in other ways to access information. But let's look at now going back to the same kind of example. What would happen if I were to print out the people in this list? Well, if I just do that, I'm going to see what you would expect to happen. I'm going to now load this up and print it. And it prints out, as shown on the screen here, Bill Gates, Drew Houston, Mark Zuckerberg. Now remember, I created them in a particular order. This is the order I created them in. So in fact, that's the way in which it prints them out. even though in the list they were in a different order. Now, let's look what happens if I do them by ID number. And if I were to go ahead and sort, and then recall this, now it prints them out by ID number. Zuckerberg first, then Houston, then Gates. So you can see in this case, I am sorting by ID, exactly as I set it up. Great. What else might we do with this? Well, let me create another version of a little set of MIT people, partly to show you that the ID number can be important because the names may not be distinctive. So here I've created 3 MIT people, Eric and 2 Johns. I've also created just a base person, also with the name John. And I want to think about things like, how might I sort these? Well, in particular, what happens? Well, first of all, what happens when I create them? In this case, I have bindings for P1, P2, and P3, 2 instances of MIT people, each with a unique ID number. P4 points to a different kind of object. It's just a person, no ID number associated with them. It's going to be important in a second. And now let's look what happens if we wanted to do things like compare them, which would be part of doing the sort. So I'm going to try some examples here. Having loaded those into my system, let's ask, is P1 less than P2? And it says true. Okay? That makes sense because the sorting here should be done on the basis of ID number. I created P1 before I created P2. Great. Now let me ask, is P1 less than P4? Oh goodness, I get an attribute error. Let's try it the other way. Is P4 less than P1? No. Wait a minute. What's going on here? Well, this is highlighting how a class or an instance of a class gets a method. So why is it that in one case it works and in another case it doesn't? So how's the comparison actually taking place? What happens is that MIT person as a class has its own less than method. And that method shadows the person method, meaning if we compare an MIT person object, since its environment inherits from that person class environment, it will see this version of less than. It won't see the person version of it. As a consequence, when we ask is P1 less than P2, that is literally converted into this form here. It says P1 dot less than of P2. Long string. It basically says from the P1 object, get the less than method. I just said because it's an MIT person, it will get that version of the method. And then it's going to apply it to self, which is P1 and P2. And it will do the appropriate comparison because these are 2 MIT people objects. It's going to use the less than method appropriately on that, comparing ID numbers. On the other hand, why does P4 less than P1 work, but P1 less than P4 does not? P4 less than P1 is equivalent to asking P4 dot less than method applied to P1, which means we use the less than method associated with the type of P4, which in this case is a person, one that compares based on name. So based on name, it can come up with an answer, which is great. On the other hand, when we ask P1 less than P4, that's equivalent to getting the less than method associated with the type of P1, which is an MIT person. And since that tries to compare on ID numbers, and P4 as a person does not have an ID number, this will throw an error, or in this case, say that there's an attribute error. I don't have an ID number associated with it. So we see that the less than method, we have to be careful to make sure we use the appropriate one for the kinds of objects we want to use. And in particular, the specific object calling it, in this case, the first one in that comparison, is the one that's going to define the type and therefore the method that we want to use. We're going to look at one more extended example in the last part of this lecture to introduce again some new ideas around using classes. But before we do, let's take a second to step back and talk about why. What's the power of object-oriented programming? Why would we like to do this? We've already said some of this earlier, but it's useful to remind you of this. The first idea is that we want to bundle together objects that share some common properties. They share common attributes, and they share procedures that operate on those attributes. That's an abstraction. And it's a really nice abstraction because it lets us make a distinction between how to implement the object and how to use it. Defining the class lets me define the methods. That tells me how I want to use that object. When I actually go to use it, though, I can simply use the instances and use that associated or inherited methods along with them. The second thing that object-oriented programming gives us, this idea of bundling things together, is another idea of abstraction, which is I can treat each instance of that kind of class, that kind of object, as if it's a primitive. I don't have to think about the internal representation. I don't have to think about the details of how to get at it. I simply know that there are a set of methods associated with it. And that lets us then build on top of that idea. And in particular, it lets us build layers of abstractions that are going to inherit from other classes of objects. We're going to come to that idea in a second when we talk about not only having classes, but having inherited classes, classes and superclasses and other superclasses, or a better way of saying it, some base level of class and sets of subclasses underneath it that inherit behaviors from classes above them in the hierarchy. And that's what we've been doing already when we build our own class of objects on top of Python objects. We're inheriting the base methods for printing, for accessing elements of lists on top of those Python objects, and we're building on top of that directly. We have already talked about this idea, but I want to remind you again that we want to distinguish between implementing the class and using the class. And when you think about it, I'm really writing code from two different perspectives. I'm thinking about how do I implement a new object type. There I define the class, I define the data attributes, what is the object, and I define the methods. How do I want to use the object? And I do that before I ever have a particular version of it around, so that when I use the class, I can simply create instances and just use the operations, again, without thinking about what's inside of them. One last way of thinking about this. I've got a class definition of an object type. I want to distinguish that from the instance of it. So a class is the type itself. When I created coordinate, it was a class type. And the class is defined generically. I use self to refer to any instance while defining the actual class. And that class defines the data and methods that are common to all instances of the class. Separate from that is when I actually create instances of the object, I have a particular version of the object. My coordinate, for example, is a particular coordinate. And nice thing here is that I can have many different instances. They have different values. They are different because they have different values, but they all have the same structure of the class. They all use the same common methods. And so I'm going to keep flipping back and forth between defining the class and the behaviors associated with all instances of the class from particular uses of that on unique and specific instances. Okay, with that in mind, let's do one last, slightly larger example. And this is going to try and get us at the idea of why would we want to have classes of objects anyway, other than this notion of bundling things together. And part of it is we might want to mimic actual systems. So different kinds of objects are all parts of the same type. So I might have different cats. Jelly, a 1-year-old brown cat. Tiger, a 2-year-old brown cat. Bean, who's very young and is black. And I might have different instances of rabbits. But I've already said that both of these can be clustered together because there are behaviors that belong to cats and there are behaviors that belong to rabbits. And I'd like to have classes capture those common behaviors so that I can build instances of them that can have those behaviors but also have other kinds of attributes. Let's see what happens if we wanted to build that out. So I need to think about what are the data attributes and what are the procedural attributes. And this is just recapping what we've done before. The data attributes, how do I represent our object with data? And well, as everything so far we've done has been numerical, I can start thinking about other kinds of things. For an animal, it might be an age, which is a number, but also a name. What are the procedural attributes I want to have? Again, I did numerical things when I was talking about things like coordinates, but for things like animals, I might want to have methods that do other things, like have it make a sound. This is letting me generalize what attributes, procedural attributes could do. And that's going to make sense as we actually start building the animal. So let's do that. I'm going to start with the notion of an animal. It's going to inherit from object, as we've already done, or as we've done in every other case so far. We're going to do a variation of that in just a second. As I've also done in every case so far, I need to define an init method that's going to create instances of the animal class. So there's the class definition, there's the name, there's the parent. There's the special method to call the instance, and there's, again, as before, the variable that's going to refer to the instance of the class. And there's the other information I want to pass in. In my case, every animal is going to have an age, even if it starts at 0. The other thing I can do here is that I can define not only bindings for data attributes that are passed in this case age, but I can also define data attributes that I'm just going to set up internally, that I'm going to set separately. And in this case, name is not something I pass in, but this init is going to create a binding for both age and name inside every instance. And initially, name is simply set to none. Newborn animal, it doesn't have a name yet. I get to name it. Point I want to make here is that I can define other data attributes that I want to use even if I don't pass them in as initial parameters when I create instances of that class. There's the first start on animal. Okay, so I could make one of these things. I could say my animal is an instance of animal and I need to give it an age, and that lets me now use animal in ways like saying what's, for example, the binding for age or the binding for name. Particular instance, particular parameter passed in that's mapped in that particular instance to that class definition variable. All right, let's start doing some interesting things with animals. I did this a little bit earlier. I said I need methods to get out values. And here I'm going to have something that gets out the age, something that gets out the name. That makes sense because those were the two attributes I defined up here, even though I didn't pass in an initial value for name. But I also want to have another kind of method here, and we call those setters. And those are methods that can change the binding for internal data attributes. So if I want to change the age, if I want to run a simulation, the animal's getting older, I can change the binding for age. I can rebind it to a nil value. I could also change the name. It starts out as none, and I could change the name by having a rebinding here. And my version of setting the name is going to use something we've seen before, which is not only the name of the variable, but I'm going to have a default binding, which is the empty string. So that if I call setName on an instance, if I don't give it an argument, I'm just going to redefine it to be the empty string, or a string of nothing, as opposed to that separate symbol none. And of course, I could pass it in as a particular name, which I'm going to do in a second. And finally, as I've done before, I'm going to want to have a way of printing out what an animal is. And here, my choice is going to be the string of animal with a colon, followed by the actual name of the animal, followed by its age, so that I can tell some information about that particular instance. I've just added some more methods to an animal. I want to remind you again that those getters and setters should always be used outside of the class to access the data attributes. So let's try this out. Let's go over and load up animal. I've done that, and let's see if we can give a particular example of that. So my animal is an animal, and it takes in an age, and I'm going to say it's 3 years old. And if I print my animal, it does what I asked it to do. It gives me a string that says it's a version of an animal. It has no name, none, and its age is 3. Well, I'd really like to give it a name. So I could say my animal, and I want to set the name. And I'm going to, I don't know, pick a particular name, the standard computer science name, foobar. And now if I print my animal, it says it's an animal, it's got the name foobar, and it's 3 years old. Now, I want to come back to this idea of always using the getters and setters outside. Again, I could use getter on this. I could say my animal, and I want to get its age. And it says it's 3, which makes sense. That's what I put in there. But let's go back to this idea. Oh, sorry. This is just going to remind us again of what we already know. I can create an instance by using the class definition. The dot notation lets me get out the pieces inside of it. And I could, in principle, get my animal's age. Again, if I type that in here, my animal age. But in fact, I really don't want to do that. I'd really rather use the getter. And that's because I want to separate the internal representation from access to that representation. And so here I'm directly accessing the data attribute. Here I'm using the method and calling it in order to get it out. And this is much better because it's going to separate out things outside of the attribute from things inside of the attribute. And in fact, that's what we call information hiding. We can actually use it in other ways. I could define a definition and change the name of a data attribute. Here, I've decided to have have init define years to hold the value of age. I'm replacing the age data with a use of the name years. And I can make that be okay by simply changing, simply changing the getter so that it refers to that piece. This leads to this important high-level issue, which is when you're accessing data attributes outside of the classes, you should always use the getters. If you're doing that access directly outside of the class and the class definition changes, I can get errors. In this case, I changed my class definition to use years as the name for age. And so if I try and get a.age and I've made that change, I'll get an error. Whereas if I use the getter and I've changed it, this will always work well. So I really encourage you to be clean and crisp about using getters outside of instances to get out the pieces internal to them. Unfortunately, Python doesn't enforce this. Python's not great at information hiding. It lets you, as we just saw, go in and directly get access to those pieces. I could also write into an instance something like its age is infinite or its size is tiny. While I could do it, please don't. It's not good style. Always write a method to store new attributes inside of it, to access using getters the attribute values that you want out there. Even though Python will let you shortcut it, you're much better off writing code that always is clearly using specific methods to get to attribute values. Okay, this is just repeating what we already knew, and I'm simply going to do it one more time. Self is always determined from the instance. We pass it in as an argument. We did that, for example, with an initialization method. But when we call a particular instance, that's provided automatically. And that's why when I use animal, I simply give the age. I don't use a specific call to the instance. I do have another way, as we've seen, of getting to it. So there's using the method associated with an instance. But I could also say, take the class, get the method out, and apply it. And we saw that earlier on when we used other versions of classes to make that happen. We also saw, as we saw here, the idea of using a default value for a formal parameter. That equal sign says start off with having a default value for that name. And so, for example, in my animal case, I did that. I set the name to be something different, and that allows me to do that overriding of the default value here. Okay, let's see what we can do with those pieces when we get to the next section. We've introduced lists, we've introduced tuples. We said they're ordered sequences of elements. They have different properties, the primary difference being mutable versus immutable. We want to introduce one more kind of data structure, a generalization that has some really nice properties. And that data structure is a dictionary. You've already seen dictionaries in your everyday life. We're going to have a programming language version of it that behaves the same way. And let me show you how that works. Let's start by using an example. Imagine I'm trying to store data about students in a database. So far I could do that just using lists. And I might have a separate list for each kind of data entry. So I might have a list of names, the names of the students in the class. I might have a list of grades for each of the students. I might have a list of the courses that they're taking. What's the grade in? So one grade might be in one class, one grade may be in a different class. I have a separate list for each item. One of the things I'd need is I want each list to be of the same length, of course, because I need to be able to associate all of those pieces together. But the problem I've got is that the association isn't captured in a common place. Here, the information is stored across lists at the same index. So if I want to get information about Anna, I have to go into index 0 and get out the name, the grade, and the course in which she got that grade. If I want to get the similar thing for Katie, I have to go to the third element of each of those lists. So each index refers to information for a different person. And I don't have an easy way to capture that kind of information. As a consequence, if I wanted to write a function to get out information, I'd have to write something like the thing shown here. I've got a function called getGrade. It takes in a student and then the list, a name list, a grade list, and a course list. And what I'd have to do is to say, given that index for that student, I'd have to go and find where that is, and by basically going into the name list and finding the thing associated with student, what spot is Anna at? And having done that, I now know the right index, and I can use that to get the grades list element and the course list element. Or said another way, I have to walk down somehow the first list to find where is that student located, and then use that to go in and find the right spot or the corresponding spot on the other list to get back the grade in the course. Clearly this is messy if I've got a lot of different information I'm trying to track. I've got to maintain multiple lists, I've got to pass them in, and especially I've got to remember to change multiple lists. If I add something to one list, I've got to go make sure I add the right elements in all of the other lists. I could do it, but it's not handy. It's really inconvenient. I'd like another way of being able to do that idea of finding things associated with a particular entry in a structure. And that's where a dictionary is going to come in. What I'd like is to have a way to be able to index to an item of interest directly. And it might not always be an integer, it might be something else. And I'd like to be able to use it using one data structure and not separate lists. So if you think about it, what's a list? It's a sequence of elements where the index is a set of integers starting at 0. And associated with each indice, I have a different element. A dictionary is going to be different. It's again going to be a collection of things, but now I'm going to customize how I index to it. Rather than saying giving me the 0th element, I'm going to say give me the element associated with this key. And so we're going to call the indices keys, and we're going to use them as labels that tell me where to find the element inside of the dictionary. So it won't have this nice linear structure I had with a list. It will have a structure to it, but it's going to give me a lot more power in terms of how I retrieve elements out of the dictionary. And I say dictionary because it behaves much like it would in a dictionary of words. I can look up a word and retrieve from that dictionary all the information associated with that word, not having to know that the word factorial is associated with entry 2745 inside of the dictionary. I simply look up factorial and find the entry associated with it. So we can build that in Python. And here's the way we do it. First of all, a Python dictionary stores pairs of data together, a key and a value. The key telling me the thing to look up. I'm going to create it initially with an empty dictionary. And you can see we're using the same basic type of structure. I've now used curly braces or brackets, if you like, in order to represent a dictionary, as opposed to parentheses or square brackets. An empty dictionary starts off with just these curly braces. And then I could create a dictionary of grades. I could give Anna the grade B, I could give John the grade A+, Denise an A, and Katie an A. And I'm going to index into the dictionary by the key element of the entry inside of a dictionary. So each one of these is association or a pairing of a key and a value. And that's going to allow me now to build arbitrary structures very nicely. So now I'm going to build up this dictionary. There it is. I happen to have stored them in that order. One of the things I'm going to say about dictionaries is I don't rely on the order. They're not going to be in any particular order other than how I happen to put them into the dictionary. And there's an example dictionary of my dictionary. Okay, what could I do with that? Well, given I've got a little grades dictionary, I'm going to be able to look up things in the dictionary. It's going to be similar to indexing into a list, but I'm going to use it based on the key. So, for example, I've got an example of grades over here. I'm going to load it into my environment. Grades, I could print out. It's just an arbitrary collection. But I can now say, I'd like to get the grade associated with John. Now, in a list, I would have needed to know what's the index at which John is stored. I can only index into a list based on an integer. But with grades, as a dictionary, I can say, give me back the value associated with that key. And there it is. If I want to get the grades associated with Sylvan, I can type that in. Sorry, I'm going to type grades properly here, and I can type in Sylvan. And it complains, as it should, because there is no key in the dictionary for Sylvan. There's no association of Sylvan with a value. But now the retrieval, the lookup, is simply give me the key, I'll find that entry in the dictionary, return the value. Sounds really good. So what are some of the operations I could do on a dictionary? Just as we had with lists, we're going to have operations on dictionaries. I could add an entry for Sylvan. So I could say into the dictionary grades for Sylvan, add in an entry. Sylvan's doing well in this class. There it is. And as a consequence, if I now say, what is the value associated with Sylvan? It's going to give me back that value. I can add an entry. It's mutable. I can change things inside the dictionary. And I've in fact just made that change to the dictionary. I can test to see if a key is in the dictionary. And literally I do that by simply invoking, for example, is John in grades? He is. Is Daniel in grades? He is not. Python is automatically walking through that structure to see, is that key in the collection of keys associated with this dictionary? We'll worry later on about exactly how he does it, but the nice thing from a programming perspective is I can test very simply to see if a key is in a dictionary. I can remove an entry. As we've done with other things, del for delete will remove an entry. So if I give del, say I want to remove the entry for Anna, in grades, I can do that. If I look at grades, Anna's gone. And in fact, what I just did was change that dictionary. I can add entries, I can test about entries, I can delete an entry. Here are a couple of other things I can do. I can actually get out the set of keys. And so let me go back to grades. I've got grades. And I can say keys, which is a method, and since it's a method, I need to type an open and close paren to say call the method. And it gives me back an iterable. Again, I can think of that like a list or a tuple. It's not quite because it doesn't generate them. It's going to give me a way to find them when I want them, but it's going to act as if I got back that collection of pieces inside of a structure. And similarly, I could get the values out. Grades values will give me back an iterable of the values associated with that structure. And if you're wondering why what I typed on my computer is a little different than what you see on the slide, it's because I did not reload the grades in. I'm using the version of grades that's here. But the behavior is exactly what I want you to see. I get back things that I could then iterate over. Like I could walk down all the collections of keys, or I could walk down all the collections of values doing something to them. One of the things to notice about both of these is I cannot guarantee that there's a particular order to them. So it's not like the traditional dictionary that you get everything in lexicographic order. It's going to depend on how I put them in there. I just simply need to know that I want to do something with the dictionary and not rely on the order in which things are returned. What else can I say about dictionaries? A couple of things. The values that go into the dictionary can be anything. It could be any type. It could be immutable types like ints or strings. It could be mutable things like lists. It could be functions. It could be absolutely anything can be used as a value. They could also be duplicates. That is, I could put the same value to be associated with different keys. As we also can see here, dictionary values could be lists. I could even have dictionary values be other dictionaries. It can be anything your heart desires. Keys have a little bit more constraint on them. The first one is they need to be unique. Well, that makes sense. If I'm going to look up something in the dictionary, I can't have multiple keys or the same key in different places in the dictionary. It has to be unique, a unique entry. The second key point is that the key must be of an immutable type. So that means an int, a float, a string, a tuple, a bool. Actually, I need something a little stronger, which we're going to come back to later on in the term. They need to be what we call hashable, but right now think of it as immutable because basically everything we're going to deal with has that property. I need to be really careful if I'm going to use a float type as a key, because if the float has an accuracy issue, I may not find the thing I wanted to associate with it. The reason they need to be immutable is I can't store something in the dictionary under one key and then change the key and expect to be able to find it still in the dictionary. It just doesn't make any sense. As I've already said, and I'll remind you, there is no order to either the keys or the values. And so I've given you an example of a dictionary here where one index, one key is an int, another key is a tuple, a third key is a string. How they're ordered in the dictionary, I don't care, but I can have all of those in one dictionary and retrieve from them appropriately. So just to compare the two pieces, differences between a list and a dictionary. A list is an ordered sequence of elements. And in fact, I index it by using an integer index because, in fact, I know it's ordered. A dictionary is simply a collection of entries. I'm going to match keys to values. There's no particular order to them. And I can look up one item by simply using that index to try, or that key to try and pull out the piece that I want here. So in this case, I look up elements by an integer index. In this case, I look up elements by whatever the key is, which could itself be some arbitrary expression. Indices and lists have an order, no order with dictionaries. And the index has to be an integer with the list. The key can be any immutable type. So you can see that dictionaries have a lot more capability in terms of what we can store inside of them. And we're going to look at an example to see how you can use dictionaries and iterate over dictionaries to do interesting things. In that last example, we looked at how using a dictionary could let us make computation much more efficient. We store away computed values that we want to reuse, so we simply look them up. Nice idea. To demonstrate it, I showed you some examples of running the code, and we simply used the delay in time before we printed out a result to try and get a sense of how different the efficiencies were of that. I'd like a little more formal way of doing that, and I'm going to show you an example using what we call a global variable. Now, I'm going to preface this by saying this is a dangerous thing to do. Globals are something that most computer scientists don't like to use because they can really lead to side effects in a very bad way. But in some cases, they're valuable, and this is one. They're dangerous to use because global variables break the scoping of variables that we get by a function call. What do I mean by that? Remember when we were looking at a recursive function and we'd call fact on something and it would call fact on a smaller argument, and that would create a separate scope, and the value of the parameter in that scope was the one we would use, and it would be different from the value of the parameter in a different scope. With global variables, we're going to have the ability to move that value, that access to that variable, out of scopes. And that's why it's dangerous to do. It also allows for side effects because we can change variable values in ways that affect other computation. But it's going to be really handy if we just want to keep track of information inside of a function. And I want to go back to my example of fib and fib efficient to show you how that would work. I'm going to take those two definitions and I'm just going to change them slightly. In particular, I'm going to add in a variable that is going to just keep track of how often do I actually call this function. And so I'm first going to say that variable is global. And this is simply a statement. Notice global is a special term. It says this variable name is something that I can access outside the scope of the function. I'll remind you, before this, anything inside the body of the function was only accessible within the call of the function itself. But this is something we're going to be able to see up, for example, at top level at the global environment. And then what I'm going to do with both of these functions is simply increment them each time I call them. It's going to keep track of how often did I actually call this function. The rest of it is just like before. It is exactly what I did when I did these two computations. So with that small change, I can now track the efficiency of this particular pair of functions. I'm going to need to initialize that global variable outside. I'm going to set it to 0. And then what I'm going to do, for example, is I'm going to call fib on an argument like 12, and then print out a string and the number of times I called that function. Because inside that function, and I'm going to go back to that previous slide for a second, it's going to update that variable each time I call it. I'll then reinitialize it to 0. I'll set up my dictionary, and I'll do the same thing with fib efficient. And it's going to give me a chance to measure, in fact, how different are these two functions in terms of how many times are they called. So I have on my computer then those two functions. I'm going to do exactly that. I'm going to start with something a little smaller, which is 12. And I've just got a variable here, fibarg, so I can just change that rather than changing it in both places. And let's see what happened if we call this. Okay, it ran it, and it said basically I got 233 as the answer. But with the inefficient Fibonacci, there were 287 calls to that function. With the efficient one, because I'm keeping track of what I've done, only 21. All right, sounds pretty good. Let's go back to the one that we used to see a bigger difference. Let's go to, say, 30, and let's call that. I get the same answer both times. That's good. But notice the difference. Wow. Using the dictionary, I only called that function 57 times. Without the dictionary, 1.7 million. Let's just do one more. We won't make it too big or we'll be here forever, but let's, I don't know, make it 34 and let's call it. And it's going to take a little while to find that answer, but it will find it, I hope, in a second. There we go. The answer is the same. Look at the difference. With the dictionary, with keeping track of those answers, 65 calls. And boy, I got to eyeball that. 11 billion in the case of the inefficient Fibonacci. So dictionaries can be really handy here, and here's a great example of that. As we go forward, we're going to use dictionaries in a lot of different ways to really efficiently capture and use information, especially the idea of being able to index on arbitrary keys, something we're going to want to be able to use as we generalize the kinds of procedures we're going to compute. We've seen now 4 different ways to collect things together into compound data structures, non-scalar data structures. We've seen strings, we've seen tuples, we've seen ranges, and we've seen lists. And I want to take a little bit of time to talk about the common operations that apply to all of them. They're all ordered collections of elements. They all have certain properties, and then they have a few differences. So I'm going to let SEQ, sequence, be a name, a variable, if you like, but a name that describes any one of these. And what do we know about all 4 of these data types? I can get the ith element out by simply saying, give me the ith element of sequence by using the square braces, right there. I can ask for the length of them. I will get it back. I can concatenate them using pluses, with one exception, which is ranges. I cannot concatenate ranges, but I can concatenate strings, tuples, lists. I can actually repeat a sequence n times by using the star. We saw that earlier with strings. I haven't shown it to you with lists, but it works exactly the same way. If sequence is a list and I say 3 times a sequence, I'll get 3 versions of that sequence all concatenated together. Again, not with ranges. It's the one exception here. I can slice into any of these things using exactly the same format, especially that colon there. I can test if something's in a sequence. So by simply asking, is this element in the sequence? Will return true. Same common form. I can say, is it not in the sequence? And I can iterate over the sequence by simply using for and in and walk down the sequence. Why am I showing you this? This is a nice property of this programming language, that given these collections of elements, exactly the same operation applies. Again, with just the 2 exceptions here of concatenation, where ranges cannot be concatenated. But it's really nice because I don't have to think about what operation am I doing based on what type. I'm overloading these operations so that I let the type of the data help Python decide which version to use to collect them off. More importantly, intellectually, I can think about the operation itself without worrying about the details of which version of it do I want to use. I can say I want to concatenate these things together. Doesn't matter if they're tuples, if they're lists, if they're strings. I can just go ahead and do them. And so I could pull all of those together in a very nice way. I've got one other piece of it that I want to think about, which is which of these are mutable and which are not. And as we've seen, only the list is mutable. So how do I think about this? Strings is a concatenation of characters. Tuple, a concatenation of any kind of object. A range, a concatenation or sequence, I should be saying, of integers, and list, a sequence of any kind of object. We've seen the examples of them, and we've seen, well, 3 of them are immutable. 1 of them has this nice property of being mutable. But all of these behave the same way, and that idea of collecting data together into a structure is something we really want to be able to use. And I'm going to show you an example of that next. Let me show you an example of using a dictionary, actually of creating and then using a dictionary. And I'm going to use an example of simply wanting to analyze song lyrics. I want to see how often does a word appear in a lyric, for example. So I'm going to write 3 functions to do this. They're reasonably straightforward functions, and it's going to let you see how we use dictionaries to capture information in a valuable way. So first I'm going to create a frequency dictionary that's going to map strings to integers. The idea is that given a set of lyrics for a song, I'm going to walk down it, and for each word, each string, I'm going to count basically how many times it actually appears inside of that lyric. So the dictionary is going to be that association of a word and number of appearances. And once I've created that dictionary, then I can do things like find the word that occurs the most often and how many times it does that. Here I'm going to use a list in case there's more than one word that occurs the same number of times. And so I'm going to return a tuple, another data structure, that has inside of it a list for the set of words and an integer for how often did that set of words, each of one of them, appear inside the lyrics. And then finally, I'm going to find the words that occur at least some number of times. I'm going to let the user choose that minimum amount, so it'll be a parameter. And then I'm going to return a list of tuples, where each tuple is one of those list int combinations that contains the list of words ordered by their frequency. And one of the things I'm going to do here is take advantage of a property of the dictionaries. From the song dictionary, I'm going to find the most frequent word, and then I'm just going to delete it, and I'm going to repeat. And because I'm mutating the song dictionary as I do it, it's going to actually pull together very nicely an efficient way to solve this problem. So let's start with the first stage. I need to create a dictionary. Here's a function that will do it. I'm going to call it lyrics to frequencies. Sounds reasonable. Lyrics will just be a string of words separated by spaces, potentially other kinds of things. I'm going to create an empty dictionary. There are the curly braces that do that. And then I'm going to just iterate over the lyrics, getting each word out as I do it. And what I'm going to do is say, if the word is already in the dictionary, and oh, there's that nice thing. I'm using the fact that I can treat the dictionary as an iterable. I can just say, if the word's already in the dictionary, increase the value associated with it by 1. Oh, that says I've already got a value there somewhere, and that's okay because it says if the word is not in the dictionary, this is the first time I've seen the word, I'm going to set the value in the dictionary corresponding to that word to 1. And once I've gone through that entire loop, I'll simply return the dictionary. On my computer, I've got a version of that code, and I've got a song. Now, even though I used Justin Bieber earlier on, I'm of a different generation. I like the Beatles. So I've got a classic old Beatles song, She Loves You. It's also a nice song because it's got a lot of repetition of the characters in it. And I've got the entire lyrics to She Loves You actually set up over here. And so now what I'm going to do is I'm going to actually load this and run it. And when I do that, I'm going to basically say, what does Beatles look like? And Beatles was set up to be the lyrics to frequencies called on She Loves You. And there's a piece of it. It's actually much longer than you'd expect because it's got, just to show you all the pieces there are all the words in She Loves You as a dictionary associated with their frequency. Okay, with that in mind, I've now got a dictionary of frequencies. That's pretty cool. What else do I need to do? Just to remind you, I can iterate over the list. I can iterate over the dictionary. Those are really handy things to do. I can update a value associated with the key. All things that I wanted to be able to do inside of that dictionary. Second thing I want to do now is I want to find the most common words, given the dictionary's input. So here's how I will do that. The first thing I'm going to do is I'm going to get the values out from that dictionary. Getting values is a method, so I'm going to call it with the open close paren. And that gives me back a set of values. I know those values are all ints, so I can get the most common number very easily. I just apply max to values. I want to stop here for a second because I want to point out a nice thing. I could have written an iterative loop that walked down this, trying to keep track of what's the best number I've seen so far, updating as I went along. It's a perfectly reasonable way to write the code. But it would have generated a lot of code. It would have made it harder to read. Here, in 2 lines, I've captured the idea I want. Give me all the values in the dictionary. It's now a collection of integers. Just give me the maximum value. Really nice. Now that I know the best, I need to find all the words that have that value. And here I will write the iterative loop. I'm going to set words up initially to be an empty list. And then for everything in the dictionary, I'm going to check. Does that entry have the value best? In other words, is it one of the most common words? And if it is, there's that nice mutation of words. Just add it to the end of the list. And when I'm done, I'm just going to return words and best. So over here, I've got my Beatles as that set of frequencies. And so I could say, give me W and B. I know it's going to return a tuple to be most common words in what I already did is the analysis of that song. And it says the most common words that occur in that song, again, not particularly surprising, A, like, her, and with. And how often do they occur? They each occur 4 times. Okay? So I've just found that out. That sounds pretty good. Now, what else could I do with this? Well, I said I wanted to find the places in which they occur most often, and to find all of those that occur more than some amount of time. So the last function I'm going to do here is I'm going to create a function that says find words that occur often in this. Again, I'm going to set up an empty list initially. And here I'm going to create a little flag. And the flag is initially set to false, because I'm going to run through a loop here. And the loop says, as long as I've still got something to do, here's what I'm going to do. I'm going to find, as I just did, the most common words in the dictionary. And if they occur more than the minimum number of times that I've set, I'm going to add them into my result. And then, for everything in that word, I'm going to remove it from the dictionary. So let me say it again. I'm going to say, given I've done the analysis, find the most common word. I don't know how many times it occurs, but I'm going to find them. As long as they occur more than the minimum I've set, then I'm going to collect those, because that's part of what I want to have. And then I'm going to remove them from the dictionary. So I'm mutating the dictionary right here, which is really nice. Because once I've done that, I could go back around and do it again. And I'm going to keep doing that until when I pull out the most common words, they don't exceed my threshold, in which case I'm going to set that flag to true, which means when I go back around to the loop, it's going to say, oh, I'm done, and I'm going to simply return the result. And if I do that over here, in fact, what I get, if I do words often of Beatles and I want everything that occurs more than 5 times in that structure, I get nothing. Now that's a puzzle. And why is it a puzzle? And the puzzle is because I did something that I should have remembered I did, and that is that I actually processed this multiple times. So let me start again by going back to this file and reloading it, because I actually mutated the structures as I went through them. And that's why when I said what were the most common words, it was just A, like, her, and with only occurring 4 times. I'd already changed the structure. Now if I do it the right way, you see, not surprisingly, what occurs most often in she loves you? Yeah. The word you, 36 times. The word yeah, 28 times. She, 20 times. Love, 13, and so on. All right, early Beatles weren't very imaginative with their lyrics. But what you've seen is how I can use a dictionary to, in fact, do analysis, take advantage of the iterable structure of the dictionary. And if you think about the 3 functions I wrote here, they're very simple, they're very crisp, and they very nicely capture exactly the computation I wanted to do. Let me show you one other place where a dictionary is an incredibly valuable thing to have. And to do that, I'm going to go back to a piece of code that we looked at a while ago. Fibonacci was counting the number of bunnies in a pen. Remember Fibonacci. It had 2 base cases. It said if n is equal to 1, the value is 1. If n is equal to 2, the value is 2. Otherwise, the nth Fibonacci number is the sum of the n minus first and n minus second Fibonacci number. It calls itself twice. It has to, because it has to do that computation. And it will certainly work, but this code is actually very inefficient. And let me show you why. Think about what happens if I want to compute fib of, say, 5. To compute the 5th Fibonacci number, I need to compute the 4th Fibonacci number and the 3rd one. But to compute the 4th Fibonacci number, I need to compute the 3rd one, which needs to get the 2nd one, which then also needs to get the 1st one. Now those 2 are the base cases. I've unwrapped it all the way down to that level. Having got fib of 3, fib of 4 also needs fib of 2, and that's also a base case. And then finally, fib of 5 needs fib of 3 as well as fib of 4, and that's got to do another set of computations. It's building a tree of computations, if you like. Now, why do I say it's inefficient? I don't need to recompute those. I already know them. Well, in the case of fib of 1 and fib of 2, they're just constants, but fib of 3, I'm doing a computation there that I didn't really need to do because I already figured it out over here. And you can imagine if I was doing fib of 6, it would need fib of 5 and fib of 4. And down here, there would be a whole bunch of other structures that included things that I'd already computed. It's inefficient. And in fact, it really slows down when you start trying to compute large Fibonacci numbers. Here's where the dictionaries can really help us. Rather than recalculating the same value many times, let's just keep track of what I've already done. So here's a nice version of fib that's very efficient. And it basically says, I'm going to compute Fibonacci, the nth Fibonacci number, but I'm going to give it a dictionary. And what I'm going to do is say, if I'm computing this Fibonacci number for the first time, I'll do the work as I normally would, and then I'm going to store it into the dictionary. But if I've already done the work, just look it up and return it. So if n is already in the dictionary, I just look up the value and return it. Otherwise, I do the recursive call, as I would have done before, compute it. Having done that, I store that value away in the dictionary, and I return the answer. And I'm saving the answer here because I need to hold on to it in order to be able to return it. To start this up, I need to give the base cases in the dictionary. So there I go. I put into the dictionary the first and second Fibonacci numbers. And then I can just go ahead and do the work. This process is sometimes called memoization. It's a way of creating a memo to yourself that remembers what you've already done. And that turns out to be much more efficient. So let's look at a couple of examples of this. And so over here, I've got versions of fib and fib efficient. I'm going to initialize the dictionary. And I'm going to just set up an argument. Say I'm going to compute for, let's start with something simple. Let's just compute the 5th Fibonacci number. And I've set up a little print routine that's going to print them out so you can see how well it does this. And if I call this, oh, it did it really quickly. And it gives the same answer, which is good. Now, let's give it a little bit bigger number. And I want to let you watch how long it takes to do the computation, because I'm going to do the straightforward one and then the efficient one. There was a little bit of a gap there, but it was almost the same. Now, let's give it an even bigger number, which is 30. Oh, and you notice the pause. And in fact, if I do one more, I don't want to make it too long, but let's make it 34. And I do this. It's working on fib. It's working, oh, and fib efficient came about really quickly. So what that's doing is saying I can use the dictionary to hold on to values that I've already computed that I don't need to recompute, and it gives me a really efficient way of doing this computation. First, congratulations. You made it to the end. This is the last lecture in this first part of 600, and we're delighted that you've stuck with us all the way along. Second, this is going to be a short lecture because we just want to take a step back and think about what have you accomplished, or what have we, hopefully together, accomplished in this course. So, to pull all of this together, let's think about where you've been and where you're headed. What are the things you've learned? What are the lessons you should take away? And how might you use this as you think about next steps? And let's start with where you've been. If you go way back to the very first lecture, we put up a set of topics. We said in this class, in this course, you're going to learn a different range of information, a different set of knowledge, a different set of tools. And if you think about it, I think we've hit all of them. You've certainly learned about how to represent knowledge with different kinds of data structures. Lists, tuples, dictionaries. They aren't the only ones. As you move on, you'll find other kinds of data structures, but most importantly, you've learned the idea of how to group things together, treat them as primitives, so that you can reason about complicated structures in very efficient ways. Second thing we certainly did was to come up with different computational metaphors, iteration and recursion. You've seen loops, whether it's for or while loops. You've seen ways of writing things that walk linearly through different kinds of computations. You've seen recursion as a way of capturing computation very effectively. And they really are that wonderful term over there. They're metaphors for thinking about how to write procedures that tackle problems. You've certainly seen the idea of abstraction, both of data types and of procedures. That notion that I can create something once and then bury the details so that I can use, for example, a procedure as if it was provided as part of the machine. knowing that having built it once, there's a contract that ensures if I give it the right kind of input, I'm going to get out output that satisfies a particular constraint. You've definitely seen how to organize and modularize systems, especially around the ideas of using object classes and methods, associating both data and procedures together inside of classes, treating them as primitives, building hierarchies, inheriting, all tools that are really valuable for organizing and modularizing your systems. You've also seen different classes of algorithms, both for straightforward things, but especially around things like searching and sorting, things that you do a lot. And associated with that, you saw how to reason about the complexity of different algorithms. Why do certain things have much more cost than others? What's the order of growth associated with inherent kinds of methods and algorithms? So those are all the topics that you covered. If you also think back to that first lecture, we also said that we were going to teach you some higher level things. You were going to learn computational modes of thinking. We were going to master the art of computational problem solving. And especially, we said, we want to help you have the confidence to make computers do what you want them to do. So what we hope is, in fact, that we started you down the path to being able to think and act like a computer scientist. That when you see a problem, you think about, how can I abstract that? How can I build the right kinds of modules? What are the interfaces between those modules? How do I approach this computationally? And what does that allow me to do in terms of solving a problem, especially to get the computer to do the hard work for us? So if we hope we started you down the path of thinking like a computer scientist, you might ask, well, what do computer scientists actually do? And I happen to put up here images of two of the earliest computer scientists and two of my favorite ones. Ada Lovelace, sometimes referred to as the first computer programmer, and Alan Turing. And what do they and more recent computer scientists really do? Well, they do think computationally. Abstractions, algorithms, automated execution. Three tools that you've seen and that we're going to summarize in a second. And in particular, just like the traditional 3 R's of reading, writing, and arithmetic, computational thinking is becoming a fundamental skill that every well-educated person is going to need. And so that ability to think about abstractions, to think about algorithms, to think about automated execution, is a tool that's as valuable as being able to read, write, communicate, and do other kinds of basic computational things. So, what is that notion of computational thinking that we hope you've learned? Well, here are basically the steps that you've seen. Given a problem, how do I identify or invent useful abstractions? How do I suppress details that I don't need to worry about? What are the interfaces between the pieces that I want? Once I've done that, how can I formulate a solution to a problem as a computational experiment using those abstractions? What is it I want to test? And then having done that formulation, how do I design and construct a sufficiently efficient implementation of the experiment? Sufficiently efficient, a key word, because we know that some things have more cost than others. Having done that, then I'm going to validate my experimental setup. In other words, debug it to make sure it works the way I want it, run the experiment, evaluate the results, and repeat as needed. That really is the tools that hopefully you're taking away here as you think about what does it mean to run a computational experiment. And then what are the components of that? Well, the 3 A's of computational thinking. Abstraction. You've seen many examples of this. How do I choose the right abstraction? How do I operate in multiple layers of abstraction simultaneously? You saw a lot of this when we played with classes, but it shows up in other places as well. How do I define the relationships between the abstraction layers? But abstraction is an essential part of computational thinking. I don't want to have to think about hundreds of thousands of lines of code at a time. I want to be able to take a piece, make sure it works well, understand the constraints on it, and abstract it away. So I can just use it as if it was a built-in thing around it. I want to be able to understand where's the right level in that hierarchy of abstractions in which to be performing my work. And you've seen examples of that. You're going to see a lot more of them as you use computation moving forward. Abstraction, a big element of all of this. Automation, second big element. How do I think in terms of mechanizing those abstractions? It's not just enough to think about what's the algorithm. How do I do it in a way where I can write it down so that the machine can actually understand it? And that mechanization is possible because we have precise and exact notations and models. And because, as we saw way back at the beginning of the class, there is some machine that can interpret that notation. And so learning a new language, in fact, is learning what's the description of the mechanisms and how do I map things from my thinking level of abstraction down into something that the computer can actually do. And then algorithms. How do I then take those ideas and capture common patterns of behavior that I want to use? And that includes both what language do I use for describing the automated process? In our case, it was Python, maybe something else in the future. But it also allows me to abstract away the details of the algorithm. Having built the algorithm once, I can extract away the details so I don't worry about it. And finally, how do I use algorithms actually as a language for communication? Talking about an algorithm at a high level is a way of actually communicating a process or an idea to somebody else. If you look back at everything you've done in this class, you'll see those three pieces constantly: abstraction, automation, algorithms. Those are the 3 A's of computational thinking that you're going to take forward. The last aspect of this is to think about computational thinking at a slightly higher level. And here, there are 2 other things that you've taken away, we hope, from this class. The first one is, when given a new problem, how difficult is it? How best can I solve it? We know that theoretical computer science gives precise meanings to these and related questions, and you've seen that. Knowing the difference between a log linear algorithm and an exponential algorithm is really important. Realizing that a choice in algorithm can move you from a more costly class to a less costly class is really valuable. Also knowing that some algorithms inherently belong in this really expensive class is a valuable lesson to take away. But you ought to, when confronted with a new problem, ask, how difficult is this? Does it fit into a class I've seen before? Is there an existing algorithm that's going to solve this problem for me with some small variations? And how do I use that? And then the last aspect of computational thinking we hope you've taken away from this is how to think recursively. It's that wonderfully twisted way of thinking, but it is an incredibly valuable one. And that is that idea of taking what seems like a difficult problem and reformulating it into a simpler version of the same problem, plus some other things that I know how to do. That reduction, embedding, transformation, simulation idea is really valuable, but it all relies on that nice notion of, given a complex problem, I don't have to start from scratch. I can simply say, I could solve this by solving a simpler version of the same problem, and then taking that solution, add in some other things I know how to do in order to make it work. And while it may seem twisted, that idea of recursion really does show out nicely. And this image, called the Drost effect, wonderfully captures it, based on a Dutch cocoa company's ad. But you get the idea that when I have a recursive problem, I can keep reducing it to simpler and simpler versions until eventually, somewhere way down in here, I get to a base case and I can pull it all together to come up with the solution. I hope this image really captures for you that idea of taking a complex problem is not so hard when you simply reduce it recursively to simpler versions. And those are the things that you've seen. So, that's where you've been. Where are you headed? Well, that's your choice, of course. But I hope that you'll take away 2 things as you think about how to use what you've seen in this class. How can you use it? And what are next steps to enhancing your knowledge? In terms of how you can use it, well, you should look, I hope, for ways to apply what you've learned. Can you use algorithmic approaches in your professional life? No matter what you do, there's got to be some place where abstraction or computational experiments can improve what you do in your job. If you're a student, ask how you can use these ideas to help you pursue your choice of discipline more effectively. You don't have to be a computer scientist to use computational thinking. An economist, a statistician, a chemist, a physicist, a biologist, mechanical engineer, they all use computation in different ways. And I really encourage you to think about how you can use algorithmic approaches to solve problems in your own domain or discipline. You can ask the same question about your personal life. Can you organize your personal finance records better? As we saw in the last lecture, can you plan your retirement better? Can you store your historical records better? Can you simply use computation to help you in things that matter to you in personal life as well as professional life? So I hope you'll think about how can you use what you've learned here in multiple ways. And the other next step is basically to think about taking another course in computation. As we said, the next course in this sequence, the second part of 600, is an introduction to computational thinking and data science, where we look at using these tools in large-scale data analysis. But you might take a course in algorithm design, in software engineering, machine learning, a very important and hot topic, in data analytics and data storage, and whatever tickles your fancy. Basically, you've got an opportunity to build as you see fit because you've learned the basics of computational thinking and algorithmic processing. So, good luck. However you choose to use computational thinking, we hope that it's a useful tool for you in many ways. As a way of approaching professional problems, as a basis for understanding the impact of computation in everyday life, and as a language for communicating ideas. And I look forward to seeing you do that as you take more courses and you add computational thinking to your own professional and personal life. Good luck.